Hello there, you beautiful person, and congratulations on signing up to Bash Scripting Mastery. You've made a great choice. My name is Ziad, and I'm going to be your instructor for this course. I have a PhD in engineering, and I created the best-selling Linux Mastery course, which has introduced tens of thousands of people to the wonders of the Linux operating system. I'm really excited to have you here with me in this course, and my intention is that by the end, you'll be able to write your own Bash scripts independently using all of the core components of Bash syntax. You'll be able to use scheduling tools to automate the execution of your Bash scripts. You'll be able to debug your Bash scripts using professional debugging tools. And you'll be able to execute your Bash scripts both on your local system and on remote servers. In section 1, we're going to start off by discussing the three core components of Bash scripts, how to write them, and how to run them securely. In section 2, we're going to learn how to save data in our scripts in variables, and how to use a variety of expansions to manipulate and use that data in different ways. In section 3, we're going to do a deep dive on how Bash is working behind the scenes so that you can avoid annoying syntax errors and understand Bash as a second language. In section 4, you're going to learn about how to allow your scripts to accept command line arguments and how you can interactively get input from your users and create interactive menus to make your scripts user-friendly. In section 5, we're going to move on to discussing logic and how you can create scripts that can do different things depending upon the situation, which is a necessary feature for any real automation. In section 6, we're going to move on to learn about how to allow your scripts to accept command line options and how to do different things based upon which options are provided. You're also going to learn about how to allow your scripts to process the contents of files. In section 7, we're going to be discussing arrays and for loops and how you can use these to create assembly lines to batch process data in your scripts. In section 8, you're going to learn about how to debug your scripts using professional debugging tools and how to read Bash error messages, as well as how to solve the most common Bash scripting errors. You're also going to learn about how to use the 3 ways to access official support documentation to help you when you're writing your Bash scripts. Then in section 9, you'll have an assignment where you'll put all you've learned together to build 3 scripts that form an integrated file system utility. Then in section 10, you're going to learn about automation and how you can use various tools to automate your scripts and how to choose which automation tool is best for the job. Then finally, in section 11, you're going to learn how to run your Bash scripts on remote servers. In each section, there'll be practical projects where you can try out the concepts covered in realistic scenarios, as well as quick quizzes to check your understanding. Each section comes with a professionally designed cheat sheet that captures all the key ideas from the section, which you can download and refer to for life. If you have any questions as you go through the course, just leave a question in the Q&A section and either I or a member of the Internet of Things Academy team will get back to you. We strive to respond to all questions within 24 hours. If you're new to the platform, I've put a link in the resources section of this video to an article by Udemy which shows you how to use Udemy's Q&A system. If you need help installing Linux or Bash, there's guidance on how to do that right at the end of the course in the course appendix, so please head there now if you need to. However, if you do already have access to a command line, one thing I'd like you to check as a bit of housekeeping is that you're running Bash by default. Please run the command echo space $shell with shell spelled in all uppercase. And if you get back Bash, then you're all good to go. If not, please run this command that you see here, and enter your password if requested, and then restart your terminal. This will set your default shell to Bash, which is what you're going to need to follow along with this course most smoothly. Also, take a note of what your original shell was, perhaps on a piece of paper or in a Word document, so that you can switch back to it if you want to when you're done with the course. Okay, so with all that said, I bet you can't wait to get started. We've got loads of awesome stuff to cover. So for the first step on your road to Bash scripting mastery, I'll see you in the next video. Hello there, you beautiful people, and welcome to our very first lecture. During this course, you're going to gain the ability to write awesome Bash scripts. But to do that, we first need to cover some very important key concepts. In this video, you're going to learn what the Bash shell is, as well as the difference between the shell and a script. You'll also learn why Bash is more popular than other shells and why scripting is a helpful thing to be able to do in the first place. By the end of this video, you'll be able to explain the difference between shells and scripts, explain the benefits of using the Bash shell in particular, and explain the benefits of using scripts in general. So this is all very exciting stuff, so let's go ahead and get right into it. So what is the shell? Well, the shell is simply a program that interprets the commands you type in your terminal and then it passes them on to the operating system. The shell is something that you, as a human, can use to give instructions to your computer. The shell will interpret these human-readable commands and cause your operating system to do what they say. In short, the purpose of the shell is to make it more convenient for you to issue commands to your computer. There are many different types of shells, but in this course we're focusing on the bash shell, which is the most popular shell. Throughout the course, I'll simply use the terms bash and the shell interchangeably. Bash stands for the Born Again shell. Interestingly, its name is actually a fun joke. Bash is based on a much older shell called the Bourne shell, or SH, which was created by Stephen Bourne in 1979. Since Bash is an improved version of the Bourne shell, people thought it would be funny to call it the Born Again shell, or Bash. As I said earlier, Bash is the most commonly used shell, and the reason for this is the advantages that it has over other shells. First, Bash has a very broad set of features available, which makes it convenient to work with and capable of achieving pretty much anything you could ever want to achieve when interacting with your operating system. For example, the Bourne shell, which Bash is based on, lacks a lot of features due to the fact that it has not been broadly developed. Other common shells, such as the C shell and the Corn shell, each have their benefits, but do not contain as many features as the Bash shell. Bash is also considered to be a fast shell when compared to other types of shells, which makes it more convenient to work with and makes it quicker to execute commands and less of a drain on your system's resources. Finally, the Bash shell is the most commonly used shell, and due to the variability of Linux systems, this is a major benefit in itself. By writing scripts for the Bash shell, you can be rather confident that your script will work when you pass it to other machines, which can save you a whole lot of work. Okay, so now we understand what a shell is. What is a shell script? Well, a shell script, or script for short, is just a file containing a series of commands that will be run by the shell. The shell reads the script and executes the commands, one by one, as if you'd entered them into the command line yourself. A bash script, therefore, is simply a script written for the bash shell, and we'll see how these are built in the next video. So why use a script? Well, the main reason is that writing scripts allows automation. Imagine that you have a set of 20 commands that you need to run to perform a task, and you want to run them once a week. How much work is it every week for you to type out those commands into your command line? What happens if something goes wrong and you break something by typing the command incorrectly? And what happens if you forget to do it one week and get an angry email from your boss? Well, this is where scripts come in. Scripts can be automated to run at a specific date or time without you having to remember to run them, and you'll actually see how to do this later in the course. Scripts are convenient ways to store sets of commands that allow you to automate tasks, save time, and increase reliability. And remember, bash scripts are just bash commands in script form. This means that, as an added bonus, much of what you'll learn in this course will be directly applicable when you work with the regular bash command line, which will improve your effectiveness and productivity no matter how you interact with your Linux machine. So in this lecture, you learned that the shell is a command line interpreter that makes it easy for you to issue commands to your operating system. You learned that the bash shell is a great shell to learn because it's fast, has a lot of features, and is very commonly used. You learned that a script is just a file containing commands that are to be run by a specific shell. So a bash script is simply a file containing bash commands. You also learned that scripts make automating sets of commands very convenient, which saves you time and makes you more productive. So now that you know what a bash script is, let's learn how to write one. In the next video, we're going to cover the core components of bash scripts, and you're also going to build your very first script for yourself. So for all that good stuff, I'll see you in the next video. Hello there, you beautiful people. Now in the last video, you learned the difference between shells and scripts. You also learned the advantages of using the bash shell in particular, as well as the benefits of writing bash scripts. Now we're going to take a closer look at how to write the scripts themselves. In this video, you're going to learn about the core components of a bash script, and you'll also learn how to run a script on your computer. By the end of this video, you'll be able to identify the core components of a bash script, you'll be able to explain what these core components do, and you'll be able to actually run scripts on your computer. All very exciting stuff, so let's get into it. Okay, I want you to think of a bash script as being kind of like a script for a movie or a theatre performance. And just like the scripts that are written for movies or theatre performances, the scripts we write in bash have three core parts: a beginning, a middle, and an end. Our bash scripts always begin with what is called the shebang line. The shebang line is always the very first line of a script, and there must be no line or blank line before it. The shebang line basically tells the shell what interpreter should be used to read the file. You can think of it as telling the shell what language the script is written in, which in our case will be bash. The shebang line starts with a hash symbol, immediately followed by an exclamation mark, or a bang. To make it more convenient for people to say, the hash bang pattern is usually shortened to shebang, which is where the shebang line gets its name. Immediately after the hash bang part comes the path to the interpreter that is used to read our file. Since we're writing bash scripts, we give the path to the location where the bash shell is installed on our system, which will always be /bin/bash. Now, since we're discussing script structure, let's go ahead and write our shebang line in a script and then move on to discuss the other core parts. Just to mention at this point that, for the sake of simplicity, I'm going to be using the Nano text editor during this course to view and edit our scripts. However, you can feel free to follow along using any text editor that you like. If you're not sure, or you're kind of new to this kind of thing, Nano is a pretty user-friendly choice, so I recommend going with that and following along using Nano. I've also created a folder in my home directory called Bash Course, where I'll be putting all the scripts that we write in the course. I suggest you do the same to make it easy to follow along. You can simply create the folder using the make directory or mkdir command by running mkdir:/bash course. Okay, let's open our first script with the Nano editor. We simply move to the bash course folder using the cd command, and then I'm going to use Nano to create a file called our first script. Awesome, we've got our script and we're ready to go. So let's write our shebang line. It's very easy, we just type #bang/bin/bash at the top and save our file. On Nano, you can save the file using Control and O, or Command and O if you're on a Mac. Our system now knows that we have a bash script. If we close this file, on Nano you can close the file using Control and X, or Command and X if you're on a Mac. We can see what type of file our shell thinks we have using the file command. If we run the file command on our script, we can see that it says that we have a bash script. However, if we go inside and change our shebang line to a path to the Python interpreter, which is /user/bin/python3, and then we save the file using Control and O, and exit using Control and X, and then we run the file command on our script once again, we see that the shell now thinks that we have a Python script. Cool, right? Let's open the script again and change our shebang line back to the one needed to write a bash script, which is #bang/bin/bash. Okay, so the second core feature of our bash script is the actual bash commands themselves. Now that we've told the shell which interpreter to use, we can now start to give it some commands to interpret. As we explained earlier, a script is simply a file containing commands for the shell. For our first script, we're going to use the echo command to print out text to the screen. We usually leave a blank line after the shebang line for formatting reasons, so go ahead and leave a blank line using the Enter key, and then type echo, "This is my first script" on the next line. Bash scripts can have many commands and many lines. Each line is read by the bash shell and executed one after another. So the sister component, I guess, of learning bash scripting is learning what bash commands are actually available to you to use in the script. And you'll learn a lot of those throughout the course. Now, the final core component of a bash script is the exit statement. Just like a movie script, the exit statement tells the shell that the script has ended. However, by entering different exit codes, the exit statement also tells the shell whether the script has completed successfully or unsuccessfully. Exit statuses can have any value from 0 to 255. To say that the script has executed successfully, we simply give the script an exit code of 0. Any non-zero exit code tells the script that something went wrong in some way. Most of the time, we just use an exit code of 1 to say that something went wrong. An exit code of 1 represents a generic error, a miscellaneous error, if you will. However, some exit codes have special meanings, and knowing these can help your scripts to play nice with other programs. I've put a link in the resources section to some documentation on what these exit codes are and what they mean, which you can check out if you're interested. Since it's kind of hard for our script to go wrong, we'll just give it an exit code of 0. To give our script an exit code, we use the exit command. At the bottom of our script, we're going to simply type exit 0. And that's it. When our script gets to this line, the script will end and give an exit code of 0 back to the shell. Note that you're not always required to place an exit status in your bash script. Although it's very helpful to define one yourself, if you choose not to add an exit status, the shell will simply take the exit code of the last command it ran as the final exit code of the script. You can now save your script and go back to the terminal. And now for the exciting part, actually running our script. Because Linux focuses a lot on security, in order to allow our script to run, we have to give our script what are known as execute permissions. Fortunately, this is very easy to do, but how you do it matters for the security of your system. We're going to touch on script file permissions in more detail a little later, but for now you can just run the chmod +x, our first script, to give the script execute permissions. If we run the ls command, we can see that the script has been highlighted on my screen in red, which shows that the execution permissions have been set. You might have a different color on your screen if your terminal has different stylings to mine. I believe the default color is green, but the important thing is that the script will look different to regular files when it has been given execute permissions. Now let's run our script. To do this, we simply give the path to the script. Since we're in the same directory as the script, we can just type /our first script. The / means in this directory, and our first script is obviously the file that we want to run. When we hit enter, we see the text, "This is my first script," printed out on the screen. So congratulations, you've now written and executed your very first bash script, all in under 10 minutes. In this lecture, you learned that bash scripts are kind of like movie scripts. They have a beginning, a middle, and an end. The beginning of a bash script is the shebang line, which tells the shell what type of script we are writing. For bash, our shebang line will pretty much always be #bang/bin/bash. The middle of a bash script is the commands. This is where the show actually happens, and the more commands you know, the more varied the scripts you can write. But don't worry, we'll be covering a lot of useful commands in this course. The end of a bash script is the exit code. The exit code tells the shell whether the script ran successfully or unsuccessfully. Finally, you learned how to run your bash scripts by giving them execute permissions with the chmod command. So now that you've learned the core components of bash scripts, let's take a look at some stylistic things you can add to your bash scripts to make them look more professional. So for all that stylistic flair, I'll see you in the next video. Hello there, you beautiful people. Now in the last video you learned about the 3 core components to a bash script, and you even created and ran your very first script. Now we're going to take a look at some stylistic components that you can add into your bash script to make it look professional. In this video, you're going to learn about adding comments to clarify your code and how to add extra information to give your scripts a professional touch. By the end of this video, you'll be able to create inline comments to clarify pieces of your code, add author information to claim the work as your own, add date information to let people know when the script was created and when it was modified, add description information to your scripts to let other people know what your script does, and add usage information to let other people know how to use your script. So let's go ahead and get started. Now I'm a big fan of learning one thing and being able to use it for multiple different purposes. So if you're like me, then you're going to love this lecture. The key thing we need to learn in this video is commenting. What is commenting, I hear you ask? Well, commenting is a general programming technique that allows you to add human-readable comments to your scripts. Unlike commands, comments are not meant to be read by the shell. They're meant to be read by the humans who are looking at your code. Essentially, comments are intended to clarify your script and make it easier for people to read and use, whether that be your colleague or yourself a few weeks later when you've completely forgotten how your script works. To help Bash know which lines are commands and which lines are comments, we need to start our comments with a special symbol. In Bash, we indicate comments with a hash symbol. When you start a line with a hash symbol, the shell knows that the line contains a comment, and it will simply skip that line and move on to the next one. The most common way of using commenting is to explain what certain sections of your code do. Now with our small script that we've developed, commenting might not be totally necessary. It's only one line after all. However, as we continue through the course, you'll begin to appreciate how good commenting can be a very helpful tool. To give an example, we can add a comment to our script like this. Now if we save the file, and then we run it, we can see that the comment is totally ignored by Bash, and the script runs just fine. Aside from explaining sections of our code, we can use comments to add some useful information that describe our script as a whole and make it look more professional. To make your script more professional, you can include 5 pieces of information. These are the author, the date of creation, the date the script was last modified, the script description, and the script usage. Firstly, let's discuss the author. This is simply your name. To add yourself as the author of the script, you would simply come up to the top below the blank line beneath the shebang line, and you'd then type a hash to indicate that the line is a comment, then a space, then type author with a colon, followed by a space, and then type your full name. So in my case, I type hash author Ziad Yahya, and this allows the future user of the script to know that I wrote it. Awesome. Our script now has an author, and the second piece of professional information that you can add is the script's date of creation. Here, you just write date created, and then type in today's date. The third piece of information is the date the script was last modified. Just like before, we'd start the line off with a hash to indicate that it's a comment, then type last modified, and then enter the date that we last worked on the script. You just need to remember to update this line whenever you modify the script so that people can know how old or how up-to-date the script actually is. Fourthly, you can put in a description of what the script does. This is really useful for jogging your memory or for easily getting someone up to speed on what the script does without forcing them to read the whole code first, which is really, really helpful. In our case, our script is just printing some text to the screen, so we can just type hash description, and then on a new line type prints "this is my first script" to the terminal. Because it can get quite long, it's usually a good idea to leave a blank line above and below the description section for readability purposes. Finally, we can enter in some usage details for our script. Usage information simply tells the user how to actually use the script, what they should type in their terminal to use it properly. Just like a man page or manual page for regular commands, we use the usage area to let our users know if the script takes any options, or whether it requires any command line arguments, and so on. Our script is actually very simple to run, so we'll just write our usage information like this. We'll first put a hash, then write usage, and then on a new line, we'll write our first script, again leaving a blank line above and below the usage section for readability. As a side note, with more complicated scripts, you might need more advanced usage information, just like how you get in the synopsis section for a man page. If you're interested, I've put a link in the resources section to the official standards on how to structure usage information for complex commands, but reading that is totally optional. And that's it. We now have 5 really cool pieces of information that help make our scripts look super professional. Great job. Hey, you're starting to look like a bash scripting pro already. So in this video, you learned how to add comments to your scripts to clarify your code, as well as how to add 5 pieces of information to your scripts to make them super professional. The script's author, creation date, last modified date, description, and usage. So now that you know all 3 components of a bash script, and how to structure your bash scripts professionally, in the next video, we're going to have a quick discussion about security, and then you'll have a challenge to write your own bash script independently. Once again, very, very, very well done. You're making loads of progress in such a short amount of time, and I'll see you in the next video. Hello there, you beautiful people, and welcome to this video where we will be discussing a very important topic: security. In the lecture on the 3 components of a bash script, you learned how to give your scripts execution permissions so that your system will allow them to run. However, we left an intentional mistake in the way that we did things last time that could potentially impact the security of your system. In this video, you'll be learning about Linux file permissions and how to set permissions on your scripts correctly so that you don't accidentally introduce any security holes. By the end of this video, you'll be able to identify different file permissions, interpret what they mean, and keep your script secure by setting the right file permissions for your particular context. This is all very exciting stuff, so let's get into it. So what are file permissions? File permissions are what determine who can perform certain actions on a given file. To view file permissions, we can run the ls-l command. As you can see, this has listed out the contents of your current folder, along with the permissions for each entry. In Linux, file permissions are represented by a set of 10 characters strung together. The first character stands alone, and the remaining 9 are broken up into 3 sets of 3. The first character is either a hyphen or a D. If it is a hyphen, which is this minus sign, then the entry is a file. If it is a D, then the entry is a directory, i.e. a folder. The next set of 3 characters represents the permissions that the file's owner has for the file. The file owner is shown in the 3rd column, which on my system says Ziad. The first character in this set of 3 is for read permissions. If the file owner has read permissions for the file, we will see an R there. If they don't, we'll see a hyphen. The second character in this group of 3 is for write permissions. If we see a W there instead of a hyphen, it means that the file owner can modify the contents of the file. The third character is for execute permissions. If we see an X there, then the file owner has execute permissions for the file and can run it like a script. The other 2 sets of 3 have the same format, but represent different classes of users on the system. While the first set represents the permissions for the file owner, the second set represents the permissions for the file's group. The file's group is shown in the 4th column, which in this case is the Ziad group. The third group of 3 represents every other user on the system, so every user who is not the file owner and who is not part of the Ziad group. Now, for bash scripts, it is recommended that unless there is a particular reason otherwise, only the file owner should have the ability to read, write, and execute the file. Everyone else should only be able to read it. By not allowing anyone else to write to the script except the file owner, we prevent others from making sneaky changes to the script without the file owner's knowledge. If they did make these sneaky changes, then the file owner could end up running some code on their computer without knowing, and that could possibly have security implications. Secondly, by not allowing anyone but the file owner to run the script, we can stop unwanted and unintended uses of the script on the system. If we take a look at our script as it is, by changing directory and running the ls-l command, we can see that pretty much everyone has the permission to run this script. Now, under the wrong conditions, this could become a security problem, so let's learn how to make our scripts more secure. To give our script the recommended permissions, we use the chmod command like so. We type chmod, then 744, and then our script name, which in our case is our first script. I'll explain what this 744 thing is in a moment, but for now let's just look at the effect. When we run ls-l, you'll see that our script now has much more secure permissions. Only the file owner has all permissions, whereas everyone else can only read the file. In other words, no one but the file owner is allowed to modify the script's content or to run it. So what is this 744 thing? Well, 744 is called an octal number, and the chmod command uses these as a way of expressing which permissions should be set. However, octal numbers can be a bit confusing to read. Fortunately, there's a useful website called permissionscalculator.org which makes them super easy to interpret. If we head over to permissionscalculator.org, we can see that we are presented with a simple user interface where we can select the permissions we want, and it will tell us the appropriate octal number to type into the chmod command. So let's say we wanted to give everyone read, write, and execute permissions, and I click all these boxes. You'll see that we get 777 as the appropriate octal number. The 0 at the front here is kind of like a bonus digit, so we don't generally tend to include that. You can see that that 0 is governed by what they call the special flags in the octal number. But seeing as we're not going to use any of those, and we generally don't use any of those, we tend to just read octal numbers as 3-digit numbers, so in this case we'd read this as just 777. If we run chmod 777, our first script, and then do ls-l to see the permissions we've set, we can see that, as we'd expect, everyone now has all permissions enabled. So, as a micro challenge for you, pause the video now and try to see if you can make it so that nobody at all can either read, write, or execute the script. So go ahead and pause the video now, try to make it so no one can read, write, or execute the script, and then come back to see how you did. How'd you get on? Well, if we go to permissionscalculator.org, it tells us that in order to make it so that no one has any permissions on the file whatsoever, and we can check that by unticking all of the boxes, we need to do chmod 000 our first script. And if you did that, then well done. It can be fun to see what it's like to not be able to read your own files, so have fun playing around with the permissions a bit. When you're done, just be sure to change your permissions back to the recommended permissions of 744 so that we can continue with the course. So, before we wrap up, let's have a quick recap of what we covered. In this video, you learned how to read Linux file permissions and interpret what they mean. You learned how to change permissions on your scripts with the chmod command and octal codes. And you learned the recommended permissions to use for your scripts for security purposes. In this video, we recommended that you use the octal code 744 unless you have a particular reason otherwise. But you might also like to use 755, which allows other users to read and run the script, but not to edit it. As a final note, it is worth bearing in mind that if you want to give someone execute permissions, you must give them read permissions too. Otherwise, their shell won't be able to read the script and therefore won't be able to execute the commands it contains. So do bear that in mind. So after the last few videos, you now know what a bash script is, what the major components of a bash script are, how to write your bash scripts professionally, and how to set secure permissions on your bash scripts. You've been making excellent progress, and I'd say it's about time for you to give it a go yourself. In the next section, you'll do your first challenge, how exciting, where you'll be challenged to write your very own bash script from scratch. I hope you're excited, so for all that good stuff, I'll see you in the next video. Hello there, you beautiful people, and I hope you had loads of fun trying out this project and building your very first bash script by yourself. If you managed to complete the project, then a massive congratulations to you, and if you struggled a bit, then well done for putting in the effort. In this video, I'm going to walk you through the model solution step by step so you can see exactly how I would have gone about it, and you can also grab a copy of the completed script from this video's resource section. So let's get started. So the first thing we're going to do is we're going to create our script file by typing nano backup script. As we learned during the previous videos, there are three core components of our bash script. There's the shebang line, the commands, and the exit statement. So let's start at the top with the shebang line. For this, we can simply type #bang /bin/bash. And that's it. The shebang line will pretty much always be the same for your bash scripts, so you can just commit that to memory if you like. Next, we have our commands. Now for this challenge, we've been very conveniently provided with the command that we're supposed to use for this script. So, on a new line, we can just copy and paste or type that command in. So that takes care of the commands. And finally, we just need to add our exit statement. If the script gets to the bottom, we're pretty sure it will have run successfully, so we just want to tell the shell that as well. You learned that the only exit code that means a successful run is exit code 0. So all we have to do is type exit 0. And that takes care of all the core components. We have a shebang line, our command, and our exit statement. So we should now have a fully functioning script. Remember that the exit statement is optional, but it's good to get in the habit of putting it in where we can. Now because our boss wants to share this script with our colleagues, they've asked us to add the 5 professional components to our script, which are the author, the date created, the date last modified, the description, and the usage. These are all pretty easy to add, so let's add them in now. As shown in the previous lectures, these should go between the shebang line and the commands. So let's just move back up in the script a little bit, and remember to create a blank line after the shebang line to keep everything nice and tidy. So let's start with the author, which will allow us to stake our claim on our script and get credit for our work. So we just type # then author, and then our full name. Then we will add in the date that the script was created, and the date the script was last modified, which in this case will be the same date. Next, we will add in our description. Now, as we mentioned earlier, it's always good to leave a blank line first to keep things tidy. So let's do that, and then let's add in our description. Finally, we want to add in our usage. As our script doesn't take any options or command line arguments, we can just put the name of the script for this. And now we've successfully created our professionally formatted script, which is step 1 in this challenge. So well done if you got this far. So step 2 is to give our script the correct permissions. Now our boss has given us some rather specific permissions that we need to give the file. The file owner, which is us, has read, write, and execute permissions. The file's group, which is our colleagues, can read and execute the file, but no writing. and everyone else can only read the file. So let's head over to permissionscalculator.org to see what octal code we will need for this. Okay, so if we give the file's owner all permissions, and the file's group read and execute permissions, and everyone else just read permissions, we can see that the appropriate octal code for this is 754. So that is what we'll use. So let's head back to our terminal and type chmod 754 backup script. And if we run ls-l, we can see that our script has the conditions we expected. The owner has read, write, and execute permissions, the group has read and execute permissions, and everyone else just has read permissions. Great job. The only thing that remains now is to run our script. So if we head to our bash course folder, and we type backup script, and then we take a look at our bash course folder again, we can see that we now have a backup file created. Awesome. Now if we run it again, and check again, we can see that our script has created another backup, which is marked with the date and time down to the very second that it ran. I'm sure your boss will be very pleased indeed. Now from this, hopefully you can see that using bash scripts is a very helpful way to make your life a lot easier. In fact, feel free to play around with this backup script and customize the folders it works on to do something useful on your system. So I hope you had fun, and I'll see you in the next video where we'll be learning about how to make scripts like these accessible from anywhere on your system. Hello there, you beautiful people. So I hope you had a lot of fun in creating your very first script and in completing the last challenge. You've honestly learned loads of stuff already, and in this video we're just going to focus on making your scripts just a bit easier to use. Until now, we can only run our scripts when we are in the folder that contains them. But in this video, we're going to make it so that you can run your scripts no matter where you happen to be on your system. In this video, you're going to learn what the system's path variable is, and how you can modify it to make it possible to run your scripts from anywhere on your system, just like you would with regular commands. By the end of this video, you'll be able to explain the purpose of your system's path variable, you'll be able to add new folders to your system's path, and ultimately, you'll be able to run your scripts from anywhere on your system. So, for extra command line comfiness, let's get started. So what is your system's path? Well, in Linux, the system's path is a variable that tells the shell which directories to search for executable files in. When you run a command in your terminal, the shell looks for that command in the directories defined in its path variable to see if it has a command that it can run. If it does not find an executable file with the same name as the command anywhere in the directories, then you will get a command not found error in your terminal. The benefit of adding your scripts to your system's path is that they then can be run from anywhere in your system simply by typing in the name of your script, just like regular commands. We can take a look at our system's path by running the command echo $path. Here we're seeing some rather terrifying output pop up on the screen, but it's really quite simple. All it is just a set of paths to folders, each separated by a colon. When we enter a command name or script name into the shell and press enter to run it, the system will start at the far left of this list and work its way through each folder looking for an executable file with that name and run the first one that it finds. While we could add our scripts to any one of these folders, we're going to create a new folder in our bash course directory and add it to our path. I'm currently in the bash course folder right now, so let's make a new folder here called scripts by running the mkdir command. And we're going to use this new folder to store our scripts. Now, we need to add our script to this folder. So let's move it in there. Okay, and now we're almost there. Now we just need to add this folder to our path so that the system will know to search it for scripts. The system's path is actually edited using the .profile file inside our home directory. The .profile file contains many configuration details for the bash shell, which the shell reads when it starts up. So let's head over to our home directory using cd and open our profile file by running nano /.profile. As a side note, this is actually a hidden file. What that means is, if you run a normal ls, it won't show up, but you can still see it if you run ls-a, where the -a option means all. Hidden files are just Linux's way of making it so that the configuration files your system uses don't clutter up your view in your home directory. Now, if we scroll down to the bottom of this file, we can update our path by adding in export path equals, then open some quotes, $path, $home /bash course /scripts. Now what this does is overwrite the path variable to include our scripts folder at the very end of our path. This is a good place to put it because it means that on the one-off chance that we give a script the same name as a command that is already installed on our computer, like ls or something, those other commands will be given priority because they're further to the left, which can save us from unwittingly running into system-wide trouble. Okay, now let's save and exit the file. Now the .profile file is usually read when our shell boots up. If we want our shell to read the new version of the file, we have two choices. We can either reboot the shell by restarting our terminal, or we can use the source command to reload the file. The source command is usually the more convenient method, so let's use that. If we run source ~.profile, this will cause bash to reload the .profile file. Now if we take a look at our path again, using echo $path, we can see that our path has been successfully updated to include our scripts folder. Great! Now because our first script is in our scripts folder, we can now run it from anywhere on our system. For example, we're currently in our home directory, but if we just type our first script, we can see that it runs perfectly. Awesome! Now whenever we want to add a new script to our path, all we have to do is move it to that folder and ensure that the script has execute permissions, just like we saw in the previous videos. For example, if we move back to our bash course folder, and we move the backup script that we created in the last challenge into our scripts folder, and then we move back to our home directory, we can see that we can run our backup script just fine without needing to be in the same folder as the script. It's really as simple as that. So to recap, in this video, you learned that the path variable tells the shell which directories to search for executable files. You've learned how to add folders to your path by editing your .profile file, and you learned that by placing scripts inside any of the folders on your path, you can make them easily accessible no matter where you are on your system, in the same way that built-in commands are. It's useful to point out that you should also try, wherever possible, to avoid giving your scripts names that may conflict with any pre-existing commands on the system. Other than that, well done. You've come a very long way in such a short time and have now completed the first section of the course. To make sure that you've got everything, in the next video we're going to summarize all that you've learned during the first section and give you a super shiny section cheat sheet. So for all that good stuff, I'll see you in the next video. Hello there you beautiful person, and congratulations for finishing the very first section of the course, all about how to structure and run your bash scripts. You've made some really excellent progress and have learned a lot about what scripts are, their components, and how to run them. In this video, we're just going to have a quick recap of the key points in this section so that you can make sure that you're comfortable with everything before moving on. I've also put a cheat sheet summarising everything that we've covered in this section of the course in the resources section for this video, which you can download and refer to whenever you need to. I'll be doing that at the start and end of each section of the course from now on, so you've always got the notes ready to hand. So with all that said, let's have a recap. In this section, you learned that bash scripts have three core components: the shebang line, the commands, and the script's exit statement. The shebang line tells the Linux operating system which interpreter should read this particular script. In essence, it tells Linux which language the script is written in. When you are writing bash scripts, the shebang line will pretty much always be #bin/bash, so you can just commit that to memory. The commands define what the script actually does. These will be dependent on the task at hand. And the exit code that is given off by the script's exit statement lets the shell know whether the script ran successfully or not. In short, an exit code of 0 means a successful run, and a non-zero exit code means an unsuccessful run. You then learned how to add comments to your scripts to explain its functioning to other people who might want to use it, as well as to yourself long after you've forgotten what the script does and how it works. Alongside inline commenting to explain your code, you learned that there are also 5 professional components that you can add into your script: the author information, the created date, last modified date, script description, and script usage. To add a comment, you simply started a given line with the hash symbol. We then looked at how to give your scripts appropriate and secure permissions using the chmod command and a cool website called permissionscalculator.org. You use permissionscalculator.org to find out the appropriate octal code to use with the chmod command for any set of permissions you might want to give a file. Unless you have a particular reason, we advise for security purposes in this course that, as a default, you give read, write, and execute permissions to the file's owner, but just read permissions to everyone else. These permissions are represented by an octal code of 744. And finally, you learned how to add scripts to your path to allow them to be accessible from anywhere on your system, just like regular commands. So you've covered a whole lot of stuff in this section, and now at the end, you should be able to explain the difference between the shell and a script, identify the 3 core components of a bash script, use inline commenting to clarify your script's functioning and add the 5 professional components to your scripts, set appropriate and secure execution permissions for your scripts, and add scripts to your path so that they can be run from anywhere on your system. And as I say, there's a cheat sheet available in the resources section for this video that you can download that contains all the key points from this section of the course for you to review whenever you want. Now in the next section of the course, we're going to be starting our journey into the wonderful world of bash syntax. Bash's rather strange syntax can be a barrier for newcomers, but don't worry, in this course we're going to build up your knowledge and skill step by step so that you'll hopefully be writing bash scripts fluently in no time. I don't want to spoil too much here though, so to take your bash scripting skills to the next level, I'll see you in the next video. Hello there you beautiful people, and welcome to this section of the course where we'll be beginning our journey into the wonderful and slightly mysterious world of bash syntax. I've done the best job that I can to deconstruct bash's syntax into a digestible format, and over the next 6 course sections or so, we're going to be taking a laser-focused approach on each important area of the bash language so that you can become confident fluently writing bash scripts in no time. So let's take a look at what we're going to be covering in this section of the course. In this section, we're going to be focusing on 2 core concepts that you'll use all the time when you're creating bash scripts. These are variables and shell expansions. Variables are what allow us to store useful data in our bash scripts so that we can work with it later, such as a user's username or a path to a specific file. Shell expansions, on the other hand, are a set of powerful features that bash provides to make it easy to do really useful things, like retrieve data from variables, work with the result of a command, and do mathematical calculations. Variables and shell expansions will prove to be absolutely core to everything you do when creating bash scripts, and you'll use the skills that you'll learn in this section time and time again. By the end of this section, you'll be able to create user-defined variables to save useful information in your scripts under convenient names of your choosing. You'll be able to use some common environment variables built into the bash shell that you can use to quickly access useful information about your system. You'll be able to use parameter expansion to get data back out of your variables, and you'll be able to use some parameter expansion tricks to modify that data in a variety of useful ways. You'll be able to use command substitution to work with the output of commands and save that output inside variables for later use. You'll be able to use arithmetic expansion and the BC command to do simple mathematical calculations. And finally, you'll be able to use tilde expansion and brace expansion to make your work with bash more convenient. Don't worry if all these concepts and terms are new to you. We'll be walking through them together step by step, and by the end of this section, you'll be able to see just how simple and useful they really are. As I mentioned at the end of the last section, from now on, I'm going to be attaching the section cheat sheet to the introduction and the summary videos of each section, so feel free to download this section's cheat sheet from the resources section of this video so you can keep it handy in case you want to refer to it as we go through. Okay, so we've got some very exciting topics to cover, so I'll see you in the next video where we're going to get started with user-defined variables and parameter expansion. Hello there you beautiful people, and welcome to this video where we're going to be learning about variables and a concept called parameter expansion. In this video, you're going to learn what parameters and variables are, as well as how to create variables and retrieve values from them. By the end of this video, you'll be able to create your own variables to store data under convenient names, and you'll be able to use parameter expansion to retrieve that data and use it as the input to commands. Okay, so let's start off with a few definitions. First of all, what is a parameter? Well, according to section 3.4 of the GNU Bash manual, which I've put a link to in the resources section, a parameter is any entity that stores values. Shell parameters are used to store and reference useful data that we can use in our scripts. There are 3 different types of shell parameters in Bash. There's variables, positional parameters, and special parameters. We will cover all 3 of these in the course, but variables are probably the most common type, so we'll be starting with them in this video. In short, variables are parameters whose values you can manually change. If you've not come across the concept of variables before, I want you to think of them like little boxes in your programs. Each box can have a name and can hold a certain value inside it. When you assign a value to a variable, you put data into the box. When you reference a variable, you get the data back out. That's important, so let me say that again. When you assign a value to a variable, you put data into the box, and when you reference a variable, you get the data back out. Okay, so with that in mind, let's take a look at how to create and use variables in our Bash scripts. Let's create a blank script in our Bash course folder called variable practice and add our shebang line. Right, now to create a variable, we need 3 things: a name for the variable, an equals sign, and the value we want to put inside the variable. Let's say we want to create a variable called student and store the name Sarah in it to use later. To do this, all we have to do is type student equals Sarah. Here we are telling the shell to create a variable called student and to store in it the value of Sarah. It's important to note here that there should be no spaces around the equals sign when you're working with Bash. If you do leave a space, Bash will think that the word student is a command and give you the command not found error. So remember to remove any blank spaces from around the equals sign when you're assigning variables in Bash. Now what we've made here is, in Bash terms, a user-defined variable. It is user-defined because we, the user, have created it and given it its name. User-defined variables sit in contrast to shell variables, which the Bash shell itself creates and gives names to. We'll be covering shell variables in the next video, but for now, just be aware that they exist. In Bash, it is customary to give user-defined variables names in all lowercase. This helps to distinguish them from shell variables, which Bash typically gives all uppercase names, so try to stick to naming your variables in all lowercase wherever possible. Okay, so now we've got some data saved in our student variable, let's see how we can get the data back out again. Let's say that we just want to print Sarah's name to the screen using the echo command. We could type echo, then hello, $, curly bracket, student, then a closing curly bracket. And then when we run this script, we see that we get hello Sarah printed out to the screen. So how does this work? Well, do you remember earlier when I said that when you assign a value to a variable, you put something into the box, and when you reference a variable, you get the data back out? Well, the $curly brace syntax here is used to reference a parameter, which in this case is a user-defined variable called student. The shell will then look for a parameter with the name student, and then replace the $curly brace syntax with the variable's full value. This process is called parameter expansion. So, in other words, by typing $curly brace student curly brace, the shell looks for a parameter called student and replaces the $curly brace student curly brace with the parameter's value, which in this case is Sarah. Pretty cool, right? So what's the benefit of this? Why don't we just write Sarah's name in our command? That would be much easier, right? Well, the main benefit of what we've learned so far is when you want to reference a given value in multiple places in your script. By using variables, you can change the value in one place and have the whole operation of the script change. This saves you a lot of typing and can make your scripts less error-prone. For example, imagine that you're creating a script to send emails on behalf of the company to thank a group of employees for their hard work. You can imagine someone writing something like this. Employee equals Sarah, then echo dear $curly brace employee curly brace. Echo, the board and I would like to thank you for the excellent work that you've been doing over the last few months. Then echo keep up the good work, $curly brace employee curly brace. Echo best wishes, echo Karen, CEO. Now if we run this script, we get a letter printed out to Sarah. Every place where employee was referenced, the name Sarah was filled in, as we'd expect. Now if we go back in and quickly change the name of the employee to John and rerun it, we get a different letter printed out with all the names changed to John. So just by changing the value we store in the employee variable in one place at the top of our script, we can change the way our script functions in multiple places. This is not only easier, but it's also less error prone than changing each value yourself manually. Although it might seem basic right now, as we progress throughout the course, variables and parameter expansions are the kinds of things that will allow us to operate on hundreds, if not thousands of files and pieces of data in our scripts with very little effort. But let's not get ahead of ourselves. We'll be covering all of that cool stuff in the later sections of the course, but for now I just want you to grasp 3 fundamental concepts. Firstly, according to the Bash manual, a parameter is an entity that can store values. There are 3 types of parameters in Bash. There's variables, positional parameters, and special parameters, with variables being the most common type. There are also 2 types of variables, user-defined variables and shell variables. We will cover the other 2 types of parameters, which are positional parameters and special parameters, in a later section of the course. Secondly, you learn that you can create user-defined variables by writing a name in all lowercase, an equal sign, and then the value you want to give the variable. Just make sure that there are no spaces around the equal sign, or you'll get a command not found error. Finally, you saw that to get those values back, we simply put the name of the variable we want inside a $curly brace syntax. This will cause the shell to look for a parameter with the name that we give it, and replace the $curly brace syntax with the parameter's full value using a process called parameter expansion. As a final side note, if the shell can't find a parameter with the name you give it, maybe because of a typo or because the parameter wasn't created yet, it will simply replace the $curly brace syntax with pure nothingness. This video has focused solely on user-defined variables, which are variables that you name yourself. But Bash makes loads of useful information available in what are known as shell variables, and it would be great for us to know how to take advantage of those. So I'll see you in the next video, where we'll be going over some very useful shell variables that you can use in your scripts. Hello there you beautiful people, and welcome to this video where we're going to be looking at shell variables, which are also known as environment variables. In the last few videos, we've been focusing on user-defined variables, which are variables that you, as the shell user, define in your scripts. However, there is another type of variable, called shell variables, that have particular meanings to the Bash shell, and that it sometimes even creates for you to make your life easier. In this video, you're going to learn about some commonly used shell variables, what they do, and how to use them for yourself. By the end of this video, you'll be able to explain the difference between Bourne shell variables and Bash shell variables. You'll be able to explain the purpose of the path, home, user, hostname, host type, and PS1 shell variables. And you'll be able to access the data held in these variables for yourself. So let's go ahead and get started. Okay, so let's start off by taking a look at what shell variables are. Chapter 5 of the Bash manual, which I've put a link to in the resources, tells us that there are 2 types of shell variables. There's Bourne shell variables and Bash shell variables. If you remember back to the beginning of the course, where we were talking about the difference between a shell and a script, you learned that there are many different types of shells. There's the Bourne shell, created by Stephen Bourne in 1979, there's the KSH shell, the C shell, and many others. Now the Bash shell is actually based on Stephen Bourne's Bourne shell. This is where Bash gets its name as the Bourne Again shell, or Bash. Unsurprisingly then, some of the shell variables available to Bash are the same as those available in the original Bourne shell. And these variables are called Bourne shell variables. As Bash has become more developed over time, other variables have been introduced that are specific to Bash alone, and these are called Bash shell variables. In essence, however, all shell variables are names recognized by the shell to have particular meanings. Sometimes, Bash will populate these values with useful information so that you have that information on hand. Other times, these variables will have significance to a specific command that will either read data from or save data in one of these specifically named variables. There's quite a lot of them though. There are 10 Bourne shell variables and around 95 bash variables, so we won't be able to cover them all here. In this video, I kind of want to make you aware that they exist, where to read more about them, and just to show you how to use some of the more common ones. Shell variables aren't really things that you memorize, but rather they're things that you become more familiar with over time as they become more relevant to you and your workflow. If you're curious, you can easily read what they all do by taking a look at Chapter 5 of the Bash manual, which I've put a link to in the resources section of this video. Okay, so let's take a look at a few common shell variables. Firstly, let's start with the path shell variable. That's right, the path variable that we saw earlier is actually a shell variable. A Bourne shell variable, to be exact. We've already seen how useful the path variable is and how it stores all the directories that the shell should search for executable files. We can take a look at the value stored in the path variable by typing echo $, curly brace, path, curly brace, or simply echo $path, which is how we saw it earlier on. I want to take the chance here to mention that although in the last video I showed you parameter expansion being done using a $curly brace syntax, which is the more, quote, official way of doing it, Bash does provide you this handy shortcut of not needing to write the curly braces when you just want to do something simple with parameter expansion, like when you're just referring to a variable's value. Parameter expansion can do a lot more though, as we'll see in the next video on parameter expansion tricks, but for now just bear those two ways of doing parameter expansion in mind, the way with the curly braces and the one without. Because it's easier, we'll stick to using the simple syntax without curly braces going forward whenever I'm just referring to a variable's value. Okay, so let's take a look at another useful shell variable, the home variable. The home variable is used to store the absolute path to the current user's home directory. If I echo $, curly brace, home, curly brace, or simply echo $home, you can see that this has displayed the absolute path to my home directory on the screen, which is /home/zed. Okay, now let's take a look at the user variable. There are many instances when we might want to get the username of the current user, like if we were making an interactive script of some kind and we wanted to greet the current user by name, or if we wanted to automatically include the user's username in the name of an auto-generated file. In these instances, we could use the user shell variable. So if we echo hello $user, we see that we get the current username printed to the screen. While the $home and $user variables tell you about the user who was logged in, the $hostname and $hosttype variables tell you about the computer that they're using. For example, the $hostname variable tells you the name that the user has given to their computer, which can be quite useful for setting up local computer networks. So if we do echo $hostname, we get the hostname of the computer printed out, which in my case is IoT Academy. The $hosttype variable tells you what type of processor architecture the current computer is running. Now on Linux, the packages that you download and install tend to be built and optimized for specific processor architectures, so the information held by the host type variable might be very useful information to have if you wanted to write an automated installation script that will download different packages depending on the architecture of the computer the script is running on. If I run here echo $hosttype, we can see that I'm running a computer with an x86-64 architecture, which is the name for the Intel 64-bit family of processors. The final shell variable I want to cover here is the PS1 variable. PS1 stands for prompt string 1, I believe, and it is the PS1 variable that controls the prompt string that you see on each command line in your terminal. If we take a look by echoing $PS1, we can see that we get this absolutely horrendous output in typical Bash-like fashion. Now, most of this is just the color codes that are responsible for adding the color to the prompt, but let's modify it quickly to show you what happens. It is worth noting at this point that although some shell variables come with preset values, you can manually modify any shell variable just like you can with user-defined variables. Okay, let's say that we went super minimalist and we just wanted the $ symbol to be our prompt before our commands. we could just type ps1 equals, then in double quotes, $, colon, and a space. We're adding a colon and a space here to give us some room on the command line after the prompt. And now, when we press enter, we see that all subsequent command lines have that prompt that we just defined. Isn't that cool? We can always change it back by reloading our .bashrc file using source /.bashrc, and we see that everything is back to normal. Now, some people like to play around with their prompt to customize it and make it colorful and whatnot, which you can do by editing your .bashrc file. I put a link to a great website called easyprompt.net, which gives you an easy interface to generate the code to build a cool prompt, complete with colors and everything. Check it out if you're interested. As a final note, you'll probably have noticed that all the shell variables that we've gone through have uppercase names. In fact, pretty much all shell variables are given names in uppercase to distinguish them from user-defined variables, which, if you remember, you should try to give names in all lowercase where possible. So that's it for our whistle-stop tour of shell variables. Although we've covered a lot in this video, we've only been able to scratch the surface of all the different shell variables available. If you want more information, please refer to the link in the resources section to Chapter 5 of the Bash manual. In this video, we've seen that shell variables are variables that, instead of being created by you, are actually created by the shell. You learned that there are two types of shell variables, Bourne shell variables and Bash shell variables. Bourne shell variables are variables that Bash has inherited from the original Bourne shell, whereas Bash shell variables are specific to Bash only. We also took a look at some commonly used shell variables, such as the home, path, user, hostname, host type, and ps1 variables. These have various functions that you will likely need to use here and there in your scripts. And finally, you learn that shell variables are named in all uppercase to distinguish them from user-defined variables, which should be given names in all lowercase. So, now that you know about user-defined variables and shell variables and how to access their values using basic parameter expansion, we're now going to move on to look at some very cool parameter expansion tricks that you can use to give you a lot of abilities when it comes to accessing values that you store in variables and other parameters as well. So for all that good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where you're going to learn some cool and highly convenient tricks that you can use to manipulate the values of parameters. By the end of this video, you'll be able to modify the case of your parameters, determine the length of parameters, and slice parameters to only output the specific parts that you want to work with. These are all very useful things to be able to do, so let's go ahead and get started. So first of all, we're going to look at how we can modify whether our parameter's value is represented in uppercase or lowercase. Being able to control whether our text is upper or lowercase can be very useful when we're formatting text for output or for making sure that data is all in a specific format before performing logical comparisons. So let's start off with creating a user-defined variable called name. In this example, I'll be using my name, but I'm going to write it in different cases so that we can see the changes. So I'll use name equals capital Z, lowercase I, capital Y, lowercase a, and capital D. Now, as we know, we can just echo this out to the screen like so. Echo $name. But if you remember, we can also wrap our parameters' names in curly braces when we're doing parameter expansion, like so. Echo $curly brace name curly brace. And this gives us access to Bash's more advanced parameter expansion features. For example, let's say that we wanted to convert the first letter of my name to lowercase. To do this, we can just add a comma after the parameter name, like so. And when we press enter, we can see that this has changed the first letter of the name variable's value to a lowercase. How cool is that? Note that the original value itself hasn't changed, it has just been represented differently. For example, if we remove the comma and print the name again, we can see that the parameter has still kept its original value. This means that we can apply different formatting to our data whenever we want without risking the modification of the underlying data, which will stay preserved. Okay, so instead of focusing just on the first letter, we can also easily change the entire parameter's value to lowercase by adding 2 commas instead of 1, like this. Now when we press enter, we can see that the entire parameter's value is now shown in lowercase. This is a very handy thing to be able to do when trying to compare whether two pieces of data are equal to one another, because the shell is typically case sensitive. Okay, now that we've seen lowercase, let's take a look at uppercase. Let's say we wanted to only capitalize the first letter of a piece of text. This is very useful when formatting people's names, for example, because people's names are usually written beginning with an uppercase letter. Our variable already has an uppercase first letter, but if we take a look at my username, using echo $user, we can see that my username is all lowercase, so we'll use that for this example. If we wanted to convert the first letter of a user's username to uppercase, psst, you might have to do this for an upcoming project. Now, instead of adding a comma, we would just add what is known as a caret symbol, like this: echo, $, curly brace, user, caret, curly brace. An easy way to remember this is that the caret symbol looks like a little arrow pointing up for uppercase. Now when we run this, we see that we have successfully capitalized the first letter. If you're wondering where to find the caret symbol, on my keyboard I can get it by pressing Shift and the number 6. If you have a different layout, just Google for the caret symbol, spelled C-A-R-E-T, on your keyboard, and you should be able to find it easily. And yep, you guessed it. Just like when we use 2 commas to convert the whole string to lowercase, we can convert the entire string to uppercase by using 2 caret symbols. So if we try this on our username again, like so, when we run it, we see that the whole username has been converted to uppercase. Awesome. Moving on from modifying cases, another cool thing we can do is to check the length of our variables. So while echo $, curly brace, name, curly brace will just print out the value of the variable name, we can use echo $, curly brace, hash, name, curly brace to tell us how many characters the variable's value contains. Notice here that the hash goes at the start of the parameter name, rather than at the end like the commas and the carets did when we were modifying uppercase and lowercase. And when we press enter, you can see that bash has given us 5 as the output, which is the number of letters in my name. Okay, and for my final trick, let's take a look at substring expansion, also known as slicing. Slicing enables us to take just a small section, a slice, if you will, of a parameter's value, rather than all of it. This can be very useful if only a part of a parameter's value is relevant to you at a particular time. So first, let's create a variable called numbers, and give it the value of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now the syntax for slicing is $, curly brace, the parameter name, then a colon, then an offset, then a colon, then length, then closing the curly brace. What this means is the shell will expand parameter, but start at character number defined by offset and expand up to a length of length. Let me explain what this means. In Bash and most other programming languages, a piece of text is just a set of characters strung together, which is why pieces of textual data in programming are referred to as strings. Each character or element in the string is given a number, which is called an index. In Bash, like most other languages, these indexes start at 0 and increase by 1 for each element. So, in our case, element 0 of our numbers variable would be 0, element 1 would be 1, and so on. So, for example, if we did echo $, curly brace, numbers, which is our parameter name, then gave it an offset of 0 and a length of 7, we're telling Bash to start at element 0, which is the first element, and keep expanding until the result we get is 7 elements long. So if we press enter, we see that we get back 0, 1, 2, 3, 4, 5, 6, which starts at element 0 and is exactly 7 elements long. For comparison, if we tell Bash to start at element 1 and give us a result that is 5 elements long by typing echo $, curly brace, numbers, 1 and then 5, we get 1, 2, 3, 4, 5. Okay, now as a convenient trick, if we leave out the length, Bash will assume that we want everything from our offset until the very end of the string. So, for example, if we do echo $, curly brace, numbers, colon 3, curly brace, we're asking Bash to start at element 3 and go all the way to the end. So here, when we press enter, we get 3, 4, 5, 6, 7. We didn't have to specify a length, Bash calculated it automatically. Notice, however, that I didn't put a colon after the 3. If we did put the colon, like this, then the shell will think that we put 0 as the length. A length of 0 will just give us an empty string back, so when we run this, you can see that we just get an empty result, so just be aware of that. Sometimes it might be more convenient to count our offset relative to the end of a string, rather than from the beginning. Instead of starting our offset from 0 and counting forwards, we can also count back from the end of a variable, which can be very useful if what you're interested in is usually a certain length from the end of a string. For example, if we want to get all characters that start 3 characters from the end, and get a length of 2, we could type the echo command, a $curly brace expansion for the parameter numbers, a colon, then we're going to put a space and our offset of -3. Notice that we need the space here when we have a negative offset, then a colon, and our length of 2. And as we can see, when we run this, this gives us 7 and 8. 7 is the 3rd character from the end, so bash starts there, and it expands until the total length of the output is 2 characters long. So we get the number 7 and the number 8. Just remember that when we have a negative offset, it's a rule that we have to put a space after the first colon and before the minus sign, otherwise bash will get a bit confused and not give us the result that we want. Of course, as we've already seen, we can just say that we want to start 3 characters from the end and take a slice from that all the way to the end of the variable. All we have to do is remove the length, like so. There are many more tricks that you can do with shell parameter expansion, so I've put a link in the resources section to section 3.5.3 of the GNU Bash reference manual for you to take a look at if you're interested. And I've also put the ones we have covered in this video on the sections cheat sheet for you to refer to as well. So let's have a recap of what we've covered here. So in this lecture, you learned how to use some of the more advanced shell parameter expansion features to modify the case of your variables. This is very useful when it comes to formatting and when doing logical comparisons. You've also seen how to calculate the number of characters in your variables, which will come in very useful when we later look at working with indexed arrays. You've also seen how to slice out a certain set of characters that may be more relevant to your purposes, which is definitely a useful tool to have in your pocket when you need it. Alright, so up next, we'll have a quiz to help you review what we've covered so far, and also help you get a bit more familiar with these advanced expansion tricks. And in the next video, we'll be moving on to a very powerful technique called command substitution, which is going to be a game changer for your ability to write bash scripts. So good luck with the quiz, and I'll see you in the next video. Hello there, you beautiful people, and welcome to this video where we're going to be looking at a very powerful shell feature called command substitution. Command substitution is probably one of the most useful shell features, and you'll use it time and time again in your scripts. In this video, you're going to learn what command substitution is and how you can use it in your scripts. By the end of this video, you'll be able to use command substitution to save the output of commands in variables, and you'll be able to use command substitution to use the output of one command inside another command. This is all very powerful abilities, so let's go ahead and get started. So first of all, what is command substitution? Well, it's kind of similar to shell parameter expansion. With shell parameter expansion, when we write something like $curly brace name curly brace, the shell will replace the $curly brace name curly brace with the value of the variable that it's referencing. Command substitution is very similar, except instead of typing variable names and getting the value of the variable, we can write out full commands and get the output of the command instead. A cool concept for sure, but let's have an example. The syntax for a command substitution is to write a $, like we did with shell parameter expansion, but instead of using curly braces, we simply wrap the command we want to run in a single set of parentheses, like so. What this will do is cause the shell to run the command and substitute the $command text with the standard output of the command that we run. As you can see, command substitution is a very similar concept to parameter expansion, and the syntax is rather similar too. Think of it like this. Instead of looking up the value of a parameter, like we do with parameter expansion, we are looking up the value that comes out of a command instead. To see how this works, we're going to use the date command. So let's create a script for doing this called substitution script, and add our shebang line at the top. One of the great things about command substitution is that it allows us to save the results of the command to a variable so that we can use it in our scripts later on. As a side note, for the sake of saving you time when we're watching these videos, I won't be entering the professional components or the exit status when writing many of the course example scripts. Professional components, however, are still important when doing complete scripts, so try not to forget about them when you're writing scripts for yourself. Okay, so let's say that we want to save the output of the date command as a variable called time. To do this, we simply need to write time equals, and then add our command substitution with $, parenthesis, date, parenthesis. Now, I want the time variable to contain the current time in hours, minutes, and seconds. The date command has really cool formatting options that allows you to control its output, which you can read more about in the date command's manual page if you're interested. For now though, I'm going to use the plus symbol to tell the date command that I'm going to give it some formatting information, and then type %H for the current hour in 24-hour format, a colon, and %m for the current minute, and another colon, and then %S for the current second. As you can see, this is quite a complex command, but we can use command substitution to save the output it gives in a variable with a convenient and simple name. Okay, so that should save the current time in our time variable. Now, I want to print this out to the user as part of a greeting message. So on a new line, let's write echo hello $user. The time right now is $time. Now we can save this and make our script executable with the chmod command by typing chmod 744 substitution script, and then we can run the script. And we see that the script has printed out a message with the current time. Awesome. Now if we open it back up, we can see that the script runs the date command, and then via the power of command substitution, we capture the output of that command and save that value in a variable called time. We then use parameter expansion to get the value of that variable back out as part of our greeting message. Pretty cool stuff, right? By the way, we don't need to save the outputs of our command substitutions in variables. We can actually just use command substitution to run commands inside of other commands. If this sounds complicated, don't worry, you've actually already seen it before. If I close out of this script and reopen the backup script that we created earlier, you'll see that we've used a command substitution for the date command inside the tar command. We use command substitution with the date command to calculate the file name of the backup based on the time that the script was run, which allowed us to create a new backup file every second without overwriting other backups. Awesome, right? So command substitution is a very powerful technique and you will use it all the time in your bash scripts. I just want to take a moment to congratulate you on just how much you are learning. You've come so far already, and where you're going is going to be even more exciting. So very well done. In this video, you learned that command substitution is a shell feature that allows you to grab the output of a command and do stuff with it. The syntax for command substitution is the $, and then the command you want to run inside parentheses. This looks just like a parameter expansion, except instead of using curly braces, you use parentheses instead. You learned how to use command substitution to save data in user-defined variables, and you learned how to use command substitution inside of other commands, just like we did with the backup script earlier on. Now, to help you get some practice with this very powerful technique, up next we have another project for you. After the project, we're going to be looking at how we can use arithmetic expansion to perform calculations in our scripts. So enjoy the project, and I'll see you in the next video. Hello there, you beautiful people. I hope you had lots of fun trying out this project on command substitution. In this video, I'm going to walk you through the model solution step by step, and you can grab a copy of the official solution script from this video's resource section. So let's get started. So for the first step, we can start by opening our backup script for editing using Nano. Now the first task we need to do is to add in 2 lines of code to make the script greet the user using their username and to tell them that we're going to back up their home directory. Now when you start realizing that your script needs to somehow work with the user's username or get their home directory, bells should start ringing in your head to say that you need to use shell variables. So let's follow our intuition and use the user shell variable to create the greeting line. To do this, we can simply type on the first line, echo hello $user. However, we're also asked to make the first letter of the username capitalized for formatting purposes. Now if you remember back to the parameter expansion tricks lecture, we can capitalize the first letter of a variable's value like this. First we wrap the variable name in curly braces, and then inside the curly brace, right at the end after the parameter name, we put a little caret, like a little up arrow, and that is what capitalizes the first letter of the parameter. As you can see, although Bash provides a shortcut of not needing to use the curly braces to do simple parameter expansion, putting in the curly braces gives us some really cool extra abilities, so do try to keep both parameter expansion syntaxes in mind. Okay, perfect. We can follow a similar procedure to create the second line, which tells the user that we're going to back up their home directory. Here we will use the $home shell variable and would simply type echo I will now back up your home directory, $home. Okay, so that's it for step 1. Let's now move on to the second step. In this step, we have to create a variable called current_dir and set it equal to the output of the pwd command. To do this, we have to use command substitution. So on a new line, we can type in current_dir equals to define the variable, and then we can use command substitution and put in $pwd parenthesis to make the value the output of the pwd command. Okay, so that's step 2 done. Now let's move on to step 3. For step 3, we need to let the user know that we will save the backup in that directory. This is also rather simple. We just need to use the echo command and parameter expansion again. Here we might type something like echo, you are running this script from current_dir, and echo, therefore I will save the backup in current_dir, or something like that. Here we can see how we defined the current_dir variable once, but used it in 2 places. Okay, so that's step 3 taken care of. Now for step 4, we just need to make a few changes to our tar command. The first change is that we need to remove the verbose option. The reason for this is that we want the user running the command to see the outputs of the echo command. If we leave the verbose option in there, then those outputs that we want to see will disappear up the terminal, they'll be pushed up the terminal because of the long stream of information that the tar command outputs in verbose mode. So to achieve this, we simply remove the -v option from the CVF options here. We now need to replace the directory with our variable so that it creates the backup archive in the user's current directory instead of in the bash course folder. So to do this, we delete the ~bash course and replace it with our variable, which is $current_dir. We can also change the directory that we're backing up. Previously, we had used the tilde for this, but now equipped with our knowledge of shell variables, we can change this to $home. This will do the same thing at the end of the day, but it just gives us a bit more extra practice. Finally, for step 5, we just need to print out a message that says backup completed successfully to give our users some feedback and reassurance. Here we just type echo backup completed successfully. And that's it. So now we can save our script. The script already had execution permissions from before, so we don't need to add in those permissions again. So we can run our backup script by running backup script again, and now that you see, we get our new output in the terminal. On my computer, it says hello Ziad with a capital letter, and it tells me that it will back up the home directory. It also tells me that I'm running the script from the bash course folder, and therefore it will save the backup file in the bash course directory. All this information is very useful, as now anyone running this script can see exactly what it is doing and also know where it is saving their backup without having to actually open the script and understand the code. We also get a message saying that the backup script has completed successfully, which as a user is a nice bit of reassuring feedback. if I run ls, you can see that this has indeed created the backup in my current directory. This is great because anyone running this script can get a backup of the home directory created right in the current directory where they're working in, and they do not have to have any specific directory on their system in order for this script to work. I'm sure your imaginary colleagues will be very, very happy indeed. As some finishing touches, just remember to update the last modified date in the script, and also update the description so that our users will know that the script backs up to the current working directory, rather than the bash course directory. Okay, so I hope you had fun doing this project, and now have a good idea of how useful command substitution and environment variables can be in your scripts. You can download the official solution script for this project from the resources section of this video. Now in the next video, we'll be taking your scripts to the next level by learning how we can use arithmetic expansion to allow your scripts to perform calculations. So for all that good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be having a look at arithmetic expansion. Computers are all about numbers, and in this video you're going to learn how to perform calculations within a bash script using arithmetic expansion. And by the end of this video, you'll be able to add, subtract, divide, and multiply numbers within your scripts. You'll be able to perform exponentiation and modulus operations within your scripts. And you'll be able to explain the impact of the order of precedence of arithmetic operators. So let's go ahead and get started. So, what is arithmetic expansion? Well, don't get too worried by the name. As you've probably already noticed by now, all of the shell expansions serve very similar purposes. Parameter expansion, which we write like this, simply replaces the syntax we write with the value held in the parameter. Command substitution, which we write like this, simply replaces the syntax we write with the output of the command. Now arithmetic expansion, which we write like this, simply replaces the syntax we write with the result of a mathematical expression. You can see that the syntaxes are all really similar between the three expansions. All start with a dollar symbol, but parameter expansion follows that dollar sign with one set of curly braces. Command substitution follows it with one set of parentheses, and arithmetic expansion follows it with two sets of parentheses. Okay, so let's see arithmetic expansion in action. Arithmetic expansion allows us to do calculations in our scripts and uses all the basic mathematical symbols that you're used to from maths class. As you'd expect, plus means plus, minus means minus, slash means divide, and the star or asterisk means multiply. These symbols are called mathematical operators, and the numbers they operate on are called their operands. So, let's create a script to test some expressions in, called arithmetic script, and add our shebang line at the top. Okay, so let's say we want to add two numbers, 4 and 2, and then print the result to the screen. We could do this like so. We'd type echo, then dollar, then a pair of double parentheses, and inside there we'll write 4 plus 2. So what's going to happen here is that the shell is going to calculate the result of 4 plus 2 and replace our expansion with that result, which is 6. So as far as the shell is concerned, it will be as if we just wrote echo 6. The shell will then run that command and print 6 to the screen. So let's see this working. As usual, we're going to give our script execute permissions by typing chmod 744 arithmetic script, and then we're going to run it. And we see that the script has printed out the number 6 as expected. Awesome. Now, arithmetic expansion gets really useful when we start using variables in our calculations. So let's head back into our script and define some variables that will hold some numbers that we can use in our mathematical expressions. We can define x equals 4 and y equals 2. Okay, now let's put these variables into our addition. To do this, we'd simply replace the numbers 4 and 2 with $x and $y. So what happens here is that the shell first does the parameter expansions, so $x becomes 4 and $y becomes 2. The shell then does the arithmetic expansion and calculates the result of 4 plus 2, which is 6. And finally, the shell runs the command echo 6, and 6 is printed out to our terminal. Now if we save it, and we run it, we see that, yep, we get 6 printed out to the screen. Great. Now, arithmetic expansion actually provides us with a very convenient shortcut. When doing arithmetic expansion, instead of putting $x and $y like we normally would have to, we can simply put x and y. If we save that and run it again, you'll see that we get exactly the same result, which might save us some typing. Okay, now let's try out the other operators in our script. Let's also add in, under our addition, another expansion for subtraction, then another one for division, and another one for multiplication. Okay, now we can save our script and exit, and then run our script. As you can see, our script now prints out 6, which is 4 plus 2, 2, which is 4 minus 2, 2 again, which is 4 divided by 2, and finally we have 8, which is 4 multiplied by 2. Awesome. It's good to see that maths is still working. In arithmetic expansion, you're able to use multiple operators within the same expression. Now, just like in regular maths, arithmetic expansion has an order in which it performs the different operations to make sure it gives the right answer. Let's say we try to run echo $, double curly braces, 2 plus 3 times 4. Now the result of this is 14, and not 20. As in mathematics, the shell is adhering to the order of precedence where multiplication has a higher precedence than addition and is therefore run first. So the shell first did 3 multiplied by 4, which is 12, and then added the 2 to get 14. If we wanted to get the 2 plus 3 to happen first, we would have to wrap them in parentheses, like this. Because parentheses have the highest precedence, the shell will now calculate 2 plus 3, which is 5, and then times that by 4 to give the final answer of 20. Note that if two operators have the same precedence, then the one that occurs first, when read from left to right, will be performed first. You can refer to the cheat sheet for this section of the course for a breakdown of how arithmetic expansion handles the order of precedence of the various operators. Now, there are a lot of other expressions that you can do with arithmetic expansion, and we're going to just take a look at 2 more here. The star operator performs exponentiation, which is raising a number to the power of another number. So if we now run the command echo $, double parentheses, 4 **2, as you can see, this has given us the output of 16, which is the result of 4 to the power of 2. Or 4 times 4. And the final operator we're going to cover here is the modulo operator. The modulo operator will perform a division like usual, but instead of giving the result of the division, it will give the remainder of the division instead. For example, if we run the command echo $, double parentheses, 4 %2, we get 0. This is because there is nothing remaining after dividing 4 by 2, because 2 goes into 4 exactly. Now if we change our numbers and try to find the remainder of 5 divided by 3, you'll see that we get the output of 2. This is correct because 2 is the remainder from dividing 5 by 3. 3 goes into 5 once, with 2 left over. The modulo operator is a cool way to check whether a number is divisible by another number. If one number is divisible by another, then the remainder of the division will be 0. And if they aren't, then the remainder won't be 0. Programmers use tricks like this to tell whether a number is even or odd by checking whether a number is divisible by 2 or not. In fact, being able to do this and build a so-called fizz-buzz program is a common test in programming interviews, so modulo might end up being your friend for landing a programming job. Now at this point, it's important to note that arithmetic expansion cannot manage decimal numbers. It can only take whole numbers as input and give whole numbers as output. So if we try to calculate 2.5 plus 1, you'll see that we actually get an error, with Bash saying that it doesn't understand what the dot in 2.5 is. If we try to calculate 5 divided by 2, we get an output of 2, where the answer should be 2.5, arithmetic expansion can't give us decimal numbers, so it just gives us the whole number part, which is 2. Because of this limitation, we will often need to use the BC or basic calculator command if we want to work with decimal numbers in Bash, and so we'll be covering that in the next video. For now though, let's wrap up with a quick review. In this lecture, you learned that arithmetic expansion is a shell feature that allows you to do mathematical calculations with whole numbers in your scripts. You learned that the syntax for arithmetic expansion is $, then some mathematical expression inside a pair of double parentheses. This is similar to command substitution, but instead of substituting the output of a command, it substitutes the solution to a mathematical expression. You learned how to use different operators in your arithmetic expansions to work with numbers in different ways. And you learned that arithmetic expansion uses an order of precedence when handling operators to determine which operators get run first, similar to how symbols in mathematics are handled. Check the section's cheat sheet for more info on this. Now, as discussed at the end of this lecture, arithmetic expansion is unable to handle decimal numbers. So in the next lecture, we're going to be looking at the BC command, and we're going to be using it to handle decimal numbers within our scripts. So for all that mathematical goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be having a look at the BC command. As I said at the start of the last video, if you're not interested in learning how to perform mathematical operations in your scripts, then you can feel free to skip this video. But if you are interested, then welcome to the right place. As I mentioned at the end of the last video, arithmetic expansion is not able to handle decimal numbers, but don't worry, this is where the BC command comes in. In this video, you're going to learn how to use the BC command to handle decimal numbers in your Bash script calculations. By the end of this video, you'll be able to use the BC command to execute mathematical expressions that require decimal values, and you'll be able to set the scale variable within the BC command to determine how many decimal places should be provided in the output. So let's go ahead and get started. So what is the BC command? Well, the BC command stands for Basic Calculator, and the GNU manual defines BC as an arbitrary precision numeric processing language. In simple terms, BC is a programming language in and of itself that can work with numbers to any number of decimal places. The BC command has an interactive interface which you can access by running the command BC. This opens up a calculator, which we can type in basic mathematical expressions, which it will process. For example, we can do 2 plus 2, and when we press enter, we get 4. We can do 8 times 6, and we get 48. To exit the calculator, we simply type quit and press enter. Now, although this interface is useful for doing quick calculations when working from your command line, we probably won't use the BC command in this way when writing our scripts. Instead of requiring the user to type in expressions interactively like we've just seen, the BC command also allows us to pipe expressions to it for it to calculate. Let me show you what I mean. If I run echo, then inside double quotes 5 divided by 2, and pipe the result to the BC command, again making sure that we put the actual calculation within double quotes, this will pipe the text 5 divided by 2 to the BC command for it to process. And when we run this, we get back the answer of 2. But hang on a minute. Didn't I say that the BC command handles decimal numbers? So shouldn't the answer be 2.5? Well, yes it does, but in order to make it work, we have to give the BC command something called a scale value. The BC command has an internal variable called scale, which can be used to adjust the number of decimal places that appear in the output. For example, if I want the output to have 2 decimal places, I would set a scale value of 2. If I want the output to have 5 decimal places, I would set a scale value of 5, and so on. So let's say we want to calculate 5 divided by 2 and get the result back with 2 decimal places. We can do this by running echo, then in double quotes, scale equals 2, followed by a semicolon and a space, and then 5 divided by 2, and piping that to the BC command. In this command, we have first set the scale variable to 2 decimal places, and then we passed the operation we wanted the BC command to do, which is 5 divided by 2. You'll notice, as I said, that I've put a semicolon between the scale value and the expression that we want to run. That's really quite important, so make sure you don't forget that. Also note that you need to put the scale value first, otherwise it doesn't work. So I couldn't put the expression, then do scale equals 2. It has to be scale equals 2, semicolon, then the expression. When I run this, you can see that I now get the output of 2.50. Now, because I set the scale variable to 2, the BC command only gave me 2 decimal places in the output. If I change this to, say, 10, we can see that we now get 10 decimal places out. So that's it. That's how you can perform decimal calculations in your bash scripts. So now that we've gone through all that stuff, let's just have a quick recap of what we've learned in this video. So in this lecture, you learned that the BC command allows us to perform calculations with decimal numbers in our bash scripts. You learned how to use the echo command to pipe operations to the BC command with the syntax echo, then in double quotes, the expression, followed by pipe and BC. You learned that the BC command has an internal variable called scale that controls the number of decimal places that are included in the output. Finally, you learned that you can set the scale variable by typing scale equals, then the number that you want, followed by a semicolon, before whatever expression you want to send to the BC command. As one final note, the operators when working with the BC command are pretty much the same as those for arithmetic expansion. The only difference is exponentiation. In arithmetic expansion, you would write 4 **2 to do 4 to the power of 2. But in the BC command, you would write 4 ⁻². So just bear that in mind. So up next, we'll have a quick quiz to make sure you're comfortable with all the great stuff we've covered on arithmetic expansion and the BC command. And after the quiz, we'll be moving on to discuss tilde expansion, which is a very useful way to make your work with bash more comfortable. So good luck with the quiz, and I'll see you in the next video. Hello there, you beautiful people, and welcome to this video where we're going to be taking a look at tilde expansion. Tilde expansion is something that you've certainly already used before in your bash scripting journey, but it has a lot of useful features that maybe you haven't come across. In this video, you're going to learn what tilde expansion is and how to use it and some of its more advanced features. By the end of this video, you'll be able to use tilde expansion to easily access your home directory and the home directory of other users. And you'll also be able to use tilde expansion to easily switch between your current and previous working directories, which is very handy. So let's go ahead and get started. Tilde expansion gets its name from the fact that it is performed using a special character called the tilde, which looks like this. Tilde expansion allows us to easily refer to the current user's home directory without having to type out the full path. For example, if I run echo tilde, you can see that this has expanded the tilde character to my home directory, which is /home/ziad. I didn't need to type /home/ziad to make that work. Tilde expansion did the hard work for me. This can save us quite a bit of typing when writing scripts, and it will also make our work more convenient, more concise, and less error prone. Now this is the typical way that you'll probably have already used tilde expansion before, but tilde expansion can do quite a bit more. For example, what follows from the tilde character is also evaluated to see whether it is a valid username on your current system. And if it is, then tilde expansion will expand to the home directory of that user. Now for demonstration purposes, I've also set up another user on my system called colleague. And if I run echo tilde colleague without any space or slash or anything, just tilde colleague, then instead of my home directory, we get colleague's home directory given back. Even though you might not have a user called colleague set up, every system has the user called root, which is the account of the system administrator. You can try this tilde expansion out by looking at the root user's home directory by typing in echo tilde root, which will give you back the root user's home directory, which is /root. As we can see, including a username following the tilde character will expand to that user's home directory instead of the current user's home directory. This can be useful when writing a script as a system administrator that needs to modify many people's home directories. Of course, this expansion doesn't work if the user doesn't exist on your system, so if I just do echo tilde abcd, for example, we can see that I just get back the literal text tilde abcd. The tilde expansion didn't work. Now, tilde expansion can do more than just expand to home directories. We can use it to provide convenient shortcuts to directories that we've already visited. Your current directory is always stored internally in bash within a shell variable called uppercase pwd. The uppercase pwd here stands for print working directory. For example, I'm currently in my home directory, which is /home/ziad. If I echo $pwd, we see that /home/ziad gets printed to the screen, because that's the current directory that I'm in. Okay, now let's say that we change our directory to the /etc directory. If we echo $pwd, you can see that we're now in the /etc directory. However, bash also keeps track of our previous directory in a shell variable called oldpwd, which is again all in uppercase. So if I echo out $oldpwd, we can see that it has stored my home directory, which is the last directory that we were in. These variables are very handy in circumstances when you want to keep moving back from one folder to another, like your shell might need to when performing an installation script. However, the variables are kind of long to type out. Fortunately, tilde expansion provides us with some useful shortcuts that we can use. We can write tilde plus as a shortcut for referencing the pwd variable, and we can write tilde minus as a shortcut for referencing the old pwd variable. Because old pwd and pwd are automatically updated every time we change a directory, there's a cool trick we can do with tilde expansion if we have a script that requires us to move between two directories repeatedly. We can actually keep using cd tilde minus to switch back and forth between the two directories at will. For example, at the moment I'm currently in the /etc directory. If I do cd tilde minus, we can see that I've switched back to my home directory. If I do cd tilde minus again, then I can seamlessly switch back to the etc directory. I can do this forever and over again, which can be very convenient in scripts where you repeatedly switch back and forth between two directories. So as shown by these examples, tilde expansion within the shell can be a very handy tool to have when writing scripts that need to work across multiple directories. Although I've tried to cover the features you're likely to use most often, there are other useful ways that the tilde expansion can be used, and I encourage you to check them out in the link I provided to the appropriate section of the bash manual if you're interested. In this video, you learn that, by default, a tilde character on its own will expand to the current user's home directory. As a technicality, a sol tilde is actually expanding to the current value that's stored in the $home shell variable. This will usually, and pretty much always, be the current user's home directory, but if you're interested, you can have some fun changing the $home variable and seeing how that affects tilde expansion. You learn that any text that directly follows the tilde without any space is checked to see if it is a valid username. If it is a valid username and that user is found, then the tilde expansion is converted to the path to that user's home directory. You also learned about the existence of the pwd and old pwd shell variables, and how you can use tilde plus and tilde minus respectively to refer to them, and conveniently switch back and forth between two directories. Okay, so that's it for tilde expansion. In the next video, we'll be taking a look at brace expansion and how you can use brace expansion to do some pretty magical things that would be near impossible to do on a graphical user interface. So for all that good stuff, I'll see you. Hello there, you beautiful people, and welcome to this video where we're going to be looking at brace expansion. Brace expansion is a way to generate sequences of text that follow a particular pattern, and it comes in really useful when you want to operate on lots of files or folders that follow a similar naming convention and you don't want to manually type out each of the different values. In this video, you're going to learn about the different ways to use brace expansion in your scripts. And by the end of this video, you'll be able to use brace expansion to generate text that follows particular patterns of your choosing, and no joke, you're going to gain bash superpowers. Now everyone wants to get bash scripting superpowers, so let's go ahead and get started. Okay, so as its name suggests, brace expansion is performed using curly braces. There are two types of lists that you can expand to within your braces. The first type are called stringed lists. String lists can contain any set of individual characters or words. String lists are useful for expanding out to months of the year, for example, or expanding out a set of usernames. The second type are called range lists. Now, range lists are useful for rapidly expanding out sequences of characters that follow a particular order, like the letters from A to Z or the numbers from 1 to 100, for example. Now, range lists lose some of their flexibility that string lists have, because string lists can contain any value, but because each value in a range list does not need to be typed manually, range lists make up for this lack of flexibility with their increased ease of use and extensibility. Let's take a look at some examples with the echo command to see how this all works. As I mentioned, when using string lists, the values do not need to have any specific order or any specific type. We can simply type echo, and then inside a pair of curly braces, pretty much anything we want separated by commas. So for example, we could type A, 19, Z, Barry, 42. Now as you can see, when we run this, the shell has expanded these different words, letters and numbers. A more useful example would be to expand out to the months of the year, like echo, then in curly braces, Jan, Feb, March, April, May, June. Now it's important to note that you cannot put any unquoted spaces before or after the commas in your braces when making a string list. If you do, then the spaces stop the shell from interpreting the brace expansion and the whole thing is treated as a normal command line argument. For example, if I run the original command but put a space between May and June, you can see that the shell has not done any expansion and has just passed the entire string to the echo command as a single command line argument. The same happens if we put a space at the beginning. So if I get rid of the space between May and June, but put a space just inside the first curly brace and then run it, we can see that again the shell has interpreted this just as one solid string rather than as a brace expansion. Although they're very flexible, string lists are often quite tedious to type out. Range lists can make our lives easier when working with continuous sequences of letters or numbers, like the numbers 1 to 1000 or the letters A to Z. To show the difference, let's create another string list to print the numbers 1 to 10. In a string list, we would need to write echo, then in curly braces, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now this is simple enough, but it took quite a bit of effort to type out. Now when we use a range list, instead of using commas to separate each value, we can start with the first value, so echo 1, and then just enter ... and the final value, which is 10. Now like the commas in the string list, there mustn't be a space around the double dots in a range list though, so do bear that in mind, no spaces around the double dots. And we see that this gave us the same output as the previous command, the numbers 1 to 10, but it was a lot easier to type. It's also arguably easier to read. It just says echo 1 to 10 when you read it. We can also do range lists in reverse. So we can echo 10 to 1, and you'll see that we get the numbers from 10 to 1 this time. We can also do exactly the same with letters in the alphabet. So if we run echo A to Z, you can see that we get the letters from A to Z. Range lists really shine when we consider that there is no limit to the size of the ranges that you can expand to. So even if you wanted 1,000 numbers, you can type echo 1.1,000, and as you can see, all the numbers between 1 and 1,000 get printed out with very little effort. Something like this would not be easy to do with string lists. You can even control the step between each value. So for example, we can do echo 1.1,000 again, but this time we're going to add in ... 3 at the end. You'll notice that now, what we get is the numbers from 1 to 1,000 in steps of 3. It's important to point out that range lists can only expand out to characters that follow a straightforward sequence. The numbers 1 to 10 and the letters A to Z obviously follow simple sequences, but if we did, for example, echo 1 ... Q, then that doesn't work, because there's no obvious connection between 1 and Q. It also doesn't work with the names of months, unfortunately. So if I did echo Jan ... December, although January and December make sense to us as humans, they don't have any special meaning to computers. A computer would be much happier with numbers 1 to 12 to represent the month numbers, for example. Speaking of which, let's explore this as a practical demonstration. Let's say that you wanted to make a digital journal on your computer to keep track of memories of what's going on in your life over time, and you wanted to create a folder for every month of the year to store your entries in. We can use brace expansion with the mkdir or make directory command to achieve this. So let's make a directory called journal using mkdir journal and move inside of it with cd journal. Now we want to use brace expansion to create our folders. Because they're so powerful, it's usually a good idea to test out your brace expansions using the echo command to see what results they give before you commit to using them in a real command. So I'll be doing that here to demonstrate. Now, brace expansion allows you to add fixed pieces of text to the beginning and end of each element of the expansion. So for our folders, we can do something like month, and then add in our brace expansion, which is curly brace 1.12 for the 12 months of the year. The month here will be prefixed to the command. So it would actually expand to month 1, month 2, month 3, all the way up to month 12. It would be nice though if instead of having 1 digit for months 1 to 9 and then 2 digits for months 10 to 12, if we could have the names of our folders have the same length. So instead of having month 1, month 2, month 3, let's say we wanted to have month 01, month 02, month 03, all the way up to month 12. Well, brace expansion has another nice feature where you can add leading zeros to the first element of the expansion to make sure that all the values of the expansion have the same number of digits. We can do this by adding a 0 in front of the 1. Now if we test this out, you'll see that by adding the leading 0, all of our month numbers have the same number of digits. So now that we've done our testing, and we're getting the results we want with our echo command, let's run this brace expansion with the mkdir command to make our folders. A quick ls shows us that we now have the folders that we want. Awesome. Okay, now to finish off our journal, let's say we wanted to create 31.txt files within each of these folders to hold each day's entry. Now obviously not every month has 31 days, but for the sake of example, we'll use 31 days for all the folders. Okay, let's build our expansion with the echo command. Now we can refer to all of the folders that we've created at once by putting in month, then in curly braces 01.12, and then a slash, just like we had when creating the folders. Now we want each of the entries to start with the word day, and we want 31 days. So I'll put 01.31 inside curly braces there. Again, we're using the leading 0 technique here to ensure that all our file names have the same length. Now because we want all of these files to be text files, we can simply add .txt at the end of the expansion to ensure that .txt gets fixed to the end of all the file names. And as we can see, when we run our echo command, that will create all of the different files that we want to make as if by magic. I told you you'd get superpowers. Now that we've tested it with echo, we can just use the touch command to create empty files. So if we replace echo with touch and run the command, bash will go ahead and create all of those files. Now if we check the first folder using ls month 01, you can see that there are 31 files starting from day01.txt to day31.txt. We can also check another folder, for example ls month 09, and you can again see the same files have been created. So with this command, we told the shell to expand firstly into all of the 12 folders, and secondly to expand and create 31 files within each of those folders. Pretty cool, right? So that about does it for this dose of superhero training and for our coverage of brace expansion. In this video, you've learned a lot of different ways that you can use brace expansion, which can be extremely helpful when writing bash scripts. You learned that there are 2 types of brace expansion. There are string lists, which are created by having a comma between each value, and there are range lists, which are done by having the ... characters between a possible range of numbers or letters. You learned how to control the step size that is used in expanding a range list by using an additional ... followed by the required step size. You learned how to use a leading 0 to make sure that all values you expand to have the same number of digits in a range list. And finally, you also learned how to use more than one brace expansion on a single command line, along with prefixes and postfixes. So a massive well done for learning about brace expansion. It's a very, very useful trick to have in your back pocket when you need it. And it's also cool to show to your friends. So up next, we're going to have a quick quiz to make sure you're comfortable with brace expansion, and then it's on to the section summary. That's right, you've almost completed another section of the course. you are doing absolutely great. So good luck with the quiz, and I'll see you in the next video for the section summary. So well done for completing your second section of the course all about variables and shell expansions. The tools and techniques that you've learned in this section will come up time and time again when making bash scripts, so a massive congratulations for working through this section and getting to grips with them. You're doing absolutely great. Now in this video, we're going to walk through the cheat sheet for this section and have a quick recap of the points that we've covered, just to make sure that you're comfortable with everything. I've also put a cheat sheet summarising everything that we've covered in this section of the course in the resources section for this video, which you can download and refer to whenever you need to. So the first thing we learned in this section is that a parameter is simply any entity that stores values. You learned that there are three types of parameters in Bash. There's variables, positional parameters, and special parameters. Variables are the most common of the three, so we focused on them in this section. You learned that a variable is a parameter that you can change the value of, and you learned that there are two types of variables. There's user-defined variables, which are the ones that you name yourself, and there's shell variables, which are the ones that have already been pre-named and have special meanings to the shell. You learned how to create your own user-defined variables by writing a name, an equals sign, and then the value that you want to give the variable. Remember that there should be no spaces around the equals sign, and the name for user-defined variables should be in all lowercase. We then moved on to shell variables, where we learned that there are two types of shell variables. There's Bourne shell variables and Bash shell variables. We looked at some of the more commonly used shell variables, such as home, path, user, hostname, host type, and PS1 shell variables, and you saw what they contain and some examples of how you might use them. I've also put some links here to full lists of both Bourne shell variables and Bash shell variables in case you're interested and want to check them out. We learned that shell variables are named in all uppercase to distinguish them from user-defined variables, which are written in all lowercase by custom. You also saw how to use something called parameter expansion to get back the values that you store in these variables. You learned that there are two ways to do parameter expansion. There's the simple way, where you just type a $sign followed by the parameter's name. This saves you some typing, but is only really good for retrieving a parameter's value as it is. There's also the more advanced syntax, where you additionally wrap the parameter name inside some curly braces. This syntax does require a tiny bit more typing, but it allows you to do a variety of highly convenient parameter expansion tricks. We then moved on to take a look at some of these tricks, and we saw how to convert various parts of the value to upper or lowercase, how to calculate the length of a value, and how to slice out a certain set of characters. Note that none of these tricks alter the value stored in the parameter. They just change how it is displayed after the expansion, and the original data stays the same. There are more tricks that you can do with parameter expansion, which you can check out with the link here if you're interested. We then looked into command substitution, where we learned how to use the $parenthesis syntax to directly reference the output of a command. We learned how to take the output from command substitution and save it into variables, or even use it inside another command. Command substitution is a really powerful technique in bash scripting, and you used it yourself to create an improved version of the backup script that you started in the first section of the course. It was then straight into arithmetic expansions, where we looked at how to run mathematical expressions using the double parenthesis syntax. We learned about the different operators that can be used, such as the more standard plus, minus, divide, and multiply operators for simple calculations, as well as more advanced modulo and exponentiation operators. We also learned that there is an order of precedence that determines which order operations are carried out in. The table here ranks the operators in order of precedence, with the ones with the highest precedence coming first and being towards the top. Note that when two operators have the same precedence, the one that comes first, when read from left to right, is the one that will be performed first. We also looked at the BC command and how to use the BC command to work with decimal numbers, because arithmetic expansion only works with whole numbers. We learned that we use the echo command to pipe an expression to the BC command, and can use the scale variable to control how many decimal places are outputted by the BC command. We then moved on to tilde expansion and saw some cool shortcuts that we can use to reference people's home folders and also reference the current and previous working directories. And finally, we wrapped up by looking at various ways that we can use brace expansion when generating text that follows a predictable pattern. So as you can see, you've covered a whole lot of stuff in this section, and now, at the end, you should be able to create user-defined variables, store data in them, and retrieve that data using parameter expansion. Should be able to understand the purpose of common shell variables. Should be able to use the advanced parameter expansion syntax to modify the case of parameter values, calculate their length, and grab particular slices of their characters. You should be able to use command substitution to use the output of one command in another command, or to save the result of a command in a variable. You should be able to use arithmetic expansion and the BC command to do calculations within your bash scripts. And finally, use tilde expansion and brace expansion to make your work on the command line more convenient. So once again, a massive congratulations for covering all that much content. What you know already is probably sufficient to create some really useful scripts. Now in the next section of the course, we're going to take your bash skills to the next level by looking at how bash processes command lines. Bash adheres to a certain flow when dealing with commands and scripts, and it's really important to be able to understand this flow to truly understand what is happening with your commands. Understanding how bash is working under the hood will save you a lot of frustration when writing bash scripts, and will really help bash seem like a structured language rather than just a random set of rules. So for all that potentially life-changing stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this section of the course where we're going to be taking a deep dive into how bash processes command lines. The thing is, bash can be really confusing, and it's super easy to make mistakes when working with it. Aside from its strange syntax, one main reason why bash can be confusing is that whenever it receives a command line, it goes through a series of rather sophisticated steps in the background to process and interpret the command line before running it. But the problem is, bash doesn't show you its workings. All of this processing happens in the background, and the command that bash ends up running after all the processing and interpretation can end up looking quite different to the command that you gave it at the beginning. Now, unless you're aware of what's going on and the intricacies of what's happening at each stage, it can be really quite easy to get confused by the results. So in this section, I'm going to be peeling back the curtains, so to speak, and I'm going to be breaking down, in detail, each step that bash is doing behind the scenes to interpret the commands that you give it, so that instead of guessing what might work, or trying out a bunch of random things when it doesn't work, you can become a more intentional and more sophisticated user of the powerful tool that is the bash shell. So grab your cheat sheet from the resources section of this video, and let's get started. Hello there you beautiful people, and welcome to this video where we're going to be kicking off our discussion of how bash processes command lines. Now when you run a script, bash simply reads the script file line by line, and for each line, bash goes through a 5-step process to interpret the command and decide what to do with it. Getting a good understanding of this process is very valuable for your bash scripting journey, because knowing exactly how bash processes every single command line it receives will help you to avoid frustrating bugs and errors later on. In this video, you're going to get an overview of the 5-step process that bash uses to interpret a command line. And then, in the following videos, we'll focus on each of those steps in more detail. By the end of this video, you'll be able to list the 5 steps that bash goes through to interpret a command line. So let's go ahead and get started. Okay, so let's start at the very beginning, the moment when the shell receives a command line. This command line may be typed by you on the terminal, or it may be read from a script. Once the shell has got that command line, it breaks the command line into what are known as tokens. This step is called tokenization, and a token is defined as a sequence of characters that is considered as a single unit by the shell. The shell determines where a token starts and where a token ends by looking for special characters known as meta characters, and it uses these meta characters to break up the command line, kind of like how humans break up a sentence using punctuation. Okay, so once bash has broken up the line into tokens, it then classifies those tokens as either words or operators. A word is defined as a token that does not contain an unquoted meta character. Operators, on the other hand, are defined as tokens that contain at least one unquoted meta character. So by looking at the definitions of words and operators, we see that the key difference is that words never contain unquoted metacharacters, but operators always do. This makes quoting an important part of how the shell operates, and we'll discuss quoting more in coming videos. Now, based on where the words are and where the operators are, the shell then moves into step 2 of its processing flow, which is called command identification. In command identification, the shell breaks the command line up into either simple or compound commands. Simple commands are the types of commands we've been using so far, such as echo, tar, etc. Simple commands are just a bunch of individual words. The first word is the command name, and all other words are interpreted as arguments to that command. Each simple command is terminated by a control operator, which may be a new line, a semicolon, or something else, as we'll learn later on. Compound commands, on the other hand, are commands that provide Bash with its programming constructs, such as if statements, for loops, while loops, and so on. We'll be coming on to compound commands later in the course. Okay, so once Bash has determined where the simple and compound commands on a given command line start and end, it will then move on to step 3 of its process, where it will perform any required expansions. This includes all the expansions that we've currently seen, as well as some new types of expansions, such as word splitting and globbing, which we'll cover more in this section of the course. After all these expansions have been performed, the shell will then move on to step 4 of its process, which is called quote removal. We often add quotes to control how a given command or command line is interpreted, so this step will simply remove all of those supportive quotes. We'll discuss quote removal more later on in this section. After quote removal, Bash then moves on to its 5th and final step, which is where it performs any redirections. You're probably already familiar with what redirections are, but we'll be covering them with a more dedicated video later on in this section of the course. Finally, after completing these 5 steps, Bash will then execute the command line that is left over. Okay, so that's a general overview of the 5 steps that Bash goes through every time that it reads a command line, whether that be one that you typed in manually in the terminal, or when it is reading your Bash script line by line. Now, because it's such an important concept when working with Bash, let's have a quick review of everything that we've covered in this video so that you can see clearly what the steps are. In this video, you learned that the shell follows 5 steps when processing a command line. First is tokenization. Second is command identification. Third is shell expansions. 4 is quote removal. 5th is redirections. Let me just go through that again. Tokenization, command identification, shell expansions, quote removal, redirections. 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 Sick of it yet? Great, because we're going to be using it a lot over the course of this section of the course, so do try to bear that in mind. Now, when the shell has done these 5 steps, it will then execute what is left over. Now, if you get the chance, it is well worth grabbing a pen and paper and spending some time committing those 5 steps to memory. It's only 5 steps, and so it won't be too hard, especially when I repeat it 100 times like I just did, but having that flow in your head will come in very, very handy. So in the next few videos, we're going to be breaking down each of these 5 steps so that you can get a clearer picture of what's going on in each stage. In the next video, we're going to be taking a look at how the shell interprets quotes. As we saw, whether a certain character is quoted or unquoted underpins a lot of how the shell is working behind the scenes, and not clearly understanding how quotes work can cause people all kinds of issues when writing Bash scripts. The good news is that they're actually quite simple when we just pause and invest a bit of time in focusing on them specifically, and I hope that by doing that it'll save you a lot of headaches later on. So for all that quoting goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be discussing how quoting works in Bash. Quoting is a topic that affects pretty much every part of how Bash processes command lines, and not fully understanding it can be a cause of a lot of errors and frustration. So in this video, you're going to learn about the 3 types of quoting in Bash, and the different effects that these types have on how the shell processes characters on the command line. By the end of this video, you'll be able to describe the differences in functionality between Bash's three quoting methods: backslashes, single quotes, and double quotes. So let's go ahead and get started. The first thing to point out here is that a command line is just a set of characters. As you've probably already noticed by now, certain characters carry special meanings and cause Bash to do certain things. For example, we saw during the section on expansion that the dollar symbol is a special character that is used to tell the shell that an expansion of some kind is about to happen. In essence, quoting is all about removing the meaning of special characters so that they can be interpreted literally by the shell. You'll see what this means practically in a minute. Now, there are three main ways to remove special meaning from characters in Bash. There's the backslash, which will remove the special meaning from the character immediately following the backslash. There's single quotes, which will remove the special meaning of every character placed inside them. And finally, there's double quotes, which are probably the most flexible of the three. Double quotes remove the special meaning from every character they contain, except for dollar signs and backticks. As we know, dollar signs are used for various forms of expansion, and backticks are just another way of doing command substitution. Now, although dollar signs and backticks are normally still given special meaning inside double quotes allow you to throw backslashes in to remove the special meaning of these characters if you want to as well. Now, when a character has its special meaning removed, it's common to say that the character has been quoted, or that the character has been escaped, and I'll be using both of those terms interchangeably. However, in this video, I'm going to give a few examples of the different quoting types so that we can see in a general sense how each one is used. Okay, now let's say we wanted to write this command line: echo John and Jane. Now, the ampersand symbol here has a special meaning to the shell. If you've not come across it in your Linux journeys before, the ampersand is an operator that is used to make certain commands run in the background, and thus free you up to type more commands on your command line while they run. Now, because the ampersand has a special meaning, this command is not going to run as we'd expect. Instead of printing a literal ampersand to say John and Jane, the shell is going to, by default, give the ampersand its special meaning, which, as you can see, will interfere with what we're trying to do. Okay, so let's explore how quoting may be useful to us here. The simplest way to remove the special meaning from the ampersand is to put a backslash before it, like so. Now, when we run that, we see that the ampersand is now interpreted literally by the shell, and we get the output that we expected, which is John and Jane. Let's take another example. Let's say that we wanted to have a variable called filePath that would store the file path to a certain folder on a Windows machine. Now, you can probably already see the problem here. The backslash is itself a special character. It quotes the characters that immediately follow it. Here, however, we need literal backslashes to make it a valid file path. If I just create the variable as it is, and then echo it back out, you see that we didn't get the result we wanted at all. The backslashes have all done their quoting, which all had no real effect because the characters following them had no special meaning, they were just letters, and then the backslashes themselves were removed using something called quote removal, which we'll come to later on. Now, to solve our problem, we need to know how to make the shell read the backslashes as literal characters. Well, one way we could solve this problem is to put a backslash in front of every backslash, like so. Now, if we did this, and we took a look at the file path variable now, we see that it does indeed work and that we get the result we want. So what happened here is that we took away the special meaning of the backslashes using other backslashes, and that kept the backslashes that we wanted in the file path variable. However, this method is a bit hard to read and could become rather error-prone and tiresome to write if we had a long file path. In this situation, we might find it useful to go with another option and wrap the file path in single quotes, like so. Single quotes preserve the literal meaning of every single character they contain, so with this method we've quoted every backslash at once and the file path remains clean and easy to read in the script. And if we take a look, we see that we got the result that we wanted. The only rule that you need to remember with single quotes is that they cannot contain another single quote, even if that extra single quote is preceded by a backslash. So bear that in mind. Okay, now let's say we wanted to get fancy with our file name creation, and we wanted to make it so that our script can automatically calculate the file path to the current user's Windows Documents folder, like this. Here, we want our shell to do parameter expansion to replace $user with the current user's username. Now, single quotes won't work here because single quotes remove the special meaning of everything inside them. This means that the dollar symbol would lose its special meaning, and therefore the shell won't do the parameter expansion that we need. Just doing escapes of all the backslashes would work, but like before, this method is kind of ugly and hard to read. The alternative is to use double quotes, which are good for their flexibility. Double quotes don't escape the meanings of dollar signs and backticks, but give you the option of throwing in extra backslashes to escape these characters if you want to. So in this example, if we wrap everything in double quotes, the dollar signs will still be given special meanings, unless there is a backslash before them. In our case, there is indeed a backslash before our dollar sign, which again takes away its special meaning. But thanks to the flexibility of double quotes, that's easy to fix. We simply put a backslash before the backslash to undo its effect. Now when we run this and take a look at our file path variable, we see that we get the answer we want. So double quotes remove the special meaning from everything except dollar symbols and backticks. However, you still have the flexibility to add backslashes into the double quotes to remove the meaning of these symbols too, and even add extra backslashes to remove the meanings of problematic backslashes. So as you can see from this section, quoting plays a very important role in how the shell processes command lines. In this video, you learn that command lines are just strings of characters, and some of these characters have special meanings, and some of them don't. You learn that we can use backslashes, single quotes, and double quotes to remove special meaning from characters within command lines and gain more control over the way the command line is interpreted so that it works in the way that we intend. You learned how to use the backslash to remove special meaning from the next following character. You learned how to use single quotes to remove special meaning from all the characters within them. And you learned how to use double quotes to remove special meanings from everything except dollar signs and backticks, which allows you to still quote most of the characters, but still do useful things like parameter expansion and command substitution. Now in the next lecture, we're going to be looking at the concept of meta characters and how the shell uses meta characters to break up the command line via a process known as tokenization, which you'll remember is the first step in the command processing flow. We'll also explain how what you've learned in this lecture about quoting can be used to influence when and how tokenization happens. So for all that good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be taking a closer look at the first step of the bash command line processing flow, which is tokenization. Now earlier in this section of the course, I gave an overview of how bash processes command lines in 5 steps. And now that we've covered quoting, which underpins a lot of how bash works, over the rest of the section I'm going to be focusing in more detail on each of those 5 different steps. And as I said, the very first step is tokenization, so we'll be starting there in this video. In this video, you're going to learn what meta characters and tokenization are, you're going to learn how the shell uses them to perform tokenization, and you're going to learn what the different types of tokens are. By the end of this video, you'll be able to explain the purpose of the tokenization step, you'll be able to identify the 2 types of tokens and their subtypes, you'll be able to explain the purpose of meta characters in the tokenization step, and you'll be able to explain the effect of quotes on tokenization. So let's go ahead and get started. When you read a sentence, you, probably without even realizing, break the sentence up into parts based on the punctuation that you see. In a similar way, a command line is just a set of characters to the shell at the beginning, but bash has certain punctuation, known as meta characters, that allow it to break up a command line into chunks, known as tokens. A token is more formally defined as a sequence of characters that is considered as a single unit by the shell. Bash recognizes 10 possible meta characters. There's the pipe, the ampersand, the semicolon, the left and right parentheses, the less than and greater than signs, and the white space characters, which are space, tab, and new line. Now once the shell has got a rough idea of where the tokens are by finding the unquoted meta characters, it will then categorize each token as either a word or an operator. Words are defined as tokens that do not contain any unquoted meta characters. Operators, on the other hand, are tokens that contain at least one unquoted meta character. As you can see, the key difference that distinguishes whether a token is interpreted as a word or an operator is whether or not the token contains an unquoted meta character. To better see the importance of this, let me point out that there are two types of operators. There are control operators, and there are redirection operators. Control operators are used to control how a command line is processed, and here's the full list of them here. Now I don't want you to worry about knowing what these all mean or memorizing them, but some of these you may recognize at a glance. For example, you may have come across the ampersand in your Linux journey. The ampersand is a rather common control operator, and it tells the shell that this command line should be run in the background. In other words, the presence of this control operator will control how the command is carried out. In this case, it'll make the command get run in the background. Now, aside from control operators, there are also redirection operators, and these tell the shell to do certain redirections of the data streams that are connected to a command. And here's the full list of redirection operators here. Again, some of these you might recognize. Now, all of the control operators and redirection operators are made up of meta characters, and thus they only matter if they are unquoted. This means that quotes not only control whether expansions happen or not, like we saw in the previous video, but they also control how the command is interpreted and how data flows into and out of the command as well. Okay, now before going any further, let's just take a quick step back and have a brief summary of the key concepts we've covered so far. We understand that the shell uses unquoted meta characters to distinguish tokens. We also understand that the shell will then decide whether the tokens are words or operators based upon whether or not the tokens include any unquoted meta characters. If the tokens don't include any unquoted meta characters, then those tokens are classified as words, and if they do contain any unquoted meta characters, then those tokens are classified as operators. Finally, we also understand that if a given token is an operator, then it is further classified as either a control operator or a redirection operator. Okay, now let's have a look at an example of how this works. I'll ask you a couple of questions as we go through as well, so that you can practice working through the concepts in your head with me. So let's say that we have this command line. At the beginning, from the shell's perspective, this is just a sequence of characters. It doesn't know where the commands are, it doesn't know where the redirection is, it just gets a stream of characters that it needs to make sense of and do something with. Now, as I just mentioned, the shell is going to start by identifying the meta characters within this command. So here is the full list of meta characters. Can you identify the meta characters in this command? Pause the video and then come back to see how you did. How'd you get on? Well, to start with, the spaces are all meta characters, so let's highlight those. We can also see from the list that the greater than sign is also a meta character, so let's highlight that too. So we have 4 meta characters here that the shell is going to identify. We've got the 3 spaces and the greater than sign. After the shell has identified these meta characters, it is then going to break the command line up into words and operators. As we discussed, words are sequences of text or tokens that do not include any unquoted meta characters. So what do you think? What will the shell identify as a word? Pause the video for a minute, have a think about it, and then come back to see how you did. How'd you get on? Well, in this command line, we have the sequence of characters ECHO, which doesn't include an unquoted meta character. So that will be one word. We also have $NAME, which will be the second word. And finally, we have OUT.txt, which will be our third word. I'm reading the words in a funny way like that because that is literally how the shell sees them. It just sees them as a stream of individual characters. Okay, the shell will then look for sequences that contain at least one unquoted metacharacter and look to see if there are any operators within them. So in this example, the shell will see the redirection symbol as an operator, a redirection operator to be exact. So in this command line, we have 3 words and 1 redirection operator. And that's it for the tokenization step. Not bad, right? I want to really make sure that you get these key concepts, so let's quickly have a recap before moving on to the next step of the command line processing flow. In this lecture, you've learned a lot about tokenization, which is the first step that the shell goes through when it starts to break down a command line. In this video, you learned that the shell identifies unquoted metacharacters and it uses them to divide the command line into tokens. You learned that the shell then uses the metacharacters to characterize the tokens into either words or operators. You learned that words are sequences of characters that do not contain any unquoted metacharacters. And you learned that operators are sequences of characters that contain at least one unquoted metacharacter. And finally, you learned that there are 2 types of operators. There's control operators and redirection operators. Okay, great. So up next, we're going to have a quick quiz to check that you've got everything, and then from there, we're going to be looking at the next step of the shell command line processing flow, which is command identification. So good luck with the quiz, and I'll see you in the next video. Hello there, you beautiful people, and welcome to this video where we're going to be discussing the second step of Bash's command line processing flow, which is command identification. In Bash, there are actually 2 types of commands, the simple commands and compound commands. And in this video, you're going to learn what those 2 types of commands are, how the shell distinguishes between them, and how the shell determines where they start and where they end on a command line. And by the end of the video, you'll be able to explain the difference between simple and compound commands, and you'll be able to explain how the shell identifies where simple and compound commands start and end. So let's go ahead and get started. As I said earlier, there are 2 types of commands in Bash. There are simple commands and there are compound commands. Simple commands are the most common type of command that you'll use, and you've used plenty already. An example is echo 123. The first word of the simple command is interpreted as the command name, and the remaining words are each interpreted as individual inputs or arguments to that command. So with the simple command echo 123, the word echo would be interpreted as the command name, and the words 1, 2, and 3 would each be interpreted as individual arguments to the echo command. All simple commands are terminated by a control operator, which could be any one of the following. Now in our example, the simple command echo 123 is terminated by the invisible new line character that is at the end of the command line. Let's take another example. Let's say we have the command echo ABC echo 123. Here's how the shell will process this command line. The shell will first do tokenization, where it identifies the unquoted metacharacters in the command line and use them to break the command line into words and operators. Now in this command line, we have several unquoted space characters, which are going to be the metacharacters for this command line. Now remember, simple commands are terminated by control operators. And because there are no control operators on this command line, the shell will simply interpret the whole command line as a single simple command. The first word, which is echo, will be the command name, and the rest of the words will be interpreted as individual arguments to that single command. In this case, we would get the output ABC echo 123, which is probably not really what we intended. Let's consider a variation. Let's say we now had the command line echo ABC semicolon echo 123. The shell would again do tokenization and identify the unquoted metacharacters and use them to break the command line down into words and operators. Given that the shell terminates simple commands using control operators, and given that we now have a control operator on the command line, which in this case is the semicolon, the shell would now break up this command line into two separate simple commands, like so. The first simple command is terminated by the semicolon, and the second simple command is terminated by the new line character at the end of the line. The first word in each command will be the command name, which in both cases here will be echo. All other words for a given command will be taken as individual arguments for that command. Putting this together, our output would be on two separate lines this time, one for each echo command, with ABC as the output from the first echo command, and 1, 2, 3 as the output from the second echo command. Okay, as one final example, let's refer back to the example that we used when looking at tokenization in the last video, which was this. As we know, the shell will start off by identifying unquoted meta characters. It then uses that information to break the command line down into words and operators. Now in this command line, there is an operator, but it is a redirection operator, not a control operator. Because there are no control operators, the shell identifies the echo command and its redirection as part of a single simple command. So in this example, the shell would interpret the command line as one simple command, with part of that command being a redirection. Now, although the redirection operator is identified as part of the command in the command identification phase, the redirection will actually only be processed much later on. How the shell deals with redirections will be covered in more detail later on in this section of the course. Finally, let's have a look at compound commands. We haven't come across any compound commands yet in the course, but we will later on. Compound commands are essentially Bash's programming constructs. Compound commands can be used to create if statements, which can help your script to decide which action to take based on logical conditions. Compound commands can also be used to create loops, which can be used to execute a certain operation over and over again until you're happy that a certain piece of work is done. Each compound command starts with a reserved word, and is terminated by a corresponding reserved word. Now by reserved word, I mean a word that has a special meaning to Bash, like if, which is used to start an if statement, fee, which is used to end an if statement, and while, which is used to start a while loop, and so on. By recognizing these reserved words and their corresponding closing reserved words, Bash is able to determine where compound commands start and end. As an example, let's take a quick look at if statements. We'll be covering if statements in more detail in section 5 of this course, which covers logic, but I'll be using an if statement here to help me illustrate how the shell processes compound commands. As I said, the reserved word that the shell uses to identify an if statement is, unsurprisingly, if. Whenever Bash sees the unquoted word if, it expects to start an if statement. Bash will then continue to read the script until it sees the corresponding closing reserved word for if statements, which is fee, which is just if spelled backwards. What this means is that compound commands can actually be written over multiple lines. They don't have to fit on just one command line like simple commands have to, and they can even contain multiple other simple and compound commands inside of them. This ability to layer or nest multiple simple and compound commands inside other compound commands is what gives Bash its programming abilities, as we'll see in coming sections of the course. As far as this lecture is concerned, however, all you need to know is that whenever Bash comes across an unquoted reserved word, it knows it has entered a certain type of compound command. Bash will then interpret everything until the corresponding closing unquoted reserved word as part of that compound command, even if it has to process multiple command lines and even other compound commands until it reaches that point. Okay, so that brings us to the end of our discussion of command identification, which is step 2 of the command processing flow. In this video, you learned that a simple command is just a list of words separated by spaces and terminated by either a new line or one of the other control operators available in Bash. You learn that the first word of a simple command is interpreted as the command name, and the following words are interpreted as arguments to that command. You learn that compound commands are what give Bash its programming constructs. And you learn that the shell uses a list of reserved words to determine where compound commands start and end. In the next video, we're going to learn about the third step in the process the shell goes through when processing command lines, which is shell expansions. You've already learned what many of these expansions do in section 2 of the course, and so the next video will just help us understand how the shell deals with those expansions as part of the command line processing flow. So for all that good stuff, I'll see you in the next video. Hello there, you beautiful people, and welcome to step 3 of the command line processing workflow, which is where the shell processes expansions. In this video, we're going to be taking a closer look at how the shell processes expansions, and by the end of this video, you'll be able to list the 4 stages that the shell goes through when processing expansions, and you'll be able to explain the effects of precedence on the order in which the shell expansions are performed. So let's go ahead and get started. So as I explained earlier, once the shell has completed tokenization, it will then perform shell expansions on the words in the command line. As I explained during the overview of the shell's processing, there are 4 stages of shell expansions. Expansion stage 1 is brace expansion. Expansion stage 2 contains parameter expansion, arithmetic expansion, command substitution, and tilde expansion. Expansion stage 3 is word splitting. And expansion stage 4 is file name expansion, also known as globbing. Okay, so with the first thing you need to know is that the expansions in earlier stages are performed first. For example, brace expansion, because it's in stage 1, is performed before all other types of expansions. A consequence of this is that expansions that happen in later stages cannot be used in the expansions that occur in earlier stages. So, for example, because parameter expansion occurs in stage 3 and brace expansion occurs in stage 1, it's not possible to use the result of a parameter expansion inside a brace expansion, because the brace expansion will have already been processed before the shell tries to process the parameter expansion. So let's say you had a variable called x with a value of 10. You couldn't do echo 1 to x in a brace expansion, for example, and get the numbers 1 to 10 printed out, because the parameter expansion of x wouldn't have been performed by the time the brace expansion had been performed, and therefore bash wouldn't know the value of x. It wouldn't know to expand from 1 to 10. You can give this a try for yourself, and you'll see what I mean. The second thing you need to know is that expansions that are in the same stage are all given the same priority, and are simply performed in the order they're found on the command line when it's read from left to right. So let's say we had the command line echo $name has 1 plus 2 apples, with the 1 plus 2 being in a arithmetic expansion. So in this line we have 2 expansions. We have a parameter expansion of $name, and we have an arithmetic expansion where we're adding up 1 and 2. Now, parameter expansions and arithmetic expansions are both in the same stage. So the order that they'll be processed is just the order that they appear when read from left to right. So in this example, $name would be expanded first with the parameter expansion, and then the arithmetic expansion of 1 plus 2 would be performed next. However, if we had this command line, you can see that in this case we have a parameter expansion, a brace expansion, and an arithmetic expansion. Now in this example, the brace expansion would happen first, even though it appears in the middle of the parameter expansion and the arithmetic expansion when you read the command line from left to right. And this is because brace expansion is a stage 1 expansion, and therefore goes before all the expansions in stage 2, and also stage 3 and stage 4. After the brace expansion is done, however, the parameter expansion of $name would be performed, because that is the furthest stage 2 expansion to the left, and then arithmetic expansion would happen afterwards. Now we've actually already fully covered the first 2 stages of shell expansions in the previous section of the course, but we still need to cover stage 3, which is word splitting, and stage 4, which is globbing. We'll be covering these in the next few videos, but for now, let's just have a quick summary of what we've learned in this video. So now you should have a good understanding of how the shell processes the command line through tokenization and then shell expansions. In this video, you learned that after tokenization, and the shell has broken up the line into words and operators, the shell performs all expansions in the command line on the words in the command line. You learn that there are 4 stages of expansion. Stage 1 is brace expansion. Stage 2 includes parameter expansion, arithmetic expansion, command substitution, and tilde expansion. Stage 3 is word splitting, And finally, stage 4 is globbing, which is also known as file name expansion. You learn that expansions in the earlier stages have higher precedence than expansions in later stages and therefore are performed first. And you also learn that commands on the same stage all have the same precedence and are simply performed in the order they appear from left to right. As I said, you're already familiar with the expansions in stage 1 and 2, but you haven't come across word splitting and globbing just yet, but we'll be covering these in the next few videos. Up next, we'll be looking at stage 3 of expansions, which is word splitting. Now, word splitting is so key to how Bash works, it's hard to overemphasize it. And in the next video, you're going to learn what word splitting is, how it works, and how you can manipulate its functioning using the IFS shell variable. So for all that good stuff, I'll see you in the next video. Hello there, you beautiful people, and welcome to this video where we're going to be taking a look at word splitting, which is the third stage of the shell's process for dealing with expansions. Word splitting is a very important part of the overall command line processing flow, and not having a good understanding of how it works is a root cause of so much confusion when using Bash. And hopefully, after we go through this video and we apply its concepts throughout the rest of the section, much of that confusion will have melted away. In this video, you're going to learn what word splitting is, you're going to learn how Bash performs word splitting on the result of certain expansions, and you're going to learn how you can set the IFS shell variable to control how word splitting is performed. By the end of this video, you'll be able to describe what word splitting is and when it is performed. You'll be able to explain what the IFS variable is and what its default value is. And you'll be able to use word splitting and the IFS shell variable to manipulate the results of various expansions. So let's go ahead and get started. So, what is word splitting? Word splitting is a process the shell performs on the result of some of the expansions to separate those results into separate words. As we learned from the video on command identification, separate words on the command line may be interpreted as different arguments to commands. Therefore, word splitting can have some very significant effects on how your command lines are interpreted, and without understanding it, you can be left rather confused when your commands don't do what you think they should have done, so it's very well worth understanding word splitting in detail. It's really important to understand that word splitting is only performed on the results of unquoted parameter expansions, command substitutions, or arithmetic expansions. You must burn that into your mind that word splitting doesn't just happen on everything on the command line. In fact, it's so important, I'll say it again. Word splitting is only performed on the results of unquoted parameter expansions, command substitutions, or arithmetic expansions. Please, please, please burn that into your mind. It's really important. Okay, now, word splitting works in a very similar way to how tokenization works. Now, as you know, when the shell does tokenization, it refers to the list of meta characters and uses the presence of those characters to break the command line up into words and operators. Similarly, when the shell performs word splitting, it also refers to a list of characters. In word splitting, this list of characters is stored within the IFS shell variable, where IFS stands for Internal Field Separator. The IFS variable contains space, tab, and new line by default. When the shell gets an unquoted result of either parameter expansion or command substitution or an arithmetic expansion, it will search within the result for the characters contained within the IFS variable. And when it finds one, it uses it to split the result into separate words. Now, IFS is just a variable, but it contains a space, tab, and new line by default, which are all invisible characters, which means we can't just print out the variable to take a look at it using normal parameter expansion. As you can see, if we do try to just echo out the IFS variable, we just get a blank response, because spaces, tabs, and new lines are invisible on the command line. However, we can use a parameter expansion trick to make the spaces, tabs, and new lines visible by typing echo, and then $, then in curly braces, IFS at Q. So as you can see, the IFS variable contains a space, a tab represented by \t, and a new line represented by \n. So now that we've got some familiarity with the IFS variable, let's take a look at what word splitting actually does. Let's create a variable that includes some IFS characters. For this, we can use numbers equals, and then inside double quotes, 1 space 2 space 3 space 4 space 5. Our parameter numbers has a space between each number, and space is one of the default characters in the IFS variable. So now let's run the command touch $numbers and then use the ls command to look at the result. As you can see from this, the touch command has created 5 individual files: 1, 2, 3, 4, and 5. What this shows us is that after the shell expanded the value of the numbers variable, it then split that value up into separate words based on the IFS characters. Each of these separate words, which were 1, 2, 3, 4, and 5, were given as individual arguments to the touch command, and with the result being that 5 individual files were created. It didn't just create one file called 1, 2, 3, 4, 5, it created 5 individual files, 1, 2, 3, 4, and 5. So let's remove the files we've created using a brace expansion by running rm and then in curly braces 1.5. Now remember, our golden rule is that word splitting is only performed on the results of unquoted parameter expansions, command substitutions, or arithmetic expansions. Therefore, any parameter expansion that occurs within quotes will not have any word splitting performed on it. So if we again run this touch command, but this time we put the parameter expansion inside double quotes, and then we run ls to see the results, you can see that now we have just one file created, and it's called 1 space 2 space 3 space 4 space 5. This shows that because the variable was quoted, the shell did not perform word splitting, and therefore, instead of 5 individual arguments being passed to the touch command, there was just one argument passed. And we can remove this file by running rm 12345. Now, let's recreate our variable, and this time, instead of using spaces, we'll use a comma between each number. So numbers equals 1, 2, 3, 4, 5. So let's run the touch command again, and once again do the expansion outside of quotes so that the word splitting takes place. This time, you can see that we've created a single file called 1, 2, 3, 4, 5. So because the default IFS variable doesn't include any commas, even though the shell did word splitting on our unquoted parameter expansion, it didn't try to split the result using the commas. So what if we wanted to use commas to separate our arguments, like if we were processing a comma-separated values or CSV file, for example? Well, to do this, we can actually change the value of the IFS variable to have the comma as its value. Because the IFS variable is just a variable, to do this, like with setting any variable, we simply run ifs equals and then a comma inside double quotes. It's important to note that you shouldn't put any spaces inside your IFS variable unless you want the shell to perform word splitting using spaces. Because our IFS variable here only contains a comma, word splitting will now only be performed using commas. Spaces, tabs, and new lines will now no longer be used unless we change the IFS variable again to include them. Now if we run our touch command again with our unquoted numbers variable, so touch $numbers, you can see that if we run the ls command, that 1, 2, 3, 4, 5 was split at each of the commas, and 5 individual files have been created once again. Let's finally just remove the last files we created by running rm 1.5 and rm 1, 2, 3, 4, 5. So now you should have a clear understanding of when and how the shell performs word splitting. Word splitting can be a bit confusing the first time you come across it, but here's a simple rule for you to remember. Simply remember that if you want the output of a parameter expansion, an arithmetic expansion, or a command substitution to be considered as a single word on the command line, maybe you want the output to be considered as just one argument to a command, then just make sure to wrap that expansion in double quotes. I'll say it again. Simply remember that if you want the output of a parameter expansion, an arithmetic expansion, or a command substitution to be considered as a single word on the command line, maybe you want the output to be considered as just one argument to a command, for example, then just make sure to wrap that expansion in double quotes. In fact, I'll say it once again. If you want the output of a parameter expansion, an arithmetic expansion, or a command substitution to be considered as a single word on the command line, then just make sure to wrap that expansion in double quotes. That really is all it boils down to at the end of the day in most cases, but now you have a detailed understanding of what's going on behind the scenes as well, and also you know how to customize word splitting for yourself. So in this video, you learned that the shell performs word splitting to break the results of some unquoted expansions into separate words, and it uses the IFS variable to do this. You learned that word splitting is only performed on the results of unquoted parameter expansions, command substitutions, and arithmetic expansions. You learned that the default value of the IFS variable is space, tab, and new line. And finally, you learned how to change the value of the IFS variable to manipulate the results of word splitting for yourself. Now, because word splitting is such an important concept, up next we're going to have a quick quiz to help you make sure that you've mastered all the important word splitting concepts. And then we're going to dive right into globbing, which is the final stage of processing expansions, and also an insanely powerful and useful feature of the Bash shell. So for all that great stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be looking into the fourth and final stage of expansion processing, which is globbing. Globbing, also known as file name expansion, is a very useful and powerful tool, and knowing how to use globbing really well will give you yet another dose of Bash superpowers. In this video, I'll be giving you an introduction to globbing and its core features, and by the end of this video, you'll be able to explain what globbing is, and you'll be able to use asterisks, question marks, and square brackets to create basic globbing patterns. So let's go ahead and get started. Globbing is the fourth and final stage of expansion processing, so in terms of our overall command line processing flow, globbing is essentially step 3D. Globbing is a bit of a funny word, but it has its origins in the glob program that was an important part of early versions of Bell Labs' Unix operating system from 1969 to 1975. The glob program was a program that would replace text containing special pattern symbols with a list of file names that matched those patterns. This allowed shell users to express what files they want a command to operate on without having to type out each file name manually. When doing globbing in Bash, we're essentially doing the same thing, so the name globbing appears to have stayed with us as a historical relic from the original Unix glob program. So with that little bit of history behind us, how does globbing work? Well, it's important to note that globbing is only performed on words. This includes the new words that appear from the word splitting that the shell will have carried out in the previous step, and also the words that were there in the first place. When the shell begins to perform globbing, it scans each word for certain special characters. And these special characters are the asterisk or star, the question mark, and the left square bracket. If the shell finds one of these characters unquoted inside a word, then it will perform globbing on that word. At the globbing stage, any word containing one of these unquoted symbols is known as a pattern. Bash will look at all the characters in the pattern to determine file names that match the pattern as a whole. Some of these characters will be special pattern characters, and thus have special meanings, while some will just be regular letters and numbers. The pattern will then be replaced with an alphabetically sorted list of the matching file names. Each file name in the list will be considered as an individual word on the command line, and thus as an individual argument to a command. So even though the pattern itself was only one word, and thus considered as only one argument to a command, due to globbing, the pattern has the potential to expand into multiple words, one for each file name, with each file name then being considered as its own argument to the command. To see how all of this works, let's take some examples. Let's say we had the following files in our current working directory. Take a minute to review this list because there's some subtle differences in the file names. So firstly, I'm going to start by discussing a special pattern character that many of you will probably be quite familiar with, which is the asterisk or the star. The asterisk is arguably the most commonly used globbing special character, and if you've used the shell before, you'll probably have used the asterisk many times. The asterisk is also the most flexible globbing character, and if we do ls star, you can see that we actually get to see everything in the current directory. So the asterisk will match absolutely anything, so we would read this pattern as literally anything. A typical use case of the asterisk is to find all file names ending in a particular file extension, like .txt or .pdf. For example, if we use the ls command and gave it the pattern star.txt, which we would read as anything then .txt, you can see that we get all the .txt files in the folder shown back to us. Notice how the PDF files, however, are not shown. And if we change our pattern to say ls star.pdf, you can see that we just get the files ending in .pdf, but the txt files are not shown. We can also say what a file name must start with. So for example, if we gave the ls command the pattern file star.txt, we would read this pattern as saying file, then anything, then .txt. And when we run it, we see that we get back all the file names that start with the word file and end in .txt, regardless of the rest of their file name. While the asterisk is happy to match pretty much anything, it's important to note that the asterisk doesn't require a physical character to take its place in the pattern. For example, notice how the pattern file star.txt still matched file.txt, even though there is no character between the word file and .txt in that file name. The asterisk was happy to match emptiness. It didn't require a character to physically take its place. Okay, so that's it for our first special pattern character, the asterisk. Let's now move on to our second special pattern character, which is the question mark. Unlike the asterisk, which will match any set of characters regardless of length, the question mark special pattern character will match any single character. Like the asterisk, the question mark doesn't really care what the character is, as long as it is just one character. However, unlike the asterisk, the question mark does require that a character actually be there to replace it in the pattern. For example, let's say that we gave the ls command the pattern file .txt. We will read this pattern as saying file, then some character, then .txt. And when we run it, we see that we get back every file that has exactly one character between file and .txt in the file name. Files such as file abc.txt or file123.txt were ignored because they have more than one character between file and .txt. In this case, they both have 3. If we wanted to match these files, we would need to do the pattern file .txt, where we put 3 question marks, which is 1 for each character. However, as you can see, this pattern with 3 question marks won't match the files we got the first time using just 1 question mark, because those files don't have exactly 3 characters between file and .txt. From this little experiment, we can say that the question mark is very flexible in terms of what content it accepts, but it's very strict in terms of its length. Okay, now let's move on to take a look at the final special pattern character, which is the square brackets. Like the question mark, the square brackets are strict in terms of their length and also occupy exactly 1 character space. However, unlike the question mark, which will match any character, the square brackets will only match the characters that you place inside of them. You can think of the square brackets as a more controlled question mark. For example, if we wanted to match the files that have exactly 1 character between file and .txt, as long as that character is a letter A or a letter B, we could type ls and then give it the pattern file ab in square brackets .txt. We would read this pattern as saying match any file name that starts with file, then has either an A or a B, and then ends in .txt. And if we run this, we see that we get back file A and file B.txt. Notice that regardless of how many characters we type inside the square brackets, we could type as many as we want actually, each set of square brackets will always only occupy exactly 1 character space in the pattern. If we wanted to match a file name such as file abc.txt using square brackets, we would need to use this pattern, which we would read as file, then either an A, a B or a C, then either an A, a B or a C, then either an A, a B or a C, then .txt. And when we run this, we see that we get file abc.txt printed out. A cool feature of square brackets is they allow us to express ranges of characters, which can save us some typing versus, manually typing out each letter individually. So let's say we wanted every file that has a lowercase letter between A and G after the word file. Instead of typing file and then in square brackets abcdefg.txt, we could simply type file, open some square brackets and put a-g.txt. And when we run this, we get file a.txt, file b.txt, and file c.txt because they all have a lowercase letter between A and G in the appropriate place in their file name. Square brackets also work with ranges of numbers. For example, if we wanted to match any digit between 0 and 9, we could type file, open some square brackets and put 0-9.txt. And we see that we get back file1.txt, file2.txt, and file3.txt, because each of these have a number between 0 and 9 in the appropriate place in their file name. You can also mix together letters and numbers as you wish. Just remember when writing ranges that Linux is case sensitive, so don't write a lowercase a in your range when you're looking to match an uppercase A, for example. Now, as one final note before we wrap up, let me point out that globbing will only search for files in the current working directory by default, but we can make it search in other folders if we explicitly provide the path to them in the pattern. For example, imagine that we want to delete every .jpg file from our downloads folder, but we aren't in our downloads folder at the current time. In this case, we would need to add the path to the downloads folder in the pattern. Now in this case, because we're deleting files rather than listing them, we're going to use the rm command, and then we're going to give that rm command the pattern ~/downloads/star.jpg, and that will delete all the JPG files in our downloads folder. From this example as well, in case it wasn't clear from the previous examples, you don't have to use the ls command. You can use whatever command. The pattern is just the thing that expands into different arguments to that command. So that's it for our discussion on globbing, and hopefully this video has given you some insight into some of the cool things that globbing can do when working with bash. In this video, you learned that globbing, also known as file name expansion, is used to generate an alphabetically sorted list of file names that match a certain pattern exactly. You learned that any word on the command line that contains an unquoted asterisk, question mark, or left square bracket will be interpreted as a pattern. You learned that the asterisk or star special pattern character will match anything regardless of its length or what characters it contains. The asterisk does not require anything to actually physically take its place in the pattern. It's happy to also match nothingness. You learned that the question mark character will, like the asterisk, match any character, but it does require that something take its place, and it will only match exactly one character. Finally, you learned that the square brackets, like the question mark, will also match exactly one character. However, unlike the question mark, and also unlike the asterisk, the square brackets will only match the characters that you place inside of them, which gives you a little bit more control over what your patterns will match. Now in the next video, we're going to move on to discussing quote removal, which is step 4 out of 5 in our command line processing flow. So you're almost there, and for all that quote removing goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be discussing the 4th step of Bash's command line processing flow, which is quote removal. The quote removal step is short and sweet, but it's still important to be aware of it. In this video, you're going to learn how the shell performs quote removal, and by the end of this video, you'll be able to explain how quote removal works, and you'll be able to identify what quotes the shell removes during quote removal. So let's go ahead and get started. So after globbing, the shell will have finished processing all 4 stages of expansions and will move on to the 4th step of the command line processing flow, which is quote removal. As discussed during the lecture on quoting, there are 3 types of quotes in Bash. There's the backslash, there are single quotes, and there are double quotes. In that lecture, we learned that quotes are used to remove special meaning from characters, and we can use quotes to gain some control over how the shell is interpreting our commands, and to make sure that the shell interprets our commands in the ways that we intend. However, once the shell has used the quotes to remove special meaning, we have no need for the quotes anymore. You can think of quotes as being like the scaffolding in a construction project. You need the scaffolding there during the build, but once the building is done, you probably want it removed to just leave the new building behind. In a similar way, the shell performs quote removal to tidy up a bit and remove all the quotes that were put there to control the interpretation. More specifically, the shell will remove all unquoted backslashes, single quote characters, and double quote characters that did not result from a shell expansion. For sake of clarity, let me say that one more time. During quote removal, the shell removes all unquoted backslashes, single quote characters, and double quote characters that did not result from a shell expansion. For example, let's say that we want to print the text $home to the screen. We want $home to be printed literally, including the $sign, and we don't want any expansions performed. How could we do that? Well, we know that we need to remove the special meaning of the $, character, because otherwise $home will expand to the value stored in the $home variable, whereas we just want the literal text $home. One way we could do it is to put a backslash before the $sign, like this. And when we run this, we see $home printed to the screen as we wanted. Okay, great. Now did you notice that the output was just $home? Where did the backslash go? Well, it was removed during quote removal. You see, the backslash was only needed by us to remove the special meaning of the $, character and to prevent parameter expansion from happening. Because the backslash in this example is unquoted and didn't result from an expansion, Bash was smart enough to figure out that we only put it there to help us express what we wanted. To use our building analogy, Bash figured out that the backslash was only there for construction purposes and removed the backslash from the final command before running it. Let's take another example. Let's say we ran echo $home, which is the same as the previous command, but this time the backslash is wrapped in single quotes. Here we see the output is $home. In this example, the single quotes were removed, but the backslash wasn't. Now why is that? Well, this is because the backslash was quoted by the single quotes. This means that when Bash got to the quote removal phase, it saw that backslash was quoted by the single quotes that surrounded it. Because quote removal only happens on unquoted backslashes, single quote characters, and double quote characters, and this backslash was quoted, the backslash wasn't included in the quote removal and therefore wasn't removed. The single quotes, however, were removed. The lesson we can draw from this is that if you want to include literal quotes in your command arguments, then you must make sure that they are quoted, otherwise they'll be removed during quote removal. Let's take one final example. Let's say we have a variable called path, like so. Double quotes remove the meaning of backslashes, so the backslash in here will be interpreted literally because they're wrapped in double quotes. Now, what do you think would happen if we did echo $path? Well, the shell will first do the parameter expansions, so at the quote removal stage, the command will look like this. Now, at the quote removal stage, what do you think Bash will do? Will it keep the backslashes, or will it remove them? Well, in this instance, Bash will keep them. Quote removal will only remove unquoted backslashes, single quote characters, and double quote characters that are not the result of an expansion. So even though these backslashes are unquoted, they are the result of an expansion, and therefore they are not removed by quote removal. So that's pretty much all there is to quote removal. Quote removal is a pretty short step, but it's useful for you to be aware of it so that you can avoid potential confusion later on. In this video, you learn that quote removal is the process that Bash uses to determine which quotes you added in just for construction purposes and to remove them from the final command. You learned that to do this, the shell will remove from the final command any unquoted backslashes, single quote characters, and double quote characters that did not result from an expansion. Now up next, we're going to have a quick quiz to make sure that you're comfortable with quote removal, and in the next lecture, we'll be talking about the final step of the Bash command line processing workflow, which is redirection. So for all that goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be looking into the fifth and final step of the command line processing flow, which is redirection. In this video, you're going to learn about the various ways to perform redirections within your Bash scripts. And by the end of this video, you'll be able to redirect standard output and standard error to files. You'll be able to append standard output and standard error to files. And you'll be able to redirect standard input to choose where your command input comes from. And after the shell has processed redirections, it will simply execute whatever is left over, so you're almost there. Let's go ahead and get started learning this last step of the command line processing flow. So as I said, the fifth and final step is for the shell to process any redirection operators that are on the command line. When dealing with redirections, the first piece of information you need to know is that Linux and other Unix-derived systems allow commands to take advantage of 3 standard data streams, each of which is given a stream number. There is the standard input stream, which is stream number 0. There is the standard output stream, which is stream number 1. And finally, there's the standard error stream, which is stream number 2. It's important to bear in mind that while these streams are generally available for all commands, whether a given command actually uses these streams or not is usually up to how the command was programmed by its developers and will vary on a case-by-case basis. The quickest way to find out which streams a command uses is usually just to try the command out for yourself, but you can also try reading the command's manual page for more information as well. Okay. Now let's take a look at what each of these streams is used for. The standard input stream provides us with an alternative way of providing input to a command, aside from using the command line arguments. As a general rule, whenever you want a command to take multiple lines of data as input, rather than just a single line or a few words, you'll probably want to use the standard input data stream rather than use command line arguments. The standard output data stream contains the main output from the command. Standard output contains the data that is produced after a successful command execution. And finally, there is the standard error stream, which contains the error output from a command. This stream contains all error messages and status messages that a command produces, but that aren't really considered as the main output of a command. Now I want you to imagine that each of these different streams is a different tube connected to the command. Now just like real tubes, each stream has 2 ends, one of which is connected to the command. Now by default, the other end of the standard input stream is connected to the keyboard, and the standard output streams and standard error streams are each connected to the user's terminal. Redirection is all about using redirection operators to express where we want the end of the tubes to connect to. A wonderful example of this is the cat command. If we just type cat, we see that the command just sits and waits for input from the user's keyboard. However, if bash sees that there's a less than sign, which is a redirection operator for standard input, then it knows instead to change the standard input source from the keyboard to the file specified by the very next word after the standard input redirection operator. So let's say that we have the file hello.txt that contains the words hello world, and we have the command cat less than hello.txt. Now instead of the standard input of the cat command being connected to the keyboard, like it would be by default, the redirection changes the connection point of the standard input stream to the file hello.txt instead. The result of this will be that instead of just hanging and waiting for input from our keyboard, the cat command will read the contents of the hello.txt file, which is hello world, and print that to the screen. The other redirection operators work in a very similar way. For example, the default redirection operator for redirecting standard output is the greater than sign. Let's say we had the command echo this is some output. As I said before, standard output is connected to our terminal by default. However, if we redirect the standard output using the greater than operator to a file called output.txt, and then when we run that command, we see that we no longer see the output pop up in our terminal window. However, if we run ls, we see that a new file has been created called output.txt, and if we look at the contents of output.txt, we can see that it contains the text, "This is some output." Redirecting standard error works in a very similar way, except it uses the to greater than operator. The to is here because the standard error is data stream number 2. So let's say that we have the command cd/root, where we're trying to enter the admin's home folder. As you can see, because we don't have permission to access this folder as a regular user, bash gives us an error saying permission denied. If we just do a normal redirection of standard output by trying to redirect the standard output to a file called error.txt, we can see that the standard error still pops up on the screen. This is because standard error is a separate stream to standard output. However, if we redirect standard error using the to greater than operator, we now see that the error message disappears. If we open up error.txt, we see that the error message has been saved in that file. The final redirection operator that we'll look at is the AND greater than operator. This operator will connect the standard output and the standard error data streams to the same place. So if we did cd/root and greater than /dev/null, we would redirect standard output and standard error, hence the little and symbol, to the file /dev/null. /dev/null is a place on the file system that's known casually in the Linux world as the bit bucket, because whatever data you send there just gets immediately deleted. Redirecting both standard output and standard error to the bit bucket is a useful way to effectively silence a command without creating unnecessary files and taking up space on our file system. Of course, you don't have to use the bit bucket, you can just redirect to a regular file like normal too. Now, by default, the operators for redirecting output that I've shown you so far each use one greater than symbol. We have greater than for standard output, to greater than for standard error, and greater than for standard output and standard error at the same time. Now, each of these operators that uses one arrow will cause the shell to truncate the destination file before sending any data to it. What this means is that the contents of the destination file will all be deleted before new data is sent, which may not be what you want. Oftentimes, you'll want the data that you're sending to be appended to what is already there in the file, rather than deleting the contents and starting from fresh each time. To do this, just use two greater than symbols instead of one. So you would use greater than for standard output, to greater than for standard error, and greater than for standard output and standard error at the same time. Okay, so that's everything that you're likely to need to know about how the shell processes redirections. So let's have a quick recap of what you've learned. In this video, you learned that there are 3 data streams, and each data stream is given a number. Data stream 0 is standard input, data stream 1 is standard output, and data stream 2 is standard error. You learned that each of these streams can only connect to one location at a time, and redirection is all about changing their connection points. You learned that redirection is performed using redirection operators, and each redirection operator has exactly one operand, which is the first word that appears on the command line after the redirection operator. In the case of standard input, this operand tells the shell where to get data from, and in the case of standard output and standard error, it tells the shell where to redirect data to. You learned how to redirect standard input, standard output, and standard error using the various redirection operators available. And finally, you learned that you can use two greater than symbols instead of one when redirecting output streams to make them append data to their destination files rather than truncate them. And that's it for redirections. After Bash has processed redirections, it will have completed the 5-step process that it uses to interpret command lines and will then just execute the command line that is remaining. You've now covered in detail how Bash processes any command line that you could possibly give it, which is a massive, massive milestone. You probably have more knowledge right now about how Bash works than most people who work with the command line, so a huge congratulations to you. In the next lecture, we're going to have a brief quiz to ensure that you're comfortable with everything about redirection, and then it's on to some worked examples to put into practice all that you've learned during this section and to work through the process together. So good luck with the quiz, and I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be working through some worked examples of how the shell processes command lines. We've covered a lot of different things in this section of the course, so now we'll be visually working through the process together on some example commands to make sure that you're able to see how it all fits together. By the end of the next few videos, you'll be able to mentally walk through how the shell will process a given command line, and you'll be able to explain how each of the steps are handled for a given command line. So let's go ahead and get started. So over the next 3 videos, we're going to walk through 3 example command lines. It'll be helpful for you to have a copy of this section's cheat sheet next to you as we walk through each example so that you can get a sense of where we are in the process and follow along more easily. So go ahead and grab that now if you can. For your convenience, I've reattached it to the resources section of each of the worked examples videos, including this one. So just go ahead and pause the video now and download it from the resources section. For each example, I'll show you how the shell responds to the commands at each step and break it down to show exactly what the shell is doing to the command line at each step. Okay, so in this video, we'll be working on this command. You can see that we have a few variables in here which have the following values. The name variable has the value simon.smith, and the out variable has the value output.txt. Now if you grab your cheat sheet, you'll see that the first step the shell will engage in is tokenization. If you remember, tokenization is the step where the shell looks for unquoted metacharacters and uses those unquoted metacharacters to break up the command line into words and operators. Now, using the cheat sheet and the list of metacharacters on there for the tokenization step, pause the video now and take a few seconds to see if you can figure out how many unquoted metacharacters we have in this command line and where the different words and operators will be. So go ahead and pause the video now, give it a try, and then unpause to see how you did. Okay, welcome back. How did you get on? Now in this example, we have 4 unquoted metacharacters. We have 3 spaces and 1 greater than symbol. Using these unquoted metacharacters, we can also see where the words and operators are. Remember, words are tokens that don't contain any unquoted metacharacters, so we can see that we have 3 words in this case. We have echo, $name, and $out. Remember, the dollar symbol isn't a metacharacter, so $name and $out still count as words. We also have only 1 operator, which is the greater than symbol. Okay, great. Now, after completing tokenization, the shell will then move on to the second step, which is command identification. Remember, the shell knows where simple commands start and finish by looking for control operators on the command line, and the shell knows where compound commands start and finish by looking for reserved words like if, while, for, and so on. In this case, the shell finds 1 simple command like so. The greater than $out part, so the redirection to $out, is still considered part of the echo command because the greater than symbol is a redirection operator and not a control operator, and the shell only uses control operators to terminate simple commands. The control operator that is terminating this simple command is actually the new line character, which is hidden but exists at the end of the line. Okay, now with command identification done, the shell will now move on to step number 3 in the process, where it performs all required expansions. If you look at your cheat sheet, you'll see that there are 4 stages of expansions. Stage 1 is brace expansion. Stage 2 includes parameter expansion, arithmetic expansion, command substitution, and tilde expansion, which all have equal precedence. Stage 3 is word splitting, and stage 4 is globbing. You should be familiar by now with the syntax for each stage, so let's read the command line and see which ones we have. Do we have any brace expansion? No, so let's skip that stage. Do we have any parameter expansions, arithmetic expansions, command substitutions, or tilde expansions? Well, we have a couple of parameter expansions. We have the one for $name and the one for $out. So let's replace those with their values. $name will be expanded to simon.smith, which will still be in quotes because the $name was within quotes on the original command line. And $out will be expanded to its value of output.txt. Do we have any other types of expansions from stage 2 of expansions? Not really, so let's move on to stage 3 of processing expansions, which is word splitting. In this case, the only unquoted result of one of those expansions is output.txt. Because output.txt doesn't contain any space, tab, or new line characters, which are the characters that word splitting is performed on by default, no word splitting is performed for this command line. Okay, now for stage 4 of the expansions, which is globbing. At this stage, the shell will search the command line for unquoted asterisks, question marks, and left square brackets. If it finds a word with any of those characters unquoted, it will interpret the word as a pattern and replace it with an alphabetically sorted list of file names that match that pattern exactly. Since we don't have any unquoted characters that would trigger globbing, the shell will skip this stage too. Awesome, we're almost there. Now, having dealt with expansions, which was step 3 of the overall process, the shell will then move on to step 4, which is quote removal. Quote removal is where any unquoted backslashes, unquoted single quotes, and unquoted double quotes that were not produced by the above expansions are simply removed from the command line. Like the scaffolding when building a house, they have served their purpose and can now be cleaned up and removed. For example, the quotes that are around Simon.Smith are unquoted and are not the result of an expansion. They were there before the expansions even occurred. Therefore, these quotes are removed, so our command line ends up looking like this. And that's it for quote removal. Now, step 5 is redirection, which is the final step before the command is actually executed. At this step, the shell scans the command line for any redirection operators. We have one redirection operator, which is part of the first simple command here. The redirection operator is the single greater than sign, so the shell knows that it has to redirect the standard output of this command to the file output.txt and create that file if it needs to. Because it is just one greater than sign, the shell also knows to delete or truncate any data that is already in the file before writing new data to it. And that's it. The shell has now fully processed our command line, and this is it in its final form with graphical representation of the redirections. Then finally, our command is executed. Now I want to ask you at this stage, how many arguments do you think were passed to the echo command? Well, the number of arguments to a command is simply the number of words that follow it on the command line. Now, because Simon Smith is referred to as one word, the echo command only takes one argument. This is a very important point. For commands like echo that just do the same thing for each argument, regardless of how many arguments they take, this doesn't make much difference, but for more advanced commands where the number and position of arguments do matter, it's a very important point indeed. Just remember that each individual word that is part of a simple command, after the command name itself, is considered as an individual argument to that command. You should now be getting a clearer picture of how all the videos in this section tie together and how the shell is working through each step of its process when processing command lines. In case you want to work through this example again on your own, I've attached a PDF version of the slides to the resources section of this video that you can download and take a look at and flick through as many times as you need to. So well done for making it through this example, and in the next video we're going to be working through another example which will allow us to focus a bit more on the intricacies of word splitting and quoting and their effects on how a command is interpreted. So I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're just going to be continuing working through the worked examples. Now in this video, we're going to be working through an example that should allow us to get a bit more of an insight into how word splitting works in detail, and also give you an insight into how the understanding that you now have about Bash's quoting rules and Bash's command line processing flow can help you avoid frustrating syntax mistakes. So let's go ahead and get started. So here's our next example, which this time takes the form of a script. The example is similar to our previous one, but it has some subtle differences that will hopefully highlight why having the rare understanding that you've gained from this section of the course can be so useful when working with Bash. The aim of this script is to take someone's username and split up the first name and last name and then save that to a file called output.txt in our home directory. So for someone whose username is Simon.Smith, the script would write Simon space Smith to the file. Admittedly, this is a bit of an artificial example, but it will help us to demonstrate some important principles. Okay, let's work through this together. The first step the shell will do is tokenization, which is where the shell will identify unquoted meta-characters on the command line and use them to identify tokens. The shell will then categorize these tokens as either words or operators. This command line is very similar to the one we had in the last video, so we have the same unquoted meta-characters, which are 3 spaces and the greater than symbol. Like before, we also have 3 words, which are echo, $name, and $out. And we also have one operator, which is the greater than redirection operator, which we know redirects standard output. So after completing this step, the shell moves on to step 2, which is command identification. The shell again finds one simple command, like so. And remember, the redirection counts as part of the command because only control operators are used to separate simple commands. The shell now moves on to step 3 and performs the expansions. Stage 1 of the expansions, or step 3a if you like, is brace expansion. We don't have any brace expansions, so we move on. Step 3b is to process parameter expansions, arithmetic expansions, command substitutions, and tilde expansions. These are going to be processed from left to right as they appear on the command line, so let's work through them in the same way, from left to right. The first thing we have is a parameter expansion, which is $name inside double quotes. So that will get expanded out to the value of the name variable, which is Simon.Smith, and it will be left inside the double quotes as one word for the time being. The next thing we have here is a tilde expansion. I want to ask you what you think will happen here. Will the shell perform the tilde expansion or not? Well, this brings us on to a really important point about double quotes. If you remember back to our lecture on quoting, double quotes will remove the special meaning from everything inside of them except for two things, which were dollar signs and backticks. Notice how tildes aren't an exception in double quotes. So what this means is that the tilde will actually be escaped by the double quotes and interpreted literally. Oops. Instead of expanding out to the user's home directory, the tilde will stay there literally as a tilde, which is not what we wanted and will likely cause us issues later on. We have one more thing on the command line, which will be dealt with in step 3b, which is the parameter expansion for $out. The dollar here is still given special meaning by the double quotes, so that expansion goes ahead, and $out is replaced by output.txt. So the result we have at this stage is as follows. We know that we have an issue with the tilde, which should have been expanded out to our user's home directory, but other than that, we're looking pretty good, right? Well, the next stage of step 3, so step 3c, is word splitting. Now, if you remember, word splitting is only performed on the results of unquoted parameter expansions, command substitutions, or arithmetic expansions. So in other words, everything from step 3b except for the tilde expansion. So in our case, we have two parameter expansions that have happened, one for $name and one for $out. Here we've run into our second problem. We set the IFS variable equal to a full stop, or period, or dot if you prefer, because we wanted the user's name to be split into two words, Simon and Smith. But doing the parameter expansion inside double quotes has stopped word splitting from happening. However, it also shows us the benefit that we got from doing the $out expansion inside double quotes. We set IFS to a dot, but we don't want output.txt to be split into two words. We want it to stay as output.txt. Because we have our IFS variable as a dot, if we had done the expansion of $out outside double quotes, output.txt would have been split into two words, which would have been output and txt. Because redirections can only point to one place, this would have caused us some other problems. Because we have some pretty serious issues with our command line already, let's go back to the beginning and revise it to make it work how we want. So here's our original command line, and here is where we got to. The first thing we want is to make sure the user's name gets split at the full stop. Because we did the expansion in double quotes, and word splitting only gets performed on the results of certain unquoted expansions, word splitting doesn't happen on the user's name. So let's remove those double quotes. Now, we want the tilde to actually become the user's home directory. At the moment, because tildes aren't given any special meaning inside double quotes, our tilde expansion did not occur. However, we can't just remove all the double quotes because that would open us up to unwanted word splitting on our output.txt. So to fix this, we have two options. First, we can simply just move the tilde outside the double quotes, like so. Alternatively, we can use the $home variable inside the double quotes, like so. You'll see this a lot in scripts. Often people use the $home variable instead of the tilde expansion to make their life easier, as they don't have to worry about the impact of the double quotes on the tilde expansion. Parameter expansion, such as $home, will work just fine inside double quotes, and arguably this method is the more aesthetically pleasing and readable option. I'm going to continue with this $home syntax for the rest of the example. Okay, now let's go back through and see what effects this will have. The tokenization and command identification steps will work exactly the same. We'll then get to step 3, where we process our expansions. Step 3a deals with brace expansions, and we don't have any brace expansions, so let's skip that step. Step 3b is about parameter expansions, arithmetic expansions, command substitutions, and tilde expansions. If we look at our command line, we have 3 parameter expansions now, which all get performed fine to give us this result. Step 3c is word splitting, and as I said earlier, word splitting happens on the results of unquoted parameter expansions, command substitutions, or arithmetic expansions. And the expansions for $home and $out all happened inside double quotes, so word splitting is not performed on them. So we have just one result of an unquoted expansion, which is Simon.Smith, the result of expanding the $name variable using a parameter expansion. Our IFS variable is currently set to a full stop, or a dot or a period, so our name will be split into Simon and Smith as 2 separate words, like so. Because we now have 2 separate words following the echo command, the echo command now officially has 2 arguments. This won't matter for echo, but is an important point to bear in mind when working with other commands whose functionality may be more fussy about the number of arguments they take and how those arguments are provided. Okay, so step 3d is globbing. The shell will search the command line for any unquoted asterisks, question marks, or left square brackets and process words containing those as patterns. Since we don't have any of those unquoted characters, we don't have any globbing patterns, so we can skip this step. Awesome, we're almost there. Step 4 is quote removal. So this is where the shell will remove any unquoted backslashes, single quotes, or double quotes that did not result from one of the expansions in all the stages of step 3. If we look at our command line, we can see that these double quotes here in the redirection are unquoted, and they didn't result from any expansions. They were there at the start. Therefore, quote removal will remove them so that we end up with this. Having done quote removal, the shell will then move on to the 5th and final step and process any redirections. We only have one redirection for this command line, which tells the shell to connect the standard output stream of the echo command to the file /home/username/output.txt and then remove the redirection from the command line. Finally, the shell will run the resulting command and we will get Simon space Smith written to output.txt in our home directory. And when we try this command for ourselves in the terminal, we see that this is exactly what happens. So that's it for our second worked example, which has hopefully given you a bit of insight into how word splitting works in detail and how understanding this process and using the cheat sheet you've got for this section can really make working with Bash's command line a lot easier and a lot clearer and a lot more transparent. And just like last time, in case you want to work through this example again on your own, I've attached a PDF version of the slides to the resources section of this video for you to download and take a look at. Up next, we're going to be having our third worked example, which contains a bit of an interesting twist. I hope you're excited, and I'll see you in the next video. Hello there, you beautiful people. Now in our final worked example, we're going to be throwing in some globbing and command substitution. This brings into the process a bit of a twist, so grab your cheat sheet and let's get into it. Our command for this example will be as follows. Now the first step that the shell will do when it receives this command is tokenization. Now, as you know, this is where the shell will find unquoted meta characters on the command line and use these to break up the command line into words and operators. Now in this example, the shell finds only one unquoted meta character, which is the space after the echo command. Even though there is another space inside the command substitution, the shell does not handle this now because it is inside double quotes. The shell then identifies words and operators. Now given that there's only one unquoted meta character and no operators, this command line is broken down into just 2 words. The shell then performs command identification by looking for control operators. In this case, there's only a single command, which is terminated by the invisible new line character at the end of the line. The first word in the command is echo, so that is the command name that the shell will look for, and the second word is this command substitution, which counts as a single argument to the echo command. You'll note again that even though there is another command inside the command substitution, because the command substitution only happens in the second stage of expansion, the command substitution isn't handled at this stage and doesn't have any special meaning yet. At this stage, the shell just sees two words. After having done command identification, the shell will go through the 4 stages of expansions. On stage 1, it will do brace expansions, and we don't have any brace expansions, so we'll move on. On stage 2, the shell will process parameter expansions, arithmetic expansions, command substitutions, and tilde expansions in whatever order it comes across them. Now in this case, we have a command substitution, and therefore it's going to be expanded at this stage. And this is where our little twist comes in. A command substitution actually runs the command it contains in a subshell, and then hands the output back to the initial command line. So at this point, because the shell identifies the syntax for command substitution, it then launches a subshell and starts the entire process all over again in the subshell. So, taking the command inside the command substitution, which is ls star.txt, we start again with tokenization. The subshell identifies again one unquoted metacharacter, which is the space. We then get 2 words identified, which are ls and star.txt. Command identification picks up again only one simple command, and so we have ls star.txt as one command. The first word is ls, so that's the command name, and the second word is star.txt, which is the first argument to the ls command. The subshell then begins to process expansions. Stage 1 of processing expansions is to check for brace expansions. There are no brace expansions in this case, so the subshell moves on. Stage 2 of processing expansions is to process parameter expansions, command substitutions, arithmetic expansions, and tilde expansions. There are none of these in this case, so the subshell moves on. Stage 3 of processing expansions is to process word splitting. Now, because word splitting only operates on the results of parameter expansions, command substitutions, and arithmetic expansions, and because none of these were performed, there is no word splitting to do either, and the subshell moves on. Stage 4 of processing expansions is to process globbing. During this step, the subshell scans the command line for unquoted asterisks, question marks, and left square bracket characters. Now, although the asterisk was quoted on the original command line, because it was passed as part of a fresh command to a subshell during the command substitution, it is now unquoted, and this triggers the subshell to start performing globbing. Let me just go over that step in a bit more detail. Our original command line looked like this, but the part that was actually passed into the subshell looks like this. This is the part inside the parentheses of the command substitution. Do you notice how the asterisk is unquoted in the command that's passed to the subshell? That's an interesting and potentially perplexing feature that is worth bearing in mind when working with command substitution, so I wanted to point it out here so that you don't get caught out by it. Okay, because the word star.txt contains an unquoted asterisk, the word will be interpreted as a pattern. As you learned in the videos on globbing, this pattern will match any file in the current working directory that ends in .txt. As an example, let's say we have the files a.txt and b.txt in the current directory. These will be found, sorted alphabetically, and replace the pattern star.txt on the command line, with each result being its own word. So we now have the command line ls a.txt b.txt. Okay, so that's it for expansions. However, we have no quotes and no redirections on our command line, and therefore quote removal and redirection are not performed. So that's the end of the 5-step process for the subshell, so finally this command is executed in the subshell. Because a.txt and b.txt are files and not folders, ls just gives their names right back, so the result of this command is simply a.txt, b.txt. This output is then passed back to our main shell as a replacement of the command substitution. This now gives us back in our main shell echo, and then in double quotes, a.txt, b.txt. the original shell process now picks right up where it left off and continues with having now successfully completed command substitution in the subshell. So what's next? That's right, word splitting. Word splitting is performed on the unquoted results of command substitutions, but because the command substitution is quoted from the perspective of this parent shell, word splitting is not performed. The next step is globbing. Globbing took place in the subshell, and now when the shell scans the command line, it will not find any unquoted asterisks, question marks, or left square brackets, and therefore globbing is not performed. So that's it for expansions. The shell now moves on to quote removal, where it removes any remaining unquoted backslashes, single quotes, and double quote characters that did not result from an expansion. These double quotes here are unquoted and weren't the result of an expansion, so they're removed and our command line ends up simply being echo a.txt, b.txt. And there are no redirection operators, so no redirections are performed. So that's it, we've done the 5-step processing flow, so finally the command is then executed and we get the output a.txt, b.txt printed out to our terminal. And if we type the command out in our terminal and we run it, we see the results that we expected. Of course, having created a.txt and b.txt for example purposes. So this has been quite a quirky example, but hopefully it has given you some insight into how Bash uses subshells to process command substitutions, which is pretty cool. As usual, I've uploaded the slides for this example so that you can work through it on your own as well. So that's it for the guided worked example videos. Now if you want some more practice of going through this 5-step process on your own, up next I've provided a problem set that you can try out for yourself, and if you need any support, please do reach out in the Q&A forums and we'll be happy to help. Either way, well done for working your way through this important section on how the shell processes command lines, and this is probably going to be the most crucial section of the course, so a massive congratulations for completing it, and I'll see you in the next video for a wrap-up and a section review. Hello there you beautiful person, and congratulations for completing the 3rd section of the course, which has been all about how the shell processes and interprets command lines. This really is one of the, if not the most important section of the whole course. You'll use the understanding that you've gained from this section time and time again when making Bash scripts, so a massive congratulations for working through this section and getting to grips with everything. You're doing absolutely great. In this video, we're going to walk through the cheat sheet for this section to have a quick recap of the points that we've covered and to make sure that you're comfortable with everything. And as always, you can find and download a copy of the cheat sheet from the resources section of this video. So let's go ahead and have a recap. In this section, you learned about the 5 steps that the shell goes through to process command lines before running them. The first step was tokenization. You learned that during tokenization, the shell breaks up the command line into tokens using unquoted meta characters. A full list of all the meta characters the shell will use is placed here for your reference. The shell will then categorize these tokens into words and operators. You learn that words are tokens that do not contain any unquoted meta characters, and operators are tokens that contain at least one unquoted meta character. You learn that there are 2 types of operators, control operators and redirection operators, all of which are listed here. Next, you learned about the second step, which is command identification. During this stage, Bash takes all the words and operators it found in the tokenization step and groups them together into simple and compound commands. You learned that simple commands are a series of words terminated by a control operator. In simple commands, the first word is interpreted as the command name, and all subsequent words are interpreted as individual inputs or arguments to that command. We also have some examples here of how simple commands are interpreted by Bash for you to refer to if you need to. We then moved on to compound commands, and you learned that compound commands are Bash's programming constructs. We haven't really covered compound commands yet in this course, but you learned that compound commands all start with a reserved word and are terminated by a corresponding reserved word. Here on the cheat sheet we have an example of an if statement, which we use to do logical checks in our scripts. We'll cover if statements more later in the course, but at a high level we can see that it starts with the reserved word if and is terminated by the reserved word fee. Because of this behaviour, compound commands can span more than one line, and this allows them to have multiple commands nested inside of them. As I say, we'll be covering compound commands in more detail later on in the course. We then moved on to step 3 of 5, which is expansions. You learned that Bash actually has 4 stages to processing expansions. Earlier stages are given higher precedence and perform first, and expansions within the same stage all have the same precedence and are simply processed in the order they appear on the command line when it is read from left to right. You learned that the first stage of expansions, or step 3a if you like, is called brace expansion, which we covered in section 2. So please refer to the section 2 cheat sheet for more information on brace expansion if you'd like some. The second stage, so step 3b, contains parameter expansion, arithmetic expansion, command substitution, and tilde expansion. All of these were also discussed in section 2 of the course, so again please refer to the cheat sheet for section 2 if you'd like more information on these forms of expansion. The third stage of expansion, so step 3c, was word splitting, and this was a new piece of content for this section of the course. With word splitting, the shell will try to split the results of unquoted parameter expansions, arithmetic expansions, and command substitutions into separate words. Word splitting is important because each word provided to a simple command after the command name is considered as an individual argument to that command. So, Bash splitting data into multiple words behind the scenes can really affect how a command functions and potentially cause a lot of confusion if you don't know what's going on. It's important to note, however, that word splitting is not performed on the results of expansions that occur inside double quotes. So if you don't want the result of an expansion to undergo word splitting, wrap the expansion in double quotes. Another way of saying this is that if you want the result of an expansion to be considered as one word, then wrap the expansion in double quotes, and that really is the key to understanding word splitting. The cheat sheet also shows a few examples here of how word splitting affects an expansion's output and how a command might function differently based upon that. Another key concept for understanding how word splitting works is the IFS variable. You learned that Bash will use any character inside the IFS variable to split words when doing word splitting. By default, the IFS variable contains space, tab, and new line characters, but you can modify the IFS variable to contain anything you like in the same way that you'd modify any other variable. To view the current value of the IFS variable, you can use the command shown here in Note 5. We use the @q here just to make the invisible characters like tabs and new lines show up, because usually they're invisible on the command line. So, having fully mastered word splitting, you then learned about stage 4 of expansions, which is globbing. Globbing is a very useful feature that can help you select a large amount of file names for a command to operate on. You learned that during the globbing stage, Bash scans each word for unquoted special pattern characters, which are the asterisk, the question mark, and the left square bracket. You can see the meanings of each of these special characters listed here. Any word containing an unquoted version of one of these characters is interpreted as a pattern, and replaced with a list of alphabetically sorted file names that match the pattern as a whole. We also have a table of examples here that you can refer to if you need to re-jog your memory of how to write the patterns. The next step that we looked at in the process is quote removal, which is step 4 out of 5. The purpose of quote removal is to remove the quotes that you added purely to remove the special meaning from other characters. You learned that during quote removal, the shell will remove all unquoted backslashes, single quote characters, and double quote characters that did not result from a shell expansion. In other words, if those quote characters resulted from an expansion or are themselves quoted, then they will not be removed. All other quote characters will. There's a table of examples here that you can refer to help re-jog your memory of how quote removal works. Then it was on to the final step of the process, which is redirection. You learned that there are 3 standard data streams that commands can connect to, which are standard input, standard output, and standard error. Note that not all commands use every data stream. For example, some commands don't have a standard input stream, and some commands don't provide standard error. The best way to find out which streams a command uses is to try the command out for yourself, or to read its manual page and check if there's any information in there. Each of these streams can only connect to one location at a time, and redirection is all about changing where they connect to. Redirection is performed using redirection operators, and we looked at the 7 most common redirection operators, which you can see the meanings of all tabulated here. An important thing to note is the difference between truncation and appending when you're redirecting output streams. The operators that use one arrow when redirecting output will truncate the destination file before writing output to it, which means that the contents of the destination file will be deleted before any new data is written. Oftentimes, this is not what you want, but by using two greater than signs, you can append the new data to the data that is already there. And finally, after having processed all these 5 steps, the shell then executes the resulting command. So as you can see, we've covered a whole lot of important concepts in this section, and you've done an absolutely phenomenal job for making it through, so well done to you. You now have an incredible grounding on how Bash actually works behind the scenes, which we can now build upon to learn how to create professional, high-quality Bash scripts. In fact, you probably have a better insight right now into how Bash works than most Bash users in the world. At the end of this section, you should now be able to list the 5 steps that the shell goes through when processing command lines and in what order they happen. You should be able to describe how quoting is performed in Bash and how this affects the way that the shell processes command lines. You should be able to describe how the shell performs tokenization using unquoted meta characters. You should be able to explain the difference between a word and an operator. You should be able to explain how the shell identifies where simple and compound commands start and finish on a command line. You should be able to explain how the shell performs all various types of expansions and in what order it performs them, and actually be able to perform all of them yourself. You should be able to manipulate the IFS variable to control how the shell will perform word splitting. You should be able to create basic globbing patterns within your Bash script. You should be able to explain how and why the shell performs quote removal. And finally, you should be able to explain how the shell processes redirections and be able to redirect standard input, standard output, and standard error however you wish. So once again, that is a whole lot of stuff, and a massive congratulations to you for covering all that much content. Well done. What you've learned here has given you a great conceptual foundation to start now layering practical skills upon, and one that will hopefully save you an incredible amount of frustration moving forward. So a massive congratulations once again, this is a truly great achievement. And of course, you can always download the cheat sheet from the resources section for this video if you haven't done so already, if you ever need to refer back to anything. Now in the next section of the course, we're going to jump right into building scripts, and we'll be looking at how you can get input from your users to customize a script's behavior. So for all that great stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this section of the course where we're going to be looking into all the amazing ways that Bash gives us to request input from our users for the scripts that we write. So let's take a look at what we're going to cover in this section. In this section, we're going to start off by having a look at positional parameters. Positional parameters are pieces of data that can be provided to your script on the command line. We're going to look at how we can use positional parameters in our scripts, and then also how you can use something called special parameters to process these positional parameters all at once. We're then going to have a look at 2 very useful commands that can be used to get input from users more interactively. We're going to be looking at the read command, which can be used to request a specific piece of information from the user by using a prompt where the user types in their answer. And we're also going to be looking at the select command, which can be used to create menus to allow users to select from a predetermined set of options at specific points in your script. And by the end of this section of the course, you'll be able to use positional parameters to have users provide specific information on the command line that your script needs to run. You'll be able to use special parameters to process positional parameters all at once, but in a variety of different ways. You'll be able to use the read command to request specific information from your users interactively at any point during your scripts. You'll be able to use the select command to create menus of predetermined options to present to your user and allow them to choose from those options at any point during your script. And you'll be able to save the information that's provided by your users in variables and use that information in your scripts. So feel free to download this section's cheat sheet from the resources section for this video so that you can keep it handy in case you need it as we go through. So we've got a lot of exciting topics to cover, so let's get into it. Hello there you beautiful people, and welcome to this video where we're going to be learning all about positional parameters. You've probably used countless commands where you first type a command name and then had to give some extra inputs on the command line to make the command work properly. Some common examples are the cd command, where you have to give the command the folder you want to move to, or the cp command, where you have to type the file you want to copy and where you want to copy that file to? Well, what makes this possible is a feature called positional parameters, and in this video you're going to learn how to make your scripts use positional parameters too. By the end of this video, you'll be able to use positional parameters to work with command line arguments in your scripts. This is a very useful ability to have, so let's go ahead and get started. Okay, so the first thing you need to know is that the shell assigns numbers, called positional parameters, to each command line argument that is entered. A command line argument is information that you give to the script when it is run, and these are all separated by spaces on the command line. An example of this is running a script, let's call it our script, and following it with some information, like someone's username, such as John, and a path to a particular folder, such as $home. In this example, John would be the first command line argument, and $home would be the second command line argument. Now the shell provides us with a set of corresponding positional parameters that can be used to refer to the values that are given as command line arguments. In this example, the positional parameter 1 would store the first command line argument, which in this case is John, and the positional parameter 2 would store the second command line argument, which is $home, and so on and so on. In other words, the parameters 1 and 2 and 3 and 4 and 5, etc. get their values based upon what is entered at certain positions on the command line, and this is how positional parameters get their name. So let's have a look at how we can use positional parameters in our scripts. Let's create a new script called positional script and add our shebang line at the top like usual. Now using the echo command, we can see what positional parameters do. So let's add a few echo commands into our script. So I'm going to add a command in here which says echo my name is 1, and then on another line I'm going to add in echo my home directory is 2, and then on the third line echo my favorite color is 3. Now I want to point out here that the positional parameters 1, 2 and 3 are just that, they're parameters. So, in order to get their values back out, in order to refer to their values, what do we need to do? That's right, we just need to use the parameter expansion syntax that we're already familiar with. You see how everything is tying together? So instead of just typing 1, 2 and 3, we will type $1, $2 and $3. Okay, so let's save that, exit the script, and give our script execute permissions as usual using chmod 744 positional script. Now in this script, we set up 3 positional parameters, $1, $2 and $3. As discussed, these refer to the values of the first, second and third command line arguments that are given to our script. So if I give the script a first command line argument of John, a second command line argument of $home, and a third command line argument of blue, and then I run it, you'll see that we get back my name is John, my home directory is /home/Ziad, and my favorite color is blue. So as I said, what is happening here is no different to the regular parameter expansion that you're already familiar with. We still have the dollar and then the parameter name, which in this case, the parameter names are just 1, 2, and 3. The only difference is that instead of us creating user-defined variables by, for example, saying 1 equals John, and naming the variable ourselves and setting the value manually in the script, it is the shell that is defining these parameters for us based on the arguments we give to our scripts. The shell is handling it automatically. When we enter these values on the command line, the shell simply saves inside a parameter called 1 the value of John, and saves inside a parameter called 2 the value of $home, and saves in a parameter called 3 the value of blue. We then simply use parameter expansion to get the values back out again with $1, $2, $3, etc., just like we would with our own variables. However, an important consequence of the fact that the shell creates these positional parameters is that numeric parameter names like 1, 2, 3, etc. are reserved. This means that we cannot save values in them manually ourselves. For example, in the terminal, if I try to do 1 equals John, you see I get an error. This is the shell's way of protecting the way positional parameters work. So how many positional parameters can we have in a script? Well, there's actually no limit to how many that you can have. The only downside of having a lot of positional parameters is that you need to know exactly which position a certain input will be in order to work with it. This means that, for sake of convenience of both the programmer and of the user, it's rather uncommon to have a lot of positional parameters in a script. Either way, an important thing to note is that if you do go into double digits, so from the 10th parameter expansion onwards, you need to use the advanced $curly brace parameter expansion syntax that we saw earlier to get the right value back. If we head back into our script, we can add a couple of lines to test this behavior. First, we'll add in a line to print out the 10th argument, and this time we're going to do it correctly using the $curly brace syntax. So we'll write echo, the 10th argument is, then $curly brace, 10 curly brace. Then, we'll also add in a line where we write echo, the 11th argument is $11. But here, we're not going to have the curly braces. We'll leave the curly braces out. So let's save our script and head back to our terminal. Okay, so let's give our script 11 command line arguments. So in this case, I'm just going to type the letters from A to K, which are the first 11 letters of the alphabet. If we run this command now, you can see that the first 3 lines give similar output to before, and that the 4th line, where we correctly wrapped our positional parameter in curly braces, has echoed out our 10th command line argument as it should, which in this case is going to be the letter J. However, you can see that the 5th command has not worked. We got A1, but we expected the letter K. So what happened here? Well, the reason for it giving us this result is that instead of doing $11, the shell just did $1, which is the letter A, and then immediately printed a 1 after it. So we got A1. So hopefully this should give you an idea of the importance of using the advanced parameter expansion syntax rather than the simple one when working with a lot of positional parameters. So as you've learned, positional parameters are a very helpful way to run a script when you expect a strict order to the inputs on the command line. In this video, you learned that command line arguments are information that you provide to your script from your command line, and each argument is separated by a space. You learned that positional parameters are the parameters set by the shell that are used to store the value of each of these command line arguments, and then named based on their position on the command line. You learned that you can't save data into positional parameters manually by yourself, and only the shell is allowed to do that. However, you learned that you can refer to the values held by positional parameters using the parameter expansion syntax that we're already familiar with. The only thing to note is that you need to use the advanced $curly brace syntax for positional parameters 10 and above. You should now be able to use positional parameters to retrieve information from command line arguments and then use that information in your scripts. Positional parameters are something that will come up all the time when bash scripting, so very, very well done for learning this very valuable skill. Because being able to use positional parameters is so useful, up next you're going to have a project where you'll have a chance to practice what you've just learned about positional parameters to create your very own calculator. And after that, we'll move on to take a look at special parameters, which is also a completely game-changing topic. So I hope you're excited, good luck with the project, and I'll see you in the next video. Hello there, you beautiful people. I hope you had loads of fun trying out this project. In this video, we're going to walk through the model solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's get started. So we're going to start off by creating our calculator script file in Nano. So I'm going to type nano calculator, and then we're going to quickly add in our shebang line. So now using the echo command, we're going to write a command line that will take our positional parameters and use them in an arithmetic expansion. So we'll start by putting in echo, and then we're going to start our arithmetic expansion with the double parentheses syntax that we saw earlier. As mentioned in the project brief, the first positional parameter, $1, is the operator that the user has tried to use, so a plus or a minus symbol, and the positional parameters $2 to $10 are the 9 numbers that we want to use in our calculation. Now, as I mentioned in the project brief, when doing parameter expansion, you can use syntax like this to first check if the parameter is empty, and if it is, fill it in with a default value, and that default value is represented by the word here. This serves as kind of a safety mechanism by making sure our parameters are never empty, and thus ensuring that our script doesn't crash. Now if we open up a calculator, you can see that I'm just using the standard calculator that comes with Ubuntu here, and if I try to do 1 plus, and then I don't enter another number and I try to see what that calculation equals, you can see that I get the error malformed expression. Here you can see that this operation has failed and has given us an error because essentially the computer is saying that you can't add blankness to 1. That doesn't make sense. In our case, if bash tried to add an empty parameter to a number, it would result in exactly the same type of error because the bash shell would say, hang on, how can I add blankness to something? Something's not right, something's missing here, and it would give us an error. Now, given that we will not always have 10 positional parameters provided to our script, maybe the user only wants to add 2 or 3 numbers, for example, we need to use this safeguard to ensure that our script doesn't fail if we didn't provide all 9 numbers. To achieve this, we have to use the syntax colon, then a minus sign, and then 0. And we're going to use that together with each positional parameter that contains a number, so that if we didn't provide a number, then the shell will add in a 0 in its place for us. So starting with the first number, which is positional parameter 2, we're going to enter it like this, putting in the 0 where word was in the example syntax. So we've now told our script that if positional parameter 2 has no value, so the user didn't enter positional parameter 2, then please enter a default value of 0 for that parameter. So following on from this, we need to add in our operator, which is positional parameter 1, so we simply put in $1, and then followed by our second number, which in this case would be $3, and again, we're going to be adding in our failsafe of 0. Okay, so what does this mean? It looks really weird. Well, let's say our operator stored in $1 was a plus. And let's say our first number stored in $2 was 7, and that our second number stored in $3 was 9. The shell will do parameter expansion, and it will end up with 7 plus 9, which will give us the result of 16. So let's say we had $1, which included our operator, and we had $2, which had a number in it, but there were no other positional parameters provided. Then because we've set this failsafe, the third positional parameter would be replaced with the default value of 0. We would then have 7 plus 0, which is a valid calculation, and thus bash would give us the result of 7. If I didn't give it the default value, bash would try to do 7 plus blank, and therefore the script would fail. So let's add in all the remaining positional parameters using this technique and separate each one with $1, which contains our operator. So that looks kind of crazy, but let's test out a few sums with our new calculator just to see what's going on here. So let's save our script and head back to our command line and give the script appropriate execution permissions. Okay, so if I now run our script, and we give it the positional parameters of plus 5, 5, 5, and 5, and then we run it, you can see that we get the output of 20. So what's happened here is that the first positional parameter, $1, expanded to the plus. The second, third, fourth, and fifth positional parameters all expanded to 5s because that's what we provided. So given this command, that would have resulted in 5 plus 5 plus 5 plus 5 as our calculation. Now because we didn't provide any other positional parameters, as discussed, the shell would replace their empty values with zeros, which means that we would have actually ended up with the calculation of 5 plus 5 plus 5 plus 5, and then for the rest of the numbers, plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. So this is working, and it's a pretty cool little adder that we've created. Just as another test, I'm going to use a minus as my operator to do subtraction this time. Then the numbers I'm going to add will just be 9, 8, 7, 6, 5, 4, 3, 2, 1, just to show that we can use all the numbers available. And as you can see, the solution is minus 27, which is correct. And that's all there is to it. So I hope you had fun doing this short brain teaser of a project, and that it gives you a good idea of how positional parameters work and how you can use them in your scripts, along with some more advanced syntax. You can download the official solution script for the project from the resources section of this video. Now in the next video, we're going to be taking your scripts to the next level by learning how we can use special parameters to expand to the positional parameters in different ways. So for all that good stuff, I'll see you in the next video. Hello there, you beautiful people, and I hope you had a lot of fun with the positional parameters project. We're going to be moving on now from positional parameters, and over the next 2 videos, we're going to be taking a look at Bash's special parameters, which are obviously mega exciting because they're special. In this video, we're going to be taking a look at the $# and $0 special parameters, and you're going to learn what these special parameters do and how you can use them in your scripts. And by the end of this video, you'll be able to explain what special parameters are and how they differ from other types of parameters. You'll be able to explain the role of the $# and $0 special parameters, and you'll be able to use the $# and $0 special parameters in your scripts. So let's go ahead and get started. So what are special parameters? Well, special parameters are, as the name would suggest, parameters that Bash gives special meaning. In this way, they are a similar concept to shell variables, but the key difference is that while we can change the value of shell variables ourselves, like we did with the IFS variable before, we can't change the value of special parameters. The thing that makes a special parameter special is that the value of a special parameter is calculated for us based on what is happening or has happened in the current script. We do not enter the values of special parameters ourselves. Although we can't alter their values manually, special parameters do provide handy shortcuts to very useful information, and because they cannot be modified, we can be confident that the data they hold is accurate. In this video, we're going to be looking at the $# and $0 special parameters, so let's start with $#. The $# special parameter expands to the number of positional parameters that have been provided to the script. To see an example, let's edit our positional script that we've created before, and at the end of it, let's add in the line echo $#. Now, when we run this script again with A, B, C, and D as command line arguments, here you can see that the output we get from that final echo command is 4. We have 4 positional parameters provided to this script, and the special parameter $# has counted these and given the output as the total number. I want to mention that the special parameters are just parameters. In fact, strictly speaking, the special parameter name is actually just hash. $# is just the parameter expansion of the hash parameter. So all that you've learned about parameter expansion, including parameter expansion tricks, applies to special parameters too. The only difference is that you can't change the value of special parameters yourself. Okay, now let's take a look at the $0 special parameter. Now, one weird thing about special parameters is that, depending on the context in which Bash is used, the same special parameter can take on different meanings. Welcome to Bash. For example, if used in a regular terminal, the $0 special parameter expands to the name of the current shell, which is Bash. However, if it's used in a script, $0 expands to the name of the script, and this behavior is the one that we're interested in this lecture. You can of course read the page in the Bash manual about special parameters that I've put a link to in the resources section if you're interested in the other variations of $0. Now, for our purposes, one benefit of $0 is that it makes it easy for us to create error messages for our users. For example, it's possible to combine $# and $0 to check whether the user has provided enough positional parameters, and if not, to echo to the user an error message telling them how to use the script. I'm skipping ahead a bit here, as we haven't covered logic yet, but just bear with me to understand the potential use case here. Let's say we had a command called special script, and we wanted it to take exactly 2 command line arguments, file1 and file2. If the user doesn't enter exactly 2 command line arguments, we want to give them an error and tell them how to use the command correctly, and then exit the script. Now, I've actually already created a script called special script in the current directory, so let's open it in Nano to see how we might go about approaching this. Now, I don't want you to get too freaked out by this strange looking code. It's mostly logic stuff, and we'll be covering logic and if statements in detail in the next section of the course. The key point here is how we're using the special parameters. Here we're saying that if $#, which is the number of command line arguments provided, does not equal 2, then echo out these pieces of text and exit the script with an exit code of 1, which, as you know, is a non-zero exit code and therefore indicates an error. Now if I close the script and run it with 2 command line arguments, we see that everything works just fine and we get no error message. However, if we run it without two command line arguments, so let's say we give it none, we can see that this time we get an error message telling us how to use the script properly. This usage message is actually being produced using the $0 special parameter. The name of the script, which in this case is special script, is being pulled in by the special parameter $0 and then used in the echo command. The bottom line here is that using $0 in our script, rather than writing the script name manually, allows us to rename our script as much as we want, but still keep our error messages in the same format, which is often convenient. For example, if we change the name of the script from special script to very special script using the mv command, and then we rerun it, again giving 0 special parameters, we can see that this time our error message has automatically changed to include the correct script name, without us needing to retype anything ourselves. So that's about it for our first video on special parameters. In this video, you learned that special parameters work just like regular parameters, but they're special because their values are calculated for us by the shell and we cannot manually change the values ourselves. Because they're like regular parameters, everything you've already learned about parameter expansion applies to special parameters as well. You learned that the $hash special parameter stores the number of command line arguments that the user provided to the script, and you learned that the $0 special parameter stores the script name and can be used to create error messages. So now that you've gotten introduced to the concept of special parameters, in the next video we're going to be taking a look at two really useful special parameters, which are $* and $@. You'll probably use these in many of your future bash scripts, so I hope you're excited to learn about them. So for all that special parameter goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be continuing our discussion of special parameters by looking at the $* and $@ special parameters. $* and $@ are incredibly useful, but they do have some special behavior that can make them a bit confusing. This is one of those more gritty areas of bash, so it might take a bit of work to understand at first, but trust me, the reward for sticking with it is so worth it. In fact, this is probably the final, more difficult part of the whole bash language. So if you do get a bit confused by this video, don't worry, just take a break and watch it again with a pen and paper and work through the concepts and you'll be fine. And of course, you can always post a question in the Q&A forum as well and we'll be happy to help out. Now in this video, you're going to learn how to use the $* and $@ special parameters and how their meaning changes when you wrap them inside double quotes. And by the end of this video, you'll be able to use the $* and $@ special parameters to have a convenient way to access all positional parameters at once. And you'll be able to explain the different meanings that these special parameters have when they're wrapped inside double quotes. So let's go ahead and get started. So to start with, we're going to have a look at the special parameter $@. Now, unlike the original way that we were dealing with positional parameters, where we had to list out each positional parameter one by one in order to access its value, $@ allows us to access all the positional parameters at once that are passed to our script, and it separates each parameter with a space. When you write $@, the value becomes $1 space $2 space $3 space all the way up to $n, where n is just a representation of the total number of command line arguments that were provided to your script. Each of these positional parameters, so $1, $2, $3, etc., is considered as its own word. Now because $@ is just a parameter expansion, the words that are produced, so $1, $2, etc., are all subject to word splitting individually. Now this is in contrast to $@ wrapped in double quotes. Now based upon what we know before from our study of quoting and parameter expansion, we might assume that $@ wrapped in double quotes would give us something like this. So $1 space $2 space $3 space all the way up to $n, and all of that wrapped in double quotes and considered as just one word. But what actually happens is this. You get $1 in double quotes, space, $2 in double quotes, space, $3 in double quotes, space, all the way up to $n in double quotes. Just like when $@ was quoted, each parameter is taken as its own word. However, because $@ was wrapped in double quotes, each of those individual words is now also wrapped in double quotes and therefore will no longer undergo word splitting. So let's see $@ in action. Let's create a script called special, and then let's open it and add in our shebang line. So to demonstrate what $@ does, we can simply add in echo $@ right down here at the bottom of our script. Now the main benefit of using the special parameters that you're seeing in this video is that they allow you to refer to all the positional parameters provided to the script in one go, without you having to know exactly how many positional parameters have been provided by the user. This allows us to provide our users with a lot of flexibility and convenience when using our scripts. Now if we save the script and then close it and give it the appropriate permissions using the chmod command, and then we run it, giving it the positional parameters 1, 2, and 3, you can see that the script has now echoed out all the positional parameters that the script was provided with. So instead of us having to type out echo $1, $2, $3, we only had to type out echo $@, which is much, much easier. And if we give our script more positional parameters, so if we run the special command with the command line arguments 1, 2, 3, 4, all the way up to 10, we can see that when we run this, Bash now echoes out all of these values as well, without us having to go in and tell the script explicitly to echo $1, $2, $3, $4, and so on all the way up until $10. All we had to do was write $@, and Bash took care of the rest. Now because $@ wasn't wrapped in double quotes, each of the positional parameters provided would be subject to word splitting. To demonstrate this, let's go back into our script and replace our echo command with the touch command, which, as you know, will create new files. And then let's go ahead and save our script. So as a quick look at what this script is doing, if we run the special script with the command line arguments 1, 2, and 3, and then we use the ls command, you can see that we've now created the files 1, 2, and 3. Now we just created these files for example purposes, just so you can see what the script does, so let me just go ahead and delete those. So now let's say we wanted to create files called daily space feedback, so that's one file, and monthly space report, and that's the other file. For this, we could run the special script with two command line arguments in quotes. We could give it daily space feedback inside double quotes, and monthly space report inside double quotes. However, if we use the ls command, you can see that instead of creating two files like we intended, which would be daily space feedback and monthly space report, we've actually created 4 files. There's daily, there's feedback, there's monthly, and there's report. This is because the touch $@ allowed our positional parameters to be subject to word splitting. And because there's a space in each of the names, and the IFS variable contains a space, each of those parameters was split at the spaces into 4 different files: daily, feedback, monthly, and report. To stop this from happening, we can just wrap the $@ inside double quotes. So let's remove these files that we've just created using the rm command, and this time let's open our script and wrap our $@ inside double quotes and save the script once again. So now let's run the same command again. So we're going to run the special script with 2 arguments, daily space feedback and monthly space report. And then when we run this and look at the ls command, now you can see that we've only created 2 files, daily space feedback and monthly space report, which is exactly what we wanted. The quoted $@ prevented word splitting from happening on the positional parameters. The distinction between unquoted $@ and quoted $@ is very important and potentially confusing if you're unaware of it. That said, you'll probably use the quoted $@ most often, so remember, when in doubt, quote it out. Next, we're going to have a look at the $* special variable. $* in its unquoted form is exactly the same as unquoted $at. There is absolutely no difference between unquoted $* and unquoted $at in practical terms. They'll always give the same result. However, quoted $* does give us some different results. Instead of placing a space between each positional parameter, like $at does, quoted $* will place the first character of the IFS variable between each positional parameter. Now, by default, the first character of the IFS variable is just a space character, but because you can change the IFS variable, quoted $* allows you to change how parameters are separated if you wish, which can be useful when generating comma-separated values or CSV files, for example. To give you an example, let's edit our script and put quoted $* in here instead of the quoted $at. I'm also going to change the command we use back to echo instead of the touch command, so that you can see clearly what is being echoed out when the shell is dealing with quoted $. Now, to see something interesting happen, we also need to set our IFS variable so that its first character is something other than a space, which is what the first character is by default. So we're going to set our IFS variable to a comma right here at the top of the script, just by writing IFS equals comma. And then we can save our script. And now if we run the script, again this time giving it the 3 positional parameters 1, 2 and 3, you can see that this has now echoed out 1, 2, 3. So quoted $* has given us each parameter separated by the first character of the IFS variable, which in this case was a comma. So now that we're at the end of the video, you should now have a pretty good idea of what $at and $* are doing. So let's have a quick recap to make sure you've got everything. In this video, you learned that $at and $* allow you to conveniently access all the positional parameters provided to the script without you having to know how many there are or explicitly refer to them in your script. You learned that $at expands to all the positional parameters provided by the script, but provides them as unquoted separate words. You learned that because the words coming out of $at are unquoted, they're subject to word splitting. You then saw that you can stop this subsequent word splitting by wrapping the $at inside double quotes. Quoted $at allows you to reserve the value of the positional parameters exactly how they were provided by the user, and therefore the $at inside double quotes is probably the most common way you will want to use special parameters to access command line arguments. We then moved on to $*, which is another common way people use to access command line arguments, and you learned that $* in its unquoted form is exactly the same as unquoted $at. They're completely identical and interchangeable. However, quoted $* is a bit of a weird one. It provides all positional parameters as one word, but with each parameter separated by the first character of the IFS variable. Because the $* is quoted, the word it produces is not subject to further word splitting. It's unlikely that you'll use quoted $* very often in practice, but now that you're aware of it, it's there if you need it. The behaviour of these special parameters is summarised in this table, and also in the cheat sheet available for this section of the course. So that concludes our discussion of special parameters. If special parameters have caught your eye, and you'd like more information about the other special parameters that are available, please check out the Bash Manual's discussion of special parameters, which you can find a link to in the resources section for this video. In the next lecture, we're going to do a quick quiz on what you've learned over the past 2 videos to make sure that you're comfortable with special parameters, and then you'll have a project where you can put these special parameters into practice. And then it's on to how to use the read command to ask your users specific questions in your Bash scripts. So good luck with the quiz and the project, and I'll see you in the next video. Hello there, you beautiful people. I hope you had loads of fun trying out this project. It was a bit of a puzzler, wasn't it? In this video, I'm going to walk you through the model solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's go ahead and get started. This is likely to be the shortest project solution video of the course, but that just goes to show just how useful the special parameters can be. So let's open up and edit the calculator script that we created for the positional parameters project. As you can see, when we use positional parameters, this was quite a complicated script, and the script could only handle a maximum of 10 parameters. So to improve this calculator, we're going to use the $at special parameter. As hinted at in the project brief, $at is the special parameter that expands to all the positional parameters as separate words. So we can simply replace the entire content of our arithmetic expansion with $at. And that's it. That's how cool special parameters are. So if we save and exit our script, we can now actually run this script and give it whatever calculation that we want, just like we would a calculator. So if I type 1 plus 2 plus 3 and run the script, we can see that it works. We can also mix and match multiple operators. For example, I can run the calculator script with 10 minus 5 plus 8, and it still works. By using $at, the exact calculation that we type in as command line arguments to the script is then placed inside the arithmetic expansion, which works perfectly for us. So that's it. Yeah, really quick. So I hope you had fun doing this short brain teaser of a project and that it gives you a good idea of how useful special parameters can be and how you might want to use them in your scripts. You can download the official solution script for this project from the resources section of this video. Now in the next video, we're going to be moving on from command line arguments and looking at the read command, which is a really cool way to ask your user questions to get input to your scripts. So for all that good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to learn about an amazingly useful command that will come up time and time again when you're writing scripts and that you'll likely use as your go-to method for getting user input. What is it? It's the read command. In this video, you're going to learn how to use the read command to get input from a user. And by the end of this video, you'll be able to use the read command to ask a user questions and receive input interactively. You'll be able to save that input in variables which can be retrieved in your script. And you'll be able to use various options of the read command to expand and adjust its functionality. All very exciting stuff, so let's go ahead and get started. The read command is a command that can be used to ask the user to provide specific input to the script. When the read command is executed, it requests input from the user and then it pauses until that user input is received. The read command serves a similar purpose to positional parameters, but instead of requiring the user to provide information at the point they run the script, the read command provides some interactivity as it allows the user to enter certain information when the script is running. When the user provides the required input, the read command saves the value that is received in a variable which can then be used elsewhere in the script. By default, the input from the user is saved in the reply variable. Alright, enough talking, let's see an example. If I type in the terminal echo $reply with reply in all uppercase, you can see that the reply variable has no value, which makes sense because there's not been any user input yet. However, if we now run the read command, you can see that the shell has paused and is waiting for our input. So let me type in the word hello and press enter. And now you can see that the command has exited successfully. If I now type in echo $reply, you can see that the value stored in the reply variable is now hello. So the shell ran the read command and then waited for the user to give it some input and press enter. After this, the read command stored whatever value the user gave it in the reply variable. Now while this is cool, only having access to the reply variable would make it quite limiting, and you could only save one piece of user inputted data at a time. What if you wanted to save two pieces of information in different variables? Well, fortunately, the read command will allow us to save data in custom variables as well. So if we run read input1, input2, we can now put in two values for two different variables. And we do this by separating each one with a space. For example, if I type in hello space goodbye, and then I press enter, now if I echo input1, you can see that this has been given the value of hello, and if I echo input2, you can see that this has been given the value of goodbye. I didn't have to call those two variables input1 and input2. I could have called them banana and apple if I wanted to, but I just called them input1 and input2 because it made sense for this video. But bear in mind, you can call them whatever you want. Okay, so now that we're familiar with how the read command works, let's use it in a script and see some more options that we can use. So let's open up a script called read.sh and then add in our shebang line. Now we're going to create a script that can echo out a few bits of information about the user. So to do this, we can put in our read command at the top, and the information we want is the person's name, their age, and where they're from. By doing this, we've created a read command that will create three variables: name, age, and town. Now we want our script to echo out these values, so we'll put the following lines into our script. On the first line, we can put echo my name is $name. On the second line, we can put echo I am $age. And third, we can put echo I am from $town. So this will just create some messages and print out the user's name, age, and town as desired. So let's save the script and head back to our command line and give the script execute permissions using chmod 744. And now if we run our script and we give it a name, such as John, give it the age of 32, and put the town as London, and then we press enter, you can see that we get back, my name is John, I'm 32, and I'm from London. Now this worked out great, but it did depend on us knowing what information the script was expecting ahead of time, and therefore we had to know ahead of time what order to provide that information. To make the information that the read command is expecting more transparent to the user, the read command has a very nice -p option, which allows us to add a prompt to the user to ask them directly for the information that we want. So let's open our script up again, and now this time we'll break down our read command into separate commands. So instead of our current read command, we can remove that and instead put in read, then -p, then inside double quotes, input your first name, followed by a colon and a space, and then after our prompt string, we'll put the variable name that we want to save the data in, which in this case will still be called name. Doing this will tell the read command to display the message input your first name into the terminal when requesting for the user's input, and then whatever the user gives will be saved into the variable called name. The prompt message appears on the same line as the user types their input, and therefore it's best to separate the enter the prompt string with a colon and a space as I've done here so that it's easy to differentiate between the prompt string that shows up and what the user sees themselves typing in. You'll see what I mean in a few moments. We can also do the same for the user's age and their town. So for the age, let's add another line with a read command, and this time give it the prompt input your age, followed by a colon and a space, and then we are going to save whatever answer the user gives us in a variable called age. And for the town, let's add another read command, this time giving it the prompt string input the town you are from, followed by a colon and a space, and let's tell the read command to save that answer in a variable called town. Now you'll have noticed that I'm quoting the prompt strings that I'm putting in. I'm wrapping them in double quotes. This is because I want the prompt sentence to be taken as one input to the -p option. So I'm wrapping the prompt string in double quotes to avoid word splitting and make sure that whatever I write is given as the prompt. So now let's save the script and head back to our command line and run it. Now you can see that the script is now giving the user a prompt to enter their first name, which is much more user-friendly. So I can type in, for example, the word Tara and press enter. Then it prompts to enter an age, so let me just type in the word 28, and then I get another prompt telling me to enter my town. So let's say I enter Rome. And when we've entered all the required information, the script uses the variables that we saved the data in to print out a custom message. Cool, right? As you can see, using prompts is a much better way of going about getting user input, as the information that is required is made very clear to the user. Another helpful option that comes with the read command is the timeout option. This option can be used to allow the command to time out and continue with the rest of the script if the user does not provide any input within a given time frame. So going back into our script again, we can add in the timeout option to each of our read commands. To do this, we'll just add the -t option in the command line after the read command, and we then need to tell the read command how long to wait for. Now this is measured in seconds, so we can just put in 5 here to give the user up to 5 seconds to respond to each question. So now that we've added in the timeout option, let's save the script again, head back to our command line, and run it again. Now this time, we're not going to give it any input. And as you can see, the command times out after 5 seconds, and the script moves on to the next command. As I said, this can be very helpful if you have a script that you want to continue running even if the user fails to give a certain piece of input. The final option that we'll take a look at is the -s or secret option. The secret option tells the command not to display what the user types in the terminal. This effectively hides what the user types in from being visible in the terminal. Now this can be helpful if the user is inputting particularly sensitive information, like a password for example, and you don't want that information displayed on the screen. However, you should note that this by itself will not ensure that the user's password is secure, as it is still stored in plain text in a variable, which is relatively insecure. To demonstrate this, let's open our script again and add in the -s option to each read command. Now if I save the script once again and head back to our command line and run it again, you can see that when I type in the name John and the age 32 and the town London, you can see that although I'm successfully providing input, nothing that I'm typing is showing up in the terminal, which may be good for more sensitive information. So I hope you've enjoyed this video. The read command is a super useful command, and you should now have a good understanding of how the read command works and also have an idea of how it can be useful when creating scripts. So as a recap, in this video you learned how to use the read command to save input provided by a user. You learned how to use the -p prompt option to prompt a user of your script for what information specifically they need to provide. You learned how to use the -t timeout option to allow the script to move on if the user doesn't respond to the read command within a certain time frame. And you learned how to use the -s secret option to mask the input the user provides so that it's not visible in the terminal for security purposes. If you want to take a look at the other cool things the read command can do, just run the command help read in your terminal. Up next, you're going to be putting everything that you've learned about the read command in this video into practice by building a really fun project. And after that, we're going to be looking at the select command, which is a great way to present a list of menu options to your users within your scripts. So good luck with the project, and I'll see you in the next video. Hello there, you beautiful people. I hope you had lots of fun trying out this project on the read command. In this video, I'm going to walk you through the solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's go ahead and get started. So the first thing we're going to do is we're going to create our script file in Nano, so nano getextensions.sh, and when that's open, we're going to quickly add in our shebang line at the top, and then we're ready to build our script. So now that we're ready to start our script, as mentioned in the project brief, in this script we're going to be gathering 3 specific pieces of information from our user. And to do this, we're going to be using the -p option in the read command. So just working from the project brief then, the first thing we're going to do is we're going to ask our user their name. So what we're going to do for this is we're going to type the read command, and then we're going to give our user a prompt using the P option to ask them, what is your first name? Followed by a colon and a space. Notice that we're making sure to wrap the prompt inside double quotes to ensure that the whole question is given as an input to the P option rather than just a word here or there. So now that we've done that, we want to save the user's response in a variable called first name. And that's it. That should grab everything we need about the user's first name. I'm going to do exactly the same now for the next question, where we're going to type in the read command and give it a prompt of what is your last name? And this one, I'm going to save the value into a variable called last name. Okay, so we've got the user's first name and last name. We now need to ask the user their extension number. So for this, following the same pattern again, we're just going to use the read command and give a prompt string of what is your current extension number. However, this is the little twist in this project, I also need to tell the user that the extension number must be exactly 4 digits long. So I'll add this into the prompt string here, put it in brackets and say must be 4 digits, so they know that, it should be 4 digits. However, as mentioned in the project brief, to limit the length of the user input, you have to use the read command's N option. This will cause the read command to wait until it receives a certain number of characters before moving on. So since we want the extension code to be 4 numbers long, I'm going to give the read command a N option, a space, and then give that the number 4. And I'm going to save the answer the user gives to this question in a variable called ext, which is short for extension. Now the final piece of information we want is the user's access code. So following a similar pattern as before, we're going to put in the read command with a prompt of what access code would you like to use? And then we're going to save that input in a variable called access. Now this one is also exactly 4 digits long, so let's tell the user in our prompt that the access code must be 4 digits, and let's also add in the -n option again to limit the entry to exactly 4 characters, as we did before. Now, because the user will also be entering some sensitive data here, I mean, you don't really want your access code being in your terminal history, right? We can just use the -s option to make that whatever the user types in as their access code remains secret so that it won't show up in the terminal as they type it. So now that I've got all the commands to receive the relevant information from the user, I need to tell my script what I want to do with this information. Now, we've been told in the project brief that we need to save this information to a file called extensions.csv, which we'll do using the echo command and a redirection. We're also given a template of the format that our data should be in, so I'll start by putting that template into our echo command. So firstly, let's write our echo command, then in double quotes, let's write $firstname to add the user's first name. Then we add in $lastname for the user's last name, and the comma is there because we're making a comma separated values file where every single value, as the name suggests, is separated by a comma. Then we're going to add in $ext for the extension number that we saved. And then finally we add in $access for the user's access code. So now we want to append to the CSV file each time that we run this script, so that every time someone runs a script to add in their details, another row is added to our CSV file. So to do this, we're just going to use the > sign to redirect the standard output of the echo command into a file called extensions.csv. And that's all there is to it. So now we can save our script and give it the appropriate permissions and test it out. Because we'll be distributing this script to others to use in the company, this time we're going to give the permissions of 755 instead of 744. This will allow other people other than the script owner, which is us, to actually execute the script. So let's run chmod 755 on our script. And if we take a look with the ls-l command, we can see that we as the file owner have all permissions, and everyone else can read and execute the file, but they can't edit it, they can't write the file. Which makes sense. So now that we've got our permissions set up, let's give it a run. And we can see that we're being asked our first question. So let's say our first user's first name is called John, his second name is Smith, his extension number is 0001, and John wants to use the PIN code of 1234 because he's a security genius. So now if we cat out the extensions.csv file, you can see that the file now exists and John's data has been saved in here. Awesome. There's a slight formatting issue here, however, on the lines that needed exactly 4 characters. This is because they immediately end the line as soon as they get 4 characters without printing a new line. This is easy enough to fix, however, so if we just go back into the extension script and add in an empty echo command after each line that has a \n, and then we save the script again, head back to the command line and run it again, we can now enter information for another user. So let's say that this time we have a user called Jane, her last name is Johnson, and her extension number is 0002, and she wants to use the pin 5678, following on from John's excellent example. We can see right away that after adding in those new lines that the interface is much nicer to use, and if we take a look at the extensions.csv file again, you can see that this has appended Jane Johnson's details below John Smith's. I'm sure your boss will be very impressed, and you can now distribute this great bash script you have to other users so they can add their information to the company spreadsheet. Now, in reality, the extensions.csv file would need to be stored in some central location that all users are given permission to access. At the moment, however, a new extensions.csv file would be created in the current working directory of each user who ran the script. If you want to take this project a bit further and make the example a bit more realistic, try modifying the script and the appropriate permissions on your file system to write to a single central .csv file that can be accessed regardless of the user who's running the script. Try making a new folder inside the system's /etc folder, and create in there a file called extensions.csv and give the appropriate permissions and playing around with the script to get the data to actually be saved in that central location. Either way, I hope you had fun doing this short project and that it has given you a good idea of how the read command works and how you can use it in your future scripts. And of course, you can download the official solution script for the project from the resources section of this video. Now in the next video, we'll be taking your scripts to the next level by learning how we can use the select command to get user input in a completely different way. So for all that good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be learning about the select command. The select command is an amazing way of getting user input, as it allows you to present your users with a menu of options to select from, hence its name. In this video, you're going to learn how to create menus using the select command and how to have the shell carry out different commands based upon what is selected. And by the end of this video, you'll be able to interpret the syntax for the select command. You'll be able to use the select command to present menus to the user and allow them to select from various options. And you'll be able to create scripts that perform different actions based upon what the user selects. So let's go ahead and get started. Okay, so as I said, the select command presents the user with a menu containing various options. The user can then select their chosen option, hence the command's name. The select command then saves the value of the option in a variable and allows you to run different commands based upon the value that's received. So let's go ahead and create a bash script that we can use to see how all this all works. We'll call this script select.sh. And then let's open up this script in Nano and add in our shebang line. Okay, so the select command uses a very specific syntax, which I'll quickly run you through now. Firstly, you invoke the select command using the word select. And then the first bit of information that you give the select command is the name of the variable that we want to save the user's response in. If we don't provide a variable name, the user's response will be saved by default in a variable called response in all uppercase. Now while this will work fine, I'm going to show you the complete way where you give your own variable name so that you know how to save the selection in a custom variable in case you ever need to. In this example, we're going to ask the user what the day of the week is. So let's say we decided that we want the user's response to be saved in a variable called day, because that makes more sense in our example. For that, we would simply type the variable name day after the word select. Next, we write the word in, which tells the select command that what follows are the options that should be made available to the user. In other words, the day variable can have one of the following options in the following list. Now these options are what will appear to the user in the terminal when we run the script. For this example, seeing as we're going to be using the days of the week, I'm just going to type in here the day names from Monday to Sunday, separating each option with a space so the shell knows that they're separate words and thus separate options. So when we've finished our list of options, we type a semicolon and then the word do. The semicolon tells the select command that our list of options has finished, and we use the word do to indicate the beginning of the list of commands we want to run after the user has provided their input. So for example, the command we want to run might be something like echo the day of the week is $day. So this will echo out the variable that's created, which is day, and that should hopefully contain the value that the user enters as a response to the menu when we run the script. Finally, on a new line, we must type in the word done. Done is another reserved word that tells the select command that we've come to the end of the commands that we want to run. And in other words, done is the closing part of do. Okay, so that's it for the select command. Now what we're going to do is we're going to save the script, head back to our terminal command line, give our script the appropriate execution permissions, and then we can run it. And as you can see, we've now been given a nicely formatted menu that presents all of our options to us. These options are numbered, so the user only needs to type in the option number. For example, let's say today was a Tuesday, we would select 2 and then press enter to select Tuesday. And we see that we get a message in our terminal that says the day of the week is Tuesday, which is the result of the echo command that we told the select command to run after receiving input from the user. Okay, so let's run the script again, and this time let's choose option number 8, which doesn't exist. Now what you can see has happened here is that I've just got pure nothingness echoed out where the day of the week should have been in our message. So we learn from this that if we select an option that does not exist, then the select command does not give any value to the variable, and therefore the variable remains empty. Now, one thing you will have probably noticed when we're running the script is that every time I select an option, it loops back to the beginning and asks me for another one again. Now, this looping behavior is the default behavior of the select command. In order to break out of the select command, you've got two options. One option is for the user to press Ctrl and C, and then the shell will stop the select command and move on, which I suppose puts the responsibility on the user. Perhaps a better option is to tell the command to automatically terminate once it has finished running the commands in its do-done block, which means that the command will quit after running a full cycle once. Now we can do this using the break command, which I'll give you an example of now. So let's open up our script again in Nano. And now all we have to do is add in the word break on a new line, just before the word done. Now this will cause Bash to break out of the select commands loop once it has run all the other commands in the do-done block once. So now that we've got the break command in there, if we go ahead and save the script, head back to the command line and run it again. This time, if we select option 2, for example, you can now see that the script runs, gives the appropriate output, and then carries on with the rest of the script. We're no longer stuck in the infinite loop that comes with the select command by default. So you can see here that where break appears, the select command knows not to loop back to the beginning again, but to end at that point. It breaks the cycle. Now I want you to think back to our discussion of the read command. And if you remember, the read command provided us with a P option that allowed the read command to give the user a prompt to explain what input they should be providing. Now, while the read command and the select command do differ in the sense that the select command provides the user with a list of all possible options up front, it can still be helpful to give the user an explicit instruction or some details so that they can figure out what option they want to choose. With the select command, we have the PS3 shell variable available to us for doing this. Now, if you think way back to our lecture on shell variables in section 2 of this course, the PS1 variable was used to control the prompt string, which is the string that appears before every command that you run on the terminal. In a similar way, the PS3 shell variable controls the prompt string of the select command. The PS3 variable is reserved specifically for the select command's prompt, so it is safe to modify within your scripts. So let's head back into our script using Nano, and this time we're going to want to set a value for our PS3 variable. Now, just above the select command, we can type in PS3 and then put in whatever we would like the user to see before they select an option. So for this example, we'll add in the question, what is the day of the week? And we'll wrap that all in double quotes so that it's saved all as one value inside the PS3 variable. Now if we save our script and head back to the command line and run it again, you can see this time that we now have a question to the user that lets them know what the options are about and therefore will help them to make an appropriate choice, which is a very handy feature of the select command. So that's about it for the select command. At the end of this video, you should now have a good understanding of the select command and some of the key features that make it so useful. So in this video, you've learned how to use the select command in a script to provide users with a list of options to choose from and how to save their selection in a variable. You learned how to use the break command to interrupt the default infinite looping of the select command. And you've learned how to set the PS3 variable to customize the shell prompt and give information to your user about the options. Just remember to reset the PS3 variable for every select command so they get a new prompt each time. Now in the next lecture, you'll be doing a fun project with the select command to test out your newfound skills, and then after that, it's on to the summary for this section as, believe it or not, you're already at the end of section 4 of the course. A massive, massive congratulations to you for making it this far, and good luck with the project, and I'll see you in the next video. Hello there, you beautiful people. I hope you had a lot of fun trying out this project. In this video, I'm going to walk you through the model solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's go ahead and get started. So let's start by opening up the extensions script that we created earlier. And you can also download a copy of this script if you want from the resources section of the project brief. Now the first task in our project brief asks us to start adding in our select commands after we ask the user for their last name. According to the project brief, the first piece of extra information that we want to ask the user for is what type of phone they use. So we'll start by using the PS3 shell variable to create a prompt string that will tell the user what information we want them to provide using the select command that will follow. So for this, I'll put inside the PS3 variable the question, what type of phone do you have? So now that we've got our prompt string set up, we can then start our select command. So as you know, we type in the word select, and then follow that with a variable name that we want to use. So I'm going to use the variable name phone, but it doesn't matter if you use something different. We then type the word in to lead into the options, which in this case are going to be headset and handheld. Then we type a semicolon followed by the word do. This will allow us to begin the commands that we want to run when the user chooses an option. So in this case, I'm going to come onto a new line and give our user a bit of feedback. So I'm going to write the command echo you chose $phone. And then we want our select command to end, because that's the only command we want to run. So we come onto another line and type in the word done, as we know that this will end the select command. Remember, however, that the select command will run on a loop by default. So we need to come up here and add in the keyword break before the word done to stop our script getting stuck in that infinite loop. So that's it for the first step of the project. We'll just repeat the same process for the second question, which asks the user what department they work in. So as we're asking the user for new information, I'll begin by modifying the PS3 variable so that it gives the user a new prompt, which this time says, which department do you work in? So now that we've got our prompt, we can now start our select command. So we type in the word select and follow that up with the variable name that we want to save the user's response in. In this case, I'm going to use the variable department, but again, it doesn't matter if you use something different. We then type the word in, and then provide the list of options, which in this case are finance, sales, engineering, and customer service. Note that we need to wrap customer service in double quotes to prevent word splitting and that ensure that it is treated as a single argument of customer service rather than the two options customer and service. We then end our list of options with a semicolon and we type in the word do to indicate the beginning of the commands we want to run in response to the user's input. In this case, I'm just going to come onto a new line and type in the command echo you chose $department. And then we want the select command to end, so let's come onto a new line and type in the word done. And like before, we just come up one line and add in the word break to prevent our select command from going into an infinite loop. And that's it for the second task in the project. Well done. We now just need to make sure that this new information is written into our CSV file, so we come down here and add in $phone and $department after the last name in our echo command, just to mirror the position in the script when we ask for the new information. And that should be it. So let's now save our script and head back to the command line and run it. We can see that I get asked for my first name, so I'll put in Ziad. My last name, so I'll put in Yahya. It's asking for what type of phone I have, so let's say I have a handheld phone, so let's select option 2. So it now asks for my department, so I'm in engineering, so I'll select option number 3. It asks for my extension number, which is 9999. I arrived to the party quite late. And I would like to use 1234 as my access code, because like John, I'm also a security genius. And we can see that our script has now completed. So if I run ls, you can see that I now have a file called extensions.csv created in the current directory. And if I look at the contents of this file, using the command cat extensions.csv, we can see that the extensions.csv file contains all of the information that I just added using the script. Now, because it's just a CSV file, we can actually open this file in a spreadsheet software and interact with the data that way as well. You can give it a try if you're interested. Either way, I hope you had a lot of fun doing this short project, and I hope it gives you a good idea of how the select command works and how you can use it in your scripts. Now, this brings to an end this section of the course on getting user input. In the next video, we'll have a brief summary of all the things we've covered in this section, and then we'll move on to learning about how to use logical constructs in Bash. So congratulations, and for all that good stuff, I'll see you in the next video. Hello there, you beautiful person, and well done for completing this section of the course all about how to get input from users. In this video, we're just going to have a quick recap of the key points in this section so that you can make sure that you're comfortable with everything before moving on. I've also put a cheat sheet summarising everything that we've covered in this section of the course in the resources section for this video, which you can download and refer to whenever you need to. In this section, we looked at a lot of different ways to get input from the user within our scripts. We started off by looking at positional parameters, which allow us to access the command line arguments that are entered on the command line when running the script. These positional parameters all have numbers for names, and they start from 1 and continue increasing by 1 each time for each command line argument that was provided to the script when it was run. In this example script here, you can see that we're echoing out a name, a home directory, and a favourite colour by providing these values to the script as the first, second, and third command line arguments. Next, we moved on to special parameters. You learned that special parameters work just like regular parameters, and like shell variables, they're created for us by the shell. However, what makes special variables truly special is that they are unmodifiable. Their values are set by the shell, and we cannot change their values ourselves. Firstly, we looked at the $hash variable, which stores the number of command line arguments that were provided to the script. In this example, we run a script and provide it with the command line arguments 1, 2, and 3. And because we provided 3 command line arguments, this means that the $hash special parameter would contain a value of 3. Secondly, we looked at the $0 special parameter, which simply stores the script's name. From here, we moved on to some more advanced special parameters. We looked at $at, which expands to each positional parameter as its own word. We noted that with unquoted $at, subsequent word splitting does occur, so in this example we would end up with 2 words. We then moved on to quoted $at, which does exactly the same as unquoted $at, except there is no subsequent word splitting. So in this example, instead of expanding to 2 words, this would expand to only 1 word. We then had a look at unquoted $, which just does exactly the same as unquoted $at. So in this example, it again would expand to 2 words, just the same as unquoted $at. However, quoted $* does something very different. Quoted $* expands to all positional parameters as 1 word, separated by the first letter of the IFS variable, and without subsequent word splitting. So in our example, we can see that this now expands to 1 word, but with the comma character added here between the 2 values, because that's the first character in this example's modified IFS variable. Then the last special parameter that we looked at was $, which gives the exit code returned by the most recent command. After special parameters, we moved on to look at the read command. The read command allows us to directly ask for input from the user and save that input into a variable. The syntax for this is very simple. We simply run the read command and give it the variable's name that we want to save the information into. We also looked into various options that you can use with the read command. We started with the -p option, which allows us to display a prompt to the user so that we can tell them explicitly what information they should enter. We then saw the -t option, which allows us to set a timeout if the user does not enter a value within a specific number of seconds. After that, we saw the -s option, which prevents the input the user provides from being shown in the terminal. Then we saw the -N option, which just limits the user's response to an exact number of characters. And finally, we saw the -n option, which rather than defining an exact number of characters, it just sets the maximum number of characters that the user can use. They can enter less characters than this, but no more. And in this example script here, we're just asking the user to provide us with their first name, age, and their zip code, and then echo this data out into a CSV file for our records. After the read command, we then moved on to the select command. The select command provides the user with a drop-down menu to select different options from, hence its name. And as you might remember, whatever option the user selects is saved into a variable by the shell, and then you can use that variable within your script. We learned that there is the ps3 shell variable, which is specifically reserved for the select command and is used to provide the user with a prompt, very much in the same way as how we did with the -p option in the read command. So the syntax for select is a little more complex than the commands we've had to deal with up to this point. Firstly, we set the ps3 shell variable in the same way as we would any other variable, so that it can contain a certain prompt that we want to ask the user. We then just call the select command and give the name of the variable that we want to save the user's selection into. We follow this with the keyword in, and then provide a list of possible options that we want to give the user to select from in the menu, and then end this line with a semicolon and the keyword do. Following this on a new line are the commands that we want to run when the user selects an option. We discussed during the lecture that the select command actually runs as a loop, and so it's important to also include the break command at the end of whatever commands you want to run to make sure that the loop ends. Otherwise it will just keep running and keep requiring the user to enter options over and over again. All of this is then ended with the word done so that the shell knows that our select command ends. In the example script here, you can see that we're using the ps3 variable to create a prompt which asks our user to provide us with the day of the week, and then we simply echo out the day of the week that the user enters back to the user. So well done! You've covered a whole lot of stuff in this section, and now, at the end, you should be able to use positional parameters to have users provide specific information on the command line that is required for your script to run. You should be able to use special parameters to process positional parameters all at once, but in a variety of different ways. You should be able to use the read command to request specific information from your users at any time during your script. You should be able to use the select command to create menus of predetermined options to present to your user for them to choose from at any time during your script. And you should be able to save the information that's provided by your users as variables and then use that information in your scripts. So a massive congratulations to you, you are making excellent progress. And as I say, you can download a copy of this cheat sheet from the resources section for this video, so you've got a copy of all the key points from this section of the course. Now in the next section of the course, we're going to be looking into all the different logical constructs that are available for us to use within our scripts, so you can make scripts that can think and decide. So for all that logical goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this section of the course where we're going to be looking into how we can make our scripts think and decide using all the logical constructs available to us in Bash. Let's take a look at what we're going to be covering in this section. In this section, we're going to start off by looking at how we can chain together commands by using list operators. We're then going to look at something called a test command, which we can use to test whether a certain condition is true or false. We're then going to go straight into looking at one of our first programming constructs that we've seen in Bash, and it's called the if statement. We're going to use if statements to check the outputs of test commands and then do different things based upon the results. We're then also going to look at how you can combine list operators with test commands to create more complex logical conditions to allow you to do rather sophisticated things. And finally, we're going to look at case statements, which provide us with a simple way of constructing branching logic. And by the end of this section, you'll be able to use list operators to create chained lists of commands. You'll be able to use test commands to compare different pieces of information and perform various logical checks. You'll be able to use if statements to determine whether a certain set of commands should be run or not, or whether another set of commands should be run instead. You'll be able to use list operators to combine together various test commands to create complicated logical conditions. And you'll be able to use case statements to create sophisticated and elegant branching logic. Feel free to download this section's cheat sheet from the resource section of this video so you can keep it to hand in case you need it. And as usual, we've got a lot of very exciting things to cover, so let's go ahead and get started. Hello there you beautiful people, and welcome to this video where we're going to be looking at lists and list operators. In this video, you're going to learn how to create sequential lists of commands and how you can use list operators to chain commands together. And by the end of this video, you'll be able to use the semicolon, ampersand, double ampersand, and double pipe list operators to create chain lists of commands. and you'll be able to explain the roles of these operators and how they differ from one another. So let's go ahead and get started. The first thing you need to know is that a list of commands is created when you put one or more commands together on a given command line. It's a bit counterintuitive to think of just one command being able to be a list, but in Bash, lines containing just one command are still considered lists. In practice, however, lists are usually considered as being made up of two or more commands on a single command line. List operators are types of control operators that enable us to create lists of commands that operate in different ways. The four list operators are the ampersand, the semicolon, the double ampersand, and the double pipe. And like I said, each list operator causes the commands in the list to be run in different ways. For example, the ampersand list operator sends the command that comes before it in the list, in other words the command that it terminates, into the background, and allows the shell to continue to process the other commands in the list. As an example, let's say we ran the command list echo 123 ampersand echo 456. You can see from the output that echo 123 was sent into the background, and we were given a job number for that command and also notified when it was completed. The ampersand operator is useful if you want to start processing a time-consuming job but don't want to have to wait for it to complete before being able to issue new commands to your shell. In other words, the ampersand operator allows you to run commands asynchronously. On the other hand, the semicolon list operator runs commands sequentially, that is, one after the other. What this means is that the shell will wait for the previous command to complete before it runs the next command. So if we again run echo 123, but instead we this time use the semicolon list operator, and then we run echo 456, you can see that this time the echo 123 ran first, and then the echo 456 was run. The commands are running one after the other in the order that they were typed. The main advantage of the semicolon operator is that it allows you to put multiple commands on one line and save some space in your bash scripts. It does exactly the same thing as putting two commands on two different lines, but using the semicolon allows you to save some space in your scripts, and it can also come in handy when working with the terminal, as you can run more than one command on a given line, which sometimes is a nice shortcut to have. With the ampersand and the semicolon operators, the shell will continue to run all of the commands in the list regardless of whether the previous command ran successfully or not. As an example, if I try to list a directory that does not exist, so for example if I run the ls command on random directory, and then I add in on the same line a semicolon and the command echo 123, when I run this, you can see that because random directory does not exist, the first command failed and it gave us the error no such file or directory. However, the shell then just moved straight on to running the following command, which was echo 123, which in this case was completed successfully. The shell didn't care that the first command failed. And this brings me on to the two remaining list operators, which are the double ampersand and double pipe. The double ampersand list operator is the AND operator, and it will run the second command in a list only if the command before the double ampersand returned an exit code of 0. In other words, the double ampersand makes it so that the second command only runs if the first one was successful. You can think of the double ampersand or the AND operator as saying, run command 1, and if that first one worked, run command 2. The double pipe or the OR operator, on the other hand, will run the second command only if the previous command returned a non-zero exit status. In other words, the OR operator makes it so that the second command only runs if the first one failed. You can think of the double pipe or the OR operator as saying, run command 1, or if that fails, run command 2. Because these list operators are always checking for the exit status of the previous command before moving on, this means that they're running sequentially in the same way as the semicolon list operator does. So if we run echo 123, double ampersand, echo 456, you can see that both of these commands ran. Because echo 123 ran successfully, and thus returned a 0 exit code, the second command, echo 456, was run as well. On the other hand, if we run echo123 double pipe echo456, you can see that the command echo123 ran, but the command echo456 did not. This is because the echo123 command succeeded, and therefore the double pipe or the OR operator ended the list instead of continuing it. So in these two examples, the first command which we gave the operator ran successfully. Let's now try giving both of these operators an initial command that fails this time. So if we switch back to using the double ampersand or the AND operator, and we run ls random directory double ampersand echo456, you'll see that the first command failed and therefore returned a non-zero exit code, and because of this, the double ampersand or the AND operator stopped the second command from running. However, if we run ls random directory double pipe echo456, you can see that this has now ran both commands. Because the first command returned a non-zero exit status, in other words, it ran unsuccessfully, the shell continued the list and ran the second command as kind of like a backup in case the first command failed, which in this case it did. So the double ampersand or the AND list operator tells the shell to run the first command and, if that completes successfully, run the second command, whereas the double pipe or the OR list operator tells the shell to run the first command, or, if that fails, then run the second command. Now interestingly, you can mix these two together to create what is known in programming languages as a ternary operator. For example, let's say I want to run a certain command, command A, let's say, and let's say that if command A is successful, I want to run another command, say command B. But if it's not successful, then I want to run a third command, say command C. To do this in Bash, I would write command A, then I'd put the double ampersand operator, followed by what I want to happen if the initial command was successful, which in this case will be command B. Then I put the double pipe, or the OR list operator, followed by what I'd want to run if command A is unsuccessful, which in this case is command C. So what this says is, run command A, and if it runs successfully, run command B, and if not, then run command C. Now, although they're a bit hard to read at first, ternary operators are a cool trick to have in your programming back pocket, and they tend to be a common topic in entry-level programming interviews, so keep this little trick in mind. So that's it for this video on list operators. Let's have a quick recap on everything we've covered. In this video, you learned about all the types of list operators that Bash has to offer. You learned how to use the ampersand list operator to run commands asynchronously, that is, run them in the background. You learned how to use the semicolon list operator to run commands sequentially, that is, one after the other. You learned how to use the double ampersand and double pipe list operators to run and OR lists of commands and to control operation based upon whether a previous command was successful or not. And you also learned how to combine the double ampersand and double pipe list operators to create what is called a ternary operator, which is a handy trick to have in your back pocket. Now in the next video, we're going to have a quick quiz to make sure that you're understanding the core concepts here, and then we're going to move on to learn how to write test statements. So I hope you're excited, good luck with the quiz, and I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be taking a look at test commands and conditional operators. Test commands allow us to do some logical checks with our scripts, and they're also the foundation of the if statement, which we'll be covering in the next video. In this video, however, you're going to learn how to use test commands and the different conditional operators that you can use to perform different logical checks. By the end of this video, you'll be able to use the test command to compare different information. You'll be able to use integer test operators to perform logical checks on numbers. You'll be able to use string test operators to perform logical checks on text. And you'll be able to use file test operators to perform logical checks on files. All very good stuff, so let's go ahead and get started. So what is a test command? Well, a test command is a command that can be used in Bash to compare different pieces of information. A test command basically allows you to create logical tests in Bash that can either be true or false. Just like how a successful command will return an exit status of 0, if a test is evaluated to be true, the test command will also return an exit status of 0. Likewise, if a test is evaluated to be false, the test command will return an exit status of 1. This might be a bit confusing if you're coming in from other programming languages, where 1 typically means true and 0 means false, but hey, what can I say? It's Bash. A test command is written using a set of square brackets, like this, and inside these square brackets, you write your test. I should mention here that there must always be a space between your square brackets and their contents, otherwise you'll get some syntax errors. So always remember to put a space after the after the opening square bracket and before the closing square bracket to make sure that you don't get any errors. Test commands can do many different types of logical checks, and the type of test that is performed is determined by the test operator that is used. For example, the -eq operator tells the shell to test if two numbers are equal to one another. So if we were to run inside our test command 2-eq2, this will test if 2 is equal to 2 and give us an exit status of 0 if that is true, or 1 if that is false. In Bash, we can use the $question variable to check the exit status of the last command. We're going to use this here by putting a semicolon after our test command and then echoing out the value of $question. This will allow us to run our test command and then echo out the exit status that it gave so we can see whether the condition was evaluated as true or false. So if I run this now, you can see that I get 0 in my terminal. This shows that the exit status from the test command was 0, which meant that it evaluated as true. This is what we expected because 2 does in fact equal 2. Now if I change the first number in our test command from 2 to 1, we're now checking if 1 is equal to 2. And if I run this now, you can see that this time we get an exit code of 1, which means that the test command evaluated to false. If we now change the -eq operator to the -ne operator and run the command again, you can see that this time we get a 0 exit status. This is because the -ne operator checks whether an integer is not equal to another, and because 1 is not equal to 2, this test was true, and we get back an exit code of 0. So if we change the first number back from 1 to 2 again, and we keep using the -ne operator, you can see that the command has now exited with an exit status of 1, meaning that our test evaluated to be false. There are other operators you can use to perform logical checks on numbers, such as the -gt for greater than, -lt for less than, -geq for greater than or equal to, and -leq for less than or equal to. I've tabulated each of these different options in the cheat sheet for this section for you to refer to when you're making scripts of your own. Note that the operators I've shown you here in this video so far are called integer test operators, and thus they only work for integers, i.e. whole numbers. In other words, you can't use them to compare decimal numbers. If you're interested in learning how you can compare decimal numbers, check out the link I've put in the resources section for this video for more information on how to do that. By the way, you can also see a complete list of all the operators that you can use in test commands by clicking the link to the Bash manual that I've placed in the resources section for this video as well. Let's now move on to the next type of test operators, which are string test operators. These work much in the same way as integer test operators, the difference being that they are used to compare strings, i.e. pieces of text, rather than to compare whole numbers. So the equals string operator, as you can probably guess, is the same as -eq, but this time it compares strings. So if we set the variable a to equal hello, and we set the variable b to equal goodbye, we can now compare these two variables by putting inside a test command $a equals $b. And of course, to check the output, the exit status for this command, we'll put a semicolon and then echo $question. And when we run this command, we can see that we get an exit status of 1 because the two pieces of text are not equal. They do not match. If we now add an exclamation mark in front of the equals sign, you can see that when we run this, we get a 0 exit status. This is because the string test operator exclamation mark equals means not equals, or not equal to, and because hello does not equal goodbye, this test evaluated as true. You can also test a single string against a value, rather than comparing two strings. For example, we can use the -z operator to test if a string is empty. So if we open up another test command, and we put inside there -z and $C, and then after the test command we put in a semicolon and our standard echo $, so we can see the result of this, what this is going to do is it's going to compare the value of the C variable, $C, with an empty or null string. And it's going to give us back either a 0 or 1 exit status, depending upon whether the value of the C variable is empty or not. So if I run this now, you can see that we get a 0 exit status. This is because the C variable is currently empty. We didn't create it, and it's therefore equal to an empty string. So if I now set the C variable to any value, so let's say I write C equals anything, and then I run the same command again, you can see that we now get a 1 exit status because the C variable is no longer equal to an empty string. Another string comparison operator is -n. -n does exactly the opposite of the -z option. Instead of matching an empty string, it matches a non-empty string. One trick you can use to remember this is to think that -z checks if a string has a length of 0, the z being for 0, and -n checks if a string has a length that is not 0, with the n being for the not. In other words, it checks if the string exists. So if we now replace our -z in the command line with -n, and we run the command again, you can see that we now get a 0 exit status because our C variable does have a value. It's not empty. So the final type of test operator that we're going to look at here are file test operators. As the name suggests, file test operators compare files. These operators compare files against numerous predetermined values. So if we wanted to check if there was a file called today.txt in our current directory, we can run inside a test command -e today.txt, and again we put our semicolon and echo out the value of $. So here I've used the -e operator to confirm if a file exists, the E here standing for exists. You can see that this has given us an exit status of 1, which shows that the today.txt file does not exist. If I now create this file by typing touch today.txt, and then we run exactly the same command again, you can now see that we have a 0 exit status, meaning that the test passed and today.txt does exist. We can also test whether something is a file or a directory. In Linux, all things are considered as files in the general sense that everything can be read from or written to. However, some of these are regular files that we're used to working with, in that we can put text in them and such, and others are classified as directories. And there are other types of files too. The -f test operator checks if something is a regular file, like a TXT file or a Word document or a PDF. So if we replace our E operator with the F operator, you can see that we now get back a 0 exit status because today.txt is indeed a regular file. However, if I was instead to use the -d operator, you can see that we've now got back an exit status of 1. This is because the -d operator checks if something exists and is a directory, and because today.txt is not a directory, the test failed. Another very useful operator is -x. This operator is used to test if a file exists and has execution permissions. The -x operator is basically designed to check for scripts, which could come in handy if you want to write a script that runs other scripts. So if I create a script using the touch command, and then I run inside a test command -x script, again followed by a semicolon and echo $, you can see that I get a 1 exit status. Bash doesn't think we have a script in here just yet. This is because my script does not actually have any executable permissions. However, if I now give it execution permissions with chmod 744 script, and then I run exactly the same command again, you can see that I now get a 0 exit status because the file now has execution permissions and has therefore passed the test. There are loads of operators that you can use when working with files, such as -r to check if a file is readable, -w to check if a file is writable, -nt to check if a file is newer than another file, and so on. As I said, I've placed a link in the resources section to a full list of the operators that you can use with test commands, so feel free to check that out if you're interested on seeing more of what's available. Okay, so that wraps up our coverage of test commands in Bash, which are a core building block of if statements, which we'll be covering very shortly. Let's have a quick recap of everything we've learned in this video before moving on. In this video, you learned how to write a test command using square brackets and test operators. You learned how to use integer test operators to perform logical checks on whole numbers. You learned how to use string test operators to perform logical checks on test data. And finally, you learned how to use file test operators to perform logical checks on files. Up next, you're going to have a quick quiz to cement what you've learned in this lecture, and from there, it's on to one of the most important components of Bash, and any programming language really, which is if statements. In the next video on if statements, we're going to be putting into practice what you've learned here about test commands to create a program that can think and decide. So I hope you're excited, enjoy the quiz, and I'll see you in the next video. Hello there you beautiful people, and welcome to this video where you're going to learn how to construct if statements in Bash. If statements are absolutely key to writing Bash scripts, as they allow you to write scripts that can perform different actions in different circumstances, which, as you can imagine, is a thing scripts need to be able to do to provide effective automation. So, by the end of this video, you'll be able to understand the syntax for Bash's if statements. You'll be able to use if statements to decide whether a certain command should be run or not. And you'll be able to use the elif and else keywords within your if statements to create sophisticated workflows in your scripts. So this is all very exciting and game-changing stuff, so let's go ahead and get started. In Bash, if statements are a type of compound command, and as you learned during section 3 of the course, the shell identifies where compound commands start and end using reserved words. Therefore, in Bash, if statements start and end using the reserved words if and phi. If is the reserved word that tells the shell that an if statement has started, and phi, which is just if spelled backwards, is the reserved word that tells the shell that an if statement has come to an end. We covered the select command in section 4, which is also a form of compound command, and therefore you should notice some similarities between the syntax you learned there and the syntax that I'll be showing you now. If statements work by checking the exit status of a command. If the command you provide the if statement returns a 0 exit status, then the commands inside the if statement will be run. However, if the command you provide returns a non-zero exit status, then the commands inside the if statements won't run. Although it doesn't necessarily have to be, it's very likely that the command we provide to an if statement will be a test command, which, as you know, will give a 0 exit status if the condition the test command checks is true, and a non-zero exit status if the condition that the test command checks is false. So basically, if statements get their name from the fact that they only run code if a certain condition is true. So let's see how this all works with an example. Let's create a script using nano called if.sh and then put inside our shebang line. Now, as discussed, we must start our if statement with the word if. After we write in the if keyword, we need to give the if statement a command to check the exit status of, which in this case will be a test command. In this example, we'll just use one test command, which in this case will just be 2-gt1 to test if 2 is greater than 1. We then add in a semicolon. When the shell comes to the semicolon here, it knows that we've finished writing the condition commands, and that what follows are the commands that we want to run if the condition as a whole evaluates as true. These commands we'll call the consequent commands. So after the semicolon, we then write the word then, and start a new line to start entering our consequent commands. We're going to keep the example here quite simple, so we'll only have one consequent command in here, which in this case will just be echo test passed. It's considered best practice to indent consequent commands to make the if statement more readable. So I'm just going to put a tab before the consequent command here. As you can see, by indenting the command a bit, it makes it a bit easier to tell what's inside the if statement, and this practice is very, very helpful as your scripts and if statements start to become more complex. Okay, then finally, we just end our if statement with the reserved word fee on a new line. So that's our if statement. Let's go ahead now and save our script and head back to the command line, give our script execution permissions, and then run the script. And from the output, you can see that we got test passed echoed out into our terminal. So let's open up our script and have a closer look at what's going on here. So what happened here is that the shell ran the test command checking whether 2 is greater than 1. And because 2 is greater than 1, that test command returned an exit status of 0. The if statement, based upon the fact that that test command returned an exit status of 0, decided that it's going to run the consequent commands inside of it. In this case, there was only one, which said echo test passed, and because echo test passed was ran, the words test passed appeared in our terminal. Let's now see what happens if we change our test command to something that will fail. So if we change our test command from 2 is greater than 1 to 2 is equal to 1, this should fail because 2 does not equal to 1. So let's try it. Let's save our script, head back to the terminal, and run it. And as you can see, because the tests failed, you can see that the consequent command was not run, and we don't see test passed appear in our terminal this time. So what we've seen so far is the most basic form of the if statement, but there's much more that can be done with it. For example, let's have a look at the else keyword. At the moment, we can only do something if our condition is true. The keyword else allows us to do something else if that condition is not true. So using the script that we've created, after the consequent commands that we want to run if the condition is true, we can add in the keyword else. And then following the word else, we can add in what are called alternate commands that we want to run if the condition at the top is not true. Another way of saying that is that these commands will run if the command we gave the if statement gives a non-zero exit status. So in this example, I'm just going to add in the alternate command of echo test failed. We can then save the script once again and head back to the terminal and run it. So here, the shell ran the test command, which was checking if 2 is equal to 1. That test failed and therefore gave a non-zero exit status. And because it gave the if statement a non-zero exit status, the if statement ran the else condition and ran the alternate commands and therefore printed the text test failed. So that's really, really cool, but there's more. Another very helpful part of the if statement is the keyword elif. Elif, as you can imagine, is a mixture between the words else and if. It allows you to check another condition if the first condition failed. So if we open our script again, let's put an elif below the commands associated with the first if condition. The elif will check another condition, and therefore we need to give it one. Here, we're going to give it the condition of 1 equals 1, and then terminate this condition like we did for the first one with a semicolon. We then put the word then at the end, again, just like we did with the initial if statement, to lead into a second set of consequential commands. And for this, we're going to use the command echo second test passed. So now if we save our script once again, and head back to the terminal, and run the script again, you can see that this time it prints out second test passed. So let's head back into our script to see what's going on here. So first of all, the if statement tried to check our first condition, and it found that this was false. It gave back a non-zero exit statement. Because the first test failed, the if statement then looked at the elif and checked the second condition. This time, the second condition passed, and therefore it ran the consequent commands inside the elif. The else statement, however, didn't run, and this is because else is kind of a last resort. Else only runs if all of the other logical checks in the if statement fail. There are three important notes to make here. The first is that you can't put an elif after an else. Else always comes last. The second is that there's no limit on the amount of elif statements that you can have inside your if statement. The third is that you can put an if statement inside other if statements. Now, this behavior of being able to put if statements inside other if statements, known as nesting, allows you to create very sophisticated branching logic in your programs, checking as many conditions as you want. Feel free to play around with this on your own and see what you can come up with. You might invent the next Iron Man. Alright, so that's it for part 1 of our coverage of the if statement. Let's have a recap of what you've seen in this video before we move on. In this video, you've learned how to write a basic if statement in Bash. You learned how to use the else keyword to run something else if the initial condition fails. And finally, you learned how to use the elif keyword to check another condition in case the first condition failed. So up next, we're going to be taking if statements to another level by learning how to combine multiple commands within a given condition. We're going to be using the AND as well as the OR chaining commands that we learned earlier together with our if statements to create this advanced and powerful behavior. So I hope you're excited, and for all that amazing logical stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be expanding our knowledge of if statements even further. In this video, you're going to learn how to create more sophisticated conditions, and thus more sophisticated logic, by combining the AND and OR operators inside if statements. By the end of this video, you'll be able to use the double ampersand operator to combine test conditions. You'll be able to use the double pipe operator to combine test conditions. And you'll be able to explain the roles and differences of each. So let's go ahead and get started. So by now, you should have quite a good understanding of what an if statement is and how to write one. In the previous video, we looked at how you can use a single test statement to create a condition that will run certain commands based on whether that single condition was successful or not. But what if you have multiple things that you want to check before you decide what to do? Well, this is where the list operators that we learned earlier start to come in. We can use them to chain together multiple test conditions to create more powerful conditions and thus more powerful logic. So let me give you an example. Let's say that we have 3 files that we want to confirm contain the same content. If all 3 files are the same, we want to delete 2 of the files so that we just have 1 left. However, if the files aren't the same, then we just want to keep them all. Okay, so with that goal in mind, let's create a bash script and add in our shebang line at the top like usual. So we want to have a script that does different things based upon whether 3 files are equal or not. So to do this, we're going to need to be able to have a look at the contents of each file. Now we're going to do this by using the cat command in this example. So first of all, we'll say the A variable equals the outcome of using the command substitution cat file1.txt. We're going to do the same for the other 2 files, but we're going to save the results into different variables. So let's add a line that says B is equal to the result of catting file2.txt, and another line that says C is equal to the result of catting file3.txt. So what we have here is 3 commands that will create 3 variables that contain the contents from each of our 3 files. So now we can use an if statement to compare whether the contents of these 3 files are the same, and then take appropriate actions based on the result of that test. So let's start off our if statement by adding the keyword if on a new line. And now, as usual, we're going to add in our test commands. So starting with the first test, I'm going to check whether the A variable is equal to the B variable. This is simply testing whether variable A is equal to variable B. In other words, we're checking whether the contents of file 1 is the same as the contents of file 2. So that's part of the battle, but in order to check whether all the files are the same, we also need to check whether file 1 is the same as file 3 as well. In other words, whether variable A is also equal to variable C. Now for this case, we want to use the double ampersand, which as you know is the AND operator. After the double ampersand, we can add in our second test, which checks whether the variable A is equal to the variable C. Now, we're saying that our test will only be successful if A equals B and A equals C, which is exactly what we want to check, because that's the way that it would be if all the three files were the same. And as you learned in the previous lecture, now that we've finished writing out our condition, we add a semicolon followed by the word then. Now we can start a new line and add the commands we want to run if all the files are the same. In this case, our goal is to remove duplicate files and only leave one file behind. So in this case, we're going to be adding in the command rm file2.txt and file3.txt. So that way we'll just have file1.txt left behind. Now because we want to do something else if the first test wasn't successful, i.e. if all the files weren't the same, I'm going to add in an else condition here as well. In this case, we just want to be told that the files don't match. So I'll add in an echo statement that says, echo, files do not match. We can now end our if statement with the reserved word phi. Okay, so let's save the script and head back to the command line and give it the required permissions to run. Okay, so to test our new script, we're going to have to create a few test files. So first of all, I'll create 3 files that are exactly the same by echoing into them the same content. So I'm going to echo the word same into file1.txt. I'm going to echo the word same into file2.txt. And you guessed it, I'm going to echo the word same into file3.txt. Now if I run ls, you can see that I've got 3 files, and each of those files contain the same data, so when we run this script, we expect file2 and file3 to be deleted. So if we run our script now, and then run the ls command, you can see that we've now only got file1.txt left behind. So our script worked, the files were found to be equal, and the 2 duplicates were removed. Huzzah! So let's create file2 again, and again give it the same content, so we're going to echo the word same into file2.txt. But this time, let's make file3 different. So we're going to echo the word different into file3.txt. Now if we run our script again, you can see that this time our script has resulted in the text files do not match being echoed out. So this time, because one of the files did not match, one of our conditions in the AND operator evaluated as false, which means that the test statement as a whole was evaluated as false. So since the condition that we gave our if statement was false, in other words it gave a non-zero exit status, the commands under the else keyword will run instead. And if we run the ls command, you can see that all 3 files are still present. Now let's say that we want to modify our script. Instead of only deleting the files when file1 is equal to file2 and file3, let's say that we want to delete the files when file1 is equal to file2 or file3. To do this, all we need to do is replace the AND operator with the OR operator, like so. Our condition now says, if A is equal to B, or A is equal to C, then we'll delete all the files. So let's now go ahead and save our script, and then head back to our terminal, and run it again to see what happens. So that appears to have ran successfully, and if I run the ls command, you can see once again, only file1 remains. This is because although file1 didn't match file3, it did match file2, and therefore the combined OR test condition evaluated to true, and the deletion commands will run. So from this lecture, you can see how to use the AND and OR operators to test multiple conditions at the same time in different ways. You'll often find that testing just one condition is not enough, and that you'll want to confirm multiple things before allowing specific commands to run. Using the constructs you've learned in this video will allow you to do exactly that. So in this video, you've learned how to use the double ampersand or the AND operator to combine multiple test conditions that all must be successful in order for the if statement to execute its code. and you've learned how to use the double pipe or the OR operator to combine multiple test conditions where only one must be successful in order for the if statement to run its code. So up next, you can have a very nice project that will allow you to put all you've learned into practice, and then it will be on to looking into case statements, which are a very handy way to write longer chains of conditional logic. So for all that logical goodness, I'll see you in the next video. Hello there, you beautiful people. So I hope you had loads of fun trying out this project. In this video, I'm going to walk you through the model solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's get started. So firstly, we're going to start off in the usual way by creating a script and adding our shebang line. Now the first task that we have to do is we've got to create an if statement that checks if the folder $home/performance exists. So we're going to start off our if statement with the reserved word if. And it's always a good idea to close off our compound commands whenever we open them so we don't forget to do so. So let's add on another line, the word fee, which will close off our if statement. So to do this task, we need to write a test statement that will check if the file $home/performance exists and that this file is a directory. Fortunately for us, we've already covered the exact logical operator for this, which is the -d operator. The -d operator checks if a file exists and checks if it's a directory, which is exactly what we want. So for our test command, we're going to open some square brackets and put inside -d, then a space, then $home/performance. And then we're going to end that test command with a semicolon. We then follow our semicolon with the word then, which will let Bash know that we're now ready to start adding in our consequent commands. So now, on a new line, we need to put in some commands that will run if the test is true. In other words, if $home/performance is indeed a valid existing directory. In the brief, we're told that if the folder exists, our script should echo out a statement confirming that to the user. So in here, I'm just going to add in echo $home/performance folder exists. Now what do we do if the folder doesn't exist? Well, we're told by the brief that we need to create the performance folder if it doesn't exist. Well, since we need to do something else if the initial condition fails, let's add in an else condition here. And because we want to create a folder, let's use the mkdir command as suggested and type mkdir, then a space, then $home/performance. Although it's not required, just for extra transparency, we can also add in another line here to say echo $home/performance folder has been created. Okay, so that should sort out the folder. Now finally, we need to log the output of the free command to the memory.log file within that folder. In particular, we're told to append the output of the free command to that file. This makes sense because memory.log is a log file, and we want to keep a record of the output each time the script is run, rather than wiping the log file clean every time. So to do this, I'm going to come right down the bottom here below the if statement, and then I'm going to type the free command and use a double greater than sign to append the output of that command to our memory.log file. So I'm putting the free command down here after the entire if statement because I want the free command to run after our if statement has checked that the required performance folder exists and done any required activity to create it if not. And that's it for the script. So let's save the script and then head back to the command line and give it execution permissions so that we can test it out. If I run ls$home, you can see that at the moment we do not have a performance folder. However, if I run the script, and then I run ls$home again, we can see that we now have a performance folder created. And if I run ls$home/performance to have a look inside that new folder, you can see that the new folder also contains the memory.log file. And if I cat the memory.log file to see its contents, you can see that this file also contains the output of the free command, which is going to be very useful for our server debugging efforts. So that's it. I hope you had fun doing this short project on if statements, and that this has given you a good idea of how if statements work and how you can use them in your scripts. You can download the official solution script for this little project from the resources section of this video. In the next video, we're going to be taking our study of logic further by taking a look at case statements, which provide a very convenient way to handle multiple logical branches. So for all that logical good stuff, I'll see you in the next video. Hello there, you beautiful people, and welcome to this video where we're going to be discussing case statements. We've learned in the last few videos about if statements and how you can use the elif and else keywords to create branching logical conditions. Case statements provide us with an alternative way to create branching conditions and can often make for a more elegant solution in certain situations. In this video, you're going to learn how to create case statements to implement branching logic, and by the end of this video, you'll be able to interpret the syntax of case statements. You'll be able to create specific cases and write commands that should be run in each of those cases. And you'll be able to create default cases that act as fallbacks that none of the other cases match. So let's go ahead and get started. So the first thing to point out is that case statements are another type of compound command, and as case statements are compound commands, we know that they must start with a reserved word and end with a reserved word. We start a case statement in Bash by writing the word case at the beginning, and we end our case statement with writing the word esac at the end, which is just the word case spelled backwards, so nice and easy to remember. Now you'll recall from our videos on if statements that when we wanted to create multiple branches, we would use elif and else keywords to create those branches. If you have lots of different branches, then it can become quite tedious to write out multiple elif statements, as you would have to write elif, then a condition, semicolon, then, elif, then a condition, semicolon, then, elif, then a condition, semicolon, then, over and over and over again in order to achieve that result. And this is where case statements come into play. The case statement achieves the same result, but with a lot less typing. In this way, case statements are essentially a simpler form of the if-then-elif statement. The trade-off, however, is that case statements can only perform logical checks on a single variable. So it's not so much that case statements should replace your ifs and your elifs, but rather that each is best used in certain contexts. If statements allow you to do anything, but are a bit more tedious to type, and case statements are more elegant, but restrain you in terms of the conditions that you can create. So let's create a script where we can start to have a look at the syntax for a case statement. Let's create a file called case script, and then add in our shebang line. So as we know, we start off our case statement with the reserved word case. This is then followed by the variable that you want to work with. So in this example, we'll use the number variable. There are two really important things to remember here. The first really important thing for you to remember about case statements is to remember to put that dollar symbol in there. We need that dollar symbol because we're going to have to check the value of the number variable against multiple cases. If we don't put the dollar symbol, then our case statement won't work because Bash won't have access to the variable's value. Typically, this will leave us on a wild goose chase looking for a super sneaky bug. The second really important thing is the double quotes. You do not want word splitting messing with the value of your variable, so make sure you wrap the parameter expansion inside double quotes when you're working with case statements. Otherwise, once again, this will leave us running on a wild goose chase looking for a super sneaky bug, wondering why our variable doesn't match the variable cases we're trying to match. And as I say, it's so easy to forget these two things, so make sure you burn them into your memory. You must add the dollar symbol at the top, and you must wrap the parameter expansion in double quotes when working with case statements. Trust me, you'll thank yourself later. Okay, so that said, we now need to give our case statement various cases that the variable's value could be. Basically how it works is that the case statement will check the value of the variable and figure out which case it falls into. Then it will execute the code associated with that particular case. Note, however, that a variable can only match one case at a time, and if it matches more than one, Bash will only run the code associated with the first matching case that you come across when you read the case statement from top to bottom. Okay, now to give Bash our cases, we follow the variable with the word in, which tells the shell that what follows are the cases that we want to investigate. Another important point to be aware of is that a case is actually just a globbing pattern. If the variable matches the globbing pattern, then it is considered to have matched that case. For the first one, I'm going to use the globbing pattern of some square brackets, and inside there I'm going to put 0 to 9. This globbing pattern will represent the case where the number variable is between 0 and 9. With case statements, once you're done with a pattern that you want to match, you have to end this with some closing parentheses, like so. This allows the shell to determine where a particular case pattern ends, and thus where the commands associated with that case will begin. So following the closed parenthesis, we can now add in the command line, or command lines, that we want to run if our variable matches this case. Now because this pattern will match any single digit number, I'm just going to add in the command echo, you've entered a single digit number. It's good practice to indent these command lines so that it's easy to see when you read the script where cases start, where cases end, and what commands they contain. In case statement terminology, this coupling of a case pattern and an associated set of commands is called a clause. Each clause needs to be terminated to distinguish it from other clauses. The standard way to terminate a clause is by putting a double semicolon at the end, like so. And after we've added that double semicolon, we're then free to add another clause as part of our case statement. For example, we could add this pattern, which will match any double-digit number, and then we can also associate that pattern with the command echo, you've entered a two-digit number. We could then end this clause with a double semicolon to close it off too. So let's add in one more clause where we're going to check if the number is a three-digit number. So this time we're just going to put in 3 square brackets, and if this matches, we're going to run the command echo, you've entered a 3-digit number. And finally, we're going to close that clause with a double semicolon as well. So to close off our case statement as a whole, we just need to write the keyword ESAC, which is just case spelled backwards, as I explained earlier. So before we save our script and try and run our case statement, we actually need a value inside the number variable. So what I'm going to do is I'm going to come up the top here and add in a read command so that we can enter whatever variable value that we want. So we're going to start our command with the word read, and then we're going to add in the word number so we can save whatever value the user enters in the variable called number, just like you learned in the section on user input. We can also give the read command a prompt that says, please enter a number, just so the user knows what to do. Okay, so now let's save our script, and then head back to the command line and give it the appropriate permissions. So now if we run the script, our read command asks us for what number we want to use. So first of all, I'll give the script 1 as the number. So as expected, this has matched to a single digit number. So it matched to the first pattern that we gave. So if I run the script again, and this time give the script the number of 15, then you can see that this time the second pattern has matched, and we got a match for a 2-digit number. And we can run our script again, and this time give it the number 333, and you can see that this time the third pattern has matched, and our case statement correctly identified that we have a 3-digit number. So our case statement is working as expected. Now, if I put in a number that is 4 digits long, so for example if I put in the number 4444, and I run the script with that, then you can see that the script doesn't match any particular case, and therefore we just get back no output. This happens because the number that we entered didn't match any of the cases provided to the shell. However, there is an option in case statements where we can add in a default case that will act as a catch-all for anything that doesn't match any of the other cases provided. So let's reopen our script again and add in our default case. So below our last case statement, we can add in a new line and add in star and then a closing parenthesis. Now as we learned back when we were studying globbing, the star pattern symbol, or the asterisk, will match anything. And because it will match anything, the asterisk is perfect for creating our catch-all default case. We need to make sure, however, that we put our default option at the end to give the other cases a fair chance to match first. If we put our default case at the beginning, it will always match and it will always run, so we need to put it at the end so the other cases have a chance to run first. Okay, so if our case statement matches our default case, we're just going to add in the command echo, you have entered a number that is more than 3 digits. And then we're going to put in a double semicolon to end our clause. Okay, so if we save our script again, then head back to the terminal and run it again, and give it a 4-digit number again, you can see that now we have the message, you have entered a number that is more than 3 digits, echoed out. And if I run the script again, and this time give it a 5-digit number, so I put in 5 5s, you can see that again, we've got the same statement echoed out. So our default case is working successfully. So from this lecture, you've learned how useful the case statement can be, and how it can be more elegant to use than long if then elif statements. In particular, in this video you learned how to write case statements, you learned how to use multiple clauses to execute different commands based on if the patterns matched or not, and you learned how to use default cases to match anything that doesn't match any of the other patterns that you provide. Now, as long as you remember to use the $sign and the double quotes when introducing your variable to the case statement, and you remember to end each clause with a double semicolon, you should now find case statements a piece of cake. So up next, you're going to have a project where you can practically apply this newfound knowledge of case statements for yourself. So good luck with the project, I hope you have fun, and I'll see you in the next video. Hello there, you beautiful people. I hope you had loads of fun trying out this case statement project. In this video, I'm going to walk you through the model solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's get started. So to start with, let's create our script, which I'm going to call citychecker.sh, and then let's add in our shebang line. Our first task is to create a select statement that will present the user with a list of cities to select from. So we'll start this off with select, and then state the variable name that we want to use, which I'm going to call city, given that we're selecting city names here. We then add the keyword in, and following this we'll add in the list of our options for our user to choose from. And then we're going to end this with a semicolon and the word do. Then let's just close off our select statement with the keyword done so that we don't forget to do this. Okay, our second task is to create a case statement within our select statement that will match these cities to their countries. So to do this, we add in our case statement here, where the commands for the select statement would normally go. So I'm just going to create the case statement with the keyword case, and I'm also going to wrap it up right away with the corresponding reserved word, which is esac. So then we need to state the variable, which we're going to check the value of, and this is going to be the exact same one that we used in the select command. So we're going to put inside double quotes, and with a dollar symbol, the variable name city, and then we're going to put the keyword in. So now we need to add in our cases. To start with, I can add in the case for Tokyo. So Tokyo is in Japan, so I need to be able to give the user this as an output. To achieve this, I'm going to start by saving the country into a variable with country equals Japan in double quotes, and then I'm going to enter this case with double semicolon. So what we have now is if the city variable matches Tokyo, then the country variable will be set to Japan. So next I need to add in the next case. Now looking at our cities, we have a number of cities that are in the same country. For example, London and Manchester are both in the United Kingdom. So as mentioned in one of the hints for this task, we can add both of these into the same case by using the pipe character to separate the different possible values. So I can add in here London, pipe, Manchester, and this will allow us to enter either London or Manchester and get the same case treatment. And for this case, we're going to want to set the country variable again, but this time we're going to be stating United Kingdom in double quotes, and then we'll end this case with a double semicolon. And then we just kind of repeat this process for all the other cities and add in all of the other case statements. Okay, so all that I've done here is I've just set the variable country with the correct country name for each city. Now we still need to tell our user the appropriate answer, so to do this we can just come down the bottom here and add a echo statement which says city is in country. Now one final thing we need to do, as you learned when we were discussing the select statement earlier on, it's important to add a break statement in here to ensure that the select statement doesn't keep looping endlessly. Okay, so let's test it out. Let's save the script and head back to the terminal and give the script the relevant permissions. And if we run this now, you can see that we are presented with a menu as required. It's pretty cool, right? If I select option 2 here for London, you can see that this echoes out United Kingdom, as it should. If I run this again and I select option 4 for Moscow, you can see that this echoes out Russia, as it should. And all the other options will work too. I hope you had a lot of fun writing this short project, and that it gives you a good idea about how case statements work and how you can use them in your scripts. You can download the official solution script for the project from the resources section of this video. And believe it or not, ladies and gents, but that's the end of this section of the course on logic. You've made amazing progress, so a massive congratulations to you. In the next video, we're going to be wrapping up this section of the course by having a recap of everything that we've covered to make sure that you've got everything and that you're comfortable to move on. So for all that good stuff, I'll see you in the next video. Hello there, you beautiful person, and well done for completing this section of the course all about how to use logical constructs in your scripts. You're making really excellent progress, and in this video we're just going to have a quick recap of the key points in this section so that you can make sure that you're comfortable with everything before moving on. I've also put a cheat sheet summarising everything that we've covered in this section of the course in the resources section for this video, which you can download and refer to whenever you need to. So with all that said, let's have a recap. So in this section, we focus on a lot of different logical constructs that are available to us in Bash. To start with, we looked at how you can chain together commands using list operators. You learned that a list is when you put one or more commands on a given line, and then we learned that the list operators are types of control operators that enable us to create lists of commands that operate in different ways. The operators we saw were the ampersand, the semicolon, the double ampersand, and the double pipe. We learned that the ampersand operator sends the command that comes before it into a subshell to run asynchronously in the background, whereas the commands that come after it will continue to run in the current shell. The ampersand operator is typically used for parallel processing. Next, we looked at the semicolon operator that runs command 1 and command 2, one after the other. The shell will wait for command 1 to complete before starting command 2. This is how the shell works normally, but the semicolon allows you to put more than one command on a single line, which can come in handy sometimes. We then looked at the double ampersand operator, which is known as the AND operator. When using this operator, the shell will only run command 2 if command 1 is successful. Then finally, we looked at the double pipe operator, which is known as the OR operator, which works pretty much the other way round to the AND operator. With this operator, the shell will only run command 2 if command 1 is unsuccessful. So after we finished with the list operators, we moved on to test commands and conditional operators. You learned that a test command is a command that can be used in Bash to compare different pieces of information. The syntax for the test command is simply placing an expression inside square brackets. You learned that you'll use different operators in your expression to test different things. So the -eq operator tests if two numbers are equal. This will make the test command successful, in other words, return a 0 exit status if the two numbers you give it are in fact equal. The -ne operator, on the other hand, tests if two numbers are not equal, so the exact opposite. In this case, the test command will be successful if the two numbers are not equal. The equals test operator checks if two strings are equal. So the first two operators we dealt with were specifically for numbers and would not work with strings. This operator, on the other hand, does work with strings. The !equals operator is the exact opposite, and is only successful if two strings are not equal, with the exclamation mark here meaning not. We then have the -z and -n operators, which check if a string is empty or not empty, respectively. Aside from checking numbers and strings, we also saw some operators that will allow us to check the properties of files. For example, the -e operator tests if there is an entry on the file system with that specific name. It doesn't care particularly if it's a file or a directory or something else, just that there is something on the file system with that particular name. And if you want to be a bit more specific, the -f operator tests if a regular file exists at a particular place. The -d operator checks for a directory, and the -x operator checks for an executable script. So after working through all of these cool test operators, we then moved on to looking into a great programming construct, the if statement. We learned that if statements start and end in bash with the reserved words if and phi. If statements check the exit status of a command and only run the commands inside of them if the command that they checked gave an exit status of 0. We write if statements by starting with the word if and then follow that with the command that we want to check the exit status of. We then type a semicolon and the keyword then, which tells the shell that what follows are the commands we want to run if the command we checked gave a 0 exit status. It's always important to remember our reserved words, so our if statement started with the word if, and here at the bottom it's ending with the word phi. In the example script here, you can see that we're using the read command to ask the user to enter a number, and then we're saving that number in a variable. We then created an if statement to test if the number provided is greater than 0 and echo out this statement if it is. We also created a subsequent test with the elif keyword to test if the number provided is below 0 and echo out a statement if it is. And finally, we use the else keyword to echo out this statement if neither of the other conditions apply. So as you know, if the value is not greater than 0 or less than 0, then the number must be 0. So we tell the user that here in this example. Now after we'd looked at the basic form of the if statement, we then moved on to looking at how we can combine conditions within our if statements. You learned that it's possible to chain together multiple test commands using the list operators that we saw earlier to create more powerful conditions. The first operator we used was the AND operator, which we used to combine multiple tests together, all of which must pass in order for the condition as a whole to pass. So here we created our first script which tested if file1.txt was equal to file2, and then using the AND list operator we asked if it was also equal to file3. And if it is, we deleted file2 and file3 because we know that they're equal and there's no point wasting extra space on our file system. However, if file1 is not the same as both files, then we just echo out this statement to the user. We then looked at another script where you learned about how to use the OR operator to combine multiple tests together where only one of the tests has to pass in order for the test as a whole to pass. So here we've got another example which tests if file1 is equal to file2 or file3, and then it will remove file2 and file3 if file1 matches either of them. Then the final lecture of this section was to look at another construct called a case statement. If you have a lot of branching logic, writing many elif statements can get rather tedious. Case statements provide us with an elegant way to implement branching logic and are often more convenient than creating multiple elifs one after another. But what's important to note, however, is that unlike the elif keyword, the case statement can only work with a single variable at a time, so you're trading simplicity for flexibility. Case statements start with the reserved word case, and they end using the reserved word esac, which is just case spelled backwards. We then add in the name of the variable that we want to check the value of, remembering that we must add a $sign before the variable name to access the variable's value, and remembering to wrap that expansion inside double quotes to prevent word splitting. We end this with the keyword in, and then we start to provide our cases. As you learned, the different cases are just globbing patterns. Each pattern is finished with a closing parenthesis and then followed by the commands that we want to run for that case. Then, after the commands, we add in a double semicolon to finish the case. We can place as many cases as we want inside the case command, and we can also give each one of them multiple commands. And you also learn that it's good practice to put right at the bottom of your case statement a default case using an asterisk that kind of serves as a catch-all and that will be ran in case any of the other cases weren't appropriate. As always, it's very important to remember our reserved words with these constructs, so the case statements start with the reserved word case, and down here you can see that we're ending it with the reserved word esac. So in the example script you can see here, you can see that we're using the read command to get the user to provide us with a number, and we save that into the variable number. In our case statement, we've then firstly added a case for an empty variable, telling the user that they didn't enter any value, because that's a possibility that could happen. And then we have 3 cases to match either a single-digit number, a double-digit number, or a 3-digit number, and then echo out an appropriate sentence to the user. And finally, we put in a default case to match anything over the 3 digits and echo out an appropriate statement to the user as well. Finally, there are a few key points about case statements that I've just highlighted here for you, which are important for you to have in mind when working with case statements. The first thing is that it's very important to remember to use the $sign in front of the variable, otherwise the case statement won't be able to access that variable's value. It's also important to always remember to wrap that variable, that parameter expansion, in double quotes to avoid word splitting issues. Always remember that your cases are just globbing patterns, so they follow the same rules as globbing that we covered earlier. Patterns are always evaluated from top to bottom, and once the case finds a match, it will no longer run any of the other remaining cases. So it's very important that you put your cases with the most specific at the top and the most general towards the bottom. And finally, you can use the star or the asterisk to set a default case that will run if none of the other provided cases match. So congratulations, you've covered a whole lot of stuff in this section of the course, and now, at the end, you should be able to use list operators to create chained lists of commands, use test commands to run various logical checks on numbers, text, and files, use if statements to determine if a command should be run or not, use list operators to combine together various test commands within if statements to create more powerful conditions, and implement branching logic with case statements. And as I say, you can download a copy of this cheat sheet from the resources section of this video so that you've got a copy of all the key points from this section of the course. Now in the next section of the course, you're going to learn how you can create options for your scripts and allow your script to take various different options to change the way that it works. And we're also going to look at how you can read and process the contents of files, which is going to be an absolute game changer. So for all that good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this section of the course where we're going to be looking into how we can process command line options to change how our scripts behave, and how we can use our bash scripts to process the contents of files. So let's take a look at what we're going to be covering in this section. We're going to start off by having a look at another programming construct called a while loop and how we can use while loops to continually run commands while a certain condition is true. We're then going to look at how we can use the getOpts command together with a case statement inside our while loop to be able to provide different options to our scripts that will allow us to change how that script behaves. We're then going to look at how we can use the while loop in conjunction with the read command to create what is called a read while loop that can run commands for each line of a file. Throughout this section, you're going to start to see how some of the different concepts we've been learning earlier on in the course are going to start fitting together and complementing each other to make our scripts more powerful. By the end of this section, you'll be able to use while loops to repeat sequences of commands while a certain condition remains met. You'll be able to use getOpts commands inside while loops to allow your scripts to accept command line options and run differently based upon which options are provided. You'll be able to use read while loops to run a set of commands for each line of a file. And you'll be able to use read while loops and something called process substitution to run a set of commands for each line of the output of a command. So feel free to download this section's cheat sheet from the resources section of this video so you can keep it handy in case you need it. And we've got a whole lot of exciting things to cover, so let's go ahead and get into it. Hello there you beautiful people, and welcome to this video where we're going to be learning about while loops. While loops are the first type of looping construct that we're going to cover in this course, and they're actually rather similar to if statements. While loops will repeat a certain action over and over again while a certain condition is true. In this video, you're going to learn how to write a while loop in Bash, and how to use while loops to continue to run commands while certain conditions are met. And by the end of this video, you'll be able to interpret while loops in scripts, and you'll be able to use while loops to repeat sequences of commands while a certain condition remains met. So let's go ahead and get started. As the name while suggests, the while loop is set up to tell the shell to run a set of commands while a certain condition is true, or in Bash terms, while a certain command returns an exit code of 0. When the condition is no longer true, in other words when the command gives a non-zero exit code, then the while loop ends and the shell continues processing the rest of the script. So you can think of while loops as repetitive if statements. So let's create a script to experiment with this, and as usual, let's put our shebang line at the top. So to see how while loops work, we'll test a number that we can set in a variable. So to get this number, we're going to put a read command at the top, and we're going to enter a prompt that says enter your number. And then we're going to save whatever the user gives us in a variable called num. In Bash, all loops are considered as compound commands, and therefore they need to start with a reserved word and be terminated by a corresponding reserved word. For a while loop, the reserved word that starts the while loop off is the word while, and the corresponding reserved word to close the loop is the word done. As a side note, the word done is actually used to close all of the different looping constructs within Bash, so we're going to be using the keyword done quite a bit in this section of the course. Because a while loop is basically a repetitive if statement, you'll be pleased to know that the rest of the while loop is very similar to an if statement. For example, what we put after the word while is the command that we want to check the exit status of. This command will often be a test command, but it doesn't have to be. You can put whatever command you want. In this example, we're going to check whether or not the value held in our num variable is less than 10. So a test command is an appropriate choice for us in this case, but remember that the command we can use can be anything, as you'll see in coming videos. For now, however, let's just throw in our square brackets to create our test command, and then inside of them, let's write $num -gt and 10. Now, as you know from our coverage of test commands, this test will be true if the num variable is greater than 10 and false otherwise. Again, just like when writing an if statement, after we've finished writing our condition, we add in a semicolon so that the shell knows that the condition has ended. And so now we're done with our test commands, we just need to advise the loop of what we want to do next. Now when writing if statements, we would add in the word then in here to let Bash know that what's coming next are the consequent commands. In other words, the commands that we want to run if the condition we just provided is true. However, when writing while loops, instead of writing the word then, we write the word do instead. So now we can give some commands that we want the loop to do while our condition is true. So for this example, we're going to be using the echo command to print out the current value of the num variable. So I'm just going to type echo $num. So let's take a step back and see what we've got here. Our while loop is first going to check if our num variable is greater than 10. And if it is, then the shell will go inside the loop, run all the commands inside there, and then go back to the top to check if the num variable is still greater than 10. If it is, then the shell will go back inside the while loop and run all the commands again, and so on forever. Bash will continue to run the commands inside the while loop forever and ever, so long as our num variable is greater than 10. In other words, so long as the command that we provided the while loop gives a 0 exit status. So as it stands, because there's no code to actually change the value of our num variable after it's been set, what we've actually created here is an infinite loop. So if we save our script and head back to the command line and give it appropriate execution permissions as we usually do, and then we run our script and give it the number 13, for example, you can see that we just get the number 13 printed out over and over and over again. Now this will run forever and ever, but we can interrupt the loop by pressing Ctrl and C. In order to stop our script from getting stuck in an infinite loop, we need to modify the num variable in some way so that at some point it's no longer greater than 10 and our test statement gives a non-zero exit status. So if we open our script back up, what we can do is we can use an arithmetic expansion to just subtract 1 from the num variable each time we go through the loop. So to do this, we just type num equals, and then open up a arithmetic expansion, and inside there put $num -1. And when we save our script, and then we head back to the terminal and rerun the script, and this time we give it the number 20, for example, you can see that this time I have the numbers 20, 19, 18, 17, and so on, all the way down to the number 11 echoed out in my terminal, and then the while loop stops. The num variable started at 20, and then because 20 is greater than 10, it was echoed out. 1 was then subtracted from 20 to give the new num value of 19. Because 19 was greater than 10, it was also printed out, and so on until the number 11. Now when we got to number 11, 11 is greater than 10, so that was printed out, and then the num variable became 10. But is 10 greater than 10? No, it's actually equal to 10. So our test command gave the result of false, and the while loop stopped. So now if we run the script again, but this time instead of giving the number 20, I'm going to give it the number 5. Now 5 is already less than 10, so if I run this, you can see that we actually get nothing printed out in the terminal whatsoever. The test command gave false straight away. So as you can see from this, while loops are basically repetitive if statements. Except instead of running once like a regular if statement will do, they'll continue to run over and over again while their condition is true. Alright, so let's have a recap. So the while loop is the first looping construct that we've come across in our journey of looking into Bash. The while loop continues to run the consequent commands inside it as long as its conditions are all true. However, once the while loop notices that its condition is false, the loop ends. You need to design your loop so that the condition will eventually fail, however, otherwise you could just end up creating an infinite loop, which is often not desirable. So in this video, you learned how to structure a while loop. You learned how to use while loops to continue to run a set of commands until the test commands fail. So now that you've learned the basics of the while loop, we're going to expand this by looking into how we can use them to process command line options using while loops along with the getOpts command. Now this is going to take your Bash scripting skills to a whole new level, so for another dose of superpowers, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to have a look at the getOpts command. getOpts is used to allow your scripts to accept options on the command line, and in this video you're going to learn how to use it for yourself. By the end of this video, you'll be able to explain the structure of the getOpts command, and you'll be able to use the getOpts command to allow your scripts to run differently, depending upon what options are provided. This is going to be a key lecture for your ability to create Bash scripts, so let's go ahead and get started. getOpts is a command that enables Bash to get the options provided to the script, hence its name. So what are options? Well, consider our trusty ls command. If we run the ls command, then we can see that this lists out all the files and folders in our directory. However, by default, this does not show all the information that we can possibly have about our files. To do that, we must run ls-l, which, as we can see, has changed the ls command's behavior. In this example, we've given the ls command the L option. In the same way, when we're writing Bash scripts of our own, the getOpts command will discover any options that the user runs the script with. So let's get into a script to have a look at this. In this video, we're going to be making a temperature converter script that will convert temperatures between Fahrenheit and Celsius, and also from Celsius to Fahrenheit. So let's create the script using nano, and then add in our shebang line at the top. Since we're discussing the getOpts command, let's start by discussing how the getOpts command is structured. The first thing we need to tell the getOpts command is what the possible options for the script are. So for this example, we'll have the options as FC inside double quotes. We're using the options F and C here as we're going to write a script that converts temperatures between Fahrenheit and Celsius. If the user enters the F option, we will convert from Fahrenheit to Celsius, and if they enter the C option, then we'll convert from Celsius to Fahrenheit. Sometimes, options take their own arguments to further define how the options should function. An example of this is the cal command, which displays a calendar. The cal command has an A option, which allows you to control how many months after the current month you want to display. If we wanted to show 1 month after the current month, we would give the A option the argument of 1. If we wanted 2 months, we could give the A option the argument of 2, and so on. Now to tell the getOpts command that one of our valid options can take an argument, we simply put a colon after that argument. In our case, we're going to put a colon after both the F and C arguments, and this will allow the user to enter either F or C along with the number they want to convert. The way getOpts works is that every time it's run, it gets the next option on the command line. That option will need to be saved somewhere so that we can process it. In our case, we're going to save the option in a variable called opt, which we can do just by writing the variable name after our double-quoted list of options here. Note that you can call this variable whatever you like, but opt is just a common choice. Now the weird thing about the getOpt command is that it actually doesn't get all the options at once. It just gets the next option on the command line each time that it's run. So, the first time that it's run, it'll get the first option. The second time it's run, it'll get the second option, and so on. In order to ensure that the getOpt command processes every option, we actually need to write the getOpt command as the condition command of a while loop. So we will put while at the front of the line and have the getOpt command as our condition. Then, like a normal while loop, we'll put a semicolon after our condition, which in this case is the getOpt command, and then write the words do and done to finish off our while loop like we learned previously. So what's going to happen here is that each time we go around the loop, the getOpt command will read an argument on the command line. If it's a valid option, that option will be saved in our opt variable. If it's not a valid option, however, our opt variable will have a question mark stored inside it. Another important thing to bear in mind is that the getOpt command only does what its name suggests. It just gets the options provided by the command line. No more, no less. Although getOpt will tell you what the next option on the command line is, it's still our job to take that information and alter the functioning of the script accordingly using logic. Fortunately, we already know everything we need in order to do this. All we need to do is put a case statement inside our while loop. Do you see how everything's starting to come together? Inside our case statement, all we need to do is add a particular case for each option the user could provide. Simple, right? So let's set up our case statement by writing case, then inside double quotes, we're going to put $opt, and then the word in. And then we're going to close our case statement with the reserved word ESAC, like you learned earlier. So what are the possible cases that we can have here? Well, the user can enter a C to convert a Celsius temperature to Fahrenheit, or they could enter an F to convert a Fahrenheit temperature to Celsius. They could also enter some other unaccepted option, which we will catch using our catch-all asterisk, like we learned before. In fact, the getOpt command will actually put a literal question mark inside the opt variable we defined if an invalid option is provided. So when working with getOpts, it's actually more correct to use a question mark to catch any unaccepted options. So let's use that here instead of the asterisk for this video, remembering to put a backslash in front of the question mark to make sure that it's interpreted literally. Finally, let's close off all these cases with a double semicolon like we learned in our discussion of the case statement. Awesome, we now have a case statement set up to manage each of our options. All we need to do now is simply convert the numbers the user provides to the appropriate unit and then give them back to our user. I've actually already prepared the command lines for this section that simply use formulas to convert between Fahrenheit and Celsius to compute the appropriate values, so let me just paste in the one for the C option. You can see here that we're just using a command substitution and the BC command we saw in section 2 to calculate the appropriate value and then save the result in a variable called result. The important part of this that I want to draw your eye to, however, is the use of the opt-arg variable, which stands for option argument. Whenever we put a colon after an option inside our list of accepted options, like we did here for the C and the F options, then getOpts will save the argument that's provided for that option inside the opt-arg variable. So basically, if someone entered the C option, followed by a space and the number 32, then because we have said that the C option is allowed to accept arguments by placing a colon after it in our option string up here, the opt-arg variable would automatically be set to 32 when the getOpts command processes the C option. In short, for this script, the opt-arg variable will contain the number the user wants to convert. I've also prepared the equivalent formula for converting from Fahrenheit to Celsius, so let me just copy and paste that in here too for the case when the user wants to enter the F option. Finally, after processing the result, we just need to come down to the bottom here below our while loop and simply echo out the result. Okay, so let's now save and close our script, and then give it the appropriate execution permissions. Now let's say that we want to convert from 32 Fahrenheit to Celsius. 32 degrees Fahrenheit is 0 degrees Celsius, so when we run our temperature converter script with a Fahrenheit value of 32, you can see that we get back 0. And when we run the script the other way, so we convert 0 degrees Celsius to Fahrenheit, you can see that we get back 32. So it looks like our script is working. If you'd like to download the script and play around with different numbers, I've uploaded a completed version of this script to the resources section of this video for you to try out. Other than that, that's it for our discussion of the getOps command, so let's quickly wrap up and have a recap of everything that we've learned. So in this lecture, you've blended together your existing knowledge of while loops and case statements with your newfound knowledge of the getOps command to build a pretty cool temperature converter. You'd probably admit that this script was pretty complicated, and you now understand how it all works, which means that you're making excellent progress in your bash scripting skills, so great job. So to wrap up, in this video you learned how to use the getOps command within a while loop to ensure that each option is processed. You learned how to use a case statement with the getOps command to create different behavior for different options. You learned how to create a case to capture unexpected options using the question mark. And you learned how to give arguments to your options by writing a colon in the getOps option string, and how to act on that information using the opt-arg shell variable. So up next, you're going to have a project that blends together what you've learned about while loops and the getOps command. And then we're going to be moving on to discuss read while loops, which will allow us to write scripts that can read and process files. So good luck with the project, and for all that file processing goodness, I'll see you in the next video. Hello there, you beautiful person. I hope you had loads of fun trying out this project. In this video, I'm going to walk you through the model solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's get started. Okay, so to start with, I'm just going to create our script with nano-timer.sh, and then I'm going to add in our shebang line. Our first task is to add getOps into our script so our user can provide the number of minutes and seconds the timer should run for using command line options. As we know, this means we're going to need to start a while loop to make sure that we process all the options, so I'm going to start off the while loop with the keyword while, and I'm also just going to finish it off with the keyword done, so I don't forget to do this later on. Then I'm going to add in the getOps command as the condition command of the while loop. Next, we need to give our getOps command an opt string that contains all of the options that we want to accept. We need to give the user options for minutes and seconds, so I'm just going to add in M for minutes and S for seconds, remembering to put in the colon after each option to tell getOps that we expect the user to provide an argument after providing each option on the command line. We're then just going to add in opt as the variable that we want to save the current option that getOps is processing at the current time, and then we're going to finish off at the first part of our while loop with semicolon and the keyword do. Now inside our while loop, we're going to add in our case statement with the keywords case and esac. For the case statement, we just need to add in our opt variable from our getOps command, remembering to wrap it in double quotes and with the $sign, and then we're just going to end this line with the keyword in. Now we have two options for this script, which are M and S, so we need two cases, one for option M and one for option S. So what commands do we want to run here for each case? We're told in our task that we need to use arithmetic expansion to calculate the total seconds that the timer should run for. So for this, I'm going to start by initializing a variable called total_seconds, and then I'm just going to set that equal to a blank value for now. Okay, now let's start writing the commands for the M option. Option M is for the minutes, so here I'm just going to update the total seconds variable, and I'm going to set it equal to itself plus whatever number the user enters with the M option multiplied by 60. Because if they enter 1 minute, that's going to be 60 seconds. Notice here that we're using the opt-arg shell variable to grab the number that the user enters as the argument for the M option on the command line. Then we're just going to end this case with a double semicolon as usual. Now for the second case, we just need to do exactly the same, but this time we don't multiply the opt-arg by 60 because this value that the user provides will already be in seconds. Okay, so that's the first task done. Now we're told for the second task that we must create a while loop that will do quite a few things. So let me add in the while loop and close it off with the keyword done. Given that we want our timer to run until the timer reaches 0, the first thing we need to do is to add in a test statement to test if our variable of total seconds is greater than 0. Now the next thing we need to do is echo out the current value of the timer, which we can just add in by typing echo total seconds. This will make our timer echo out the total value of our variable at each iteration of the loop. Next, we need to reduce the value of the total seconds variable by 1 each time the loop runs to simulate a second passing. To do this, we're just going to set our variable again by typing total seconds equals. And then using arithmetic expansion again, we just need to reduce this by 1. So all this is doing is just taking the current value of the total seconds variable and reducing it by 1 with each iteration of the loop, which is exactly what we want it to do. Now if we left this like this and ran it, it would still count down to 0 and echo out the value each time, but it would all happen so quickly that it wouldn't be very useful as a timer. So to change this, we can slow down the loop with the sleep command. The sleep command is used to basically pause your script before continuing. So if we put the sleep command in here, and say we want it to sleep for 1 second by typing 1s, then the loop will pause here for 1 second before it iterates again. This will help us simulate the timer counting down 1 second at a time. And that's the end of that while loop for us. Finally, we need to echo out time's up once the loop ends. So to do this, all we have to do is echo this out at the end of the file by typing echo time's up. Now we put this message at the end of the script here because we only want it to run when the while loop has finished counting down. Okay, so let's test it out. Let's save this script and head back to the command line and give it the relevant permissions. Now let's run our script, and first off let's just give it 10 seconds using the S option. If I run this, then you can see that it is indeed counting down 1 second at a time backwards from 10 until it reaches 0. Now if I now run this again and I put in the M option with the argument of 1 and the S option with the argument of 5, you can see that the script is now counting down from 65, which is 1 minute and 5 seconds, and it keeps going until it reaches 0. Now because of the way we wrote the script and because we had the total seconds variable initialized to an empty value and then used it within each case, it doesn't matter which option we actually write first. So if I flip the options around but keep the values the same, you can see that it's still working and is again counting down from 65 seconds. So that's great. So congratulations, you now have the most advanced egg timer in the world. I hope you had fun doing this short project, and I hope it's given you a good idea of how while loops work and how you can use them in your scripts. You can download the official solution script for this project from the resources section of this video. In the next video, we're going to be taking a look at how we can use what we've learned so far to process the contents of files line by line. Now this is going to be super useful, so congratulations once again for completing this project, and for all that file reading good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we'll be looking at read while loops. Read while loops are simply a combination of the read command and while loops that you can use to iterate over contents of a file line by line, which, as you can imagine, is a super useful ability to have. So, like I said, in this video, you're going to learn how to use read while loops to iterate over the contents of a file line by line. And by the end of this video, you'll be able to use read while loops to iterate over the contents of files, and you'll be able to use read while loops and process substitution to iterate over the output of commands. So this is very interesting stuff, so let's go ahead and get started. The first thing I should know is that read while loops are not actually a different type of loop. Read while loops are just while loops that use the read command as their test condition. And read while loops are commonly used to iterate over files line by line. So let's see this in action. I've already created a test file for us to work on, so if we open it using the cat command, we can see that it's just a simple text file with this is line 1 on line 1, this is line 2 on line 2, and this is line 3 on line 3. Okay, so now that we've got a file to read, let's have a look at how a read while loop is structured. Let's create a script called read while, and then add in our shebang line at the top. So as with any while loop, we start with the while keyword, and then we add in the commands we want to check the exit status of. As you will have noticed in our discussion of the getOps command, the command that we provide a while loop does not need to be a test command. We can actually provide any command as long as we can get 0 and non-zero exit statuses from it, which pretty much all of them provide. So in this example, to create a read while loop, we'll be using the read command as our test condition. If the read command successfully receives input, it will give us an exit code of 0, and thus our loop will run. However, if our read command doesn't receive a line, for example, if our file is empty or we get to the end of the file and there are no more lines to read, then the read command will give us a non-zero exit code and the while loop will stop. So, in other words, the read while loop allows us to run a block of code once for each line of a file. As you will recall from our discussion of the read command, we can tell the read command the name of the variable that we want to save the data that it reads into. Now, as we're reading lines of a file, I generally create a variable called line, but you can call it whatever you want. And since that's the end of our read command, we end the line with a semicolon and the word do, just like we always do when making while loops, and then we close off our while loop with the keyword done. So this has set us up with a read while loop, which will run through a file and save the current line it is processing into a variable called line. The next thing we need to do is to tell our read while loop which file to read. Now this is very simple. All we need to do is come down here to the done keyword and add in a redirection from standard input, like so. We would then type where we want the data to come from. So if we had a specific file name that we always wanted the script to read, we could put that in here. But in this example, I'm just going to type $1 in double quotes after the redirection operator. Here we're telling our read while loop to read the file that we refer to in the first positional parameter that we provide to the script. This allows our script a bit more flexibility, as we can tell it to process a new file every time we run the script, rather than hard coding a specific file name into the script itself. Notice how we're wrapping the $1 inside double quotes to avoid any potential word splitting issues. Okay, cool. So the only thing we need to do now is to tell the while loop what we want to happen for each line in our file. In this example, I'm going to keep it simple and just print out each line. So let's just type in echo $line. Okay, so that's it. Let's now save our file and head back to the command line and give our script the appropriate permissions. Now if we run our script and give it the file name that we want it to read as the first command line argument, you can see that our script will now echo out each line of our file. Easy, right? Now of course we can do more than just printing the lines out. Because we have access to each line of our file in our line variable, we can do pretty much anything we want with each line of the file. The choice is really up to you. Now I want to show you a particular rookie mistake that is so easy to make when constructing read while loops. If we head back into our script, and this time, instead of redirecting the standard input of our while loop, let's redirect the standard input of our read command. This is a very common mistake, and it's common because it actually makes sense. But let's look at what happens when we save the script and head back to our terminal. When we run the script, you can see that our read command keeps spitting out line 1 over and over again. So this is not what we want at all. Fortunately, I can stop this by interrupting the script using Ctrl and C. So the important lesson to learn from this is don't redirect the standard input of the read command, redirect the standard input of the while loop. Now, it's also quite common to want to iterate through the output of a command rather than just the contents of a file. Now we can do that using a read while loop as well. Now to do this, instead of redirecting standard input so that it comes from a file or from a command line argument like we have here, what we're going to do is we're going to redirect it so that the standard input comes from the output of a command, or more precisely, from a process. Now we can't pipe to while loops, but we can use something called process substitution, like so. In Linux and other Unix-derived systems, it's possible to use process substitution to represent running processes as files, and thus read data from them just like you would read from regular files. Here, we're using process substitution to represent the command ls$home as a file. And then we're using that file as the standard input of our read while loop. And when we save this and head back to our command line, and then we run the script, you can see that we're now iterating through each line of the ls command as if it was actually a real file. Awesome, right? Being able to run commands like this and iterate through their results line by line is a super powerful ability, and now you know how to do it too. So in this lecture, you've learned a whole lot about how you can use the read command in a while loop to iterate over files. You also learned how to use process substitution to represent commands as files and thus process their results in read while loops. If you're interested, I've also put a couple of links in the resources section to some great resources about process substitution, which you can read to learn more about it. So now that you've learned how to iterate over files with read while loops, up next is a project to help you put this knowledge into practice. And after that, believe it or not, you've come to the end of yet another section of the course. So a massive congratulations to you, good luck with the project, and I'll see you in the next video. Hello there, you beautiful people. I hope you had loads of fun trying out this project. In this video, I'm going to walk you through the model solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's get started. So first of all, because this script creates loads of random folders, testing it can get rather messy. So I'm going to create a new folder called testing ground for us to work in. And then I'm going to move our folders to create.txt file inside there as well. Okay, cool. So let's change into our testing ground folder, create our script, and add in our shebang line. Okay, so now that we're set up, the first thing that we're told that we need to do is to create a read while loop that will iterate over the provided file and create a directory for each folder name in the provided list. So let's get started with our read while loop. So we're going to start this off with the words while read. All this is doing is setting up a while loop that uses the read command as the command it will check the exit status of. Now, as you learned, the read command will always give a successful exit status as long as there's a line to read, which means that this while loop will continue to run as long as there continues to be content in the file that we provide it. Speaking of content, we need somewhere to save each of our lines, so let's tell the read command to save each line in a variable called line. Finally, we can add a semicolon and the word do to end the first part of our read while loop, and while we're at it, we can come down to the bottom here and add the word done to close off our read while loop. We can now begin to add within this do done block the commands that we want to be run once for each line of the file. In this example, we're going to be using the mkdir command to create directories. Then we're going to provide the line variable as input to the make directory command, so that we'll create a folder for each line of our file. However, we have to be careful here. If we save our file and then head back to our terminal and have a look at the folders to create.txt file that we were given, you'll notice that there are spaces within the various provided folder names. This means that unless we prevent it, word splitting will break each of our lines into multiple words, and thus our make directory command will end up creating multiple folders for a given line, rather than just one, which isn't what we want at all. For example, this top line that says daily space reports will be split into the words daily and reports, thus causing the make directory command to create two folders instead of one. So if we head back to our script, can you remember how we can stop the word splitting? That's right, we wrap our line variable inside double quotes. It's as simple as that. So that's pretty much it for our read while loop in terms of the actions that we want it to do. All we need to do now is tell it where to get its data from. The project brief tells us that our read while loop should draw its data from whatever file we refer to in the first command line argument provided to the script. So after our done keyword here, we're just going to add in a standard input redirection to $1. We can also wrap the $1 in double quotes just to be cautious and make sure that we prevent any word splitting issues. Alright, so let's save our script and head back to the command line and give our script the appropriate execution permissions. So if I run our script and provide it with the folders to create.txt file as the first command line argument, we can see that the script appears to have run successfully. And if I run the ls command, we can see that it has created all the folders from the list that we provided in that file. Awesome job. And that's it. So I hope you had a lot of fun doing this short project and that it's given you a good idea of how read while loops work and how you can use them within your scripts. You can download the official solution script for the project from the resources section of this video. And believe it or not, that brings us to the end of yet another section of the course. You're doing incredibly well, so to celebrate your success and to recap what we've learned so far, I'll see you in the next video. Hello there, you beautiful person, and well done for completing this section of the course all about how to process options and iterate over files. You've made some excellent progress, and you've learned a lot about how to write while loops together with the getOps command to enable your scripts to process command line options to change their behavior. And you've also learned how you can use the read command together with the while loop to iterate over the contents of files. In this video, we're just going to have a quick recap of all the key points in this section so that you can make sure that you're comfortable with everything before moving on. I've also put a cheat sheet summarising everything that we've covered in this section of the course in the resources section for this video, which you can download and refer to whenever you need to. So with all that said, let's have a recap. In this section, we started by looking at while loops. You learned that a while loop runs a set of commands while a certain condition is true, hence its name. While loops continue until either the condition command that we provide them becomes false, in other words, it returns a non-zero exit code, or until the loop is interrupted. The syntax for a while loop, as always, is to start with the appropriate reserved word, which in this case is while. We then have the condition, which is tested on each pass through the loop, and then we put a semicolon and the keyword do. Then we have the commands which are going to be run for each iteration of the loop, and the loop is then ended with the reserved word done. So as an example here, you can see that we're using the read command to get a number from the user. And then in our while loop, we're then testing if this number is greater than 10, and if it is, we're printing out the number and reducing the value of the number by 1 using this arithmetic expansion here. The result of this is that if we start with a number greater than 10, the loop will continue to run, reducing this number by 1 each time until the value is 10, and then the loop will fail its test and stop running. And essentially we will print out backwards by 1 each time from the number we're given until we get to the number 10. It's important to remember that you must ensure that the condition you provide the while loop does in fact become false at some point to avoid creating infinite loops. So after we looked at the basic form of a while loop, we then moved on to looking at how we can use this together with the getOps command to allow us to give our script command line options. It's important to remember that, although getOps does allow us to process command line options, it doesn't get all of these options at once. It only gets the next option on the command line each time that it's run. This is why we use the getOps command together with a while loop. Because the getOps command returns a 0 exit status when it successfully gets an option, using the getOps command as the condition in a while loop allows us to process command line options one by one until there are no more options left. The syntax for the getOps command is to type the word getOps and then provide it with a set of valid options in what is known as an opt string or an option string. Then you give the getOps command a variable name that you want to save the current option in. It doesn't matter what you call your variable, however for convenience sake I normally just use opt because it's short and easy to remember, it's short for option. Note again that this variable will only store one value at a time, which is the most recent option that the getOps command has found. Okay, so that's the overall syntax for the getOps command, but there's also a specific syntax for the opt strings themselves. Each individual letter placed inside the opt string is considered as its own option. A limitation of the getOps command is that it can only process one letter options, and therefore it can't do long form options like we sometimes see with some of the commands we run in our shell. So for an example, you can see here that if we wanted to select the options capital A and lowercase b, we would write capital A and lowercase b inside our opt string. It's important to remember that our options are case sensitive, as is common with most commands and constructs within Linux. We can also control whether our individual options can take arguments of their own. For each option that we want to allow to accept an argument of its own, we must place a colon after that letter in the opt string. Then, when the getOps command picks up this given option, if that option is allowed to take arguments, and an argument is provided, then that argument will be saved in the optarg shell variable, which stands for option argument. So in this example, if we ran our script and gave it the capital A option and gave an argument of 10 to the capital A option, the opt_arg variable would store the value of 10 when getOpt processes the capital A option because there's a colon after the capital A inside the opt string. So we then looked into a few practical examples of how to use getOpts. As we learned, the getOpts command is often used in conjunction with a while loop so that we can get all of the options that are provided. In order for us to allow the script to perform different actions based on the options that are provided, we also tend to use the getOpts command together with a case statement. This way, we learn that we can provide different actions for the script based on the different options selected by the user. So the syntax for the getOpts command with a while loop and a case statement looks like this. We start our while loop and give it the command getOpts, and then we have the opt string provided here for the getOpts command and select our variable. This is then placed into the test condition area for the while loop, and therefore we also place a semicolon after it, followed by the keyword do. We then start our case statement here with the word case and set our variable, which in this case would be the same as the one we created for the getOpts command, except this time we're going to wrap it in double quotes and put a $sign in front of it. This is then ended with the word in, as usual with our case statements. We then create the cases for each option and add in the commands that we want to run for each of the different options if selected. At the end, we end our case statement with the keyword esac, and following this we end our while loop with the word done. You learned that when an unexpected option is provided to our getOpts command, so an option that's not in our opt string, the getOpts command will save a literal question mark inside the variable that you provide it. Therefore, instead of using a star or an asterisk for the default case, it's good practice to put a \question mark case when working with the getOpts command. We use a backslash here to escape the special meaning that question marks have in globbing patterns and to ensure that the question mark gets interpreted literally. In our example script, we created a temperature converter. We use a while loop here with the getOpts command, and we allow our user to enter either the C or an F option so that they can provide a certain temperature in either Celsius or Fahrenheit. So we have a case for the C option, which will convert the temperature provided from Celsius to Fahrenheit, and we have an F option that will convert the temperature provided from Fahrenheit to Celsius. Then, as the last case in our case statement, we've got a \question mark to catch anything else, and we also echo out a message that says invalid option provided. And then finally, we echo out whatever result that was computed, if one was computed, to the user. Then after discussing case statements, in the final lecture of this section, we learned about how to use the read command together with a while loop to create what is called a read while loop. Read while loops are simply just while loops that use the read command as their test command. You learned that they're used to read lines of output one by one and do something for each line. A read while loop can be used to iterate over the contents of files or iterate over the output of a command line. And you learn the syntax for iterating over the contents of files as shown here. Using a while loop, we give the while loop the read command, set our variable, which will store the contents of each line, and end this with a semicolon and the keyword do, as we usually do. We then add in our commands that we want to run for each line of the file, and end our loop with the keyword done. Finally, at the end here, we redirect our file to the standard input of the while loop so that it will iterate over the contents of the file. It's important to remember that we're redirecting the standard input of the while loop and not the read command. Now in our example script here, we created a read while loop that will iterate over each line of file1.txt and echo it out to the user. We then moved on to have a look at how we can do pretty much the same thing, but instead of iterating over the contents of a file, we iterate over the output of a command. You learned that this is achieved using a new concept, which we introduced in this section, called process substitution. Process substitution simply allows us to treat the output of a command as a file. The syntax for process substitution is the less than sign and then a set of parentheses wrapped around whatever command you want to run. You also learned that if you want, you can actually put an entire pipeline inside here rather than just running a single command. Now because the process substitution is treated by Bash as a file, all we've got to do is to read that process substitution into standard input. It's important to note here that we must remember to include the redirection operator before our process substitution. even though the process substitution has the same character in it, this less than sign, this is not acting as a redirection operator, and so you still need to include the redirection operator in front of the process substitution to tell the shell to read this imaginary file created by the process substitution itself. So in this example, we're using exactly the same script as when we were processing a file, but instead of iterating over the lines of a file, we're now iterating over the lines of output from the command ls$home and printing out each of those lines to the user one by one. So a massive, massive congratulations to you. You've gained a whole lot of useful skills in this section, and now, at the end, you should be able to use while loops to repeat sequences of commands while a certain condition is met, use the getops command to allow your scripts to process command line options and to run differently according to what options are provided, use read while loops to run a set of commands for each line of a file, and use read while loops and process substitution to run a set of commands for each line of the output of a command line. And as I say, there's a cheat sheet available in the resources section for this video that contains all the key points from this section of the course. Now in the next section of the course, we're going to be learning how to use arrays to manage data in your scripts and to create assembly lines for batch processing of data. So I hope you're excited, and I'll see you in the next video. Hello there you beautiful people, and welcome to this section of the course where we're going to be looking into data structures that you can use in your bash scripts. In bash, you can use arrays to store a lot of data in one place and then iterate over that data to effectively create assembly lines in your scripts. So let's take a look at what we're going to cover in this section. In this section of the course, you're going to learn how to create and work with arrays, and you're also going to learn how to iterate through them with what is known as a for loop. By the end of this section, you're going to be able to create literal indexed arrays for yourself. You're going to be able to add, remove, update, and extract elements from indexed arrays. You're going to be able to use the read array command to easily generate massive arrays without having to type out the values for yourself. You're going to be able to use for loops to iterate over these arrays and create automated assembly lines inside your scripts. And you're also going to be able to use these for loops with logic to perform different actions for each element of the array depending upon the results of a logical check. So feel free to download this section's cheat sheet from the resource section of this video so you can keep it handy in case you need it. And as usual, we've got a whole lot of exciting things to cover, so let's go ahead and get into it. Hello there you beautiful people, and welcome to this video where we're going to take a look at the most common type of arrays in bash, indexed arrays. In this video, you're going to learn how to create and work with indexed arrays. And by the end of this video, you'll be able to explain the difference between arrays and regular variables. You'll be able to create literal indexed arrays. And you'll be able to add, remove, update, and extract elements from indexed arrays in bash. So let's go ahead and get started. So why are we learning about arrays? Well, let's start off by comparing arrays with regular variables. As we've seen them so far, variables can only be used to store one piece of data at a time. A variable called number, for example, has so far only been able to hold one number. A variable called name has only been able to hold one name. Arrays, on the other hand, are a type of variable that allow us to hold multiple different values at the same time. We can then use the array to manage hundreds, potentially even thousands of values at once, or we can choose to work with a small subset of the array as we see fit. So let's say we wanted to create an array of numbers, imaginatively called numbers. I can do this by putting numbers equals, and then opening a set of parentheses to make the variable into an array. Then we can write inside these parentheses the numbers we want to store, with each number separated by a space. Arrays can contain any type of data. I'm using numbers in this example, but arrays can also store text data and a mixture of both. Notice how, unlike other programming languages, in bash we do not use commas to separate each element of the array. In bash, we separate the values using spaces. Okay, so that's how we can create an array, but how can we work with them? In this type of array, each of the entries in this array is called an element, and each element is accessed using a position number called an index. This is why the formal name for the type of array we have just created is an indexed array. Indexes start from 0 and increase by 1 for each element. So the first element in the array actually has an index of 0, and is therefore often called the 0th element to reflect this. So in this case, with our array of numbers, the number 1 would be the 0th element, the number 2 would be the first element, and so on. So now if I just echo out this array like a normal parameter, you can see that I just get the 0th element, the number 1. In Bash, if you just do a simple parameter expansion on an array name, then Bash will default to just giving you the 0th element only. But let's say we wanted to access the third value of the array. How could I do that? Well, to do that, I would need to use the $curly brace syntax that we learned before. If I now use the $curly brace syntax, I can write the array name inside here, and then specify which index I want to access inside square brackets, within the curly braces. So let's say I want to get the third value from our array. Because indexes start from 0, the first value would be given with index 0, the second given with index 1, and the third given with index 2. So to get the third value, in human readable terms, I need to put in an index of 2 inside the square brackets. And when I run this, you can see that it has now echoed out the value at index 2, which is the number 3. Now what if we wanted to get the whole array? Well, instead of just putting a specific number, we can just place an @ symbol inside the square brackets. Just like how the @ special parameter allowed us to access all positional parameters provided to a script at once, the @ symbol here has allowed us to access all of the values in an array at once. As you can see, we're simply referencing different values of the array using parameter expansion. But because we're using parameter expansion, we can also still use all of the parameter expansion tricks that we learned in section 2 on the array. The most important of these being slicing. During our lecture on parameter expansion tricks, we learned how to perform slicing on parameters by adding in an offset and a length after the parameter name to slice out specific characters, and we can do the same with indexed arrays. So if I run the same command again, but this time I put a colon and a 1 after our square brackets, we can see that this now offsets our expansion to start at index 1, and we only get everything from position 1 until the end. If we now throw in a length, like so, you can see that instead of giving us all the values from index 1 all the way to the end, this has only expanded out until we had an array with a length of 2. As you learned in our lecture on parameter expansion tricks, these expansion tricks do not change the actual array. If we look at our full array by removing the offset and the length, we can see that it still contains the numbers 1 to 4. So now we've seen how to create index arrays and how to access the information in them. One great thing about arrays is that you can add in elements, remove elements, and update specific elements without having to write the entire array all over again. So say we wanted to add the number 5 to the end of our numbers array. What we can do is specify the array, which in this case is numbers, and then we can use the operator += to add a value to the array. The way this works in Bash is that to add a value to an array, you have to add an array to the end. So if we wanted to add the number 5 to our array, we can't just put the number 5 here. We need to wrap that 5 in parentheses to make it an array before we can add it to our existing array. Notice how we're ensuring that there are no blank spaces around the += operator. And if I now echo out the entirety of our numbers array, you can see that we now have the number 5 in our array as well. So what if we wanted to delete an element from an array? If we want to delete an element, we can just use the command unset and state the array, along with the index number that we want to remove inside square brackets. So let's remove the number 3 from our array by putting in index 2, because that's the index where the number 3 is when we count from 0. Now if I take a look at our entire array again, you can see that the number 3 has been removed. Deleting elements does give rise to some strange behavior, however. In Bash, you can see the index numbers of elements by putting an exclamation mark at the front of the parameter expansion. So if we do that, like so, here you can see something a little bit strange is going on. The indexes that we have in our array are now no longer in sequence. We have 0, 1, 3, and 4, but index 2 is missing. So when we deleted the number 3 at index 2, that index was just deleted. Indexes 3 and 4 weren't brought down to ensure the continuity of the index scheme. This strange behaviour when you delete an index can cause you some issues if you're not aware of it and were expecting the indexes to readjust automatically. So I thought I'd point out that behaviour to you and also how you can use the exclamation mark to see index numbers. Finally, what if we wanted to change an element in an array? Well, fortunately, this is very simple. If we wanted to change an element, so let's say we wanted to change the 0th element to the letter A, for example, we could do that by typing numbers, then in square brackets the number 0, equals A. Again, ensuring that there are no spaces around the equals sign. And when we take a look at our numbers array, we can see that the letter A is now our new 0th element. So in this lecture, we've covered a whole lot about how you can do basic manipulations on indexed arrays, which is a very powerful ability to have in any programming language, but especially in Bash, as you will see shortly in coming videos. Before moving on, however, let's have a recap to make sure that you've got everything from this video. In this video, you learned that the difference between an array and a regular variable is that arrays allow us to store more than one value under a given variable name. You learned how to create a literal index array. You learned how to view the index values of elements in an array using an exclamation mark inside the $curly brace syntax. You learned how to access values from your array using index values and slices. You learned how to grab the whole array at once using the @ symbol. You learned how to add elements to and remove elements from your arrays. And you learned how to replace individual elements of an array with another value. So now that you've got the basics down, in the next lecture we're going to be looking at the readArray command and how you can use it to create arrays automatically from files. So for all that array creation goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be looking at how you can create arrays using the readArray command. The readArray command is a super useful command in Bash because it allows us to generate arrays both from the contents of files and from the outputs of commands. This is very useful because once we have that data in the form of an array, it's much easier for us to do batch processing on that data using something called a for loop, as you'll learn in the video after this one. In this video, however, you're going to learn how to use the readArray command to generate indexed arrays from the contents of files, and you're going to learn how to use the readArray command to generate indexed arrays from the outputs of commands. And by the end of this video, you'll be able to use the readArray command to easily generate indexed arrays without having to type the values out manually for yourself. So for yet another dose of Bash superpowers, let's go ahead and get started. Okay, so first we're going to have a look at how we can use the readArray command to create an array from the contents of a file. So as its name suggests, the readArray command converts whatever it reads on its standard input stream into an array. The benefit of using the readArray command is that it makes creating large arrays a whole lot easier than having to type out each value manually for yourself. So currently I have a file called days.txt, and if I run the cat command on it, you can see that it contains a list of all the days of the week, so pretty simple. So I want to create an array with the contents of this file. To do this, we use the readArray command, and then we have to specify the name of our array, which in this case we will call days, but you can call it whatever you want. And finally, we redirect the standard input of the readArray command to the days.txt file, like so. So what will happen here is that the readArray command will read the contents of the days.txt file into a new indexed array called days. Now if we view the contents of this array, you can see that we now have an array that contains all the days of the week. Now it's important to note at this point that the readArray command will create a new element in the array for each new line provided as input. So if we echo out the indexes, you can see that each day has been created as a separate element in the array, because each day was on its own line in the file. Now this brings me on to an important point that you should bear in mind when using the readArray command to create arrays from files. During this course, you've learned about the existence of invisible whitespace characters, spaces, tabs and new lines, and how they can have quite an effect on how Bash processes things. In computing, every line in a file ends with an invisible new line character. This is how computers know that a line has actually ended. By default, when the readArray command reads a file, it takes each line of the file as well as the invisible new line character and stores the whole thing as a new element in the array. So if we take a look at the invisible characters in the array, using the parameter expansion trick that we learned back when we were learning about the invisible characters in the IFS variable, you can see that each new day has a new line character at the end, represented here by a \n. Because this new line character is being stored with each element, it can really mess up your formatting when you come to get the data out of the array later on, as you're not just dealing with the raw data that was on the line, which in this case was the days of the week. Instead, you're actually getting the raw data and an invisible new line character. So to avoid this sneaky issue, it's important that whenever you're using the readarray command to create an array from a file, that you provide the readarray command with the -t option. This -t will remove trailing new lines by default and only store the raw data from each line in the array. So if we run our readarray command again, with the -t option this time, and then we echo out the value using our parameter expansion trick, you can see that this time our array just includes the raw days of the week and no sneaky extra new line characters, which is great. We will look at this in more detail in a future lecture, but for now just remember that whenever you use the readarray command to create an array from a file, you should always use the -t option unless you have a particular reason not to. So now that you've seen how you can create an array from the contents of a file, let's now take a look at how you can create arrays from the outputs of commands. Let's say that we have a folder with some files in it, and we want to add those file names and their path into an array so that we can access that information at multiple points throughout our script. So for this example, let's create a folder called array, and then we can change into that folder using the cd command and create some files. Here I'm going to create 100 empty files using the touch command and a brace expansion. If we now run the ls command, you can see that the 100 files have indeed been created. So let's say that we wanted to create an array that would store the absolute path to each of these files. To get the full file paths, we can use the command ls:/bashcourse/array/star, which as you can see gives us the complete paths to each of the files in our arrays directory. So now that we have the output that we want, how do we get that to be the input of the readarray command so that it can create an array that contains that data? Okay, so from what we know already, we can run the readarray command to create an array and tell it to save what data we give it into an array called files. But how do we get the output of the ls command into the readarray command? Now unfortunately, we cannot simply pipe to the readarray command. But why not? Well, the reasons for this are quite complex, and I've put a link in the resources section for you if you want to read up on it. But in short, the problem is that every command in a pipeline is run in its own subshell. So if we were to run the readarray command as part of a pipeline, the new array that the readarray command creates would only exist within that subshell, and therefore we wouldn't be able to access the array from the rest of our script. So instead, we have to use something called process substitution. Process substitution is a new concept for us, but it essentially allows us to represent the standard output of a command as a file. We can then just read this file into the readarray command by redirecting standard input, just like we did earlier when working with a real file. And since we aren't creating a pipeline, we get around the issue with subshells. The syntax for creating a process substitution is a less than sign, followed by a single set of parentheses. We can then put our ls command inside these parentheses. This syntax will represent the output of the ls command as an imaginary file, but we also need to actually read that file into the standard input of the readarray command. To do this, we simply add a standard input redirection operator before our process substitution, like so. So now what we have is a command line that is going to provide the output of our ls command to the readarray command as a file, and then the readarray command will use this to create the new array. So I can run this now, and the new array will be created. So if we echo this out, you can see that this has indeed created the array with 100 file paths. Just to check that these are in fact different elements in the array, if we echo out the indexes using the exclamation mark, you can see that it has in fact created the array with 100 different elements in it. However, again, because the process substitution represented the output of the ls command as a file, the readarray command has included those sneaky new lines at the end of each element. So again, it's important that we give our readarray command the -t option to strip away any new line characters that appear at the end of each line in our imaginary file. And when we take a look this time, after adding the -t option, we can see that those pesky new lines have disappeared, which is exactly what we want. So hopefully this shows you just how powerful the read array command is. It has allowed us to even create an array with 100 different elements in basically just one line of code. Pretty cool, right? So that's it for this dose of superpowers. Let's go ahead and have a recap. In this video, you learned how to use the read array command to read the contents of a file into an array. And when you read from a file, each new line becomes a new element in the newly created array. And you also learned how to use the read array command and a new concept called process substitution to read the output of a command into an array by representing the output of that command as an imaginary file. And finally, you learned to always try and use the -t option where possible to strip away any pesky new line characters and prevent them from being included in the data in your array. So being able to use the read array command to create arrays on the fly from files and commands is an incredibly powerful skill, especially when you combine it with what you're going to learn in the next video. Up next, we're going to have a quick quiz to check that you've learned everything from the past 2 lectures, and from there, it's on to looking at how you can iterate over arrays like an assembly line using something called a for loop. You are minutes away from unlocking one of the most powerful abilities you can have in the bash shell, so I hope you're super excited. So good luck with the quiz, and I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be looking into how we can use for loops to iterate over arrays. For loops are a central part of any programming language, and the reason for this is simple. For loops allow you to leverage the structures of arrays and give you the powerful ability to perform the same thing over and over for each element in an array, just like on an assembly line. This gives you the ability, with just 1 or 2 lines of code, to batch process the same action maybe hundreds or even thousands of times in a uniform fashion for a given set of elements, which can be an incredibly useful thing to do. Perhaps you want to create an array of all the users on the system and modify a setting that requires each of them to change their password. Or maybe you want to create an array of all the servers on a network and ping each one to check that they're all still active. The pattern of storing useful information in arrays and then performing batch processing on them with a for loop is a cornerstone of programming, so hopefully this lecture is about to take your bash programming abilities to the next level. In this video, you're going to learn how to write a for loop and how to use them to iterate over arrays. And by the end of this video, you'll be able to use for loops to iterate over lists of elements that you write manually. You'll be able to use for loops to iterate over arrays. And you'll be able to use for loops with logic to perform different actions for each element of an array. So I hope you're excited, and let's jump into it. So what is a for loop? Well, a for loop iterates over a list of words or elements in an array and performs a set of commands for each element within that list, hence its name. The for loop will continue to run until there are no more elements for it to iterate over. You can think of this as kind of like batch processing on an assembly line. The same process is performed for each element on the assembly line. So let's see this in action. Let's create a script called forloop.sh and add in our shebang line. So as you may have guessed already, we start our for loop with the reserved word for. At this stage, if we were constructing a while loop, we would now specify some commands that we would test the exit code of to see if the command was successful or unsuccessful. The for loop, however, is different. With a for loop, the commands are run for every member of an array of elements. So if there are 100 elements in the array, then the commands inside the for loop will be run 100 times, once for each element of the array. On each iteration through the loop, a variable is updated to contain the element that we're currently working on. For this, I will just use element as the variable name, but you can use whatever you want here. Now we have to add the word in. The word in tells the shell that what follows this is the list of elements. So I can just put in first, second, and third here as our elements, each separated by a space. Then we terminate this with a semicolon so that the shell knows that we're finished with our list of elements. Next we add in the word do, just like we did with a while loop, to tell the shell that what follows is the commands that we want it to run. So now we can put in the commands that we want to run for each item in our list. Given that we've used element as our variable name, we can use that variable within our commands. So I'm going to run the command echo this is $element. And all this is going to do is it's just going to echo out the element in the list that we're currently working on, and it's going to allow us to see how the for loop is processing our list. Now we just end the for loop with the word done, and then we can save and close our script. So if we now give our script execution permissions, and then we run it, you can see that this has now echoed out a different line for each element of our list. The for loop uses the list of elements that we provided and iterates over it one element at a time, and it runs the set of commands that we provided it each time for each element until there are no more elements for it to iterate over. At that point, the for loop comes to an end. So now that we know how a for loop works and how to get it to work with a list that we kind of manually write in our scripts, we're now going to apply this with an array to have a for loop iterate over the elements of an array. So I'm going to create another script called fileCreator.sh and add in the shebang line at the top. The first thing we need to do here is to create an array. So to do this, we're going to use the readArray command, and remember to give it the -t option to remove any new line characters from the input we're going to provide it. Then we need to tell the readArray command to create an array called files, and this time we're going to ask it to read from a list of file names called files.txt. So now that we have our array, let's go ahead and add in our for loop. So now we need to give our for loops a variable name that we want to use to store each of the elements in our array. So because our array contains a list of files, the variable name file makes sense here. We can then type the word in, and then we need to give our for loop what we want it to iterate over. So this time, given that we want to use our array, we'll simply place a parameter expansion of our array here, again using the @ symbol in square brackets to make sure that we're expanding to all the elements of the array, because we want to process every element. You'll notice that we're also making sure to wrap our parameter expansion in double quotes to protect the elements of the array from word splitting. Then, as we did before, we're just going to add in a semicolon and the word do, and now we can move on to adding the commands that we want to run. So let's say that every time we get a file name, we want to create a file with that name. For this, we can just add in the command touch and then $file in double quotes, and that command will create the file. And then we can just end our for loop with the keyword done. So now if we save our script and then head back to the command line and give it execution permissions, I've actually already created a file that contains a list of files. So if I run cat files.txt, you can see that I've got a whole list of files here that I want created, and if I run ls, you can see that these files are not yet created in my current directory. So if I now run our script, and then run the ls command again, you can see that all of those files have now been created. Pretty awesome, right? Now before we wrap up, I'm going to modify this script a bit to demonstrate how you can combine your for loops with logic, which is a super useful thing to be able to do. So let's say we wanted to loop through our array and do some logical checks to see if the files already exist before we try to create them. To do this under the existing for loop, we can start by adding in an if statement to check if the file already exists. So if the file already exists, then we want to echo out to our users saying echo $file already exists. But if the file doesn't exist, then we want to use the touch command here to create the file and also tell the user that the file was created successfully. And then we just end our if statement with the keyword fee. So now if we save our script and head back to the command line, and then just delete the text files that we created before, and run our script again, you can see that this time we now have a confirmation for each file being created, and we can run ls to see that all these files do indeed now exist once again. If we run our script once again, you can see that now we're being told that the files already exist, which means we're not bothering to try and recreate them, seeing as they already exist, which is probably a better way to go about doing things. Pretty cool, right? You've now learned how you can batch process arrays using for loops, and how you can use logic within your for loops to perform different actions. In this video, you learned the syntax for a for loop, you learned how to write a for loop to have it iterate over a list of elements that you give it manually, and you learned how to use for loops to iterate over arrays that have been created using the readArray command. And finally, you learn how to use logic within your for loops to perform a different action based upon a certain logical check on each element. Now, because what you've learned here is so important to you unlocking the power of Bash, up next you're going to have a fun project to work on so that you can practice these new skills. And then, believe it or not, you've come to the end of yet another section of the course. So congratulations on your great progress. Alright, I hope you enjoy the project, and I'll see you in the next video for a section review. Hello there, you beautiful people. I hope you had loads of fun trying out this project. In this video, I'm going to walk you through the model solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's get started. So firstly, make sure that you've downloaded the urls.txt file, which you can get from the resources section for this video. I have mine stored here in my bash course folder, as you can see, and if I cat urls.txt, we can see that it contains a big list of URLs. Okay, so now I can create my array project script in Nano, and add in our shebang line. So now the first task is to create an array of URLs using the readarray command. As we learned in our lectures on the readarray command, to do this, all we have to do is type readarray, give it the T option to avoid any pesky new line characters, and give the readarray command the name of the array that we want to create, which in this case will be URLs. Then we simply need to tell our readarray command to read its standard input from our urls.txt file, like so. And that's it! This goes to show just how easy it is to create an array using the readarray command. So now the second step is where our for loop comes in. We're asked to iterate over this URLs array and run the curl command to pull headers from the list of URLs and save them into individual text files. As we know, we need to start our for loop using the for reserved word. We can then use URL as our variable because we're going through a list of URLs and each element is an individual URL. And then we can put the keyword in. So now we need to tell our for loop to go through all the elements of our array. To do this, we're going to open up a parameter expansion with the $curly brace syntax, give the array name, and then put a @ symbol inside square brackets. We're also going to wrap this in some double quotes to prevent our array elements from undergoing word splitting. We want them to be read through the for loop exactly how they appear in the array. Okay, now we enter semicolon and the word do, and we can now begin to add the commands that we want to run for each element of our array. In other words, for each URL. For this project, we're told to use the curl command with the --head option to get the header information from the web requests that we make to each of these URLs, and then save the header information for the websites into individual files. The first thing that we need to do here is to create the file name that we want for each file. Currently, we have the complete URL, including the www at the beginning and the .com at the end. But all we want is the actual name of the website. To do this, we can use the cut command to cut out the website name from the URL, and then save that in a variable using command substitution. So to start off with, I'm going to create the variable name, which in this case is called webname. So now what we need to do is we need to get the data we want to save in this variable using command substitution. So you'll probably have found in your independent research that in order for the cut command to work, we need to pipe the data we want cut into it. So firstly, we're going to echo out the URL variable, which gives us the current URL. We will then pipe this output into the cut command. So the way the cut command works is that it will split a given stream of data into columns, and each column is known as a field. Each field is separated by what is called a delimiter. With the cut command, we can use the -d option to set the delimiter, which separates the various fields. So if we put in -d here, and we give the d option a dot as an argument, the cut command will split the URL at the dots. So www will be the first field, the web page name will be the second field, and the com will be the third field. Having done this, we can then tell the cut command that we specifically want the second field by specifying that using the -f option and typing 2. So this cut command will break the URL down into 3 fields and give us just the second field as output, which is the website name. So next we need to get our header information, and we're going to use the curl command with the -- head option to achieve this. So we'll start by putting in curl -- head here. Then we need to give this command the URL we want it to operate on, so we're just going to use the $URL variable from our for loop in double quotes to do this. Then finally, we need to redirect the output of the curl command to a text file with the name of the URL. So we add in our redirection operator. There's no need to append here because we're creating a new file each time, so we'll just use one greater than sign. And then because we want the file names to be based on the website name, we're just going to use the $webname variable in double quotes, followed by .txt. Then we end our loop with the word done. So let's have a recap to see what we've just built. We use the readarray command to create an array of URLs from our urls.txt file, and we told our for loop to iterate through that array. Each element of that array, in other words each URL, will have its website name extracted by the cut command, and then it will be pinged with the curl command. And then the header information will be saved in uniquely named text files, one for each URL. Pretty epic, right? Okay, so now let's save our script and head back to the command line and give it the relevant permissions to run. Then if we run it, you can see that it is currently running. Now as you can see, pinging websites is not always the fastest process, so it can take a little while to run. Okay, so once it's done, we can run the ls command and see that we now have all these text files created, each with the URL as its name, as we requested it to do. And if I cat one of these files to see its contents, you can see that it does include the HTML header information that was required. So here we can see just how awesome using for loops with arrays in Bash can be. So I hope you had fun doing this project, and that it gives you a good idea of how arrays and for loops can be useful to you in your Bash scripting. You can download the official solution script for this project from the resources section of this video. And yes, you are now at the end of yet another section, so a massive congratulations to you. You've made absolutely astounding progress, and you should be really pleased with your efforts. In the next video, we're going to be going through a summary for this entire section to make sure that you've got everything, and then we're going to be moving on to discuss how to debug your Bash scripts. But I won't spoil too much here. Congratulations once again for completing this project, and I'll see you in the next video. Hello there, you beautiful person, and well done for completing this section of the course, which was all about how to work with arrays in Bash. You've made some really excellent progress, and you've learned a lot about how to create, edit, and iterate over arrays. You also learned how to use the readarray command to create large arrays easily from the contents of files and the outputs of commands. In this video, we're just going to have a quick recap of the key points in this section so that you can make sure that you're comfortable with everything before moving on. I've also put a cheat sheet summarising everything that we've covered in this section of the course in the resources section for this video, which you can download and refer to whenever you need to. So with all that said, let's have a recap. In this section, we looked at how to work with indexed arrays. Up until this point, we've been only working with variables, and you learned that the key difference is that variables can only store one piece of data at a time, whereas arrays can store multiple pieces of data at the same time. This makes arrays awesome tools for storing a lot of data in one place for batch processing. You learned that the syntax to create an array in Bash is simply the name of the array followed by an equals sign. Then each individual element that you want to add to the array is contained within a set of parentheses, and each element is separated by a space, as you can see in this example. It's very important to remember that in Bash, you use spaces to separate the elements of an array and not commas, which is different to how you might do arrays in other programming languages. You learned that each value in the array is called an element, and that each element has an individual index, and the indexes start from 0. We then looked at how you can expand an array. These expansions help us to extract the data that we want from an array without modifying the array itself. Because arrays are stored in parameters, just like every other piece of data in Bash, some of the expansions that we used are exactly the same as those we saw in the lecture on parameter expansion tricks in section 2 of the course, whereas some others are specific to arrays only. So with these expansions, we started off with putting the array name inside $curly brace syntax, which just gives us the first element of the array. We then saw how you can get all the elements in an array by using an @ symbol inside square brackets within the $curly brace syntax. We also looked at how you can add an exclamation mark here as the first character inside the $curly brace syntax to make the expansion give us back the appropriate index numbers rather than the elements themselves. We then moved on to looking at the offset syntax here, which allows us to start our expansion from a specified index instead of starting from index 0. We also had a look at negatives offsets, which can be used to define starting points by counting back from the end of the array rather than from the beginning. Then finally, we looked at customizing our expansions to use the offset and length values together, which allows us to start our expansion from a given index number using the offset until we have the amount of elements specified by the length. After we finished with expansions, we moved on to look at how you can modify existing arrays. You learned how to add new elements to the end of an array by typing the array name, then plus equals, and then a set of values that you want to add inside parentheses. You can add just one element, or if you want to add multiple, just make sure to separate each value with spaces inside the parentheses as shown here. We then looked into how you can remove a specific element from an array by using the unset command and specifying the array and the index number of the element you want to remove in square brackets. Just remember that this will affect the index numbering in the array, which can have consequences when you come to iterate over the array. Then finally, we looked at how to change the value of a specific element within the array by using the array name with the index number in square brackets, and then providing the value that we want to change this element to. So up to this point, all of the arrays that we've created and worked with were small arrays with only a few elements in them, which is fine for us to type out manually. But next we moved on to look at the read array command and how we can use this to easily create much bigger arrays, which would be quite a chore to type out ourselves. You learned that the read array command converts what it reads on its standard input stream into an array, hence its name. We looked at how the syntax to create an array from a file is to start with the read array command, state the name that we want for the array, and then simply redirect the file to the standard input with this redirection operator. Now, unless you have a particular reason, you should always make sure that you use the read array command's -t option to remove any trailing new lines from the end of each line of the file, so that the data you save in the array is just the raw data and is free from any formatting characters. So once we had a look at how to create arrays from the contents of files, we then looked into how to do the same with the output of commands. Just like when making read-while loops, you saw how to use process substitution to do this, because process substitution simply allows us to treat the output of a command as a file. The syntax for creating an array from a command is exactly the same as creating an array from a file, except you replace the file name with the process substitution syntax instead. It's very important when you're using the read array command to always remember about trailing new line characters, so there's a specific section in the cheat sheet here which discusses it. By default, when the read array command reads a file or a process substitution, it will save each entire line as a new array element, including the invisible new line character at the end of the line. This can cause issues when it comes to formatting, so it's always best to remove these new line characters. Therefore, I suggest that you always use the -t option when using the read array command to prevent any new line characters from being stored in your array's values, and thus it will help you avoid issues down the road. Then finally, in this section, you learned how to use a new concept called for loops to iterate over the arrays that you've created. You learned that a for loop iterates over a list of words or elements and performs a set of commands for each element within that list, hence the name. We looked at how for loops are an amazing tool when coupled with arrays that allow us to create assembly lines that we can use for batch processing of a lot of data. We started off by looking at the syntax for a for loop without an array, which we construct by first typing the reserved word for, and then followed by the variable name that we're going to use to store each element in the list we're going to provide, and then the word in. The word in is then followed by the list of words that you want to iterate over, and then this line is ended with a semicolon and the word do, so that the shell knows that what follows are the commands you want to run for each element in that list. You then add in the commands that you want to run, so this can be as many commands as you want, and these are just separated on their own lines. The for loop is then ended with the reserved word done. In our example, we just iterated over these 3 words and echoed them out in the statements that said this is first, this is second, and this is third. but essentially this example shows you how you can create your own lists and iterate over them. We then finished off by learning how to use for loops to iterate over arrays. The only difference here is that instead of explicitly listing the words or the numbers that we want to iterate over, like we did in the last example, we provide the for loop with the @simple expansion, which, as you know, expands to all the elements of the array. This will cause the for loop to iterate over all the elements of the array one by one. In our example script, we created an array with the readarray command from a file containing a list of files. We then iterated over this array with our for loop and checked with an if statement if the files existed, and if they did, we just echoed out the file name and confirmed that that file exists. If it didn't, then we created the file and echoed out that that file was created. So a massive congratulations once again. You've covered a whole lot of very useful stuff in this section, and now, at the end, you should be able to manually create indexed arrays, add, remove, update, and extract elements from indexed arrays, use the readarray command to easily generate indexed arrays from files and commands, use for loops to iterate over arrays, and use for loops with logic to perform different actions for each element of an array. And as I say, the cheat sheet is available in the resources section for this video, and it contains all the key points from this section of the course. So I have a very exciting announcement. You've now learned all the core parts of the Bash programming language, which is a massive, massive achievement. So many congratulations to you. Well done. Now, to beef up your skills even further, in the next section, we're going to be discussing debugging. In the next section, you're going to learn how to perform debugging on your scripts and also how to interpret and solve common error messages that are associated with Bash scripting. Now, this information will be very useful to you as you practice and master your new skills, so for all that debugging goodness, I'll see you in the next video. Hello there, you beautiful people, and welcome to this section of the course where we're going to be looking into the techniques that you can use to debug your Bash scripts. Once you've learned how to write scripts, understanding how to debug them and identify any errors in them is the next big step. So let's take a look at what we're going to cover in this section. In this section, we're going to be looking at how you can use a great program called shellcheck to check your scripts for errors. We're also going to be looking in depth into some more common errors, and we're going to look at what they mean and how you can resolve them. Then we're going to go over all the professional sources of documentation you have available to you when writing Bash scripts. By the end of this section, you'll be able to use the shellcheck program and interpret the feedback it provides to help you debug your scripts. You'll be able to interpret the structure of Bash's error messages. You'll be able to understand what common Bash error messages mean and how to fix them for yourself. You'll be able to determine the difference between internal and external commands. And you'll be able to determine the appropriate use cases for the help, man, and info commands, and you'll also be able to use each of them to get help when you're stuck. Feel free to download this section's cheat sheet from the resources section of this video so you can keep it handy in case you need it. And I hope you're super excited, so let's go ahead and get right into it. Hello there, you beautiful people, and welcome to this video where we're going to start taking a look at a very cool and useful debugging tool called shellcheck. Syntax mistakes are really easy to write when you're writing long Bash scripts, and they can often be difficult to see, especially when you're focused on writing the script's logic. Fortunately, there's a great tool called shellcheck that can check the syntax of a script that you've written to ensure that there aren't any syntax mistakes in it. What? No more hunting for missing brackets, quotes, and semicolons? That's right. Shellcheck is a Bash scripter's best friend. So in this video, you're going to learn how to use shellcheck to check scripts that you've written for syntax errors. And by the end of this video, you'll be able to interpret the feedback that shellcheck provides, and you'll be able to understand the limitations of shellcheck so that you can remain in control and not trust this great tool too blindly. So let's go ahead and get started. So in this course, we've been talking a lot about Bash syntax. And as we've learned, Bash has a very strict and often crazy looking syntax that scripts have to conform to for them to give the outcomes that you're wanting. If you get the syntax wrong, your scripts won't work in the way that you expect them to, if they even work at all. Similar to how a spell checker would pick up spelling and grammatical errors within a normal Word document like an essay, shellcheck picks up on subtle grammatical errors that you have made within your Bash scripts, which means that you can spend less time debugging and ripping your hair out. On top of this, shellcheck will also make recommendations for how your script can be made more streamlined and it will also point out potential compatibility issues with the commands that you've chosen to use. Now, shellcheck has both a web interface and a command line interface. We will be covering both in this video, but we're going to start with the web interface, which we can access by opening a browser and heading to www.shellcheck.net. For your convenience, I've put a link to shellcheck.net as well as a link to the official Shellcheck GitHub page in the resources section for this video. So as you can see, this is a very simple web page, and it basically consists of a large box that we can paste our scripts into for Shellcheck to give us feedback. We can also see a black box here, which is where Shellcheck will tell us of any problems that it finds. So let's give this a go now. I've set up some scripts that contain some common errors in them to demonstrate how useful Shellcheck is. You can find a copy of these scripts in the resources section for this video as well. The first script that I've set up is a modified version of our getExtension script from our read command project. The original script was error-free, but I've introduced a few errors for this video so that we have some errors to work with as an example. If I try and run this script now, you can see that I'm told that there is a syntax error on line 5. So if I put this script into Shellcheck, you can see that Shellcheck has identified a number of issues. As you can see, all of these issues are relating to the quoting within the script. So firstly, we're told that at line 3, I forgot to close my double quotes. So if I have a look at the end of this line, you can see that in fact I did forget to close the quotes after the semicolon here. Now if you remember, when we ran our script in the terminal, we were told that the error was at line 5, but Shellcheck has identified the issue at line 3. So why is there a discrepancy here? Well, this is because when you make a mistake, like missing a quote, this error effectively carries over to all the quotes that come later within the script. Bash was only able to tell us where it detected the error, which was line 5, but Shellcheck was smart enough to tell us where the error began, which was on line 3. So if I add this remaining double quote in there, you can see that now all the quoting issues that were there go away. Shellchecker's ability to tell you where an error starts, rather than just where it detected it, is really helpful, and it can save you a lot of debugging time, because at least you know you're looking in the right place. However, we're not done yet. Shellcheck has detected one more issue in this script. We're told here that to avoid globbing and word splitting issues, we should be wrapping our parameter expansions in double quotes, which we also know from our earlier lectures is good advice. Shellcheck has even recommended here what we could do to correct this. Shellcheck is telling us that we can actually just wrap all these variables in a single set of double quotes, instead of wrapping each expansion individually, which will make our script a bit neater. So if I do this now, you can see that all the errors are resolved, and Shellcheck says that this script now contains no errors. Cool, right? So the second script that I've set up for us is a modified version of our temperature converter script that we used in our lecture on command line options. Again, I've introduced a few errors here for us to fix that the original temperature converter script did not have. In the previous example, the main errors that we encountered with syntax were that we had forgotten to close some quotes. However, Shellcheck is far more powerful than just picking up these basic errors. In this script, I've included some errors that will allow me to demonstrate some really cool abilities that Shellcheck has to provide us with some more advanced feedback. Shellcheck understands the flow of the shell and how compound commands are structured, and is able to give us recommendations to both improve our scripts and also avoid potential issues. So if we look at our new script in the Shellcheck interface, you can see that to start with we're given an error about our case statement. The first line is telling us that we have a syntax error in our case statement. The second line is telling us that we have an error at line 8, which is the reserved word done. And we're told that the shell could not parse this case item. So the shell seems to think that this done keyword is a new case, but it's not supposed to be. Can you spot what might be causing this error? Pause the video for a minute now and see if you can confirm what's wrong at line 8 here, and then come back to see how you did. Did you spot it? The issue here is that our done reserved word is in the wrong place. I forgot to close off our case statement with the reserved word esac before closing the while loop with done. So if I remove done from here and move it to below esac, then you can now see that this has resolved the error. So as I highlighted when we were writing these constructs in earlier lectures, to avoid this type of error in our scripts, it's best practice to always close whatever construct you're creating immediately after you open it. This will ensure that you don't end up forgetting to close your constructs or end up putting your reserve words in the wrong places like I did here. Okay, shell check is still highlighting something else to us about this script. It's important to note that the issue we're seeing now did not appear before we fixed the previous issues. Because shell check is testing the script from the shell's perspective, it first needs all syntax errors to be resolved before it can see further into the script and provide advice on the script in general. So just bear that in mind that fixing one error may end up revealing other ones. Okay, so now shell check has given us some advice rather than an error. We know this because this is now highlighted in yellow instead of red. So shell check has identified that we've allowed our script to accept a T option, but there's no associated case to handle it. If we look into the script, you can see that I have added a T option at the top here, but I've not added any case to deal with it in the case statement. This just goes to show how effective shell check can be in providing advice on our scripts. It's even able to analyze this and tell us that we've forgotten to include one of our options in our case statement, which is super smart. So if I remove this T option here, because we don't need it, then you can see that this recommendation goes away and shell check tells us that there are no more issues detected. Okay, so now that you have a good idea about how to use shell check and how its web-based interface works, we're now going to take a look at how we can use shell check from the command line. That's right, you're about to get another dose of superpowers. So for this I'm using Ubuntu, so I'm just going to install shell check on Ubuntu now. If you're using a different system, then you can refer to the shell check GitHub page link that you can find in the resources section of this video, and the GitHub page will tell you the specific commands you need to run to install shell check on your system. To install shell check on Ubuntu, we just have to run the command sudo apt install shell check, and then follow through the installation like you normally would for any package. Now that shell check is installed, the easiest way to use shell check is simply by running the command shell check, followed by the script that you want to run it on. I'll just run this on the first script that we ran, which is getExtensions.sh. As you can see here, the output we get is very similar to what we saw on the web interface. The output has told us line by line what the errors or suggestions are for this particular script. This will work very similar to how the web interface works, except we can now run shell check on our scripts directly from the command line and no longer have to copy and paste our script contents into a browser. You may find this more convenient in general, and if you're using a system without a browser, for example a headless server, to implement and work on scripts, then this can come in really handy. So now that you've seen how useful shell check can be for you, it's important to understand that shell check does have one main limitation. We've seen that shell check is designed to check if your script contains syntax errors, and we've also seen shell check's amazing ability to identify potential issues with our scripts, such as missing cases in case statements, so no doubt shell check is a super smart program. However, the limitation is that, although shell check has the ability to assess the contents of a script, it's not able to detect issues with the environment that the script will be running in, which may also be a source of errors. For example, if your script requires a specific file or folder to exist in order for the script to work, shell check will not identify whether or not this file or folder actually exists. That's up to you to ensure within the script. Similarly, shell check does not know how permissions are set up on your system. So if you're writing a script that wants to create files or folders in a restricted folder that you don't have access to, shell check would not be checking whether you have the permissions required to do so. Again, that's something that's left up to you. Shell check also won't be able to tell you whether you need a certain package installed to run a certain command. Again, it would be up to you to ensure that you've installed the required packages to run the commands in your scripts. So, in summary, shell check will help you take care of the tiny niggling details which typically give rise to bugs. Ensuring that the script is set up in an appropriate environment to run correctly, however, is up to you. So I hope that this lecture has helped demonstrate to you the role that shell check can play in supporting you to write bash scripts. Although there are a few things that I've detailed which shell check isn't able to help you with, shell check does an amazing job of finding those irritating little syntax errors that can take a lot of time reading through your script again and again to try and identify, and hopefully you'll find shell check to be a very useful tool in your bash scripting toolkit moving forward. So in this video, you've learned how to use the shell check web and command line interfaces to check your scripts. You've learned how to interpret the output that shell check provides and to fix a script based on that output. And you've learned how to distinguish between the things shell check can help with and the things that it can't. So now that you're familiar with shell check and you've seen how to use it, up next we're going to have a project that will allow you to put all of this into practice. Then from there, we're going to be moving on to look at how error messages are structured and what some common error messages are and how you can resolve them. So for all that debugging goodness, I'll see you in the next video. Hello there you beautiful people, I hope you had loads of fun trying out this project. In this video, I'm going to walk you through the model solution step by step, and you can grab a copy of the official solution script from this video's resource section. So let's get started. Okay, so for this, I'm going to be using the web interface of ShellCheck to work through each of these scripts with you. So let's take a look at the first script in ShellChecker. Okay, so what this script does is decompress different archives. This script gives the user the opportunity to provide two options that do different things. One of these allows us to set a file name, the other does some other behavior. As we're just focused on the syntax for now, don't worry about the functionality of the options here, it's not really that important. Based on what option the user enters, there's a case statement that will check the file name provided against 3 different archive types, and if it matches, then we're going to run the relevant command to decompress that particular archive type. If the file name doesn't match one of these types, however, then we'll tell the user that the file provided is of an unknown type. Finally, we just randomly check if the system is Linux, and if it is, then we echo this statement here out. You know, because Linux. Okay, so as you can see, ShellChecker is telling us that the script has some errors, so let's work at resolving these now. Firstly, ShellChecker has identified an issue with our options. We have an error on line 5 that is telling us that we have an n option in the getOps command that is not handled by the case statement. Then we can see that on line 7, we also have a case that is not identified by the getOps command. So this is clearly a typo here where I've typed in the wrong option. I wanted to accept an n option in the case statement, but for some reason I gave a case for a v option. I'll just change the case to match an n here instead of a v, and now you can see that these two errors have gone away, so we've resolved this issue successfully. Okay, now we're told that our case statement does not handle invalid flags. So as we know, when handling case statements, it's always a good idea to create a default case to catch any unexpected options that the user might throw in. However, when we covered the getOps command, you learned that when the getOps command gets an unexpected option, it stores a literal question mark in the variable that is used to store options. So I'm going to add in a \question mark here, remembering to add the \, to ensure that the question mark gets interpreted literally, rather than just as a general globbing character. And then I'm just going to close the clause with a double semicolon. As we didn't provide a command, but just close the case immediately, this will simply make the script do nothing if it gets an unexpected option, which is completely reasonable. And when we take a look at our ShellChecker, we can see that this error has also gone away. Now we kind of have two errors which are referencing one another. We're told that the star.gz case is overriding the pattern star.tar.gz. As you learned during the case statements lecture, the cases are simply globbing patterns, and that they're handled by the shell from top to bottom. So because the star.gz pattern would match exactly the same files as the pattern star.tar.gz, we know that this wouldn't work because the star.gz pattern would already have matched anything that would match the more specific star.tar.gz, and therefore would render the star.tar.gz pattern ineffective. This will also cause us an issue because the command gzip-d is not the correct command if we want to compress a .tar.gz archive. So given that cases are processed sequentially from top to bottom, the solution to this is just to move the star.tar.gz case above the more general star.gz case, like so. Now you can see that this has resolved the error because the more specific star.tar.gz will first match everything ending in .tar.gz, and anything left will move on to the next case to be matched. So as a top tip, make sure you put your more specific cases at the top of your case statements and more general cases at the bottom, and you won't run into this issue. Okay, and now finally we have just one error remaining. This error states that we have a syntax error with our test here, which means that these values would never match. So this is less clear, but if you have a look at this, you can see that the syntax of our command substitution is wrong. I've accidentally added $2 at the beginning of it instead of just one. So if I just remove the extra $, you can see that this resolves the error, and now shell checker is telling us that our script no longer contains any errors. Great work. So now let's take a look at our second script in shell checker. Although we're just focused on syntax here and functionality isn't important for now, in case you're interested, this script is checking our .myconfig file to see whether we've set the backup option to true, which would enable the backup that this script is creating to run. If it's not, then our script echoes out an error message and then exits the script with an error code of 1, indicating an unsuccessful run. However, if the backup option is set in that file, then our backup line here will run to create a script backing up our home directory. Okay, so the first error that we have been advised of here is that we're recommended by shell checker to quote our grep pattern so that the shell won't interpret it differently. So let me do this now. Secondly, you can see that we've used a tilde expansion incorrectly here. As we mentioned in our lecture on expansions, tilde expansion cannot occur inside double quotes. So here, just like shell checker has advised us, we just need to use $home instead of the tilde, just like you learned earlier. Next, we have another quoting issue. Here we've used single quotes to quote this argument for the echo command, but we have a parameter expansion inside, which single quotes would prevent from running. So instead of using single quotes, we need to use double quotes, which we can see has solved the issue. Once again, shell checker has so helpfully told us the exact cause of a really subtle issue, as well as how to solve it. Okay, so finally we have one more issue. Shell checker is telling us that we have a Unicode quote here, which needs to be deleted and retyped. As you can see, these quotes look different to the ones that are surrounding $home on the same line. This is quite a common issue that you'll run into when writing shell scripts. Often we might copy and paste a command into our shell script, maybe from a web page that we're reading or when we're looking for help online, and in doing so we can often bring across the wrong form of quotes into our scripts. And this is what's happened here. Even though these are technically double quotes from an English language perspective, they're still perceived as a different character to bash than the double quotes it was expecting. And so bash, which is just a computer program at the end of the day, doesn't know how to read them. So if we follow shellcheck's guidance and just delete these quotes and retype the double quotes again manually, we can see that this resolves the issue. And that's it. There are now no remaining issues with our script, and according to shell checker, our script is now perfect. So I hope you had fun doing this project, and that it gives you a good idea of how powerful shell checker is and how much easier it can make your life when troubleshooting your scripts, even if they become as complicated as these ones. And as always, you can download the official solution scripts for the project from the resources section of this video. So up next, we're going to be giving you some more debugging independence by taking a look at some of the most common error messages that you'll come across when writing bash scripts, and we'll also cover how you can go about solving them. We're going to be focusing on the errors that shell checker won't be able to detect, which means that solving them is all up to us. So for all that debugging goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be looking at how bash error messages are structured. We're also going to be taking a look at some common error messages, what they mean, and how you can best resolve them. In this video, you're going to learn how to interpret the structure of error messages, and you're going to learn how to interpret and fix common types of errors that you might face when writing bash scripts. And by the end of this video, you'll be able to interpret the structure of error messages, you'll be able to understand what common error messages mean, and you'll be able to fix the most common errors that you'll come across when writing bash scripts. So let's go ahead and get started. As we start to take a look at error messages within bash, it is important firstly to understand how these error messages are structured. Error messages in bash tend to follow the same basic structure, and knowing this structure will help you to understand what the error message is telling you, so that you can better understand where the error is coming from and thus be more able to fix it. So if I run the command ls1234, which aims to list the contents of a non-existent folder called 1234, you can see that I get an error message. Here, this error message is in 3 parts, with each part being separated by a colon. The first part is the program name that gave the error. In this case, the program name is ls because the error is being produced by the ls command. The second section helps us to narrow down the problem. Sometimes this section just tells you the particular piece of text or the line that caused an issue. In this case, the ls command has been quite helpful and is telling us that the issue is related to our typing of 1234. In particular, the ls command cannot access 1234. Now we may be wondering why that is the case. Is it because we didn't give the script appropriate permissions and therefore it's not allowed to access 1234? Or is it because the file 1234 doesn't exist? Or is it some other reason? So the final part of the error message is where we get the reason why the error arose, which in this case was no such file or directory. So piecing this together, this error message is telling us that the command ls tried to access the folder 1234, but it couldn't, and the reason it couldn't is because that folder does not exist. So that's the way error messages in Bash are usually structured. The first piece of information is the command that failed. This is then followed by one, maybe two pieces of additional information that can help you narrow down what the issue may be. If you'd like to learn more about where this structure came from, you can refer to the link that I've provided to the GNU programming standards in the resources section of this video. So understanding error message structure is all well and good, but these error messages can still be quite cryptic. So what we're going to do now is we're going to go over some of the most common types of errors that you will encounter in your Bash scripts so that you can gain some confidence in tackling the most common issues that you're likely to face. So what are some of the common errors that we might face when writing Bash scripts? The most common errors are syntax errors that we make ourselves when writing scripts. So for example, let's say that we have this script called monday.sh, and if I run this script, we can see that I get a syntax error. Now the message that we receive here tells us that we have a syntax error on the line containing the if statement. Can you spot it? Well, here it is. With if statements, we have to leave a space after the if and before whatever command we provide as a condition. So if I edit the script in Nano, and add in the space, and then I save the script again and head back to the terminal, you can see that the script now runs perfectly. Syntax errors such as this are exactly the type of errors that shell check can be used very effectively to detect. So if you're having trouble with syntax errors, shell check is going to be your go-to tool. So besides syntax errors, what other errors might we face? Well, one of the main areas that we experience errors in our Bash scripts is around creating and accessing files. For example, one of the most common errors that you'll come across is the no such file or directory error that we just dealt with. As we saw, if I try to run ls on a folder that does not exist, you get this error. It's important to understand that in Linux and other Unix-derived systems, the file system does not draw a sharp distinction between files and folders, and this is why there is just one error message that mentions both. You will see this error message regardless of if you're trying to access a non-existent file or a non-existent folder. Of course, it's not only the ls command that produces this error. Any command that tries to access a file or folder which does not exist will produce a no such file or directory error. For example, if I try to run cat1234, then again I get exactly the same error because there's no file called 1234 and therefore we cannot read its contents with the cat command. Also, if we try to create a file within a folder that does not exist, for example by using the command touch1234/test, you can see that we also get the same error. If you're getting this type of error in your scripts, then there are three common causes. You've either mistyped the file path, or word splitting has interfered with how a file path is being interpreted, or you need to ensure that the files/folders that you want to work with actually exist before running your script. Okay, now another very common error is the file exists error, and it's directly the opposite of the one we've just seen. As the name suggests, the file exists error tells us that a file that we're currently trying to create already exists. For example, if I create the folder 1234, and then I try to create the same folder again, you can see that we get this error stating that this file already exists, and so we cannot create it again. Because scripts are designed to be run more than once, one of the best ways to go about avoiding errors like this is to modify the script logic so that the script checks whether or not the files we want to create already exist before it runs the commands that create them. As an example, if we want to create a directory like we do here, we could first use an if statement to check whether the directory already exists before we create it. Here I'm using the exclamation mark in the test command to mean not. So this if statement reads, if 1234 is not a directory, then run the make directory command to create it. A shorter, although perhaps less readable way of doing it would be to use the OR list operator that we learned before, like so. If you remember from our earlier discussion of the OR operator, the way the OR operator or the pipe operator works is that the second command will only run if the first test fails. So in this case, the mkdir command will only run if 1234 is not an existent directory. Okay, so the next common error that we're going to discuss is the permission denied error. This error simply means that you do not have the required permissions to do what you're currently trying to do, and it's normally experienced when you're trying to create or edit files or folders in restricted areas. For example, if I run touch/root/1234, you can see that I get this error. This is because I'm trying to create a file in the root user's home directory, but that folder is only modifiable by the system administrator. We can confirm this by running the ls-l command on the / directory, and we can see that the root folder which is in there is owned by the root user, who, as the owner of the directory, has all permissions to read, write and execute, whereas everyone else, including us, has no permissions at all. The most common cause of the permission denied error is when your script wanted to do something that was only allowed for the root user, but the script was run as a normal user instead. Most often, this error can be solved by putting the word sudo before the script name when you run it, which you can see works for us in this case. A similar error is the operation not permitted error. This is another error related to permissions and usually arises when you're trying to do something on the system that regular users are not allowed to do. For example, this error can arise when you're trying to kill a service that's being run by another user, and because you aren't the one running that service, you aren't permitted to stop it. The best solution to this type of error, as with all errors related to permissions, is to run your script as the root user by putting the word sudo before the script name like you saw earlier. This will solve the problem because the root user is always permitted to do whatever they want on the system. Then finally, another common error is the command not found error. This error simply means that the program you're trying to run is not installed on the system, or more correctly, could not be found on the system's path. So if I try to run the command non-existent now, you can see that I get the command not found error. In practice, there are multiple reasons why you can get this error. Most often it's due to a typo in the command name, so be sure to check your spelling whenever you see this error. You will also run into this error if you created a script and you placed it on your system's path, but you forgot to give that script execution permissions. So make sure you always give your scripts the appropriate execution permissions when you finish writing them, just like you've been learning in this course. Alright, great job! You should now have an understanding of how error messages are structured in Bash and how to interpret and tackle some of the most common error messages that you're likely to encounter. In this video, you learned that error messages are broken up into parts separated by colons. The first part is the program name that's causing the issue, and the remaining parts will help you narrow down what the issue is. You learned how to understand what common error messages mean, and you should now be able to tackle the no such file or directory errors, file exists errors, permission denied errors, operation not permitted errors, and command not found errors. So great job! Now armed with your knowledge of shell check and the techniques you've learned in this video, you should now feel much more confident when writing Bash scripts. Okay, so up next we're going to have a quick quiz on all that you've learned in this lecture to make sure that you've got everything, and then it's on to having a look at the different ways that you can get help when you're stuck and how you can find official documentation on commands. So good luck with the quiz, and for all that good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be taking a look at the different ways that you can find help when life is hard and you're struggling with your Bash scripts. In this video, you're going to learn how to use the man, help and info commands to find information about commands on your system. And by the end of this video, you'll be able to determine the difference between internal and external commands. You'll be able to determine the appropriate use cases for the help, man and info commands. And you'll be able to use each of these commands appropriately to find the information that you need to write your scripts. This is probably going to be a game changer, so let's go ahead and get started. As you learned earlier on in this course, a Bash script is essentially just a file that contains a series of commands. So, as the thinking goes, if you know how each of the commands works in your scripts, then you'll know how your script is working and thus be able to figure out any bugs. It is with this idea in mind that I want to present to you the 3 commands for getting information on how to use a given command in Bash. These are the man command, the help command, and the info command. Now before I demonstrate each of these commands, the first thing I want to point out is the distinction between internal and external commands. Internal commands are commands that are built into the Bash shell. Imagine a situation where you hypothetically only had Bash and you had no other software installed on your system. Internal commands are the commands that are built into the Bash shell itself and therefore would still be available to you to use. External commands, on the other hand, are commands that are external to Bash. As you can imagine, there are many more of these than the internal ones, but Bash can still run these external commands as long as they're accessible to it by being placed on the system's path. So, how do we know if the command that we're using is an internal or external command? Well, fortunately, Bash has an internal command called the type command for exactly this purpose. So if I go into the terminal and I run type-a cd, you can see that this tells me that the cd command is a shell built-in. In other words, it's an internal command. However, if I now run type-a ls, you can see that this tells me that the ls command is stored in a particular location on our file system, which means that it's not stored inside Bash and is therefore an external command. Okay, so with that distinction between internal and external commands made, I now want to introduce you to the 3 tools that you can use on the command line to get help. If you want to get some information on an internal command, you will want to use the help command. But if you're working with external commands, you'll want to use either the man command or the info command. We're going to cover all 3 in this video, but let's start with the help command. So to use the help command, you start by typing the word help, and follow that with the name of the command that you want to find help on, which in this example will be the cd command. You can see that we get quite a lot of information about the cd command, including a synopsis on how to use the command, along with a description of the command and a list of the various options for the cd command and what each of those options do. I bet you never knew there was so much to say about the cd command, huh? If we wanted to just get the description of the cd command, we could run the help command with the -d option, which you can see just gives us a short snippet of information about the cd command rather than the whole amount of documentation available. If we were already familiar with what the cd command does, but we just wanted to be reminded of how to use it, we can run the help command with the -s option, which you can see just gives us the usage information. You can actually see a full list of Bash's internal commands just by running the command help on the command line, which gives over 70 different results. The first 6 or so of these are just language constructs, but the rest are commands that you can investigate with the help command. And of course, because the help command is an internal command itself, you can see more of what the help command can do by running help. Okay, so now that we've covered how to get help on internal commands, let's transition now to external commands, which are the majority of the commands you're going to encounter. As I mentioned, when it comes to external commands, you have 2 primary ways of getting help. You have the man command and the info command. First up, we're going to discuss the man command, which is short for manual. The man command is the traditional Unix way of distributing documentation for commands. Manual pages, or man pages, are often short but detailed pages that summarize the key points on how to use a given command. The manual is pretty comprehensive, so pretty much any external command that you can think of will have a man page associated with it. As I said, the man command only works for external commands, so if we try to run man cd, you can see that we're told that there is no man page for the cd command. This is because the cd command is a Bash built-in command, an internal command in other words, and so only the help command can provide documentation for it. However, if we type man ls, you can see that we get a manual page for the ls command successfully because ls is an external command. So firstly, if we have a look at the man page, you can see that the man page is separated into some very clear sections. Firstly, we have a name section, which tells us the name of the command and gives us a short snippet of what the command does. In this case, the official role of the ls command is to list directory contents. Then we have a synopsis section which tells us how to type out the ls command. The synopsis section can get quite crazy to read, but it does follow some relatively simple rules. I've put a link in the resources section to a guide that will show you how these synopses are written if you'd like to know more. We then get a description section which tends to give very detailed information about the command and how it works. As you can see here, we have a full list of the options that the ls command can take, as well as a description of what each option does. Sometimes the information about options is broken up into its own section, but in this case the option information is kept up here in the description. And then, after this very long description section, we get more general information, such as what the exit code of the commands mean, who wrote the ls command, where to report bugs, and so on. To exit a man page, you just press Q on your keyboard and you get back to the terminal. The manual is a wonderful treasure trove of information, but because it's so massive, you're probably wondering, how can you actually search for what's in there? How can you find commands that do certain jobs that you want to do? Well, the man command comes with a very useful -K option that allows us to search the entire manual for pages that have a certain keyword or key phrase in the short description at the top of the man page. The -K here, by the way, is short for keyword. So let's say that I want a command that can compress files, but I'm not sure which command will work for what I want to do. I can run man-k and give it the keyword compress. Here you can see that this now lists out all of the man pages that contain the word compress in the short description at the top of the man page. Of course, your keywords do not have to be just one word. So if I search for the phrase list directory contents, making sure to wrap that phrase in double quotes so it's treated as one argument to the K option, you can see that we get back the ls command amongst others. We can do a more extensive search using the -K option, which will search the entire man page for a given keyword or phrase, not just the short description at the top like the lowercase k option does. So if we search for the word partition, you can see that the first command the search finds will open up in the manual. But if we quit this by pressing lowercase q, you can see that we get a prompt appear in our terminal. Unlike the small k option, which provided us with a full list, man is now showing us each page one at a time, and we can either press enter to view it, Control D to skip it and see the next one, or press Control C to quit this search prompt altogether. If we open this man page by pressing enter, and then we search for the word partition by first typing a /, typing the word partition and then pressing enter, you can see that the word partition does indeed appear inside this man page. The search technique that I just taught you by typing a /, then the keyword, then pressing enter, by the way, is available on any man page, not just when you use the -K option. So as you can see, the man command can be a very helpful and easy way to find commands that you might need when using Linux. If you want to read more about what the man command can do, and you have a thing for meta documentation, I encourage you to read the documentation for the man command by running man. So you'll most likely use the help and the man commands most often. However, there is also another command called info that also provides us with documentation on external commands. The info command opens what are called info pages, and these tend to be more detailed on average than man pages. You will often use the info command on an ad hoc basis when you've already checked the man page, but you still aren't quite clear about something and you will just want to see if there's a bit more official information available. So if I run info ls, you can see that this looks quite a bit different to a man page. Perhaps the biggest difference is that info pages have links in them. So if I come down here a bit in the page, you can see that there's a menu with various links on it. If I press enter while my cursor is hovering over the link called which files are listed, you can see that this takes us to a section of the documentation on the ls command that contains the options that control which files the ls command will show. Another cool thing about the info command is what happens if we head back to our terminal and just run info. The info command provides a sort of table of contents for all the core commands that you can run from your system, which you can dig into for more information. A key place to click is this core utils link here, which will open up a treasure trove of information on all the core commands on your system, each broken down by topic. For example, if we want to know about the commands that are related to disk usage, I can come down here to disk usage, press enter, and then be shown a list of all related commands to explore as I like. The info command is an amazing tool for exploration, and I hope you have a lot of fun using it to dig around and see what your system can do. So there you have it. You should now have a pretty good idea of how you can look up help and documentation on commands, and how you can figure out what tools are available at your disposal when writing bash scripts. When you combine this with all the information available to you through search engines and forums, there shouldn't be anything that you can't tackle if you put your mind to it. So in summary, in this video you've learned the distinction between internal and external commands. You learned how to use the type command to see whether a command is internal or external. You learned how to use the help command to get information on internal commands. You learned how to use the man command to get documentation on external commands. And you learned how to use the -k and -big K options with the man command to search the manual for relevant commands to use. You learned how to use the info command to get more detailed information on external commands. And you learned how to use the info command to browse a detailed system documentation that categorizes for you all the core commands that you're likely to use. Phew, that's a lot of stuff, but hopefully you've found it useful. I've also sprinkled some more bonus information in the cheat sheet about what we've learned in this video, so be sure to check that out if you're interested. Up next, you're going to have a quick quiz to make sure that you've got all the key points from this lecture, and then, believe it or not, we've come to the end of yet another section of the course. So many congratulations to you, you're doing amazingly, good luck with the quiz, and I'll see you in the next video for a section review. Hello there you beautiful person, and well done for completing this section of the course all about how to debug your scripts. You've made some excellent progress, and you've learned a lot about how to use shell check to identify syntax errors in your scripts, and also how to read and understand common error messages and how to fix them. In this video, we're just going to have a quick recap of the key points from this section so that you can make sure that you're comfortable with everything before moving on. I've also put a cheat sheet summarising everything that we've covered in this video of the course in the resources section for this video, which you can download and refer to whenever you need to. So with all that said, let's have a recap. In this section, we started by looking at the shell check program, which is such an amazing tool to help us identify errors in our scripts. You learned that you can use shell check both in a web interface that's available at www.shellcheck.net or by installing shell check to run on your system's command line. The commands to install and run shell check can be found here. We then had a look at the key strength of shell check, which is to check your scripts for syntax errors and to make suggestions for improvements in how your scripts are written. You learned that the shell check does have one major limitation, and that this is it doesn't detect issues with the environment that the script will be run in, such as if a program is installed or if you have the relevant permissions. We then moved on to discuss common errors that you can run into when writing bash scripts, as well as how to fix them. Remember that the key limitation of shell check is that it's not aware of the environment that the script is running in, so here we focus on errors that primarily relate to your system environment and the errors that shell check would not be able to pick up on. There's a table here of the common errors we covered, what they mean, and also how you can go about resolving them. Then, in the final lecture of this section, we took a look at all the great ways that you can find help with commands and programs on your Linux system. The first thing that you learned is that there are internal and external commands in bash. Internal commands are those that are built into the bash shell itself, whereas external commands are just executable files stored somewhere external to bash on the file system. You learned that to find out if a command is internal or external, you can use the type command with the A option and state the name of the command. As the cheat sheet says here, if you're dealing with internal commands, then the help command is going to be your best resource for getting help. If you're using an external command, however, then you can use the man command and the info command. In general, I recommend that you start off by using the man command, and then use the info command if you want more detailed information or you're looking for some extra information that wasn't covered in the man page. And as I say, the cheat sheet contains all the key information that we covered, so you have it to hand in case you ever need a quick refresher on how each of the commands work. So you've covered a whole lot of stuff in this section, and now, at the end, you should be able to use shell check and interpret the feedback that it provides, interpret the structure of error messages in bash, understand what common error messages mean and how to fix them, determine the difference between internal and external commands, and determine the appropriate use cases for the help, man, and info commands, as well as understand how to use them. And as I say, the cheat sheet is available in the resources section for this video, and it's going to contain all the key points from this section of the course. So a massive congratulations to you. You should now not only be familiar with all the core parts of Bash scripts, but also with how to debug your scripts once you've written them. Now I bet you're itching to create something truly substantial. So in the next section of the course, you're going to have your Bash scripting assignment. I won't spoil too much here, but I know you're going to love it. So for all that good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this section of the course where we're going to be looking into a whole load of amazing programs that you can use to automate your scripts. Up to this point, we've been building scripts and then running them manually. But what happens if you need a script to run all by itself at a specific time or a specific date, or even on a repeated schedule? Well, this is what we're going to be looking at in this section of the course. So let's take a look at what we're going to be covering. So we're going to start off by looking at the command to do the most basic type of scheduling of commands and scripts. We're then going to look at a whole load of different things you can do with the cron service, which is a truly amazing way of automating your scripts, especially if you work in a server environment. After that, we're going to look at the anacron service, which takes automation to a whole new level, and it's great for people who want to automate things from their laptops or PCs. By the end of this video, you'll be able to schedule jobs using the command and manage these jobs. You'll be able to use the cron service to schedule your scripts to run automatically at regular scheduled times. You'll be able to navigate the cron tab guru website and use it to create well-formed cron expressions. You'll be able to understand the different cron directories that your system makes available, and you'll be able to use them to run your scripts at common times, and even create cron directories of your own. You'll be able to explain how anacron works and how to use it to guarantee the execution of your automated scripts. And you'll be able to explain the respective limitations of cron and anacron so that you can make educated decisions about when it's appropriate to use each one. So feel free to download this section's cheat sheet from the resources section of this video so you can keep it handy in case you need it. And we've got a whole lot of exciting things to cover, so let's go ahead and get right into it. Hello there you beautiful people, and welcome to this video where we're going to be learning about our first command scheduling tool, which is the command. In this video, you're going to learn how to use the command to schedule tasks, and by the end of this video, you'll be able to schedule jobs using the command, you'll be able to manage jobs that are scheduled by the command, and you'll be able to describe the limitations of the command. So let's go ahead and get started. The command offers what is perhaps the most basic way to go about scheduling tasks in Linux. The command does not come with Ubuntu by default, so we're going to need to install it, which we can simply do by running sudo apt install and then letting that command run. Okay, so now that the command is installed, we can start using it. The command runs using what is known in Linux as a daemon service. Building on the idea of an invisible spirit or ghost, a daemon in Linux is a type of program that runs invisibly in the background, doing things behind the scenes. The daemon, or ATD for short, continually runs in the background, checking your list of scheduled jobs against the current time, and when the current time matches up with the scheduled time of a job, that job is executed. To check if the daemon is running, on Ubuntu we can run service ATD status, which says that the daemon is active and running on my system. If it's not running on your system, you can just run sudo service ATD start in order to get it running. Likewise, if you ever want to stop the service, you can just run sudo service ATD stop, but I'll leave it running for now. You can also use the restart keyword if you ever want to restart the service for whatever reason. Okay, great, so we have the ATD service running, which means that we're all set up to use the command. Okay, so you use the command by first typing the word and then follow that with the time that you want the command to run. So let's say I want to run a script at 9:30 AM. I could just type 9:30 AM here, and then press enter. Now that we've entered the time, we can see that a prompt has opened. The commands we enter into this prompt will be bundled together as a single job that will run all the commands that we enter at the time that we're scheduled. The first thing to know is that, as we're told here, the commands that we enter into this prompt will be executed using the sh shell. If you remember from the very start of the course, the sh or the bourne shell is an older precursor to the bash or the bourne again shell. I'll show you how to make it so the at command will run jobs using the bash shell in a moment, but for now let's just continue setting up a simple job. So in here, let's say we wanted this job to run the command echo hello world. I'd simply just type that command in and press enter. Now you can see that the at prompt has dropped down to a new line. This is so you can add in as many commands as you want to run for a given job. To end the prompt and end the list of commands that are included in this job, you just press Ctrl and D. And as you can see, the at prompt is now closed. We now have a message on the screen that tells us that we've created a job which has been given a specific ID and will run at the next available date at 9:30 AM. If the time we scheduled for the job has already passed, then at is smart enough to know that we mean that time the next day. So if we ran this command at 8 AM, for example, then the at command would set this job to run at 9:30 AM today, because 9:30 AM won't have happened yet. However, if it's 2 PM when I run this command, then the at command will schedule the job to run at the next available 9:30 AM time point, which would be 9:30 AM tomorrow. At also provides us with various mechanisms to manage the jobs that we've scheduled. For example, to list all the jobs that we've scheduled, we can run @-l. Here we can see the jobs that our @daemon is scheduled to run, and you can see the one that we've just created listed here as well. On each line, we're given the ID number for the job, followed by when this job is scheduled to run. What follows the time information is the queue name that the job is a part of. At allows you to add jobs to different queues, which is useful for parallel processing of tasks. The queue name that this job is a part of is just called A, which is the default queue for the at command. Check out the at man page for more information on using queues with the at command if you're interested. Then finally, we see the user that the job will be run as, which in this case will be my user account. If we want to remove this job, we can give the at command the R option and run @-r followed by the job ID. Now if we run @-l again, you can now see that there is no output because there are no longer any scheduled commands or scripts. Okay, so this is all well and good, but at the moment we're just running individual commands. How can we use the at command to schedule scripts? Well, to do this, we just have to give the at command the -f option, which allows you to specify a script file to be run for the job. So let's create a script called @script, and then add in our shebang line. By the way, the script can be called whatever you want. It doesn't have to be called @script, but I've called it @script here because that makes most sense for this example. By adding our shebang line, we're ensuring that this script gets run with the bash shell rather than the older sh shell that the at command runs with by default. Then we can just add in the commands make directory @dir and touch @dir/file1to100.txt. And now we have a script that will create a folder called @dir and add 100 empty files to it. So the time is now 10 AM. If I run ls, then you can see that I currently do not have a folder called @dir. If I run the script and say at 10:05 AM -f @script, then this script that we've just created should run at 10:05 AM. I want you to notice how readable the at command is. It pretty much just says at 10:05 AM run the @script file. Okay, now if we run @-l, we can see that this has in fact been added to the job queue. So let's wait a bit and see what happens. Okay, it's now 10:06, and if I run ls again, you can see that I have a folder called @dir, and if I ls inside of it, we can see that the 100 files have been created too, which shows that the script that we set up to run at 10:05 did in fact run. Awesome. So we had a look at how we can set a command to run at a specific time, but there are many other ways that you can express the scheduled time with the at command. For example, alongside the time, we can also set the day that we want the script to run. So if you run at 9 AM, Monday -f @script, then the command will run on the next Monday at 9 AM, which we can confirm by running @-l. It's worth noting here that according to the man page, the time must come before the date when using the at command. So you would write 9 AM Monday like we have here, not Monday at 9 AM. You can also use various date formats. All the possible date formats are detailed in the man page, but I'll show you the most common ones now. For those of you who like the month to come first in the date, we can run exactly the same command again, but instead of Monday, we can put 12/23/2021, and that will run the script on the 23rd of December 2021. For those of you who like the day of the month to come first in the date, you can get the same result by putting the date as 23.12.2021, where we're using dots here instead of slashes. And if we run @-l again, we can see that we now have two commands scheduled to run on the 23rd of December 2021 at 9 AM. Now there are a few other cool tricks and shorthands with the command which can make scheduling things very easy. Firstly, we can use simple words like at 9 AM tomorrow -f @script to schedule something for 9 AM tomorrow. We can also do at 9 AM next week, and to schedule something at 9 AM exactly 7 days from now. And if I run @-l again, you can see that I now have two more scheduled jobs, one at 9 AM with tomorrow's date, and one at 9 AM in a week's time. Now the final trick I want to show you is how to use the now keyword. With the command, you can use the word now, followed by a plus, and then you can give some details to set things to run a specific period after the current moment in time. So you could run at now plus 5 minutes, or at now plus 2 days, to run the script at 5 minutes from now, or to run the script 2 days from now, respectively. So from all of this, you can see that the command can be a very helpful tool. It's going to enable you to quickly and easily schedule scripts to run at pre-scheduled times and dates. There are two limitations of the command though that I want to point out to you. The first is that the command will only execute jobs if your PC is turned on at the time. If your PC is off when a given job is scheduled to run, then that job will fail to execute and the command won't be able to recover it after the fact. This makes the command more suitable for use on servers that are always on, rather than on laptops that tend to be turned on and off frequently. The second limitation is that there's no way to set up recurring jobs with the command. You can't schedule a job to run every Monday at 9 AM, or every first day of the month, for example. Aside from these limitations, however, the command is a great tool for quickly scheduling one-off tasks. Okay, so that's it for our coverage of the command. I recommend you play around with the command for yourself. It can be a lot of fun. For now, however, let's have a recap. In this video, you learned how to install the command on your system and start the daemon, ATD. You learned how to use the command to schedule commands or scripts to run at specific times or specific dates. You learned how to manage jobs with the command's -l and -r options. And you learned the two key limitations of the command. So the command is great and a really simple way to schedule one-off jobs to run at specific points in the future. But one of its limitations is that it doesn't allow us to schedule jobs on a recurring basis, and this is where our next command comes in. In the next video, I'm going to introduce you to the cron command, which allows you to set up powerful recurring schedules for your bash scripts, which makes it an absolute must-have tool for any system administrator or automation enthusiast. So for all that great stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where you're going to be expanding your automation abilities by learning how to use the cron command, which deserves pride and place in the toolkit of any automation enthusiast and system administrator. In this video, you're going to learn how to use the cron service to schedule your scripts to run on a repeated schedule. By the end of this video, you'll be able to explain what cron is and how it works, and you'll be able to use cron tabs to schedule your scripts to run automatically at regular scheduled times. So let's go ahead and get started. So in the last video, we started off our discussion of scheduling by looking at the command, which is a very easy way to schedule a script to run once at some specified time in the future. But what if you want to run that script on a repetitive basis? What if you want to do a weekly backup, for example, or get a status report for your servers every day at 9 AM sharp? Well, this is where cron comes in. Like the command, cron works by running a daemon service that is continually running in the background to check whether it's time to run a pre-scheduled job, and if it is, then it runs it. So if we run service cron status, you can see that the cron service is active and running on my system. If it isn't running on your system, you can simply run sudo service cron start, and that will start the process for you. The way cron works is by providing each user with what is known as their own personal cron table, or cron tab for short. A cron tab is basically a text file that contains a table of which commands the user wants cron to run, and at what times they want to run them. Think of each user's cron tab as their own personal timetable for cron. To edit the cron tab for your current user account, you just run cron tab -e. The E option here stands for edit. Using cron tab -e is always the best way to edit your cron tab. Because a cron tab is just a text file, it is possible to just edit the file by opening it directly using a text editor like Nano or Vim. But using the cron tab -e command has the added benefit of automatically restarting the cron service when you finish working on the file, so that whatever changes you make are immediately picked up by cron, which prevents errors and makes sure that every change you make works immediately. If this is your first time using the cron tab -e command, then you'll be first asked which editor you'd like to use to edit the file. Nano is a pretty easy editor, so if we just type in 1, you can see that we're now editing the cron tab using Nano. So what you'll probably notice first is a big bunch of commented lines which provide some instructions on how cron tabs work. Like every table, a cron tab is broken down into rows, and each row contains the scheduling information for a single command or script. In other words, every row that you add into your cron tab will be treated as a separate scheduled job. Furthermore, each of these rows is broken down into 6 columns. The first 5 columns are scheduling information, and they represent the minute, the hour, the day of the month, and the day of the week that you would like the job to run at. So as you can see, cron affords you a lot of control here. The 6th and final column is the command or script that we want to be run at that scheduled time. So let's create a script that we can use to see how cron works. I'm going to call mine cron script, but you can call yours whatever you want. And then let's add in our shebang line. Now to demonstrate cron well, I'm going to add in the date command and then redirect the output to a file called cronoutput.txt in my home directory. Again, the file name doesn't matter here, I'm just using this file name as an example. So every time this task is run, it will append the current date and time to a new line of the cronoutput.txt file. Okay, so let's save our script and then head back to the command line to give our script execution permissions. Okay, so now we've got a script to work with, let's reopen our cron tab using cron tab -e. So let's imagine that we want our script to run every minute of every day all year round. It is a very important script after all. As we're adding a new job, we need to add a new line to our cron tab. The first column of the row is for the minutes of the hour that we want the script to run on. For example, if we wanted the script to run at 15 minutes past the hour, so at times like 12:15, 1:15 and so on, we would just need to put a 15 here. Given that we want the command to run every minute, rather than at a particular minute of each hour, we simply add in a star here, which is used in cron tabs to represent all of the options that are valid for that particular column. Given that this is the minutes column, we're telling cron that we want to run this script every minute that's available. We're now going to move on to the hours column. In cron, all of your columns need to be separated by some space, but cron doesn't really care how much, as long as there is some. I'm just going to put in a few spaces here, but feel free to space things out and align things with as many spaces or tabs as you like. And don't worry, you don't need to be consistent here. As I said, the next column is for the hours, and again we could put any number here to say which hour we want it to run on. These hours are based on the 24-hour clock, and therefore it can be any number from 0 to 23. If I put, for example, a 2 here, because we've put a star in the minutes column, our script would run for every minute between 2 AM and 3 AM. Likewise, if I put a 14 here, our script would run for every minute between 2 PM and 3 PM, and so on. Now because we're wanting this particular job to run every minute of every hour, then we can just again enter a star here to represent every hour. The next column is for the day of the month. A 1 here would be for the first day of the month, a 2 here would be for the second day of the month, and so on. Again, in our case, we want to have this run on every single day of the month, so again, we will enter a star here. The next column is the month number. So this can be anything from 1 for January to 12 for December. We can also represent months using 3-letter month names instead of numbers. For example, we could enter JAN for January, or MAR for March, and so on. making sure to write them in uppercase. So again, in our example, we want this to run every single month, so we can just add a star in this column as well. Now the final column is the day of the week. This can be written using the numbers from 0 to 6, where 0 is Monday and 6 would be Sunday. Again, we can also use 3-letter day names instead, so we could type MON for Monday or SAT for Saturday, and the same goes for the other days of the week. Just make sure to write them in all uppercase. As you can see, there's a bit of flexibility in the ways that you can enter values in the cron tab columns. For example, all columns allow you to enter commas to express multiple values at once. For example, you could put a comma in between the Monday and the Saturday, and as long as there are no spaces around the comma, this will represent both Monday and Saturday together. We can also use hyphens in our cron columns to represent ranges of values. So if we typed Monday-Saturday, this will represent all days between Monday and Saturday inclusively. As I said, commas and hyphens apply to the other fields as well, not just the day column, and there are other ways to enter values as well, which you'll be exposed to in the next video. For now, however, we're just going to add in a star here because we want this to run on any day of the week. Okay, now all we have to do is add in the command that we want to run. In our case, we just want to run our script. So in the final column, we just need to add in ~bashcourse/cronscript.sh to tell cron that we want to run the cron script file from our bash course directory. So what we have here is a new cron tab entry that will run our cron script file that's in our home directory every minute of every hour, every day, of every month, on any day of the week. So if I save this script and then head back to our command line and wait for a minute, and then I cat open the cron output.txt file, you can see that we've started to get lines with the output of the date command written into this file. If I wait a couple of minutes more, and then I cat cron output.txt again, you can see that there are now additional lines in this file, which shows that our script is continuing to run automatically every minute. At times, you might be writing bash scripts that require administrative privileges, and putting these in your user's cron tab would give you errors because you as a regular user do not have the relevant privileges in order to run those scripts. Luckily, there is a system-wide cron tab that enables us to add lines in and specify which user we want to run them. So if I run sudo nano /etc/cron tab, you can see that this opens up a cron tab which looks very similar to the one that we've just been working with. The only difference here is that you get another column which allows you to specify which user you want to run the cron job, as you can see from the lines that are already here. So if you need to run your script as root, you can simply add the line in here instead of putting it in your user's cron tab, and just make sure to specify the user root in the user column like it's done here. However, because we did not use the cron tab command, whenever we edit this file, we'll need to restart the cron service for these changes to take effect. We can do this by going back to our terminal and running the command sudo service cron restart. Okay, so that's it for our initial introduction to cron. Before wrapping up, I just want to mention that cron has the same limitation as the @ command, in that if your PC is turned off when a particular job is supposed to run, then that job won't run and cron won't be able to recover it later, which might cause you some problems. Therefore, like the @ command, cron is also best used in an always-on server environment rather than on your personal laptops. But don't worry, very soon we're going to be seeing a command that will work on personal laptops too. Okay, with that said, it's time to celebrate. You now know how to use the cron service to schedule your scripts to run on a regular cycle and put tasks on autopilot, which is a great achievement, so congratulations! In this video, you learned how to check whether or not the cron service is running. You learned how a cron tab is structured. You learned how to edit your cron tab to schedule scripts to run repeatedly at specific intervals. And you learned how to edit the system-wide cron tab to schedule scripts to run as the root user. An important part of using cron is being able to correctly express when you want things to happen, and to also test that what you expect will actually happen before you simply set it and forget it. So up next, you can have a quick quiz to make sure you've got everything so far, and then I'm going to give you an introduction to a great tool called Cron Tab Guru, and walk you through how you can use it to test your cron tab expressions before you set them loose. So for all that guru goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where I'm going to be taking you on a tour of a great tool called crontab Guru. Crontab expressions can be a little strange at first, so in this video you're going to learn how to use crontab Guru to create cron expressions for your crontabs. And by the end of the video, you'll be able to navigate the crontab Guru website and use crontab Guru to create cron expressions that will schedule jobs whenever you want. So let's go ahead and get started. Okay, so here's the homepage of crontab Guru at the website crontab.guru. The first thing that you'll see is that we're told that this is a quick and simple editor for cron schedule expressions, and it's made by a company called Croniter. And in my experience, crontab Guru is definitely quick and simple to use. Okay, so this first section of the page is what we use to write out our cron expressions and check their meaning. Here you can see that we have 5, 4, star, 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 and crontab Guru is telling us that that means that if we gave a cron job this expression, that job would run at 4:05 AM. So this box here is where we place our expressions and develop them, and the bit in quotes at the top here tells us in human terms what our expression means. All we have to do is make sure that our expressions mean what we want them to mean, and then we can copy and paste them into our cron tab, add the command that we want to run, and voila! We now have a new cron job scheduled. You can see here between these two boxes that we have a section called Next. This tells us the time that this expression would next run. If we click the word Next, you can see that it also drops down to show us when this expression would run quite a way into the future. Below the box where we place our expressions, we can see the names of each of the columns in our cron expression. We have a column for the minute, hour, day of the month, and day of the week. If I change the day of the week here to 4, you can see that the expression immediately updates to at 4:05 on Thursday. So as you can see, we're always kept up to date with what our crontab expression means in a human readable way. Then below this, we have a great description of what options are available to us for each column. If I click on minute, you can see that I have the option to enter an asterisk to represent all possible values for that column. I could also enter a comma to add multiple separate and distinct values in the same column. So I could enter 5,8 to represent minutes 5 and 8. We also have the dash to represent a range of values. So I could enter 5-10, which would represent every minute from 5 to 10. We can also enter a / to do something called a step. And this allows us to do things like */5, which will run every 5 minutes. We can also do things like 15/5, which will cause this expression to run every 5 minutes, starting from minute 15. But you can see that crontab Guru gives us a smart warning this time that this is not a standard cron expression, and although it may work, it isn't guaranteed to work on all cron versions. So that's pretty cool too. We can also see the full allowable values for this column, which as you can see, for the minutes column, we can enter any value from 0 to 59. If I click on the hour column, you can see that our options get limited to 0 to 23, which are the hours on a 24-hour clock. If we put an asterisk or star in any column, it's as if we were entering all the possible values for that column. So it's great that crontab Guru gives us an explicit list of what those values are for each column. One more nice feature in this section is the random button up here. As you can see, when I click it, it generates a random cron expression each time. This can be helpful if you're not quite sure what you're looking for, and it's also useful for getting used to the crontab language, as you can see a variety of expressions and what they mean rather quickly. So now that we've dealt with the main page, there are also quite a few helpful resources that are provided on this site beyond just the cron expressions tool. So down the bottom here, firstly we have a link to examples, and as you can see this comes with a great collection of ready-made examples or recipes if you like that you might want to use. So let's say that I decided that I want to run a cron job every 30 minutes. I can come to this page and select every 30 minutes here, and I'll get a working expression that I can use to run a cron job every 30 minutes. There are many great examples on that page, so I encourage you to check them out. The next reference is to a page with some really key tips on using cron. The first tip tells us some information about how the day of the month and the day of the week fields work together, because it's not quite obvious. As it says here, we can note that if we specify numbers in these fields, they form what is called a union, meaning that they will do both. So in this example, the cron tab will run on Mondays and on the third day of the month. If we instead use a star as the first character in these fields, they create what's called an intersection. So in this example, */2 and star would result in the cron job running on the second day of the month, only if it's also on a Monday, so an intersection. The next tip tells us that we're strongly recommended to ensure that our servers that run cron use the UTC time zone. There's also a useful link on this page as to why, and it goes into quite a lot of detail. Just note for now that cron doesn't really cope with daylight savings very well, and it can really mess up the scheduling of your cron jobs. So they advise that it's a good idea to avoid this by using UTC, which is a standard time zone and doesn't have any daylight savings in it. The fourth tip here, we're told to stay away from using the shortcut @reboot, which causes a cron job to run when the system boots up. Again, there's a nice resource provided here that explains the bugs, but basically it's because the boot process is a very complex process. And during that process, many different things get run at different times, and often the cron service might start running before other services or even file systems are available. And so when your commands or scripts get run by cron, it's possible that what they require to run is not available yet, and thus your scripts end up failing. The last two tips here are about implementing more difficult scheduling by either combining cron expressions or using another program called mcron. There are resources that you can look into in more detail if you want to perform more complex scheduling with cron, or if you want to learn how the mcron command works and how to use it to schedule jobs as well. There's also a great link here to another resource which has some best practices for using cron, which can be really helpful to read, and it can give you some additional really useful pointers on how to use cron better. So up next we have a link to the cron tab man page. Now this is exactly the same as what you'd get if you were to run the command man cron tab in your terminal, and provides all the information about how cron tabs work as provided by the official documentation. Finally, there are some links to cron monitoring and uptime monitoring, which are great tools developed by Croniter that help you keep track of your cron jobs and detect if something isn't working. One of the big challenges with cron is that it doesn't report well when something fails or doesn't work. So if you're running an environment where these cron jobs are really essential, like a server, then although I'm not affiliated with Croniter in any way, these tools could be quite helpful to you. There's also a link here to the cron reference, which if I click on it, you can see there's another set of resources with some good information on the cron service and how it all works. We've already covered a lot of this in the course, but it's definitely worth going through any resources that are available to make sure that your knowledge is as broad as possible. Okay, cool. So hopefully now you can see what an amazing tool crontab guru is and how easy it is to use when you're working with cron expressions. So in this video, you've learned how to navigate the crontab guru website. You've learned how to use crontab guru to create cron expressions, as well as how to use the recipes and examples that are provided for common expressions that you're likely to need. And you've seen how you can access some useful resources around the cron service that you can use to expand your knowledge even further. So after this, it's time for you now to put all this talk about cron expressions into practice. Up next, you're going to have a quiz where you can use crontab guru to help you construct the correct cron expression for each scenario. And then we're going to be looking at cron directories, what they are, how to use them, and we're also going to create some of our own. So for all that great stuff, I'll see you in the next video. Hello there, you beautiful people, and welcome to this video where we're going to be having a look at cron directories. Cron directories are another feature of cron, and they make running scripts periodically a whole lot easier. In this video, you're going to learn what cron directories are, where the cron directories are located, and how to use them. By the end of this video, you'll be able to understand the different cron directories that your system makes available, use cron directories to run your scripts at common times, and create your own cron directories to bundle groups of scripts together to run whenever you want. So let's go ahead and get started. So what are cron directories? Well, cron directories are folders on your system where you can place all of the scripts that you want to run at a particular frequency. For example, there's a cron directory that will run the script it contains every hour, there's one that will run its contents every day, and there are those that will run their contents every week and even every month. The cron directories are stored in the /etc directory of the Linux operating system. We can take a look at them by running ls/etc to list out all of the contents of the etc directory, and then we can use the grep command with pipe grep cron to only show us the files and directories that contain the word cron. So you can see here that in our etc directory there are quite a number of cron folders. We have the cron.d directory, which typically you won't touch, and then we have our 4 periodic directories. There's cron.daily, cron.hourly, cron.weekly, and cron.monthly. As their names suggest, they run scripts that are contained within them either hourly, daily, weekly, or monthly. Cron directories are great for those jobs that you want to happen on a predictable frequency, but you don't really care what specific time or day that it gets done. For example, let's say that you wanted a certain script to be run once a month. All you need to do is pop your script inside the monthly folder and ensure that it's executable, and that's it. You can then rest assured that cron will run your scripts once a month without you needing to write an explicit cron tab record for that particular script. Okay, so we understand that each of these folders is set to run all the scripts contained within them at a particular schedule. So where is the schedule set? Well, those times are stored in the /etc/cron tab file, which we can take a look at now. Because it's a system config file, we need to be the root user to access it, so we type sudo nano/etc/cron tab. Here at the bottom of the cron tab, you can see that there are 4 lines relating to our periodic cron directories. You can see a line for cron.hourly, cron.daily, cron.weekly, and cron.monthly. If we look at the expression for the cron.hourly folder, you can see that these are set up to run on the 17th minute of every hour of every day. We then have the cron.daily directory, which you can see here from the expression is set up to run on the 25th minute of the 6th hour of every day. So this will run at 6:25 AM every single day. Next is the weekly cron directory, and as you can see the expression is set up to run on the 47th minute of the 6th hour on day 7. So this will run at 6:47 AM on a Sunday. As a side note, notice here that the system is using a 7 to represent Sunday instead of using a 0 like we did in previous lectures. Using a 7 to represent Sunday isn't compatible with all versions of cron, and so as a general practice it's better to use a 0 to represent Sunday instead of a 7 so that you don't run into any unnecessary compatibility issues. Then finally we have the monthly cron directory. This expression is set up to run on the 52nd minute of the 6th hour of the 1st of each month. So this will run at 6:52 AM on the 1st of every single month. Now each of these scheduled times seems quite random, and they probably are to be fair, but hey, they work. And if we look over to the command section, we can see that each of the cron tab entries works by using the run parts command. The run parts command is designed to run every executable script in a given folder. So in this cron tab file, all we're doing is providing a set of time points for when the run parts command should run and process all of the executable scripts that we place inside each of our cron directories. Pretty simple, right? It's worth pointing out, however, that these last 3 rows for the daily, weekly, and monthly scripts do first use a test command to check if a program called anacron is installed and executable. You'll be learning about anacron in the next video, but suffice it to say here that anacron has some significant advantages over regular cron. So what these lines are saying is that if anacron is installed, then do nothing because anacron will take care of it, but if not, then use run parts to process the folders instead. Okay, so let's see this in practice. Let's say that we want our backup script to run once a week, just like we had in our cron project. Well, instead of setting up a cron tab entry for the script like we did in the project, all we had to do was drop the backup script into the cron.weekly directory. So for example, we could have just used this copy command to copy the bash script into the cron.weekly directory. Note that because the cron directories are inside the /etc folder, which is used for system-wide configuration files, we have to start our copy command here with the sudo keyword to ensure that we have the required permissions to add the script to the folder. However, an important point to bear in mind is that the run parts program is kind of picky in how it wants scripts to be named. In particular, it doesn't allow file names to include dots like we have here in .sh, so we need to remove these from the script names when placing them inside cron directories. So now if I run that command, and then I ls/etc/cron.weekly, you can see that this file is now here, and that's enough to make our backup run once a week. Pretty easy, right? One issue with this approach is that every script that we put inside the cron directories will be run by the root user. We can see this reflected in the user field of the jobs in the /etc/crontab file, which is the only file that has the user column. Running scripts as root all of the time is not generally a good idea, and it's best to avoid running as root unless the commands in your script specifically need root privileges. So, as we've learned, these cron directories are nothing more than regular folders that we just give the run parts command a specific time point to execute. So this means we can actually create our own custom cron directories. Let's say that we want to run multiple scripts at 2 AM every day. We can create our own cron directory to do this. So let's create a directory for this. I'm going to create the folder cron.daily.2am inside my home directory, which is where I currently am. Now let's open our own regular user's cron tab for editing using crontab-e. Now I can add a new line here at the bottom of the file. We want this to run at exactly 2 AM, so I'm going to put 00 in the minutes column and 02 in the hours column to set 2 AM. We also want this to run on every day, so I'm just going to put in *** for the other fields. Now we just need to add in our command here. We have to start this with the run-parts command, making sure to remember the dash in the command's name. Run parts is just a regular command, and how it works is that it takes a directory as an argument and it will run all of the executable scripts within it. So let's give it the directory ~cron.daily.2am, which is the folder that we just created. Use the --report option here to make the run parts command log each of the scripts that it ran. So now all we have to do is save this cron tab, and now we have a folder in our home directory where we can place any scripts that we want to run every day at 2 AM. How awesome is that? Obviously, you can create as many folders as you like to run at whatever times you like, and your newfound knowledge of cron directories will make your future automated empire easier to manage. So now you have a great under the whole cron service, from how to use your cron tab and how you can use cron directories to automate the runnings of your scripts. In this video, you learn how cron directories work, how to use the system's existing cron directories to run scripts periodically as the root user, and also how to create your own cron directories. Okay, so in the next video, you're going to take what you've learned about cron and use it to build a fun automation project. And then you're going to learn about another tool called Anacron, which is an absolute automation goldmine for laptop users. So I hope you're super excited. So good luck with the project, and I'll see you in the next video. Hello there, you beautiful person. I hope you had loads of fun trying out this fun automation project. In this video, I'm going to walk you through the model solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's get started. Okay, so the first task is to make a new update script. So to do this, I'll create a script called updatescript.sh using nano, and then I'll add in our shebang line. So the first commands that we're going to add in to our script are the commands to update our system. Because I'm running Ubuntu, I'm going to be using the apt or apt package manager, but there'll be equivalent commands for whatever distribution you're running on, and you'll probably be familiar with them already. If not, they're just a quick Google search away. Okay, so on Ubuntu, we're going to firstly add in apt-y update. This command is used by Ubuntu's apt package manager to check the repositories and update the apt cache and identify the packages that need updating. The second command that we'll add in is apt-y upgrade. This command installs the updates that were identified by the apt update command. Note that I'm using the Y option here to ensure that when we run the script, we don't need to manually enter yes when it asks us if we're sure. We're giving our consent ahead of time. Then finally, we know that we need our script to reboot our system after it's done the updates. Now you might have just added in reboot here into your script, which you're 100% correct to do. However, there is a little trick that we can use to handle this, which I want to share with you now. In Ubuntu, there's a file called /var/run/reboot-required, which is created when a reboot is required to fully update a package. So instead of just rebooting every time that we run the script, we can instead check whether this file exists, and if it does, then we can reboot. But if not, then we can just end the script without rebooting, as rebooting isn't necessary. So how do we check if a file exists? That's right, we can use an if statement with a test command like so. This test command is using the f operator to check if our reboot required file exists. And now we're just going to end this with a semicolon and the word then. Now we just need to add in the reboot command inside our if statement and close off the if statement with the keyword fee. So this statement just checks if the reboot required file exists, and if it does, then it reboots the system. Okay, so that's it for our script. So let's save it and head back to our terminal and give our script the execution permissions it needs using the chmod command. Okay, so as we can see from the pwd command, we now have a script that's ready to go in our bash courses scripts folder. As we mentioned in the project brief, this script cannot be run as the normal user because the commands we're running affect the system as a whole, and therefore the script must be run as root. So that means we can't just add a line into our user's cron tab. Instead, we're going to have to modify the system-wide cron tab, which is /etc/cron tab. To open this, we'll run sudo nano /etc/cron tab and then enter our password. Okay, so next we need to set up the cron tab expression. Now the brief says that we want to run this backup script every day at midnight. So let's write out our expression in cron tab guru to help make sure that we've got our cron tab expression correct. So under the minute column, we can just put 00 because we want this to run exactly at midnight. Then under the hours column, we can also put 00. Remember that cron uses a 24-hour clock expression, so 0 or 00 represents midnight and 12 represents midday. So the next field is the day of the month, and because we want the script to run on every day, we're just going to put a star here to tell our script to run any day. The next field is the month number, and again because we want our script to run every month, let's also put a star in here. Then finally, the last field is the day of the week column, and again we're going to put a star in here as we want the script to run on any day of the week. As you can see, cron tab guru is telling us that this will run at midnight every day, which is exactly what we wanted. So let's copy and paste this expression into our cron tab, and then finish off our new cron tab entry. So now that we have the expression in our cron tab, all we need to do is tell cron what we want it to do at the time that we've scheduled in our expression. So here I'm just going to put the path to our script, which is /home/ziad/bashcourse/scripts/updatescript.sh. Note that although we're only giving the script owner execution permissions, the root user will still be able to execute this script because at least one type of user has execution permissions. And that's all there is to it. If we now save our cron tab and close it, we need to restart the cron service manually now because we weren't able to use cron tab-e to edit the system-wide cron tab. However, this is still easy to do. All we have to do is just type sudo service cron restart, and our update script will be run automatically now at midnight as long as our PC is still on at that time. This is a great feature for you to use on your system to keep everything continually up to date. So I hope you had fun doing this short project and that it gives you a good idea about how the cron service works and how you can use it to automate your scripts. Now in the next video, we're going to be having a look at another tool called Anacron. Anacron is very similar to cron, except it has one killer advantage. Anacron is able to detect whether a scheduled job was missed when the system was off and run it again once it discovers the missed job. This makes Anacron an automation goldmine for laptop users, so I hope you're super excited. So for all that automatory good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be taking a look at the super awesome Anacron program. Anacron has a secret weapon that gives it a big benefit over the normal cron service, and in this video you're going to learn what the Anacron program is and how to use it. And by the end of this video you'll be able to explain how Anacron works, and you'll be able to run your scripts using Anacron. So let's go ahead and get started. So far we've seen the at command and the cron command. The at command allowed us to schedule scripts to run on a one-off basis, but there was no way to schedule scripts to run on a repeated schedule. The cron command allowed us to run commands on a schedule, but it requires that the machine is actually on at the time the scripts need to run. If the machine isn't on and the job is missed, cron has no way to recover them, which makes cron best suited to always-on server environments. Now Anacron, which is the topic of this lecture, has the ability to recover missed jobs. You can set a command or script to run at say 1 AM, but if the system is turned off at that time, Anacron will notice the job was missed when the system is booted again, and then it will run any missed jobs. How cool is that? If you're a desktop or laptop user and you turn your system off frequently, this should sound like a dream come true. So how does this work? Well, to schedule a job using Anacron, we set up lines in the /etc/Anacron tab file, which works very similarly to the /etc/cron tab file that we saw in our recent discussion of cron directories. Now one thing that is important to note here is that the /etc/Anacron tab file is stored in the /etc directory, which as we know stores system-wide configuration files. This tells us two things. The first thing it tells us is that this system-wide Anacron tab is a file that is run by the root user, in other words the system administrator. There is no user-specific Anacron tab file by default, only the system-wide one here exists to begin with. The second thing that is kind of a follow-on from the first one is that we can only edit this default Anacron tab file as the root user. If I try to run nano/etc/Anacron tab, you can see that this has opened with an error at the bottom of nano that says that the file is unwritable. This is because we do not have the permissions as a normal user to edit files that are in the /etc directory. So if I instead run sudo nano/etc/Anacron tab and enter my password, now you can see that this is opened in a writable form because I'm opening the file as the root user. Okay, so the first thing that you'll note with the Anacron tab is that we have 4 lines at the top. These lines, as you can see, are just variables that are set by the Anacron tab. As you can see, these are some of the system variables like path and home. All this does is write over those values with new values for these variables within the Anacron environment. You can also see here that Anacron is setting the default shell, and by default it's set to /bin/sh, which is the original Bourne shell. Given that we want to run all our scripts and commands in bash, we can just change this to /bin/bash to ensure that bash is always used. I'd like to point out here that if we always put our shebang lines in our scripts, then the scripts will always run with bash, but it's nice to also set that explicitly here too for some extra reassurance. The other thing that we want to quickly edit here is the path variable. Earlier on in the course, we added our scripts folder to our user's path, but this change wouldn't take effect for Anacron or for the root user. It was specific to the individual user that we were using. So what we can do is we can just add in here /home/ziad/bashcourse/scripts so that all our scripts are available to Anacron to run as well. Now at the bottom you can see that we have 3 lines again for the daily, weekly and monthly folders. This is similar to what we had in our system-wide cron tab, as we saw in our discussion of cron directories. In that video, we saw that the system defaults to using Anacron for running scripts stored in these 3 folders, and only if Anacron is not installed will the cron service run them. So this is quite an important thing to point out. If Anacron is installed on your system, then all of the scripts that you store in the daily, weekly and monthly cron directories will be run using Anacron instead of cron. Because of the ability for Anacron to ensure that a job gets rerun in the situation when the system was off at its initial scheduled time, this means that we can feel comfortable when placing scripts in these 3 folders, as we know that they will always be executed eventually. Okay, so now that we've spoken about some setup, how are lines in the Anacron tab file written? So looking at the lines that are here, the first argument we put in here is called period in days. This is the frequency that the job will be run in days. As you can see here, the daily folder has a 1 in this column, which shows that its contents will be run every single day. The weekly folder has a 7, which shows that it will be run every 7 days. You can see that the monthly folder has @monthly in this column, which is shorthand for once every month. As you can see from this format, we can't set the specific month of the year or the specific day of the month, so using @monthly here enables us to ensure that the job will run once per month, regardless of how many days the month is, which is useful because, as you know, some months are longer than others. Something to note at this point is that Anacron is not able to run jobs in minutes or hours in the same way that cron can. The most frequent period that Anacron can handle is daily. Okay, now the second column is called delay in minutes. So this is a delay that can be put in to cause Anacron to wait a certain amount of minutes after Anacron begins its daily execution, before it actually runs the command in question. Our systems have limited resources, and so if a lot of scripts run all at the same time, then this could have negative effects on the performance of the system, and the delay column allows us to space things out a bit. As you can see, because they each contain multiple scripts, the current jobs for the daily, weekly, and monthly folders have all been separated by 5 minutes to ensure that they don't run at the same time. If you don't have a particular need to set a delay, you can just put a 0 in this column. The third column is called the job identifier. This column just allows you to provide a reference name to refer back to this particular job in any log files produced by Anacron. The job identifier can contain any character except for blanks, such as spaces and tabs, and also slashes. Then finally, the fourth column is the command or script that we want to run. So let's say that we want to add in our backup script here to run once every week as we did in our cron project. Given that our backup is running on our laptop, and our laptops might not always be on at the scheduled time for the backup, it would make more sense to run our backup using Anacron instead of cron. Now obviously, because all cron directories are executed using Anacron by default, we could just add the backup script to the weekly cron directory. But let's set up a new Anacron job manually for ourselves to see how it would be done. So to create a new job that will run every week, we would add a new line in our Anacron tab file and add a 7 in the period column, because we want this script or job to run on a 7-day or weekly cycle. Now it's for the delay column. Given that disk operations are quite resource intensive, I want to be 100% sure that there isn't any other job running at the same time as my backup script. Given that we currently have delays of 5, 10, and 15 minutes, we want to choose a longer delay for our backup script to ensure that our backup happens after all the other operations are finished. So we can add in 30 here to play it safe so that we have a clear 15 minutes between our last set of scripts running and this one running. Then we can add backup_script as a reference for this job in the logs. And finally, we can just add in backup_script.sh to run our backup script. This script will be accessible because it's in the folder that's included in the path variable that we put at the top of the Anacron tab file. And that's all there is to it. Once this is added here, the Anacron program will ensure that this script runs once per week. If the system is off when this job is supposed to run, then once the system is turned back on again, the job will be run 30 minutes after Anacron boots up. As an important side note, Anacron will only ever run this job once, even if it missed running the job many times. So if you went on holiday for a month, and thus missed 4 weekly backups, when you switch your machine back on, Anacron would only run 1 missed job, not 4, so just bear that in mind. So just as a final thing, you may be wondering after all of this, how does Anacron actually know whether a job ran successfully or whether it needs to be run again? Well, this is one of the roles of the job identifier. Each job has a job identifier which is used by Anacron to log timestamps of when the job was last run. These are stored in the /var/spool/Anacron folder in individual files, one for each job identifier. So if I ls that folder, you can see that in here we have the daily, weekly, and monthly jobs. So if we cat the daily file, you can see that in here there is just a single timestamp which shows us the year, month, and date which the job was last run. So all that Anacron is doing is checking this timestamp and seeing if it's further in the past than the specified time period for the job. And if it is, then it knows that that job has been missed, and it will run that job again after the specified delay. Pretty simple, but crazily effective. So that's it for our coverage of the Anacron program. You should now have a very clear understanding of the different options that are available to you to automate your scripts in Linux, and how to use each of them like a pro. In this video, you learn that Anacron is an automation service that is great for systems that aren't always on, such as laptops and personal desktops. You learn how to write lines in the system-wide Anacron tab file to schedule your jobs. And you've learned how the Anacron program determines whether to run a job or not. If you'd like to learn more about Anacron, try running the commands man Anacron and man Anacron tab in your terminal for more information. So up next, you can have a quiz to give you some practice writing out the entries in the Anacron tab files for yourself, and then it's on to the section summary because, believe it or not, you've completed yet another section of the course, so well done. Your progress is absolutely stunning, so yet another massive congratulations to you. So have fun with the quiz, and I'll see you in the next video. Hello there, you beautiful person, and well done for completing this section of the course, which was all about how to schedule the automated execution of your scripts. You've made some excellent progress, and now you should feel pretty comfortable with scheduling your scripts to run with the cron, and anacron commands, as well as being able to tell the differences between them. In this video, we're going to have a quick recap of the key points in this section so that you can make sure that you're comfortable with everything before moving on. I've also put a cheat sheet summarising everything that we've covered in this section of the course in the resources section for this video, which you can download and refer to whenever you need to. So with all that said, let's have a recap. In this section, we started by looking at the command. You learned that the command is the most basic way to schedule tasks on Linux. It allows you to run a script at a one-off point in time. However, you can't set up repeated scheduling with the command. You learned that in order to work, the command requires the daemon, known as atd, to be running continually in the background. We looked at how you can install the command and how to ensure that the daemon is running. All of the commands we discussed are shown here. We then looked at the syntax that you use for running the command, which is simply typing the word and following that firstly with the time you want the command or script to run, and following that with the date. If you don't enter a date, then the command will schedule the job to run at the given time, either today or tomorrow, depending upon whether or not that time has already passed for the current day. When the scheduling information is provided, then the command opens up a prompt where you can start to add in as many commands as you'd like to be run as part of this job. As you learned, these are entered on new lines, so you can simply just keep adding lines in until you're done, and then you use Ctrl and D to save the commands and exit the prompt once you're done. We then looked at how you could schedule a script to run with the command. Here you learn that you can specify a path to a script as an argument to the command's F option, and then that script will be run at the scheduled date and time. The command also allows you to manage the scheduled jobs using various options, and here is a table of the options that we discussed. Firstly, there's the L option, which lists all the jobs that are currently scheduled with the command, and it will also show you the job's ID as well as their scheduled date and time. Secondly, there's the R option, which allows you to remove a scheduled job if you provide the option with the job ID of the job that you want to remove. I've also tabulated for you some of the different formats that the command allows for the date and time when scheduling jobs. Be sure to have a look at the man page for the command to get a full breakdown of all the formats available. We also discussed the limitations of the command, and they're written down here for you so that you can refer to them and make an informed decision about which tool you want to use when scheduling jobs. The main limitation of the command is that it doesn't allow you to schedule recurring jobs, and this brought us on to discussing the cron command. You learned that, like the command, the cron command also requires its own daemon service, cron-d, to be running in the background in order for cron to work. Here are the commands that you can use to manage the cron service and ensure that it's running. We then looked at how you can edit cron tab files, which you learned are files that express, in a table format, the cron jobs that we want to schedule and at what time we want them to run. You learned that each user has their own cron tab file, which contains the jobs for their particular user account. You learned that to edit the current user's cron tab, you need to run the cron tab command with the E option to open it for editing. It's important to remember to always use crontab-E rather than trying to use something like nano to edit the crontab file directly. This just makes things easier for you as it ensures that cron restarts and that all of the changes that you make take effect when you finish editing the file. You then learned about cron tab syntax. Each row in a cron tab expresses a new job, and each row is made up of 6 columns which are separated by white space. You'll remember from the lecture that each element must be separated, but that it doesn't really matter how much white space you add. Any type and quantity will be treated the same, and you don't have to be consistent. Below here, I've placed this table for you that you can reference that will tell you what each of these different columns are and the information that you can place in them. Just as a note, it's always important to make sure that your scripts are given execution permissions, as we've been continually doing throughout this course. Otherwise, cron won't be able to run the scripts. We also had a look at some very handy shortcuts which I've placed here for your reference. Firstly, we have the star or the asterisk, which, when you place it in a column, will represent all of the valid values for that column. Then we have a comma, which can be used to separate values to add multiple values within a single column. So for example, 1, 5, 8 will put the values 1, 5 and 8 in a single column. And finally we have the dash, which can be used to put ranges in your column. For example, 1-8 will represent all of the numbers from 1 to 8 inclusively. We also saw how to use a great website called crontab.guru, and we saw how to use that to check that the crontab expressions that we enter in our cron tabs do indeed mean what we expect. So from here, it was on to looking at cron directories, which are folders on your system where you can place a group of scripts that you want to run at the same frequency. We saw that there are 4 pre-configured cron directories on your system. The first one runs the scripts it contains hourly, the second one runs them daily, the third one runs weekly, and the fourth one runs monthly. Each of these can be found in the /etc directory, and due to this it's important to note that the scripts will always be run by the root user. An important note to remember is that these files mustn't contain a dot in the file name, and therefore it's very important to remove the .sh from the end of your script if you want to place it in these directories. Then one final note, as mentioned earlier, you must always ensure that all scripts that you put in these directories have execution permissions so that cron doesn't run into problems when trying to run them. We then had some fun creating our own cron directories. Now as you learned, any directory on your system can be turned into a cron directory by adding a new line in your user's cron tab. This line will use the normal scheduling syntax in the first 5 columns, and then instead of just adding the command or script you want to run, you're going to use the run parts command like shown here. Finally, we had a discussion of the limitations of cron. The main limitation of cron is that, like the at command, cron jobs will only run if the system is turned on and the cron daemon is running at the scheduled time. Then finally for this section, after we'd finished with all this great stuff on cron, we then moved to look at the anacron service. You learn that the advantage of anacron is that it has the ability to monitor whether a job has been run or not, and if not, it will then run it when it discovers that the job has been missed. By default, there is one anacron tab in the /etc folder, and this requires root privileges to modify because it's a system-wide configuration file. So to modify this, we use the command sudo nano /etc/anacron tab. You learned that anacron has quite a different syntax to cron, and each row in the anacron tab is made up of 4 columns. The first column is the period, which contains how many days you want between each time your command or script is run. The second is the delay, which is the delay from when anacron detects that the job needs to be run to when it actually runs it. Remember that this delay is used to space out your commands so that you don't end up with a lot of commands or scripts running at the same time, which could possibly negatively impact your system's available resources depending upon what you're doing. The third column is the job identifier, which is simply the name given to the command in the anacron logs. The job identifier can contain any character except for slashes and blanks. Then the final column is the command or script that you want to run. And again, just to understand that each of these commands has its limitations, the main limitation with anacron is that the shortest frequency that it can handle is daily, and therefore you can't run commands at the specific time like hourly or minutely that you can with cron. Also, Anacron will only recover one instance of a job that was missed, so just bear that in mind. If you're away for, let's say, 2 weeks and you wanted to run a script every day, Anacron would only recover the last job that it missed. It wouldn't recover every single job that was missed. So you've covered a whole lot of stuff in this section, and now at the end, you should be able to schedule jobs using the @ command and manage these jobs, explain what cron is and how it works, use cron tabs to schedule cron jobs that will run your scripts automatically at regular scheduled times, navigate the cron tab guru website and use it to create cron expressions, understand the different cron directories that your system makes available and use them to run your scripts at regular intervals, create your own cron directories to bundle groups of scripts to run whenever you want, explain how Anacron works and how it's structured, run your scripts using Anacron to ensure that your automations always get run, even if your system was off at the time they were supposed to, and explain the limitations of the @ cron and Anacron commands so that you can make educated decisions about when it's appropriate to use each one. And as I say, the cheat sheet is available in the resources section for this video, and it contains all the key points from this section of the course. Now in the next section of the course, we're going to be doing something truly awesome, and we're going to get into setting up and running some scripts on an actual remote server. So for all that remote server goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this section of the course where we're going to be learning how to work with bash scripts on remote servers. This section of the course is going to be a practical section where you're going to take all the knowledge you've learned so far and put it into practice remotely on a server. If you don't yet feel like a bash professional, you definitely will after this section, so let's take a look at what we're going to cover. In this section, we're going to be connecting to a remote system using the SSH command. This will allow us to work on a remote computer using the command line as if it was our local PC, and then we're going to use this SSH magic to create, execute, and automate scripts on our remote system. Then we're going to learn how to use the scp command to push and pull files to and from a remote server, and use that to upload scripts to our remote servers that we create locally, and also to allow us to download the output files produced by scripts that we run on that server. It's basically magic. And by the end of this section, you're going to be able to explain what SSH is, you're going to be able to use SSH to connect into a remote system, you're going to be able to use SSH to create, execute, and automate scripts on a remote system, you're going to be able to use the scp command to upload files to and download files from a remote server, and you're going to be able to automate tasks that interplay between remote and local systems. As an important side note, if you're working on this course from your work location or from your work laptop, your workplace may have security policies and firewalls in place that prevent you from using the SSH and scp commands that we're going to be using in this section. If your workplace does have these restrictions in place, then this is going to be something you'll need to raise with your IT department to have resolved. Alternatively, you can just work on this section of the course from a personal laptop from home to get around the issue. Oh, and as usual, there's a cheat sheet available for you to download from the resources section of this video, so feel free to download that so you can keep it handy in case you need it. So we've got a whole lot of very exciting topics to cover, so let's go ahead and get started. Hello there you beautiful people, and welcome to this video where we're going to run through how you can set up a Linux instance on DigitalOcean that we can use to practice working with a remote server. I would like to advise at this point that using DigitalOcean is optional and not a requirement to complete the course. So if you don't want to set up a DigitalOcean droplet for whatever reason, and you have access to a system that you can SSH into already, then feel free to use that. Or if not, then you can always take a watch and learn approach and just observe the commands that we're using in this section. This section isn't very long, and you'll still be able to learn all the concepts just from viewing the videos. In this video, you're going to learn how to set up an Ubuntu droplet on DigitalOcean, which is a cloud server hosting platform. By the end of this video, you'll be able to set up an Ubuntu droplet on DigitalOcean, and you'll have set up an SSH key that you can use to access this droplet, and we're going to be using that in the next video. So let's go ahead and get started. Okay, so first of all we need to navigate to www.digitalocean.com and then select Sign Up. As you can see here, we're presented with the options to create an account either with our email address, Google account, or GitHub account. So you can select whichever option works for you here and complete all the required information to sign up. Once you are signed up and logged in, you'll be presented with a page like this. We can now click on the Create button and then select Droplet to create our very first droplet. As you can see, by default, the Ubuntu operating system is already selected, which is exactly what we want. For the purposes of this course, we're just going to choose the most basic droplet and the lowest price. Here, we're already on the basic options, so we're just going to select regular Intel with SSD here, and then select the option for $5 a month. Okay, now we don't need any additional storage for this droplet, so we can just skip that and move on to choosing our data center. Now when you're working with a cloud-based server, it's always best to choose the location closest to your geographic location. This is because the speed of accessing the server is determined to a large extent by your distance from the server. The less distance your data needs to travel, the faster your connection will be. So because I'm based in the United Kingdom, the best option for me is London, but you can select whichever option is best for you from the list of available options. We don't need to worry about VPC, and we don't need any extra options, so we can just skip these sections. Then we get to authentication. Now here by default, the option is selected to use SSH keys to access your server. With SSH, you get two options. You can either set up SSH using a password, or you can set up SSH using SSH keys. SSH keys are more secure, and so we're going to be selecting that option here. An SSH key is an encrypted certificate that is used to authenticate your SSH connection. A copy of this certificate is stored on the server, and another copy is stored on your system. Speaking in rough terms here, when you attempt to make an SSH connection to the server will compare its copy of the SSH certificate with the copy on your system, and if they match, then authentication is successful. So to create our SSH key, we're going to click the New SSH Key button here, and DigitalOcean has very kindly put all the steps required to create a key right here on the right-hand side for us. So here on the right-hand side, we're told to use the command ssh-keygen, which will cause our terminal to generate a new SSH key. However, before you go ahead and create a new SSH key on the computer you're working on, let's keep things simple and first check if you already have an SSH key on your system. You can do this by running ls:/.ssh. If you run this and you see a file called id_rsa.pub, like you see here, then this means you already have an SSH key. If you do, just open that file in Nano and copy and paste its contents into this box on DigitalOcean. However, if you don't have any SSH keys, then you can run the command ssh-keygen in your terminal to create a new one, which I'm going to walk you through now. When we run this command, we're now prompted about where we want to store this certificate, and we're also given a default location. So let's just press enter here to keep things simple and use the default location. Next, we are then asked to create a passphrase for our certificate. You'll need to remember this passphrase every time you try to connect via SSH using this certificate, so try to make it something secure and something memorable. I'm going to type something in here and press enter. And then I'm going to type it in again and press enter again to confirm. Now this process creates two files in our .ssh directory in our home directory. Your SSH certificate has a secret part and it has a public part, and the public part is stored in the file ending in .pub, which stands for public. We need to provide the public key to DigitalOcean, so that means we're going to be interested in the file ending in .pub. So in my case, that's going to be id_rsa.pub. You can then simply open up your public key file in Nano, and then copy and paste the contents of that file into the SSH key box on DigitalOcean. I'm going to do this off camera for security purposes, but just copy the contents of the .pub file and paste it into that box. Give the SSH key a name of id_rsa using this box here, and then click the Add SSH Key button. Okay, so now that we've added our SSH key, we already have one droplet selected, which is all we need, and we then have the option to set the hostname that we want for our server. I'm going to call mine bash-course-server, but you can call yours whatever you like. We're then done with everything we need, and we just need to click the Create Droplet button here, and DigitalOcean will start to deploy our droplet. Okay, so after waiting a little while, you can see that our droplet has now deployed, and DigitalOcean is providing us with the IP for the droplet that has been created. Now, one last thing that I'd like to highlight to you is regarding pricing. Although the current pricing on DigitalOcean is $5 a month for this type of droplet, the cost is billed hourly, but the hourly cost is only $0.007 per hour. You can switch individual droplets on and off using the slider here, but be warned that this doesn't stop billing. To stop the billing, you must destroy the droplet completely. Given that you're using this droplet only for this section of the course, you can just use the droplet to follow along and do the exercises, and then just delete the droplet from DigitalOcean to stop any billing, and thus keep the total cost well below $5, assuming it takes you less than a month to complete the videos. To destroy a droplet, you can click on Droplets on the left panel here, hover over the droplet you want to destroy, and click on More, and then click Destroy. Then on the next page, you can then click Destroy this droplet, and then click Confirm. So as you can see, DigitalOcean provides you with a great way to quickly set up a risk-free remote Linux server environment to experiment with, and as long as you remember to completely destroy the droplet when you're done, and not simply just turn the droplet off, then it won't cost you very much at all to play around with. And as I say, using DigitalOcean is totally optional. So we now have our very own remote cloud server all set up and ready for us to run our bash scripts on. How awesome is that? In this video, you learned how to set up a droplet on DigitalOcean, and you learned how to create an SSH key and add this into your DigitalOcean droplet. In the next video, we're going to use SSH to connect into our server and start working some magic with bash scripts. So for all that amazing remote stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to start looking into how to access and work on a remote server. In this video, you're going to learn how the SSH service works and how to use it to access and run bash scripts on a remote server. By the end of this video, you'll be able to explain what SSH is and how it works. You'll be able to use SSH to access remote servers. You'll be able to create and run scripts on remote servers. And you'll be able to automate those scripts on remote servers too. Needless to say, this lecture contains a whole lot of awesome stuff, so let's go ahead and get started. Okay, so first of all, what exactly is SSH? SSH stands for Secure Shell, and it's a protocol that allows one machine, the SSH client, to open a shell on another machine, the SSH server, over an encrypted network connection. This ability to access shells on remote machines via a secure connection is where the SSH or Secure Shell protocol gets its name. To start an SSH connection, you run the command SSH. When using SSH, you connect into the remote system using a user account on that system. So following the SSH command, you add in the user which you want to connect to the remote system as, which in our case, if we're using the DigitalOcean droplet that we created in the last video, will be root. Following this, we add in the @ symbol and then the IP address of the system that we want to connect to. We can get this from going to DigitalOcean, clicking on the Droplets tab, and clicking on the IP address here to copy it to our clipboard. We then head back to our terminal and paste in this IP address to add it to our command line. Alternatively, you can of course just type the IP address out yourself. If I run this now, then you can see that I receive a message saying that the authenticity of the host could not be established, and it asks me whether I want to continue connecting. And I'm going to say yes, and press enter. And it now asks me for a password, and it references the name of our SSH key. So to do this, I'm going to need to enter the password that we created for the SSH key, and then press enter. And it now shows me that we're logged in successfully into the remote server, and the hash at the start of the command line tells us that we're logged in as the root user. You may be asked to enter the password you created for your SSH key in the last video, and if so, just enter that if prompted. Now, because your local machine will have not seen the new server before, you may also receive a message saying that the authenticity of the host could not be established, and it will ask you whether you want to continue connecting. If that happens, just type in yes, and it should log you in right away. So even though it doesn't look like much, we're actually now connected to the remote system over a secure SSH connection. As you can see from the prompt, we are connected as the root user to our system, which has a host name of bash course server, just like we set up in the last video. If I cat the file /etc/os-release, you can see here that it tells me that this is Ubuntu version 20.04 that I'm connected to, which is the version that I set up on the DigitalOcean droplet in the last video. If I run the command echo $shell, you can see that we're also connected into the bash shell as well, so we should feel right at home. So putting this all together, we're connected to a remote server into a bash shell session as the root user. So we now have the ability within this session to do the same as what we've been doing in our terminal and our local machine throughout the course. So what I'm going to do is I'm going to create a basic bash script here called remote.sh, and I'm going to add in the shebang line at the top as we normally do. Now we can just make this script say echo I am very far away in double quotes, and we're going to append that output to a file called remote.txt. Then I can save the script and head back to our terminal and give the script execution permissions like we always do. And when we run it, we can see that we have a file called remote.txt on our file system, which contains the text, I am very far away, which makes a lot of sense for a remote server. So we now have a working bash script on a remote server, but let's take it a bit further and throw in some automation. Now, unless we turn it off, our server is always on, so cron is a good choice for automation here. So let's ensure that the cron service is running by running service cron status. We don't need the word sudo here because, if you recall, we're already logged in as the root user. Now we can see here that cron is indeed running on this machine, but if it's not in your case, just run service cron start like you learned in our discussion of cron earlier in the course, and that should start the cron service for you. Okay, so now that we're sure that the cron service is running, let's open up our cron tab for editing with cron tab-e. Because this is the first time that we're using the cron tab on this machine, it's asking us what editor that we want to use to edit the cron tab. I'm just going to type a 1 in here and press enter to select Nano, but you can select what editor you like. Then we can come down the bottom of the cron tab and add in the line $home/remote.sh, and that's going to cause our script to run every minute. So let's now save our cron tab and head back to the command line. And if I wait a few minutes, and then I run the command cat remote.txt, you can see that our script is successfully running automatically on our remote server because there are new lines added to the file. How awesome is that? So we've now logged into a remote server, created a bash script on it, and automated that bash script to run every minute using the cron service. Now, because our DigitalOcean droplet is always on, this automation will continue to run even though we're not connected to the server. So if I disconnect from our server, which we can do just by running the command exit, you can see that I'm now back on my local machine. And I'm just going to wait here a few minutes to give that automation some time to run on the remote server. Okay, so now a few minutes have passed. If I reconnect to our server by typing ssh root at and then the IP address of the server, when we connect, if I take a look at the contents of the remote.txt file again by typing cat remote.txt, you can see that the file now has a bunch of new lines. So as we can see, because our server is always on, cron is continuing to run our script even when we are not personally connected to the server, which is awesome. So congratulations, you're now able to set up remote automation. Alright, so in this video you've learnt a lot about how to use SSH to connect to and run scripts on your remote server. In this video, you learned what SSH is and how it works. You learned how to use SSH to access our remote server. You learned how to create and run scripts on your remote server. And you learned how to automate your scripts on remote servers as well. Now in the next video, we're going to take your remote server skills to the next level by showing you how to use the scp command to push and pull files from your server securely. So for some next level remote server skills, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be discussing the SCP or secure copy command. Now when working with remote servers, there are times when you want to write a script or program on your local machine and then upload the file to a remote server where it will run. There are other times when you want to get the results of a script that ran on the remote server and save a copy of the output file to your local machine. A great command for this is the SCP command, which is the topic of this video. In this video, you're going to learn how to use the SCP command to push files to your server and how to use the SCP command to pull files from your server. And by the end of this video, you'll be able to explain what the SCP command is and how to use it. You'll be able to use the SCP command to push files to your remote server, and you'll be able to use the SCP command to pull files from your remote server to your local system. So let's go ahead and get started. So to start with in this lecture, we're just going to create a script on our local machine. So I'm just going to run nano ipscript.sh, and then I'm going to add in the shebang line at the top like usual. So for this, I just want to run the command curl ifconfig.co. So all this command does is it's going to give you the public IP address of the computer that it runs on. So when we upload this script to the remote server, we should be able to see that the output of this command matches the IP address of the server, so we know by running the script that it's actually running on the remote server. And what we're going to do is we're going to redirect the output of this command to the file ~ip.txt. So let's now save the script and give it the relevant permissions in order to run it. Okay, so now this script is on our local system currently, but here is not where we want to run it. We want to run it on the remote server. So how can we actually get the file there? Well, to do this, we can use a command called scp. scp, or the secure copy command, is a command that uses SSH to securely copy files from one location to another over an encrypted SSH connection. So we can use the scp command by firstly entering scp. Now the scp command wants two arguments provided to it. The first argument is the source, and the second argument is the target. The source is the file that you want to copy, and the target is where you want to copy it to. So firstly, we want to copy our script from our local system to our remote server. So our source will be the path to the script locally, so I'm going to put in ~ipscript.sh as the source. And now we want to put this file on the remote server, so the target needs to be the path to our server. Because SCP is using an SSH connection, the way of writing this is very similar to how we initiated an SSH connection with the remote server in the last video. We start off by typing the user we want to log in as, which is root, and then we put an @ symbol, followed by the IP address of our remote server, like so. So this is the route to the server that we want to use. Then after the IP address, we put in a colon, and we follow this with the file system path to where we want the file to be copied to on the server. Now when writing this path, you have to imagine that you're already on the remote system. So seeing as we are logged in as the root user, let's say we want to save the file in the root user's home directory. If we were already on the remote server and logged in as root, the path to the root user's home directory would simply be ~/. So we're just going to put that in here. This command will copy the script file from our home directory on our local system and place it in the root user's home directory on that server. Okay, so if we run this now, you can see that this has completed successfully. So now if I connect to our server using regular SSH by typing SSH root @ then the IP address of our server, then when we log in, when we run the ls command, you can see that the file we sent is actually now stored on our server, which is amazing. So now we can actually run this script as we usually would, and that script is going to be executed on our remote server. If I run ls now, you can see that I now have a file called ip.txt, and if I view the contents of this file using cat ip.txt, you can see that this file contains the same IP address that we'd use to connect through SSH to this server. This shows that we are in fact on our remote server and that this script was transferred and run on that server successfully. So what if we now want to pull this ip.txt file down to our local system? We can use the scp command from our local system to pull files down from our remote server, as well as copying files to the server. And all we've got to do is simply swap around the source and target. So if we exit from our remote server to get back to our local machine, now from the local machine, if we run the scp command again, this time we want to start with our remote location as the source. And we're going to add in the same information we did last time. So we're going to put in root, then the IP address, and a colon. So now given that we want to copy the ip.txt file that was created, all we need to do now is just put in ~/ip.txt, because that is going to be the path on the remote server to our ip.txt file. And we put that after the colon. So next we need to set our target. And so let's say we want to save this file in the current user's home directory. So for this, all we need to do is put in ~/ as our target. So if I run this command, and then I run the ls command, you can see that we now have a file called ip.txt saved here in our home directory. So now when I run cat ip.txt, you can see that the contents of this file are the same as they were on the remote server, showing that we have in fact copied this file from the remote server to our local system. Isn't that super cool? As a side note, just be aware that we were able to pull the files to our local system because we initiated the connection from the local system. If you tried to initiate the connection from the remote server, you wouldn't be able to connect to your local machine by default because of the default firewall protections that will likely be on your router. You can get around these, but it isn't recommended for security purposes. Alright, so now you know how to use the scp command to push files or scripts to your remote server, run them on your remote server, and pull the output back to your local file system. In this video, you learned what the scp command is and how it works. You learned how to use the scp command to copy files to your remote server. And you learned how to use the scp command to copy files from your remote server to your local system. So I bet you're dying to put this stuff into practice. So up next, we're going to have a project for you to create a really cool remote server monitoring script. This script will log performance-related details of the server and enable you to access these details remotely to review how the server is running. So good luck with the project, and I'll see you in the next video. Hello there, you beautiful person! I hope you had loads of fun trying out this remote server monitor project. In this video, I'm going to walk you through the model solution step by step, and you can also grab a copy of the official solution script from this video's resource section. So let's get started. Okay, so the first task that we're given in the brief is to create our performance checker script on the remote server. So let's start off by logging into the remote server through SSH as the root user, just like we learned earlier on. Okay, so now that we're on the server, let's open a script called performance_checker.sh and then add in our shebang line. The first step of this is to add in a date command that will append a timestamp to our log. So to do this, I'm just going to type the date command and then just append the output of this command to our log file, which we're going to put in the root user's home directory, and we're going to call performance.log. Okay, so that's it for the first step in the first task. Now the second step is to add a few commands that will allow our script to test the server's internet connection. We've been given the code required to do this in the brief, so I'm just going to copy and paste that code into our script here. As you can see, this code uses the ping command to test the connection to google.com, which I've heard is a pretty reliable website. And we use the -c option here to set how many times that we're going to run the ping test, and we're just going to set it to 1 so that we just run a single test to see whether we're online or not. Now here at the end we have the ampersand greater than sign operator, which, as you know, redirects standard error and standard output, and we're redirecting it to the /dev/null file. In other words, we're redirecting it to the bit bucket. And we're doing this just to dump this output and delete it immediately so that we don't get any unwanted output printed into our terminal when we run this script. Following that, we're going to be using an if statement to check if the $question mark special parameter which as you know holds the exit status for the most recent command, we're going to check if that is equal to 0. The ping command will only give us 0 exit status if there is a valid connection, so we're using this to check if there isn't a valid internet connection. If there is, then we're going to save internet connected into our log file, and if not, then we're going to save the text internet disconnected into our log file. Okay, the third command that were provided in the brief checks how much RAM the system is currently using, so I'm just going to paste that in here too. This command will first echo out a heading that says RAM usages, which is just a bit of formatting to help us separate the sections in the log file to make it easier to read. Then we're going to use the free command, which outputs the current memory usage on your system. The -h option here just makes the memory usage outputted by the command more human readable. We then pipe this output into the grep command and give the grep command the argument mem to limit the outputs to only the line that has the word mem in it, which is, if you look at the output of the free command on its own, that's the line that tells us the memory usage. Then we just append this output to our performance.log file. Then we enter our fourth bit of code, which shows us the swap usage. So I'm just going to paste that in here. Again, with this command, we're going to start out by echoing out a bit of formatting to show in the report that we're moving on to a new bit of information. And as you can see, we're going to use pretty much the same command again this time, but instead of using grep to limit the output to the lines that contain the word mem, this time we're going to limit it to the line that contains the word swap, which is the one that contains all of the information about the swap memory on our system. And then finally, we're going to copy and paste the last bit of code that the brief gives us to check the disk usage. Again, we're taking care of some formatting here with an echo command. And then we're using the df command to check the disk space usage. And we're appending this output into the performance.log file as always to make our log complete. Now finally, I'm just echoing out a blank line here just to make sure that we've got a blank line between the entries that are created each time the script runs. And again, this is just some formatting to make the resulting log file easier to read. Okay, so that's the script complete, nothing like a bit of copy and pasting. So let's go ahead and save the script and then head back to the command line and give it the permissions required to run. Now following this, our second task is to automate this script to run on our server every hour. Now because our server is always on, we're going to use cron for this task, and we're going to open up our cron tab with cron tab -e. We need this to run every hour, so to do this, we're going to add in the cron expression 0, then star, 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 star. And what this is going to do is it's going to run this job at the start or 0th minute of every hour of every day. Then we just add in the path to our script in the command field, which is going to be ~performancechecker.sh, and then we're going to save the cron tab file to create this cron job. And when we head back to our terminal, we now have this script set up and a cron job running every hour to log our server's performance. Now currently this output is sitting in the performance.log file on the root user's home directory on the server, but we want this pulled to our local laptop every hour so that we can easily have it to hand for our team if they ever ask us any questions. So let's now exit from our local server to get back to our local machine to set this up. We're now told that we need to set up a cron tab to download this file from the server onto our local system on an hourly basis. So to set up our new cron tab entry, let's open up our cron tab for editing with cron tab -e. So first we need to create our cron tab expression, which in this case is going to be 15 in the minute column, then star, 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 and star. Now this is going to cause our cron job to run at 15 minutes past the hour of every day. Now as mentioned in the brief, we put 15 here because we want to ensure that there is plenty of time between when our script on the server runs and updates the actual log and when we pull the log down. Okay, and the last step to finish off our cron tab is to add in our command that's actually going to pull down the log. Now, as you learned during the last lecture, to transfer files between our remote server and our local machine, we want to use the scp command. And as you learned, the first argument to the scp command is the source, which is the file that we want to copy. And because this file is on a remote system, we're going to need to log in over SSH. So first we're going to put the user that we want to log in as, which is root, then the @ symbol, then the IP address of the server, which is this, and then we're going to put in a colon followed by the path to our log file on that remote system. So seeing as we're logging in as the root and the performance.log file is in the root user's home directory, we're going to put in a tilde, then slash, then performance.log. Okay, so that's it for the source of the SCP command. We're now going to add in our target location, which we've been told is our user's desktop. So for this, we're just going to put in tilde slash desktop. Okay, so we now have an entry in our cron tab that will copy our performance.log file from our server to our local system's desktop at 15 minutes past every hour. So let's go ahead and save this and then head back to our terminal to make sure that cron tab gets set up. So we now have a performance logger set up on our remote server, which is running every hour and logging performance-related information to a file. And we also have a cron job on our local computer that will pull this log file to our local machine every hour as well, so we always have an up-to-date data file to share with our team. If that isn't awesome, I don't know what is. So I hope you had fun doing this project and that it's given you a good idea of how to work with remote servers, automate remote tasks, and how to move files between your server and your local system. If you've been working on DigitalOcean, remember to destroy the droplet now so that you don't get charged any more than necessary. You can see how to destroy the droplet by referring back to the video where we set up the droplet. And with that said, you've now completed this section of the course on working with remote servers. That's an amazing achievement, so very well done indeed. In the next video, we're going to wrap up with a summary of this section and take some time to celebrate your achievement. So for all that good stuff, I'll see you in the next video. Hello there, you beautiful person, and well done for completing this section of the course all about working with remote servers. You've made some excellent progress and you've learned a lot about how to use the SSH command to log in and work on remote servers from your command line, as well as how to use the SCP command to transfer files between remote servers and your local machine. In this video, we're going to have a quick recap of the key points of this section so that you can make sure you're comfortable with everything that we covered. I've also put a cheat sheet summarising everything that we've covered in this section of the course in the resources section for this video, which you can download and refer to whenever you need to. So with all that said, let's have a recap. In this section, we started by having a look at the SSH command and how it works. You learned that the SSH protocol, or the Secure Shell protocol, is used to provide a secure connection to a shell on a remote system. You also learned that connecting via SSH will enter you into a command line shell on the remote system, which is pretty awesome. We then had a look at the syntax for SSH, which you learned starts with the command SSH, followed by the username that you want to log in as, an @ symbol, and then the IP address of the server you want to connect to. You saw that you can then run commands just like you were used to, but instead of those commands running on your local computer, they're actually running on the remote server, which is a pretty awesome ability if you think about it. And after we looked at how you can use SSH to remotely connect into a system, we then had a look at the SCP command. The SCP, or Secure Copy command, is used to transfer files between machines over a secure SSH network connection. We used SCP to transfer files and scripts between our local system and our remote server. As you learned, the syntax for the SCP command starts with the command SCP, and the SCP command is then given two arguments. The first is the source, which is where you want to copy from, and the second is the target, which is where you want to copy to. And here is the syntax for transferring files from the local system to the remote server, and here's the syntax for copying from the remote server to the local system. And as you can see, because SCP uses SSH, whenever you want to refer to a file on a remote system, you have to first use the SSH syntax of providing the user, and then the IP address in order to log in, and then you put a colon, followed by the path to the location that you're referring to on the remote machine. So you've covered a whole lot of stuff in this section, and now, at the end, you should be able to set up an Ubuntu droplet on DigitalOcean, set up an SSH key to access this droplet, explain what SSH is and how it works, use SSH to access and work with remote servers, set up and run a script on a remote server, automate scripts on remote servers, explain what the SCP command is and how to use it, and use the scp command to push and pull files to and from your remote server. And as I say, the cheat sheet is available in the resources section for this video, and it contains all the key points from this section of the course. And with that, my beautiful people, we've now come to the end of the whole course. So a massive congratulations to you, you've come so far, and I'll see you in the next video for a recap of everything that we've covered, and some well-earned celebration. Hello there, you beautiful person, and congratulations for making it all the way to the end of the course. I wanted to create this video so that we could take a moment to celebrate your monumental success, and so we could also have a review of just how far you've come. If you cast your mind all the way back to the start of the course, you'll recall that we started off by looking at the 3 core components of bash scripts, how to write them, and how to execute your bash scripts securely. In section 2, you learned how to save data in your script within variables, and how to use a variety of expansions to get that data back out again. In section 3, we took a deep dive on how Bash is working behind the scenes to help you to avoid annoying syntax errors and understand Bash as a second language. In section 4, you learned how to allow your scripts to accept command line arguments and how you can interactively get input from your users and create interactive menus to make your script user-friendly. In section 5, we moved on to discussing logic and how you can create scripts that can do different things depending upon the situation. In section 6, you learned how to allow your scripts to accept command line options and to do different things based upon which options are provided. You also learned how to allow your bash scripts to process the contents of files. In section 7, you learned about arrays and for loops and how you can use these to create assembly lines to batch process data in your scripts. In section 8, you learned how to debug your scripts using the professional debugging tool shellcheck, and you learned how to read Bash's error messages as well as how to solve the most common bash scripting errors. You also learned how to use the help command, the man command, and the info command to access official support documentation to help you when writing your bash scripts. Then in section 9, you put all that you'd learned so far together in a big assignment to build 3 scripts that formed an integrated file system utility. Then in section 10, you learned about automation and how you can use the cron, and anacron services to automate your scripts, as well as how to choose which automation tool is best for the job. Then finally, in section 11, you learned how to run your bash scripts on remote servers using SSH and SCP. And all along the way, you've been completing practical projects as well as quizzes to check your understanding. So to come full circle and review the goals of the course that we set out to achieve, now that you're at the end of the course, you should be able to write your own bash scripts independently using all of the core components of bash syntax. You should be able to use scheduling software to automate the execution of your bash scripts. You should be able to debug your bash scripts using professional debugging tools. And you should be able to execute your bash scripts on local and remote systems. Bash is not the easiest thing in the world to learn, and yet here you are at the end of the course with some incredible new skills in your toolkit. So a massive congratulations to you. You've really done amazingly well. It's been such a long road, and you've learned so many new things, and I hope you've benefited from and enjoyed our journey together. For now, all that remains is to say goodbye for now, and to thank you for choosing to study bash scripting with Internet of Things Academy. Thank you once again, and we hope to be learning along with you sometime again soon. Hello there, you beautiful people, and welcome to this video where I'm going to give you a quick overview of how you can check whether you're using the bash shell by default, and if you're not, I'll also show you how to set the bash shell as your default shell for your system. So to do this, we're just going to go to our terminal and run the command echo, then a space, then the $symbol, then shell in all uppercase. Now here, as you can see, the terminal that I'm currently in is currently using the bash shell already. And if you see this or something similar, then you're 100% good to go because you're already using the bash shell by default. However, if I run this command again in another terminal, you can see here that this terminal is running the sh shell and not bash. And if you're running a shell other than bash, then it's a good idea to take note of what shell you're using by default, perhaps on a pen and paper or Word document, and then run the command chsh, which stands for change shell, then give it the -s option, and then give it /bin/bash. And that will change your default shell to the bash shell. If I now restart my terminal and run the command echo $shell again, you can see that now we're using the bash shell by default, so I'm all good to go. By keeping a note of what your shell was by default, you can simply use the same chsh command to switch back to the default shell that you had before making this change. Of course, you just swap /bin/bash for the path to the original shell that you wrote down. As a quick note, it's good to know that if you don't want to fully change your default shell for whatever reason, you can switch in and out of the bash shell on demand by just typing the word bash on a new command line and pressing enter. This will drop you into a bash subshell, as you can see here. And you can get out of this again by typing exit and pressing enter. You can also put the word bash before you run any command or any script, and this will ensure that the specific command or script is run with the bash shell. Okay, so you should now have bash set up as your default shell, or at least know how to use bash on demand. If you're on Linux or Mac and this has worked for you, then this is enough for you to go and get started with the course. Have fun! Hello there you beautiful people, and welcome to this video where I'm going to show you how to set up the Windows subsystem for Linux on your Windows 10 system. In this video you're going to learn how to enable the Windows subsystem for Linux features on your Windows 10 operating system, and you're also going to see how to install the Ubuntu terminal and how to set up a cool piece of software called Windows Terminal. Bear in mind that this installation will only work on Windows 10 and not earlier versions of Windows. If you are on an earlier version of Windows, please check out installation option 3 for how to install VirtualBox. So let's go ahead and get started. So firstly, we need to enable Windows features for the Windows subsystem for Linux. In Windows 10, there are built-in features that enable the running of a Linux terminal within your Windows operating system, which is super cool. To start with, we just open up our Start menu, open the Settings menu, and click on Apps. Then here in the top right hand corner, we select Programs and Features. So as I mentioned, these are Windows features that are already built in. So we just come to the left here and select Turn Windows Features on or off. This step may require administrator privileges, so just enter your administrator password if you're prompted to. In this menu, we need to scroll down to Windows Subsystem for Linux and select the checkbox, and then we press OK, and it will install. After this, click Restart Now to restart your system and enable these features. Now what we've done so far is we've enabled the Windows Subsystem for Linux features on Windows, but we do not yet have a distribution of Linux installed. So we need to go to the Microsoft Store to install one now. Now when you're in the Microsoft Store, you'll find that there are many distributions of Linux available. For example, if I search here Kali, you can see that Kali Linux appears as an option. If I search SUSE, you can see that SUSE appears as an option. For this course, I advise that you install Ubuntu, as that's what I'll be using, and it will give you the best compatibility between what you see on the screen and what's happening on your machine. So what we're going to do is we're just going to search Ubuntu in here and click Install, and then this is going to install the Ubuntu distribution. So after waiting a while, once this is installed, I can click Launch here, and I'm asked to enter a username. And so I'm going to choose Ziad as my username, and then I'm going to enter a password here that I want to use. Now if I close this and open my Start menu and search Ubuntu, you can see that I have an option for Ubuntu listed here, and if I click on it, I get an Ubuntu terminal opened. This uses the same bash shell that Ubuntu does, and so using this you can do everything in the course. Finally, I want to show you how to install a cool piece of software called Windows Terminal, which makes working with bash more convenient. To install Windows Terminal, let's go back to the Microsoft Store and search Windows Terminal, and then when that pops up, select it here and install it. Now if I launch this, you can see that I get a Windows command prompt open here for me to use. If I come to the top here and select this down arrow, then it opens up a menu where I can select the different terminals that are installed on my system. So here I can select Ubuntu, and it will open up my Ubuntu terminal for me, which I can now use here. This is a really cool piece of software that enables us to install however many different distributions of Linux that we want, and we can access them all here, including our Windows command prompt and PowerShell, all from one central location, which is very convenient indeed. So if you've made it this far, you should now have an Ubuntu distribution and access to a Bash terminal set up on your Windows 10 system, and you can use that to follow through the course. So have fun! Hello there you beautiful people, and welcome to this video where I'm going to show you how to install the VirtualBox software program on your system. This installation route is most suitable to users who are using a Windows system that isn't running Windows 10, and it can also be suitable for Mac users if simply switching to the Bash shell by default didn't work for you. After installing VirtualBox in this video, over the next two videos we're then going to set up a Linux virtual machine using VirtualBox that you can follow through the course with. So let's go ahead and get started. So first of all, let's navigate to the website www.virtualbox.org. Here you can see the option to download the latest version of VirtualBox, when we're just going to click here to go to the download page. And up here I get the options for which operating system I want to download VirtualBox for. Now since I'm using Windows, I'm going to choose Windows here, but you can choose the option that's appropriate for you. We then wait for the download to complete. So now that the download is completed, I can just run this installation file. We see that an installation wizard opens up, and I just click Next to start the process. We're then asked to select which features we want to install. Now I want to install everything, so we can just leave this as it is and click Next. Here we're then given a bunch of options for the installation. We're asked if we want to create a Start menu, Desktop menu, and Quick Launch menu entries or shortcuts, and I'm going to create all of them, so I'll just leave all of these selected, but you can deselect this if you wish. The final option here is to associate specific file types with the VirtualBox program. This will automatically associate certain file types with VirtualBox and make working with virtual machines more convenient, so we're going to want to leave this checked and then click Next. Finally, we're given a warning here that installing VirtualBox will briefly reset our network connections and disconnect us from the internet. This is because VirtualBox has to set up its configuration and access our network interfaces on our machine. This is fine, so just click Yes here to proceed with the installation. Finally, we just need to click Install here to install everything, and the installation process will now begin. You can see that we're asked to give VirtualBox administrative privileges to install itself, which we accept, and allow the installation to continue. So we wait a while, and once the installation is complete, we just click Finish to complete the installation, and run the VirtualBox software. Okay, so this was a super simple installation video, and if you followed through successfully, you should now have VirtualBox installed on your computer. In the next video, we're going to download and install an Ubuntu ISO image and use that image to configure a virtual machine in VirtualBox. So for all that virtual good stuff, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where we're going to be getting you set up with your very own Linux virtual machine running a specific flavor of Linux called Ubuntu. Flavors of Linux are called distributions in the Linux lingo, and we're going to be getting you set up with the Ubuntu distribution of Linux for your VirtualBox virtual machine. So what I want you to do is to head over to www.ubuntu.com/download/desktop, which will bring you to a page that looks like this. So here I see the 20.04 release, which is the most recent long-term support version at the time of recording. So I'm going to go ahead and download that. Now you may see multiple options, and it's always best to download the latest version or the closest long-term support version. There won't be any real differences for the purposes of this course. An interesting thing is that you can tell when the Ubuntu releases were released just by looking at the version numbers. So here I can tell that it was released in 2020 and in the 4th month, which is April. So 20.04 means it was released in April 2020. And when I click on download, you can see that this gets the download started. Now, as you can see, this download file is 2.7 gigabytes at the time of recording, which is, needless to say, quite big. So the download might take a while, depending on how quick your internet is. So I'm going to have to wait for that to download. So what I'm going to do right now is cut the video here and then come back once it's downloaded. So just be patient with this. You'll not really ever have to do this again. Once it's done, it's done. Just pause the video and wait for that download, and then unpause the video to continue with the rest of the setup. Okay, so now that the download has completed, we can go ahead and install the virtual machine. So what we're going to do is we're going to open up VirtualBox, and here it is. So we're just going to create a new virtual machine by clicking New. And I'm going to call it Ubuntu, because I'm imaginative. And as you can see, it's found the type, which is Linux, and the version, which is Ubuntu 64-bit, which is the version that I downloaded. If you downloaded a 32-bit version, then go ahead and select 32-bit instead. Now you can select where you would like the virtual machine to be saved to. Now I'm going to go and leave that where it is, but feel free to change this and save the virtual machine wherever you would like by clicking the down arrow and clicking Other, which will bring up a navigation box which you can use to navigate to wherever you want to save the virtual machine. I'm just going to click Cancel and leave it where it was, and I'm going to click Next. It's now going to ask me for the amount of memory or RAM in megabytes to be allocated to the virtual machine. Now, an important thing to note here is that this memory is only allocated when the virtual machine is running. When you close the virtual machine, it will be given back to the host computer. So don't worry about this too much, just give it a generous amount. Let's say we're going to aim for about 80% of the green distance. You don't want to go all the way up here because that might make your system jutter and stutter a bit. So just take it up to about 80% of the green section, but not all the way up so that you leave a bit of buffer. And then click Next. Then it's going to ask you about a hard disk. Now what you need to remember is that this virtual machine thinks it's a computer, and so it needs a hard drive space. So what we're going to do is we're going to create a virtual hard drive that this virtual machine is going to think is a real hard drive, but it's actually just a file saved on our actual computer. So what we're going to do is create a virtual hard disk now by clicking Create. It's going to then ask us what type we want it to be, and you can just leave it as the first option there, which is VirtualBox Disk Image. Now it's going to ask if we want this disk to be dynamically allocated or fixed size. Dynamically allocated means that when the data fills up on that imaginary hard drive, the file will get bigger, so the file will become larger dynamically. Fixed size means that the file will be a fixed size no matter what, even if it doesn't contain any data. So even if it's empty, it will still take up that much space on your actual hard drive. So for efficiency's sake, let's choose to have our virtual hard drive dynamically allocated. Then you can call it whatever you want and save it wherever you want by clicking on this arrow. Just leave it as the default if you're not really fussed about where it goes. Now it doesn't really matter massively what size you give it. I usually give mine 20 gigabytes, which is usually more than enough, but you can choose whatever is good for you and for your machine. So long as you have something above about 5 gigabytes, you should be absolutely fine. I'm just going to have 20 gigabytes here as an imaginary hard disk, and then I'm going to click Create. Now we're almost there now. We're very, very close. All we have to do is click on Settings to set up a few more things. So to make sure that our virtual machine has just a bit more power, we're going to click on Settings, go to System, click on the Processor tab, and increase the number of processors to 2 cores if you have them. So 2 processors or up to the end of the green. That basically just allows the virtual machines to have just that bit more performance, which will probably improve your experience. Everything else should be the same, except when you click on Storage. On Storage, this is where we're going to insert that disk image so the imaginary computer can boot from that Ubuntu image. You'll see this bit here that says Controller IDE and a disk that says Empty. Click on that, and then click on this little disk icon on the top right. Then click Choose/Create a virtual optical disk in the drop-down menu. And when you do this, a new window will pop up. In here, click Add. Now we're going to go to our Downloads folder and click on the 20.04 disk image that we downloaded and click OK. When that's all done, click OK, and we're basically all good to go. The only thing you need to do now is to restart your machine. So once you restart your machine, you'll have successfully completed the second step of the VirtualBox installation, and then in the next video, we're going to walk through the last and final step, which will have you all set up and ready to go. So go ahead and restart your computer, and then for all that virtual goodness, I'll see you in the next video. Hello there you beautiful people, and welcome to this video where I'm going to show you how to launch Ubuntu on your virtual machine and navigate any final setup that we need to do. VirtualBox can cause some people technical difficulties, so if you do experience any technical difficulties while following through this video, in the next segment there is a list of troubleshooting guidance with solutions to common issues, which you can use to fix any issues that arise. And of course, if you can't fix the issues after trying the solutions in there, then do leave a question in the Q&A and one of the team will get back to you to help you out. But hopefully, by the end of this video, you'll have a fully set up virtual machine that you can use to follow through the course. So let's go ahead and get started. So now that we have our virtual machine configured in VirtualBox and the Ubuntu ISO is connected to it, we can just open up VirtualBox and hit the Start button here to start running our virtual machine. And the first thing we notice is we have a menu pop up asking for the drive that we want to use, and we can just select OK here to use the default value. Now this boots into the Ubuntu ISO file, and the first thing that happens is that the integrity of our installation image is tested. Once this is completed, we get a menu opened which gives us a few options. Firstly, on the left-hand side we can choose our language. Now I'm going to leave mine as the default that I get, which is English, but if your preference is another language, you can select it here. Now we have two options. The first is to try Ubuntu, and the second is to install Ubuntu. And now installing Ubuntu is what we want to do, so I'll select that here. Now we can select our keyboard layout. Now for me, it's going to be English UK, and that's what comes up by default, but you can also select whichever keyboard layout is relevant to you. There's a nice box down here where you can test the keyboard layouts, so if you're not 100% sure, you can select what you think is most appropriate, and then use this box down here to test out a few keys and ensure that they're working as you expect. And once you're happy, just click Continue to move to the next menu. Here we get options about our installation. The first is to choose between normal or minimal installation. Just select normal here. Then we have some additional options. By default, our system will download updates while installing Ubuntu. I recommend that you leave this box checked because we want Ubuntu to download and install updates when we actually set up the virtual machine so that we have the most up-to-date software on our virtual machine right from the beginning, which will help us avoid any technical issues down the road. The other option here is to install third-party software such as graphics or wireless drivers and support for playing different media formats. Please leave this checked as well and then click Continue. The next menu is where we get to select what we want to do with the partitions on our hard drive. I just want to use the whole virtual disk that we created earlier, so I can just leave this as it is. We're then prompted with the details of what partitions will be created. And we can just click Continue here to action this. Now here I can select the country that I'm in for the right locale and time zone to be used on the computer. Mine has selected London by default, and this should always select the location closest to you by default, but if not, just modify it to where you are, and then click Continue. Then finally, I'm asked to set up details for the user account that we're going to be creating on the virtual machine. So I can add my full name here, and my computer's name is then selected by default, which I'm happy with. And my username here is also set by default, which I'm also happy with. So all I need to do is just add in my password here. Here I also get the option if I want the system to log in automatically or require a password before logging in. You can choose your preference here, but I'm going to select login automatically given that this virtual machine is just for, working through this course and I'm not worried about anyone accessing any data on it. Then I'm going to select Continue again, and now our installation process will start running. The installation process can take quite a while depending upon your internet connection, so just leave it running and then come back when it's done. Okay, so now that the installation is complete, we just click Restart Now to reboot our virtual machine. Next, we are asked to remove our installation medium before restarting, so we can just close our virtual machine window here, click Power Off the machine, and return back to VirtualBox. In VirtualBox now, we just need to open our settings, go back to storage, and remove our host drive which contains the installation medium like this. We can now close the settings window and start our virtual machine again. This now boots our virtual machine into our new instance of Ubuntu, which we've just installed on it, and this booting can take a few minutes. So once this is booted, we are first asked to set up any online accounts we want on Ubuntu. You can just skip this as this virtual machine is only for the course. We're told about Ubuntu's live patch feature, which is more for server environments than for personal machines, so I'm just going to click Next here to skip this. I'm happy to send Canonical some information to help improve Ubuntu, so I can leave this next option as it is, but you can change this based on your preference, and then click Next. And I'm going to leave my location services off, given it's not relevant for this virtual machine. And now we're told that we're all ready to go. We don't need to install any other software, so we can just click Done here and close this update window for now. And now we have our Ubuntu machine up and running. Now the first thing that you might notice here is that the resolution is very low. And if you're having this issue, you can just open up our menu and type in Display, and then click here on the Display Settings menu. I can then just change the resolution to my preferred resolution here, and click Apply, and then because everything appears fine, I'll just click Keep Settings here, and now things look much better. Now in terms of accessing the command line, if I just open the menu here and type in Terminal, then it brings up my terminal and I can just click on it to run it. And given that we're going to be using the command line a lot throughout this course, we can just right click here on the icon on the taskbar and click on Add to Favorites. So now it will always appear here even when it's closed, which will make it more convenient to access the terminal when we need it. So now you have Ubuntu installed and set up on your virtual machine ready to use for doing this course. And just to reiterate, if you're experiencing any technical difficulties when setting up the virtual machine, in the next segment there is a list of troubleshooting guidance with solutions to common issues which you can use to fix your specific issue. And of course, if you try those solutions and they don't work for you, then also try asking in the Q&A forum and one of the team will get back to you. But hopefully, if everything went through okay, then you should now be set up and ready to go for the course. Have fun!